everyone and welcome to the Deep Learning Full Course, your complete guide to mastering the core of modern AI. In this course, you will learn how deep learning powers technologies like computer vision, speech recognition, NLP, and autonomous systems. We will start with the fundamentals of neural networks and gradually move to advanced architectures like CNNs, RNNs, LSTMs, and transformers. You will also get hands-on experience with popular frameworks such as TensorFlow and PyTorch to build and train deep learning models from scratch. And by the end of this course, you will not only understand the theory but also gain practical skills to apply deep learning to real-world projects, setting a strong foundation for your AI career. So before we begin, please like, share and subscribe to Edureka's YouTube channel and hit the bell icon to stay updated on the latest tech content from Edureka. Also, check out Edureka's postgraduate program in generative AI and machine learning in collaboration with Illinois Tech. It offers a unique opportunity to explore the cutting-edge world of generative AI and develop advanced AI-powered solutions. This program covers in-demand topics including machine learning, deep learning, natural language processing, prompt engineering, generative AI, LLMs, RAG, agentic AI, and more. Learn from industry experts through a curriculum built around real-world, hands-on use cases designed to equip you with the practical and job-ready skills. So check out the course link given in the description box below. Now, let us get started with the first topic, that is, what is deep learning?
But the first thing that we need to focus on is why artificial intelligence? Why do we need artificial intelligence? Now let us understand this with an example. So nowadays, if you have noticed, if your car exceeds the speed limit, so you'll get a letter or basically a challan at your home. How do you think that happens? Do you think that there's a person who is sitting in a chair and actually noting down all the number plates that crosses the speed limit? Well, that is not possible because there might be millions of cars that pass through that road. And at once there might be many cars that will be passing through that road. So for a human being to actually do this task is next to impossible. Now let us see another approach to this particular problem. So what we can do, we can actually make use of cameras that will click the picture of the car that exceeds the speed limit, and then we can convert that picture into a text. For example, we have a UKPLATE. So in this way, the human error, the risk of human error has been reduced, and at the same time, machines, they never get tired. So because of that, you can capture all the images of cars that actually crosses the speed limit. Similarly, you can think of many other examples as well. It is used in order to recognize a sign, that is in banks if you want to authenticate whether that person is the bank customer or not. Apart from that, it is even used for self-driving cars as well. So in US, around 30,000 people die every year because of road accidents. So that can be completely removed if we use the self-driving cars, which is based on the concept of artificial intelligence. And let me tell you guys, you might find it very fascinating that people in MIT are using artificial intelligence in order to predict the future. So you can imagine why we need artificial intelligence. If you have any questions, any doubts, you can ask me. It is even used in places where humans can't reach. For example, deep oceans or navigation in Mars. So in those places, we need machines which are smart enough to carry our tasks. So this is why we need artificial intelligence. Let us move forward and understand what exactly is artificial intelligence. Now, artificial intelligence, I know the word sounds pretty complex and there are a lot of Hollywood movies that are based on artificial intelligence. If you have seen Terminator or Matrix, so all these movies are based on artificial intelligence, but you don't need to worry about it because till now we haven't reached that level as they have shown in movies like Terminator. But yeah, the concept is pretty similar. So basically, we want systems and softwares in such a way that they can imitate the human behavior. Now, what happens in artificial intelligence? Artificial intelligence is accomplished by studying how human brain thinks and how human brain learns, decide and work while trying to solve a problem. And then we use the outcome of this study as the basis of development of intelligent software and systems. So our major goal is to have systems or softwares that can imitate the human behavior. The way they think, the way they decide, the way they solve a problem. So in that similar fashion, we want our machines to do that. So this is basically artificial intelligence in a nutshell. Let us move forward and look at various applications of artificial intelligence. So this slide basically talks about the application of artificial intelligence. Now I've listed only 3 of them, but there are millions of applications. For example, it is used in speech recognition. So whenever you search something on Google, so you can just tell Google and it will search it for you. Similarly, it is used for understanding natural language as well as for image recognition as well. And there are many other applications in which artificial intelligence finds its use. For example, it can be used in self-driving cars, it can be used in Siri for recommending some products, and even when you go to websites like YouTube or Pandora, YouTube knows which video you want to next. Pandora knows which song you want to listen to. How do you think this happens? It happens all because of artificial intelligence. So all of these are a few examples of artificial intelligence, but nowadays it is used almost everywhere, guys. Trust me on that. Now let us move forward and understand how to achieve artificial intelligence. Now in order to achieve artificial intelligence, there were a few technologies that came. First came machine learning. Now there were certain limitations of machine learning. In order to overcome those limitations came deep learning. Now let me tell you guys, the concept of artificial intelligence is not new. It was first coined in 1956, but it was just a theoretical concept. Then in 80s and 90s, we were talking about neural networks. But since we didn't have enough computational power, so we couldn't utilize it properly. But in late 90s and 2000s, we started using neural networks for machine learning. Then in 2006, the term deep learning was coined for the first time that overcame the limitations of machine learning. And from 2010, deep learning was used commercially as well. So this was just a small history about artificial intelligence, machine learning, and deep learning. Now in order to understand this deep learning, we need to first look at machine learning and what were the various limitations of machine learning that led to the evolution of deep learning. So we'll move forward and understand what exactly is machine learning. Now what is machine learning? So machine learning is nothing but a type of artificial intelligence, or you can say a subset of artificial intelligence. And it provides computers with the ability to learn without being explicitly programmed. So you don't need to hard code your machine for that. Let us understand this with an example. So we have a problem statement in which whenever you give a certain input, we need to determine the species of the flower. And what is that input? That input will be sepal length, sepal width, petal length, and petal width. So wherever we get these four parameters or these four variables, our machine should be able to predict what sort of a flower it is. Now, how do you think that will happen? First, what we need to do, we need to train our machine on the basis of the data that we have. So in this data, we have sepal length, sepal width, petal length, and petal width, and we have species. So our machine will learn from this data. It will determine what should be the length and width of the sepal and petal in order to classify it as setosa or versicolor or other species of flowers as well. Now what happens next? So you have trained your data. So you have trained your machine from the data set. Then what happens, whenever you give a new input to this particular machine, it will predict the species of the flower. So this is how machine learning works. It is nothing but machine learning in a nutshell. So basically, I'll just revise it once more. So you have a data set. So you split that data into training and testing data. So what happens with the help of training data, you train your particular machine. And after that, you test it in order to determine the accuracy. And once it is done, whenever you give the new input, it will predict the outcome or the desired outcome. So this is how machine learning works, guys. Let us move forward and understand various types of machine learning. So the first type is called supervised learning. Now in supervised learning, what happens, you have input variables X and an output variable Y. And you can use an algorithm to learn mapping function from the input to the output. Now let me simplify it for you. So what happens in supervised learning, the data that you have already contain the classification. Now let me talk about the previous example itself. So from our data set, we knew that if we have this width, this length of our sepal and petal, so that will be the species of flower. So the classifications are already defined. So that will be under supervised learning. Now let me tell you how it actually works. So you have data, you divide that data into training data as well as test data. So on the basis of this training data, you train your machine, and after that you create a model. So as you can see that this phase is called training phase, and after that you create a model. Now in order to check this model to get the accuracy, you have test data. So you'll pass that test data and you'll see the accuracy. That is nothing but the actual output minus the output that is present in the test data. So with that you can get the accuracy. So this is nothing but supervised learning, and if you have any questions you can ask me right now. So we'll move forward and understand unsupervised learning. Now in unsupervised learning, unlike supervised learning, you don't have any predefined classes. So what happens, you have data. So on the basis of that data, you try to create your own class. You try to make sure that whatever class you create has high intra-class similarities and have a low inter-class similarities. That means if I've created two classes like this, class 1 and class 2, so the elements of this particular class should have high similarity, but at the same time it should have low similarity with the elements of class 2. So you can think of examples as well of unsupervised learning. For example, if I have a data about my customers, so if I have a website and there are millions of visitors on my website, and I want to make sure that I group people on various criteria. For example, I can group people on the basis of willingness to purchase a product that is there on my website, or where they are coming from, what is the source, all those things. So I want to group my customers, and I want to make sure that I have certain high priority customers, and I have low priority customers, and I have medium priority customers. So with the help of unsupervised learning, I can actually do that. I can make certain classes of people on whom I should focus more on as compared to the other class. So this was just an example, guys. You can use it in various other fields as well. So in marketing, this is how you can use unsupervised learning. So this brings us to our next type of machine learning, which is called a reinforcement learning. Now this is reinforcement learning, guys. Now what happens in reinforcement learning? The machine learns by interacting with space or an environment. So it learns with its experience, with its past experience, and also by new choice exploration. Now I'll take the analogy of dogs. So if you have any dog or a pet at your home, so if you have trained your dog in order to get the newspaper, and if it gets it, then you reward it with some chocolate or things that the dog likes, right? So the dog will know whatever he has done, he's actually rewarded for that. So it'll continue doing that. But apart from that, if he does something else, if instead of the newspaper, he brings something else. So what you'll do, you might even punish it. So because of that, the dog will come to know that it has to get a newspaper every morning. Now, the same example is there in front of your screen. So you have this machine. So it has two choices, either to touch the fire or touch the water. Now, first, what it does, it goes on and touch the fire. So because of that, it gets some burning sensation. Now it has only other option, that is to touch the water. So when it touches the water, it gets some reward. So because of that, it'll understand that it does not have to touch fire ever again. Now there's a diagram that is there in front of your screen. So what happens is you have an agent, all right, that agent performs some action. And on the basis of that action, it'll be exposed to some sort of an environment. Now if that action is correct, then it'll be rewarded with that. But if it is not, then it will change its choice and it will again perform some action. So this process will keep on repeating. So this is how reinforcement learning works. So let us move forward and understand, when we have machine learning, why do we need deep learning? That is, we'll look at various limitations of machine learning. Now the first limitation is high dimensionality of the data. Now the data that is now generated is huge in size. So we have a very large number of inputs and outputs. So due to that, machine learning algorithms fail. So they cannot deal with high dimensionality of data, or you can say data with large number of inputs and outputs. Now there's another problem as well, in which it is unable to solve the crucial AI problems, which can be natural language processing, image recognition, and things like that. Now one of the biggest challenges with machine learning models is feature extraction. Now let me tell you what are features. So in statistics, we consider features as variables, but when we talk about artificial intelligence, these variables are nothing but the features. Now, what happens because of that? The complex problems such as object recognition or handwriting recognition becomes a huge challenge for machine learning algorithms to solve. Now, let me give you an example of this feature extraction. Suppose if you want to predict that whether there will be a match today or not. So it depends on various features. It depends on whether the weather is sunny, whether it is windy, all those things. So we have provided all those features in our data set. But we have forgot one particular feature, that is humidity. And now our machine learning models are not that efficient that they will automatically generate that particular feature. So this is one huge problem, or you can say limitation with machine learning. Now obviously we have limitation, and it won't be fair that if I don't give you the solution to this particular problem. So we'll move forward and understand how deep learning solves these kind of problems. Now, as you can see that the first line on your slide, which says that deep learning models are capable to focus on the right features by themselves, requiring little guidance from the programmer. So with the help of little guidance, what these deep learning models can do, they can generate their features on which the outcome will depend on. And at the same time, it also solves the dimensionality problem as well. If you have a very large number of inputs and outputs, you can make use of a deep learning algorithm. Now, what exactly is deep learning? Again, since we know that it has been evolved by machine learning, and machine learning is nothing but a subset of artificial intelligence. And the idea behind artificial intelligence is to imitate the human behavior. The same idea is for the deep learning as well, is to build learning algorithms that can mimic brain. Now let us move forward and understand deep learning, what exactly it is. Now the deep learning is implemented with the help of neural networks, and the idea or the motivation behind neural networks are nothing but neurons. What are neurons? These are nothing but your brain cells. Now here is a diagram of neuron. So we have dendrites here, which are used to provide input to our neuron. As you can see, we have multiple dendrites here, so these many inputs will be provided to our neuron. Now this is called cell body, and inside the cell body we have a nucleus which performs some function. After that, that output will travel through axon and it will go towards the axon terminals, and then this neuron will fire this output towards the next neuron. Now the studies tell us that the next neuron, now, or you can say the two neurons are never connected to each other. There is a gap between them. So that is called a synapse. So this is how basically a neuron works like. And on the right hand side of your slide, you can see an artificial neuron. Now let me explain you that. So over here, similar to neurons, we have multiple inputs. Now these inputs will be provided to a processing element like our cell body. And over here in the processing element, what will happen? Summation of your inputs and weights. Now when it moves on, then what will happen? This input will be multiplied with our weights. So in the beginning, what happens? These weights are randomly assigned. So what will happen if I take the example of x1? So x1 multiplied by w1 will go towards the processing element. Similarly, x2 and w2 will go towards the processing element, and similarly the other inputs as well. And then summation will happen, which will generate a function of s, that is f of s. After that comes the concept of activation function. Now what is activation function? It is nothing but in order to provide a threshold. So if your output is above the threshold, then only this neuron will fire, otherwise it won't fire. So you can use a step function as an activation function, or you can even use a sigmoid function as your activation function. So this is how an artificial neuron looks like. So a network will be multiple neurons which are connected to each other will form an artificial neural network. And this activation function can be a sigmoid function or a step function. That totally depends on your requirement. Now once it exceeds the threshold, it will fire. After that, what will happen? It will check the output. Now if this output is not equal to the desired output, so these are the actual outputs, and we know the real outputs. So we'll compare both of that and we'll find the difference between the actual output and the desired output. On the basis of that difference, we are again going to update our weights. And this process will keep on repeating until we get the desired output as our actual output. Now this process of updating weight is nothing but your back propagation method. So this is neural networks in a nutshell. So we'll move forward and understand what are deep networks. So basically deep learning is implemented by the help of deep networks, and deep networks are nothing but neural networks with multiple hidden layers. Now what are hidden layers? Let me explain you that. So you have inputs that comes here. This will be your input layer. After that, some process happens and it'll go to the next node, or you can say to the hidden layer nodes. So this is nothing but your hidden layer 1. So every node is interconnected if you can notice. After that, you have one more hidden layer where some function will happen. And as you can see that again, these nodes are interconnected to each other. After this hidden layer 2 comes the output layer. And this output layer, again, we are going to check the output, whether it is equal to the desired output or not. If it is not, we are again going to update the weights. So this is how a deep network looks like. Now there can be multiple hidden layers. There can be hundreds of hidden layers as well. But when we talk about machine learning, that was not the case. We were not able to process multiple hidden layers when we talk about machine learning. So because of deep learning, we have multiple hidden layers at once. Now let us understand this with an example. So we'll take an image which has 4 pixels. So if you can notice, we have 4 pixels here, among which the top 2 pixels are bright, that is, they are black in color, whereas the bottom 2 pixels are white. Now what happens? We'll divide these pixels and we'll send these pixels to each and every node. So for that we need 4 nodes. So this particular pixel will go to this node, it will go to this node, this pixel will go to this node, and finally this pixel will go to this particular node that I'm highlighting with my cursor. Now what happens? We provide them random weights. So these white lines actually represent the positive weights and these black lines represents the negative weights. Now this particular brightness, when we display high brightness, we'll consider it as negative. Now what happens? When you see the next output or the next hidden layer, it will be provided with the input with this particular layer. So this will provide an input with positive weight to this particular node, and the second input will come from this particular node. Since both of them are positive, so we'll get this kind of a node. Similarly, this node as well. Now when I talk about these two nodes, the first node over here, so this is getting input from this node as well as from this node. Now over here we have a negative weight. So because of that, the value will be negative, and we have represented that with black color. Similarly, over here as well, we are getting one input from here which has a negative weight, and the another input from here which again has a negative weight. So accordingly, we get again a negative value here. So these two becomes black in color. Now if we notice, what will happen next, we'll provide one input here which will be negative, and a positive weight, which will be again negative. And this will be also negative and a positive weight. So that will again come out to be negative. So that is why we have got this kind of a structure. If you notice this is nothing but the inverse of this particular image. When I talk about this node over here, we are getting the negative value with a positive weight, which is negative, and a negative value with a negative weight, which is positive. So we are getting something which is positive here. Now, obviously, I want this particular image to get inverse. I want these black strips to come up. So what I'll do, I'll actually calculate the inverse by providing a negative weight like this. So over here, I've provided a negative weight, it'll come up. So when I provide a positive weight, so it'll stay wherever it is. After that, it'll detect, and the output you can see will be a horizontal image, not a solid, not a vertical, not a diagonal, but a horizontal. And after that, we are going to calculate the difference between the actual output and the desired output, and we are going to update the weights accordingly. Now, this is just an example, guys. So guys, this is one example of deep learning where what happens, we have images here. We provide these raw data to the first layer, to the input layer. Then what happens, these input layers will determine the patterns of local contrast, or it will fixate those patterns of local contrast, which means that it will differentiate on the basis of colors and luminosity and all those things. So it will differentiate those things. And after that, in the following layer, what will happen, it will determine the face features. It will fixate those face features. So it will form nose, eyes, ears, all those things. Then what will happen, it will accumulate those correct features for the correct face, or you can say that it will fixate those features on the correct face template. So it will actually determine the faces here, as you can see it over here. And then it will be sent to the output layer. Now, basically, you can add more hidden layers to solve more complex problems. For example, if I want to find out a particular kind of face, for example, a face which has large eyes or which has light complexion, so I can do that by adding more hidden layers. And I can increase the complexity also at the same time if I want to find which image contains a dog. So for that also I can have one more hidden layer. So as and when hidden layer increases, we are able to solve more and more complex problems. So this is just a general overview of how a deep network looks like. So we have first patterns of local contrast in the first layer. Then what happens, we fixate these patterns of local contrast in order to form the face features such as eyes, nose, ears, etc. And then we accumulate these features for the correct face, and then we determine the image. So this is how a deep learning network, or you can say deep network, looks like. So we'll move forward and I'll give you some applications of deep learning. So here are a few applications of deep learning. It can be used in self-driving cars. So you must have heard about self-driving cars. So what happens, it'll capture the images around it, it'll process that huge amount of data, and then it'll decide what action should it take. Should it take left, right, should it stop? So accordingly, it'll decide what action should it take. And that will reduce the amount of accidents that happens every year. Then when we talk about voice control assistants, I'm pretty sure you must have heard about Siri. All the iPhone users know about Siri, right? So you can tell Siri whatever you want to do, it'll search it for you and display for you. Then when we talk about automatic image caption generation, so what happens in this, whatever image that you upload, the algorithm is in such a way that it'll generate the caption accordingly. So for example, if you have say blue colored eyes, so it'll display a blue colored eye caption at the bottom of the image. Now when I talk about automatic machine translation, so we can convert English language into Spanish, similarly Spanish to French. So basically automatic machine translation, you can convert one language to another language with the help of deep learning. And these are just few examples, guys. There are many, many other examples of deep learning. It can be used in game playing. It can be used in many other things. And let me tell you one very fascinating thing that I've told you in the beginning as well. With the help of deep learning, MIT is trying to predict future. So yeah, I know it is growing exponentially right now, guys.
These are the terms which have confused a lot of people, and if you two are one among them, let me resolve it for you. Well, artificial intelligence is a broader umbrella under which machine learning and deep learning come. You can also see in the diagram that even deep learning is a subset of machine learning. So you can say that all three of them, the AI, the machine learning, and deep learning, are just the subset of each other. So let's move on and understand how exactly they differ from each other. So let's start with artificial intelligence. The term artificial intelligence was first coined in the year 1956. The concept is pretty old, but it has gained its popularity recently. But why? Well, the reason is earlier we had very smaller amount of data. The data we had was not enough to predict the accurate result. But now there's a tremendous increase in the amount of data. Statistics suggest that by 2020, the accumulated volume of data will increase from 4.4 zettabytes to roughly around 44 zettabytes or 44 trillion GBs of data. Along with such enormous amount of data, now we have more advanced algorithm and high-end computing power and storage that can deal with such large amount of data. As a result, it is expected that 70% of enterprise will implement AI over the next 12 months, which is up from 40% in 2016 and 51% in 2017. Just for your understanding, what is AI? Well, it's nothing but a technique that enables the machine to act like humans by replicating the behavior and nature. With AI, it is possible for a machine to learn from the experience. The machines adjust their responses based on new input, thereby performing human-like tasks. Artificial intelligence can be trained to accomplish specific tasks by processing large amount of data and recognizing pattern in them. You can consider that building an artificial intelligence is like building a church. The first church took generations to finish, so most of the workers who were working in it never saw the final outcome. Those working on it took pride in their crafts, building bricks and chiseling stone that was going to be placed into the great structure. So as AI researchers, we should think of ourselves as humble brick makers whose job is to study how to build components, example parsers, planners, or learning algorithm, or etc. anything that someday someone and somewhere will integrate into the intelligent systems. Some of the examples of artificial intelligence from our day-to-day life are Apple series, chess playing computer, Tesla's self-driving car, and many more. These examples are based on deep learning and natural language processing. Well, this was about what is AI and how it gains its hype. So moving on ahead, let's discuss about machine learning and see what it is and why it was even introduced. Well, machine learning came into existence in the late 80s and the early 90s. But what were the issues with the people which made the machine learning come into existence? Let us discuss them one by one. In the field of statistics, the problem was how to efficiently train large complex model. In the field of computer science and artificial intelligence, the problem was how to train more robust version of AI system. While in the case of neuroscience, problem faced by the researchers was how to design operational model of the brain. So these were some of the issues which had the largest influence and led to the existence of the machine learning. Now this machine learning shifted its focus from the symbolic approaches it had inherited from the AI and moved towards the methods and model it had borrowed from statistics and probability theory. So let's proceed and see what exactly is machine learning. Well, machine learning is a subset of AI which enables the computer to act and make data-driven decisions to carry out a certain task. These programs or algorithms are designed in a way that they can learn and improve over time when exposed to new data. Let's see an example of machine learning. Let's say you want to create a system which tells the expected weight of a person based on its height. The first thing you do is you collect the data. Let's see, this is how your data looks like. Now each point on the graph represents one data point. To start with, we can draw a simple line to predict the weight based on the height. For example, a simple line W equal H minus 100, where W is weight in kgs and H is height in centimeter. This line can help us to make the prediction. Our main goal is to reduce the difference between the estimated value and the actual value. So in order to achieve it, we try to draw a straight line that fits through all these different points and minimize the error. So our main goal is to minimize the error and make them as small as possible. Decreasing the error or the difference between the actual value and estimated value increases the performance of the model. Further on, the more data points we collect, the better our model will become. We can also improve our model by adding more variables and creating different prediction lines for them. Once the line is created, so from the next time if we feed a new data, for example height of a person to the model, it would easily predict the data for you and it will tell you what his predicted weight could be. I hope you got a clear understanding of machine learning. So moving on ahead, let's learn about deep learning. Now what is deep learning? You can consider deep learning model as a rocket engine and its fuel is its huge amount of data that we feed to these algorithms. The concept of deep learning is not new. But recently, its hype has increased and deep learning is getting more attention. This field is a particular kind of machine learning that is inspired by the functionality of our brain cells called neuron, which led to the concept of artificial neural network. It simply takes the data connection between all the artificial neurons and adjusts them according to the data pattern. More neurons are added if the size of the data is large. It automatically features learning at multiple levels of abstraction, thereby allowing a system to learn complex function mapping without depending on any specific algorithm. You know what? No one actually knows what happens inside a neural network and why it works so well. So currently you can call it as a black box. Let us discuss some of the example of deep learning and understand it in a better way. Let me start with a simple example and explain you how things happen at a conceptual level. Let us try and understand how you recognize a square from other shapes. The first thing you do is you check whether there are 4 lines associated with the figure or not. Simple concept, right? If yes, we further check if they are connected and closed. Again, if yes, we finally check whether it is perpendicular and all its sides are equal. Correct? If everything fulfills, yes, it is a square. Well, it is nothing but a nested hierarchy of concepts. What we did here, we took a complex task of identifying a square in this case and broke it into simpler tasks. Now this deep learning also does the same thing but at a larger scale. Let's take an example of machine which recognizes the animal. The task of the machine is to recognize whether the given image is of a cat or of a dog. What if we were asked to resolve the same issue using the concept of machine learning? What we would do? First, we would define the features such as check whether the animal has whiskers or not, or check if the animal has pointed ears or not, or whether its tail is straight or curved. In short, we will define the facial features and let the system identify which features are more important in classifying a particular animal. Now, when it comes to deep learning, it takes this to one step ahead. Deep learning automatically finds out the feature which are most important for classification, compared to machine learning where we had to manually give out that features. By now, I guess you have understood that AI is the bigger picture and machine learning and deep learning are its subpart. So let's move on and focus our discussion on machine learning and deep learning. The easiest way to understand the difference between the machine learning and deep learning is to know that deep learning is machine learning. More specifically, it is the next evolution of machine learning. Let's take few important parameters and compare machine learning with deep learning. So starting with data dependencies. The most important difference between deep learning and machine learning is its performance as the volume of the data gets increased. From the below graph, you can see that when the size of the data is small, deep learning algorithm doesn't perform that well. But why? Well, this is because deep learning algorithm needs a large amount of data to understand it perfectly. On the other hand, the machine learning algorithm can easily work with smaller dataset. Fine. Next comes the hardware dependencies. Deep learning algorithms are heavily dependent on high-end machines, while the machine learning algorithm can work on low-end machines as well. This is because the requirement of deep learning algorithm include GPUs, which is an integral part of its working. The deep learning algorithm requires GPUs as they do a large amount of matrix multiplication operations, and these operations can only be efficiently optimized using a GPU as it is built for this purpose only. Our third parameter will be feature engineering. Well, feature engineering is a process of putting the domain knowledge to reduce the complexity of the data and make patterns more visible to learning algorithms. This process is difficult and expensive in terms of time and expertise. In case of machine learning, most of the features are needed to be identified by an expert and then hand-coded as per the domain and the data type. For example, the features can be a pixel value, shapes, texture, position, orientation, or anything. Fine. The performance of most of the machine learning algorithm depends on how accurately the features are identified and extracted. Whereas in case of deep learning algorithms, it try to learn high-level features from the data. This is a very distinctive part of deep learning, which makes it way ahead of traditional machine learning. Deep learning reduces the task of developing new feature extractor for every problem. Like in the case of CNN algorithm, it first tries to learn the low-level features of the image, such as edges and lines, and then it proceeds to the parts of faces of people, and then finally to the high-level representation of the face. I hope the things are getting clear to you. So let's move on ahead and see the next parameter. So our next parameter is problem-solving approach. When we are solving a problem using traditional machine learning algorithm, it is generally recommended that we first break down the problem into different subparts, solve them individually, and then finally combine them to get the desired result. So this is how the machine learning algorithm handles the problem. On the other hand, the deep learning algorithm solves the problem from end to end. Let's take an example to understand this. Suppose you have a task of multiple object detection, and your task is to identify what is the object and where it is present in the image. So let's see and compare how will you tackle this issue using the concept of machine learning and deep learning. Starting with machine learning, in a typical machine learning approach, you would first divide the problem into two steps. First, object detection and then object recognition. First of all, you would use a bounding box detection algorithm like GrabCut, for example, to scan through the image and find out all the possible objects. Now, once the objects are recognized, you would use object recognition algorithm like SVM with HOG to recognize relevant objects. Now, finally, when you combine the result, you would be able to identify what is the object and where it is present in the image. On the other hand, in deep learning approach, you would do the process from end to end. For example, in a YOLO net, which is a type of deep learning algorithm, you would pass an image and it would give out the location along with the name of the object. Now let's move on to our fifth comparison parameter. It's execution time. Usually, a deep learning algorithm takes a long time to train. This is because there are so many parameters in a deep learning algorithm that makes the training longer than usual. The training might even last for 2 weeks or more than that if you're training completely from the scratch. Whereas in the case of machine learning, it relatively takes much less time to train, ranging from a few weeks to few hours. Now the execution time is completely reversed when it comes to the testing of data. During testing, the deep learning algorithm takes much less time to run. Whereas if you compare it with the KNN algorithm, which is a type of machine learning algorithm, the test time increases as the size of the data increase. Last but not the least, we have interpretability as a factor for comparison of machine learning and deep learning. This factor is the main reason why deep learning is still thought 10 times before anyone uses it in the industry. Let's take an example. Suppose we use deep learning to give automated scoring to essays. The performance it gives in scoring is quite excellent and is near to the human performance. But there's an issue with it. It does not reveal why it has given that score. Indeed, mathematically it is possible to find out that which node of a deep neural network were activated, but we don't know what the neurons were supposed to model and what these layers of neuron were doing collectively. So we fail to interpret the result. On the other hand, machine learning algorithm like decision tree gives us a crisp rule for why it chose and what it chose. So it is particularly easy to interpret the reasoning behind it. Therefore, the algorithms like decision tree and linear or logistic regression are primarily used in industry for interpretability.
Now let's explore different types of ML models. So not all data is structured the same way, and different problems require different approaches. So for example, predicting stock prices requires the models that learn from historical trends. And then identifying objects in images needs models that recognize patterns in visual data. Next, the chatbots and voice assistants rely on the models trained to understand and generate human language. So to tackle these challenges, as I discussed previously, that ML is divided into different learning models, such as supervised, unsupervised, and reinforcement learning. And each has its own strengths and it is used depending on the problem at hand. Since we know why different ML models are needed, let's see how they play a crucial role in generative AI. Well, generative AI is one of the most exciting applications of machine learning. And unlike traditional ML models that make predictions or classifications, generative models create entirely new content. And here's how ML enables AI to generate. So first here we have text. A language models like GPT generate human-like text for chatbots, content writing, and coding. Next is the image. So AI-powered tools like DALL can create realistic images from textual descriptions. Next is videos. So advanced ML models synthesize lifelike video content, transforming media, marketing, and even filmmaking. So these advancements in generative AI are reshaping creativity and automation, proving that machine learning is not just about making decisions, it's about creating new possibilities. So now that we have seen how ML models enable AI to create new content, so now let us briefly understand the different types of machine learning models. So here, the first type of machine learning model is supervised learning. Supervised learning trains a model using labeled data, where each input has a corresponding correct output. And this makes it ideal for tasks where historical data can be used to predict future outcomes. For example, let's say spam detection. Email services like Gmail uses supervised learning to classify emails as spam or not spam. by learning from past labeled examples. The next example is the price predictions. So real estate platforms use regression models to predict house prices based on the features like location, size, and amenities. Now, let us see some of the popular algorithms. So first, let's discuss on decision trees. These models break down the data into a tree-like structure, where each node represents a decision based on a feature. So they are easy to interpret and work well for both classification. For example, deciding if an email is a spam or not, and regression example predicting house price. However, they can become overly complex. Next is the support vector machines. So SVMs are powerful for classification tasks as they find the optimal boundary, also called a hyperplane, and that best separates different classes in the data. They work well for high-dimensional spaces and cases where the distinction between categories is clear, such as handwriting, facial recognition, or medical diagnosis. So now that we have seen how labeled data is used, so now let's explore how unsupervised learning finds patterns without labels. Well, unsupervised learning works with unlabeled data, identifying hidden patterns and relationships without predefined categories. So here we have some of the popular algorithms. So first is the k-means clustering. This algorithm partitions data into a predefined number of clusters by grouping similar data points based on their attributes. It works well for tasks like customer segmentation, where businesses can group customer based on purchasing behavior. However, it assumes clusters are spherical and may struggle with irregular shaped data. Next, we have autoencoders. So these are specialized neural networks designed to learn efficient data representations by encoding and reconstructing input data. Let us see some of the examples. So first example here we have is customer segmentation, where e-commerce platforms group customer based on their shopping behavior to offer personalized recommendations. The next example is market analysis. Businesses analyze purchasing trends to find association, such as which products are frequently brought together. Now we have covered both labeled and unlabeled learning. So let's see how semi-supervised learning combines the best of both worlds. So, semi-supervised learning bridges the gap between the supervised and unsupervised learning by using a small amount of labeled data along with large amount of unlabeled data. So for example, let's say AI assistant medical diagnosis. Labeled medical images such as X-rays with diagnosis are scarce, but large amounts of unlabeled images exist. Semi-supervised learning helps AI learn patterns from both labeled and unlabeled data, improving accuracy in disease detection. Alright, now let's explore the reinforcement learning, where AI learns through trial and error. Well, reinforcement learning is inspired by the concept of learning through trial and error. So models interact with an environment, receive rewards or penalties for actions, and refine their strengths over time. For example, let's say gaming. Mario AI, developed using reinforcement learning, learns to navigate levels by optimizing actions through trial and error. The next example is robotics, where robots learn to walk, balance, or perform tasks through reinforcement learning by maximizing positive outcomes. Also, reinforcement learning uses agents, actions, and rewards to improve decision making, making it ideal for tasks requiring continuous learning and adaptation. So now that we have covered all the types of machine learning models, so let's go over some of the key tips to help you choose the right one for your needs. So here are the tips. When it comes to supervised learning, classifying emails as spam or not, and diagnosing diseases from patient data. Next is the unsupervised learning. So unsupervised learning is best when you're grouping shoppers by behavior and detecting fraud in banking. Next we have semi-supervised learning. And this is best when you're improving speech recognition with limited labeled data and identifying fake news. And finally, the reinforcement learning. This will be best when you're training self-driving cars to navigate, optimizing AI in video games like Mario. So whether it's supervised, unsupervised, semi-supervised, or reinforcement learning, each model plays a crucial role in shaping AI's future. So as generative AI continues to evolve, these models are driving innovation in text, images, and video generation. So which machine learning model do you find the most fascinating? Let me know in the comments below.
Why mathematics in machine learning? Aspiring machine learning engineers often tend to ask me, what is the use of mathematics machine learning when we have computers to do it all? Well, that is true. Our computers have become capable enough to do the math in split seconds where we would take minutes or even hours to perform the calculations. But in reality, it is not the ability to solve the math. Rather, it is the eye of how the math needs to be applied. You need to analyze the data and infer information from it so that you can create a model that learns from the data. Math can help you in so many ways that it becomes mind-boggling that someone could hate this subject. Of course, doing math by hand is something I hate too, but knowing how I use math is enough to explain my love for math. So allow me to extend this love to you guys too, because I won't be teaching you just the mathematics for machine learning, but the various applications you can use it for in real life. So what math do we need to learn for machine learning? Here is a pie chart which comprises of all the needed math. Linear algebra covers a major part, followed by the multivariate calculus. Statistics and probability also play a big role, and you need to know the knowledge of algorithms and much more. This is the requirement that is needed to master machine learning. So now that we have developed this understanding, let's do some math. We shall kick off with linear algebra. Linear algebra is used most widely when it comes to machine learning. It covers so many aspects, making it unavoidable if you want to learn mathematics for machine learning. Linear algebra helps you in optimizing data, operations that can be performed on pixels such as sharing, rotation, and much more. You can understand why linear algebra is such an important aspect when it comes to mathematics for machine learning. So let's move over to the first topic in linear algebra, scalars. So what is a scalar? A scalar is basically a value. It represents something, right? So scalars are just values that represent something. Suppose we had a laptop on sale and it is priced at 50,000 rupees, right? So this 50,000 rupees is the scalar value of that laptop. What are the operations that can be performed on scalars? It is just basic arithmetic. So for example, we have addition, subtraction, multiplication, division. All of those operations can be applied on scalars. Okay. For example, over here, we are buying a laptop and the accessories. What is the total price? It will be the addition of both the prices. So 50,000 for the laptop and 5,000 for the accessories brings it up to 55,000 rupees. What happens if you're buying a laptop at a 50% discount? So it is half the price, right? It is 50,000 divided by 2, that becomes 25,000 rupees for the laptop. So this is just a brief introduction and all that is required from scalars. So once we are clear with this, let's move over to vectors. So vectors can get a bit complicated as they are different for different backgrounds. Let me tell you how. Computer science people can interpret vectors as a list of numbers that represent something. Physicists consider vectors to be a scalar with a direction and it is independent of the plane. Mathematicians take vectors to be a combination of both and try to generalize it for everybody. All of these standpoints are absolutely correct, and that's what makes it so confusing for anyone learning about linear algebra for mathematics for machine learning. In machine learning, we usually consider vectors in the standpoint of a computer scientist, where the data is in the tabular form consisting of rows and columns, right? And when our data is in the form of pixels or pictures, we consider them as vectors that are bound to the origin and transform them to matrices and perform operations that we shall discuss later. So now that you have a brief idea about vectors, let's jump over to the operations that you need to know when working with vectors. Operations on vectors can be applied only when you know what kind of data you're working with. Suppose you have pixel data and you want to apply rotations but end up doing something wholly different. Your model will not work because it is doing all the wrong operations here. It's important that you make sure that you know what you're working with. Only then you will be able to apply the required operations. So the first operation that we have here is vector addition. So let's understand what vector addition does. So for example, vector addition is also called as dot product. Vector addition is something that is completely different from operations that we've been learning now for scalars. Okay, it's not simple arithmetic. It is actually the total work that is done by both the vectors in a quantified form. So for example, let me say that I want to walk forward by 50 meters, and that is one vector. Okay. So me walking forward for 50 meters is one vector. And from there, I go right for 25 meters, right? So that is the second vector. So what is the work that is completely done by both these vectors is me moving forward and then moving right. So let me say, for example, V1 is what I walked forward. Okay. And then V2 is something that I moved right. So what is the addition of this? The addition is basically putting both the vectors point to point and then finding the displacement or the work that has been done. If you look at it over here, it is V1 plus V2's work that is in the quantified form of V1 plus V2. It is the displacement. So for example, V1 is a distance and V2 is a distance. V1 plus V2 is the displacement. So that is basically what is a dot product. I hope you've understood this. So let's move over to the next operation, that is scalar multiplication. So what is scalar multiplication? So whenever a vector is multiplied with a scalar value, it either grows or shrinks. What this means is that you have a particular value, a scalar value, which is either positive or it is negative, and it may be greater than 1 or lesser than 1. Whichever is lesser than 1 and it is negative, it will always make it shrink, or else it will do the opposite, it will make it grow. So let me just show you an example over here. So let's say I have a vector called v1. Now if I'm trying to multiply this with a positive scalar value, say k, positive scalar value into v1 will make the vector grow. Whereas if I am trying to multiply this particular vector with a negative scalar value, say minus k, it will be shrinking down. So it is minus k into v1 gives me a shrink vector. So as you can see, this was my normal vector. And if I multiplied it with a constant k, which was positive, it grew. And if it was negative, it shrank down. So that is basically what is scalar multiplication. So the next vector operation is a projection. So what does projection help us with? So for example, let's say I have two vectors, okay, v1 and v2. Now I do not know much about v1 and I just know more about v2. So if I can try to find a way in which I can project the vector v1 onto v2, I'll be able to obtain information about v1. So let me just show you. So for example, I have a vector v1 and I had another vector v2. So I know all about v2, but I do not know about v1 vector. So what happens over here is if I'm able to project the projection of vector v1 onto v2, I will be able to analyze and know the unknown features that vector v1 has. Okay. Actually, if you go with this into deep learning, right, you can be able to find unknown features of the vector, which can help you modify your one image into so many images that you can basically simplify and modify that image into something that it is not. Okay, that comes under deep learning, but we're not going to cover that. But this is a very important concept that you need to understand. It is basically like it's said over here. Projection is the shadow of a vector that it places on the other vector. So whatever information that v1 vector has, I'll be able to somehow extract it from the vector v2 because the projection falls onto v2. That basically brings us to the end of all the vector operations that you need to remember for machine learning. Let's move over to matrices. So what is a matrix? A matrix is the composition, or it is the mixture of numbers, symbols, expressions which are in a rectangular array. It can be rectangular, it can be square, it depends on the order. So what do we use matrices for? We use matrices to convert our equations into the form of arrays. For example, if you've got an equation, you cannot simply put that into your computer saying that, okay, solve this and give it to me. You need to convert it into a list or an array so that you will be able to perform your operations on it, right? That is the reason matrices are so much important to us. And that is the reason it is much more easier for us so that we can convert our equations into lists and arrays and then perform our operations on them. So suppose, for example, you have two equations over here. So how do you convert these two equations into matrices? So what does equation tell you? If you have 2x plus 2y is equal to 10, what this basically is trying to convey the information to you is that you have two constants x and y. In these constants, if you keep giving different numbers, you will be able to find a different value for it. Let's say, for example, the scalar value is 10 and you have 2x plus 2y, which is basically a vector. I need to find the points of x and y. Find the points of x and y meaning that I'm trying to find the direction of the vector. And then if I'm able to substitute values and then find out how 2x plus 2y is equal to 10, I'm finding all the information I need from that vector so that I can basically find out what all the other information I need from it. That is how functions are very important. You need to understand what a function is trying to convey to you. Let's say, for example, you have the equation of a straight line. So what does a straight line be? It is y is equal to mx plus c. What does this mean? It means that the y coordinate is equal to some value m into x plus a constant. So I'm able to plot this. I'll be getting the y coordinate, the x coordinate, and I'll be able to get a straight line. So whatever numbers I put into these, I will always be getting a straight line. So that is the reason it is called the equation of a straight line. It is always going to be constant. So you have to understand what a function is trying to convey to you. Once we are done with that, let me just tell you how you convert equations into matrices. It's really simple. Take out all the numbers. So you have 2x plus 2y equal to 10, right? So 2x and 2y has two numbers, 2. So those two become one row. 4 and 1 in the second equation become one row. X and y becomes one column, and 10 and 18. So let me just show it to you. So as you can see, we have a matrix 2, 2, 4, 1. Then we have x and y is equal to 10 and 18. If you multiply it accordingly, you will be getting back the same equation that we had earlier. This is how matrices are used in linear algebra. So once you know how the equations are converted into matrices, let's move over to the matrix operations. So what is the first operation? Simple addition. What does addition help you with? It is just basically adding all the directions of two vectors. Why is it two vectors? Because I'm converting vectors into matrices, right? You are simply just going to add the corresponding elements of both the matrices. Simply add the corresponding elements of both the matrices. And you have to remember that if you are adding two matrices, it has to be of the same order. What do I mean by order? It is basically the number of rows into the number of columns. So for example, if I have the first matrix, that is 2, 2, 4 and 1, I have two rows and I have two columns. So that becomes a 2 cross 2 matrix. That is the order of the matrix. The next one also, 2, 3, 1, 4, it has two rows and two columns. That makes it an order of 2 cross 2. So if I had 3 rows and I had 2 columns, it would be 3 into 2. So I hope you've understood what order is. Let's say I had these two matrices and I want to add them. So what I do, it is 2 plus 2. So let's say I have 2 over here and I have 2 over here. So what is 2 plus 2? It becomes 4. What is 2 plus 3? It becomes 5. What is 4 plus 1? It becomes 5. What is 1 plus 4? It becomes 5. So it is adding the corresponding elements of the matrix. So I hope you've understood that. So let's move over to the next operation, matrix subtraction. It's the same thing as how you did it for addition. You just subtract the corresponding elements. If you had 2 minus 2, it becomes 0. 2 minus 3 becomes minus 1. 4 minus 1 becomes 3. 1 minus 4 becomes minus 3. Simple. You can understand this very easily. Moving ahead from matrix subtraction is matrix multiplication. What do you do with matrix multiplication? You are basically multiplying the rows with the columns. The matrix of row 1 with the columns of matrix 2. What happens? You have to remember that the number of rows in matrix 1 has to be equal to the number of columns in matrix 2. Only then will you be able to perform the matrix multiplication. So for example, if I had a 2 cross 2 matrix, it would be A11 into B11, A12 into B21, A11 into B12 plus the A12 into B22 accordingly. So let me show you an example for matrix multiplication so that you can understand how it works. Suppose I have a 2 cross 2 matrix that I've already been using for matrix addition and subtraction. Now, how am I going to perform the matrix multiplication is basically I'm going to, multiply the first row into both the columns of the matrix 2. So I have 2 into 2 plus 2 into 1. Then I have 2 into 3 plus 2 into 4. The same thing goes for the second row also. So what do I get? I get 4 plus 2, 6 plus 8, 8 plus 1 and 12 plus 4. That accordingly gives me 6, 14, 9 and 16. So this is the matrix multiplication. It's really simple to understand. So if you have any doubts, leave them in the comment section. We'll get back to you as soon as possible. So once we are done with matrix multiplication, let's move over to the transpose. So the transpose is a really simple operation. All you do is you convert the rows into columns. That's it. But why is it so important? Transpose is really important when you want to change the dimensionality of your data. Suppose all your data is in a row. You can reiterate through there, or all your data is in a column. You can do it accordingly. So it is really important when you work with transpose because it helps you to change the dimensionality. It helps you flip the dimension. So for example, if you're working with pixels, right, pictures, if you change the rows or the columns of your pictures data, you are basically changing the picture and then you can, analyze it more, get more information from it. So transpose plays a very important role. You need to understand that. So for example, I have 2, 2, 4 and 1. What happens is the first column becomes the first row and the second row becomes the second column. So as you can see here, it is 2, 2, 4 and 1. And that is all transpose is. So let's move over to the next operation. We have determinant of a matrix. By now, all we have been doing is having matrices being added, subtracted. So what is all of this? It is basically all the vectors being added, subtracted, multiplied, then flipped with their dimensions. You will understand this when you do all of this practically. Because all of this is something that we do not do it in our daily lives. But when you're learning with machine learning, when you're performing machine learning, all of these operations come into picture. So all that you've learned by now is basically adding values of vectors, subtracting vectors, multiplying two vectors, then transpose, that is the flipping of vectors, and now you're going to learn about determinant. What is a determinant? All the matrices that we had till now, they are basically directions. They are basically directions and values of all the vectors. Now, all these vectors are definitely going to have a scalar value in them so that you can understand the weight, you can understand the depth of that particular matrix. What is the determinant helping you with? The determinant helps you with understanding the weight or the sensitivity that it can provide on the data set. That is the reason determinant is really important. It is the scalar value of the matrix and it can help you give the eigenvalues of the matrix. What do I mean by eigenvalues? I'll teach that to you in the next part because we are going to understand in depth what are eigenvalues and eigenvectors. That is the reason determinants are so important. So let's say, for example, I had this particular matrix A, B, C, D, E, F, G, H, I. It would be A into E, F, H, I, and then it would be minus B into D, F, G, I plus C into D, E, G, H. So what happens now is I'm going to get this particular equation. So it's AEI plus BFG plus CDH minus AFH minus BDI minus CEG. This is basically what is going to give me the scalar value of the matrix. So I hope you've understood the importance and how determinants are important in machine learning. So next we will learn about the inverse of a matrix. So how do I explain inverse to you? It's a very simple example if you understand that. Suppose I am walking on a road and I walked straight for 50 meters. But then I remember that I had to get back something from the place I started. So I walked back 50 meters. What is the distance that I traveled? The distance that I traveled was 100 meters. Why? because I went 50 meters forward and 50 meters backward. But what is the work that I have done? It is 0. Why is that? It is because I am at the same place that I started from. That is not the work done. If I move from one place to another place, that is the work done. That is some displacement that my body has achieved. But I have not achieved that over here. Why? It's because I have gone straight and come back straight for 50 meters, making my work done 0. So just the same way inverse of a matrix works. Suppose you have a vector that moves in the forward direction. You will have the inverse of that particular vector that comes in the negative direction, and it makes all the work done 0. Sometimes there is no inverse of a matrix that exists. That's because the vector does not have all the information that is required to obtain its inverse. So I hope you have understood what is a inverse. Let's see how do you find an inverse of it. Okay, for a 2 cross 2 matrix, this is how you're going to find it. It is finding the determinant into the transpose, or finding the inverse of the matrix. So it is A and D that is going to be switched over, and minus B and minus C. This gives you the inverse of the matrix. So for orders 3 and above, what do? You find the determinant of A, and then you accordingly find all the different determinants inside of it. So that is basically how you find the inverse of a matrix. Let's move over to how a vector can be used as a matrix. Okay. So by now that I've been telling that vectors can be easily translated into matrices, and I've already shown it to you. And why is it so important? It's because they help you apply operations on the data very easily. And then you have certain well-known operations such as scaling, rotation, sharing, and much more. All of this come under computer graphics. Okay. Making these operations on your image or your vectors becomes really easy when you're working with matrices. So that's the reason matrices are so important. So for example, right now I've shown you that if there was an equation v1 as 3x plus 4, it would be 3 and 4. And then you had x and y, then you would have x plus 2y, which would become 1 and 2, and then x and y. That is how vector as a matrix works. What are some of the well-known operations, right? I'm assuming that there is going to be a 2 cross 2 matrix. Whenever you're scaling, it is basically increasing the size. So how do you increase the size? It is Sx and Sy, which are the scaling factors which you perform on your x and y coordinates. Then you have sharing, which is basically moving or reshaping your particular object that you're working with. So it can be M, which is the sharing factor. And then you have the rotation. So how do you rotate your particular object, in which direction? So all of that can be done using these particular matrices. So let's move over and understand how matrices can help you solve equations and obtain solutions much more easily. So that is basically vector as a matrix. We have two methods over here. They are the echelon method and the inverse method. For our tutorial, I've been taking the row echelon method because it's much more comfortable for me. If you are much more comfortable with column echelon method, you can go ahead with that. But because I am comfortable with row echelon methods, I've used row echelon method. And next we have the inverse method. So we are basically going to solve the equations. We are going to find the coordinates at which our points give us that particular value. So let's move over with the first method, which is the row echelon method. And I have some equations over here which go ahead like 2x plus y minus z equal to 2, x plus 3y plus 2z equal to 1, x plus y plus z equal to 2. So I'm going to convert all of this into a particular matrix. So let me show you how the matrix looks. It is 2, 1, minus 2 and 2, 1, 3, 2, 1, and 1, 1, 1, 1. So all the information about the equations have been put into the matrix form. And the answers that we are going to get are x is equal to 2, y is equal to minus 1, and z is equal to 1. So this is the reason I'm going to get all these particular values, that is 2, 1, and 2, which I'm getting from the equations. Whenever I put the x, y, and z values into them, I'm going to, get those particular coordinates. Now, let me just tell you why we are solving equations, okay? So if I am telling that there is this particular vector that goes like this, or comes in this direction or something like that, I want to find the x, y, and z coordinates so that I can obtain the information, visualize it, and then learn more about that particular vector. Now say for example, this is just 2x plus y minus z equal to 2. Let's say, for example, what if it was a 2 boxes plus 1 candle minus 1 chocolate is equal to giving me a profit of 2 rupees. Okay. So as you can see, these are just simple equations, and these are the coordinates that we get. X is equal to 2, y is equal to -1, and z is equal to 1. But what is the importance of this? Okay. Let me just give you a simple example so that you can understand what we are actually trying to find out over here. Okay. Suppose I have a factory and I want to get a profit of 2 rupees. And I have boxes, I have candles, and I have chocolates. So if I take the first equation, I'm saying that if I have 2 boxes, 1 candle minus the chocolate, it is going to give me 2 rupees profit. So what is X, Y, and Z exactly? X, Y, and Z are the investment costs. How much do I need to invest into them so that I can get back what I really required? So for boxes, I need to invest 2 rupees. For chocolates, I need to invest nothing. For candles, I need to invest -1 or something like that. Okay. If I invest so much, I'm going to get 2 rupees profit. So this is like a real life example which is being converted into some equation, and then we just need to solve it. That is the reason vectors are so important, and how they can be converted into matrices and then, solved very easily. How does the row echelon method work? I'm going to be taking the step 1, which is R1 divided by 2. R1, when we divide it by 2, we get 1, half, minus half, and 1. So what's the step 2? We will do R2 minus R1. So we have R2, which is the minus of R1. I'm going to get the particular equation, which is 1 half minus half and 1, 0, 5 by 2, 5 by 2, and 0, 1, 1, 1, 2. Simple enough, right? So what is the next step? It'll be R3 minus R1. So it is 1 half minus half 1, 0, 5 by 2, 5 by 2, 0, and 0 half 3 by 2 and 1. The next step is 2 by 5 by R2. So you get 1 half minus half 1, 0, 1, 1, 0, and 0, 1 by 2, 3 by 2, and 1. So what's the step 5? Step 5 is basically R1 minus half of R2. So I get 1, 0, minus 1 and 1, 0, 1, 1, 0, and 0, 1 by 2, 3 by 2, and 1. Step 6 is R3 is equal to R3 minus half of R2. So I have 1, 0, minus 1 and 1, 0, 1, 1, 0, and 0, 0, 1, 1. Step 7 is R1 plus R3. So I have 1, 0, 0, 2, 0, 1, 1, 0, and 0, 0, 1, 1. Step 8 is R2 is equal to R2 minus R3. So I have 1, 0, 0, 2, 0, 1, 0, minus 1, and 0, 0, 1, 1. If you put all of this back into the equation, you will find out that for the first row, 1, 0, 0, 2 is equal to x plus 0 is equal to 2. The value of x is equal to 2. The value of y is equal to -1, and the value of z is equal to 1. So this is how the row echelon method works. And what do you have to actually perform in row echelon? It is basically the first row has to start with the value 1. The second row has to have a 0, and then somewhere in the middle it has to have a value of 1. And then the third row should be starting with zeros and then getting some value where it starts with 1 only. So row echelon or column echelon, whatever method you use, you have to make sure that whichever element is the first starting element of the row, it has to have a 1, or it has to be preceding with zeros. So as you can see here, the first row has 1, 0, 0, 2, and then you have 0, 1, 0, minus 1, and then you have 0, 0, 1, 1. So that is how you are performing the row echelon method to solve your matrix. So if you remember, we had x is equal to 2, y is equal to -1, and z is equal to 1. Those were the answers that we wanted. Once we are done with row echelon method, let's move over to the inverse method. So suppose we have some equations, 4x plus 3y is equal to -13, and -10x minus 2y is equal to 5. What does the inverse method tell us? Let me show it to you. So this is the matrix that you come up with. So it is 4, 3, -10, and -2. Then you have x and y, and which is equal to -13 and 5. So what does the inverse method actually tell us? For example, we know that A into A inverse is equal to 0 work done, right? It is the identity matrix, I matrix. So if I have A into the A inverse, so it is like I'm doing the work and I don't do the work. is equal to no work done. So A into A inverse gives me the identity matrix. If A into B is equal to C, so A is my, all the numbers, then B is my X and Y, and C is the output value. If I do A into A inverse into B is equal to C into A inverse, I am going to get B is equal to C into A inverse. Because A into A inverse gets cancelled, so B is equal to C into the A inverse of it. So that's what I'm going to do. So what is the inverse of the 2 cross 2 matrix? The inverse is found by this formula, and the inverse is actually 1 by 22 minus 2 minus 3, 10 and 4. So that's the inverse of the matrix. So let me show you how it works. What happens is I'm having A into A inverse into B is equal to C into the A inverse. So A into A inverse is obviously going to get cancelled out because it's an identity matrix. So I'm just going to be left with X and Y is equal to 1 by 22 into minus 13 and 5, minus 2, minus 3, 10 and 4. So what I do later, I'm going to just multiply, and this is what I get. So it's basically 1 by 22 and 11 by minus 110. So if I do 1 by 22 into the particular matrix that I've found, it is going to be X is equal to half and Y is equal to minus 5. So that is how I'm going to be using the inverse method to find or solve the equations. I hope that was simple to understand. So once we've done all of that, we are now capable enough to understand what an eigenvector is. Eigenvectors are really important when you're working with data. All of that, what vectors, matrices, what all we've been doing by now, think of it as the data you're working with in your machine learning algorithm, right? What is an eigenvector? Eigenvector does not change the direction even if a transformation is applied to it. What does a eigenvector really give us? So for example, I have a data. If I am trying to do any transformation on it, it should not change from what it was really. It should not change from what it was initially. It should not become something that is totally irrelevant to me. If I have such data that even if I apply transformations to it, it does not change what it was supposed to be, that is an eigenvector. What does an eigenvector give me? They are the most sensitive parts of my data set, and I can use them and I can trust them for my analysis purposes. So that is why eigenvectors are so important. Eigenvectors help you transform and make your data much more careful. So for example, let me show you what an eigenvector looks like. Okay, so I have a particular rectangle and I have a lot of vectors, but for my example I'm just going to be using two vectors. Okay, I have a v1 and v2. These vectors are basically trying to explain all the data that is there in the particular rectangle. What happens if I perform the sharing operation? When I perform the sharing operation, my v1 vector has changed its direction completely. It was at some other direction, and after sharing or after performing some operation, it has completely changed its dimensionality, its direction. All the information that it held initially has now completely been changed. Whereas my v2, it has not changed its direction. Yes, it has moved forward. It has multiplied, but it gives me the same information that it was giving me earlier also. So that becomes an eigenvector. Think of this now in the form of a matrix. If my matrix is changing so drastically, how will I be able to perform operations on it? It becomes really difficult. Okay, so for example, think of the vector v2 as a list, which is then just multiplied by 2. It does not make a difference. Why? It's because even if I multiply by 2, it's just going to double the value. But the operation that I want to do on it, the information that it is giving it to me, that's the same. So that's the reason eigenvectors are so important. And what are eigenvalues? The values that we perform on these eigenvectors are all that are eigenvalues. It's that simple to understand. So that is all you need to know about eigenvectors. All the data which is not transforming anything is basically the data that you should be learning with. What are the applications that linear algebra helps us with? You have the first and foremost, which is the principal component analysis, PCA. It is used for dimensionality reduction and it helps increase the quality of data. Then you are working with applying transformations. It helps in encoding. It helps in the single value decomposition, where it is again reducing the dimensionality of a single value data. And then it is used for natural language processing, for latent semantic analysis, optimization of your deep learning models. All of this can be achieved through linear algebra. So it is a very important aspect of machine learning. Once we are done with all of this, let's start our coding for PCA. We will now be coding for principal component analysis. Let me show you how it really works. So I am having all the programs already prepared for you guys, so we do not extend this big tutorial even more further. Let me go to the presentation mode. So what happens over here is I am having these important libraries, which are import numpy as np. Then I have the pyplot as plt. And then from sklearn.decomposition, import the PCA. So principal component analysis is already present. I'm just going to import it from sklearn. So I'm going to get a range of around 200, 300, how much ever it is. After I'm getting that particular range, I'm going to get data. I'm going to get all of that data, and then I'm going to put it into my particular list. So what happens over here? I have np.dot and in the range of 2, 2, and it is in the range of 2, 200. So in the range of 2, 200, whatever numbers that you can randomly generate, please give it to me. And then dot t. Why is it dot t? It's because all of this which I'm going to get is basically in the form of a column. I do not want it in the form of a column. I want it in the form of a row. So that is the reason I'm using dot t. Dot t is used to transform it. So I'm just going to scatter that on the plot and then show it to you guys. That is what this particular function does. And then I am doing PCA is equal to PCA of n components is equal to 2. And then I'm going to fit the data into it. And then I have a function which is to draw the vector. So I'm going to do arrow props, dictionary style, all of that. I've just given the styling over here. And then I'm going to annotate and draw it accordingly. So this is my draw vector function. And then I'm just going to scatter plot everything that I had. So I have the vector. How am I going to get a vector? It's using this particular formula, which is the vector and 3 and np.sqrt. So what is PCA explained variance and components? Okay. So if you remember, I had fit PCA with the data that I have generated, right? So explained variance is basically going to tell me how much is the variance between my data points and what are the components that are really required that I look at and perform my analysis on them. So these are what the required components are for me. And after I do all of that, I'm going to get another vector. I'll show that to you guys. And then what I'm going to do is I'm going to find one component only over here and I'm going to fit the data. Okay. And I'm going to transform and perform the inverse transform so that I'm going to get a particular linear line which I can just look at and find all the important aspects of the data that I wanted to from it. Let me run the program and let me show you all the outputs. So as you can see here, this is all the data that I had generated using the dot function of the random generating thing. So this is all the random data that I have generated. Then what I did, I had to find out two components, right? Then what I had to do, I had to find out two components. What can I understand from this particular information? This one is a small vector. So this small vector means that this is the only amount of information that it can give. Whereas this vector is so long. What this means is that the longer the length of the vector is, the more information that it can pass to me. Simple enough, right? Longer the length of the vector, the more information that it can pass to me. So what all information I have through this particular vector, all of this is going to give me the best for my analysis. So that's what I'm going to do. I'm going to get all the data points that are according to this vector. So as you can see here, all of these data points are very, very important for my analysis. So this is how I converted such a big, huge data set into one particular line. And if I follow all these points, I'm going to get almost the same amount of information the whole data set is going to give it to me. As you can see, this was such a huge data set, but it's just come up to just one line. It's so easy. Think if you're working with tons and tons of data, it becomes really difficult when you're working with it. That's the reason use PCA, and it's just not use PCA. Make sure that you're able to reduce the data as much as you can so that you can get at least all the amount of information that you can from that particular data. You do not need all the data, but you need the information from that data. That is basically how PCA works. I hope it was clear to you guys. So basically that was all we needed to learn from linear algebra, and I hope it was clear to you guys. So now that we know all about vectors, let's move over to multivariate calculus. Multivariate calculus is one of the most important parts of the mathematics in machine learning. It helps us solve the second most important problem that we were facing in developing machine learning models. The first problem is obviously the pre-processing of the data. The next is the optimization of the model. Multivariate calculus helps us to optimize and increase the performance of a model and give us the most reliable results. So how does something that almost half the class hated help us solve such a problem? So let's break all the ice that's surrounding this, but before that we need to understand the basics. So let's calculus. So the first topic in calculus is a differentiation. Differentiation is basically breaking down the function into several parts so that you can understand every element and analyze it in depth. They are very helpful in finding the sensitivity of a function to the varying inputs. A good function gives you a good output, which can be described using a rather easy equation. The same cannot be said for a bad function. So for example, right here I have y is equal to e power x. It is really easy to tell that, okay, if it is e power x, this is going to be the graph for it. But look at y is equal to 1 by x. It is such a horrendous graph that I cannot explain it using a particular equation. Those are the types of equations. Those are the good functions and the bad functions. We know all of this, but what are we really after? So let's do all of that right now. Okay, so most of us already know all of this, but what are we really after? So let's understand that with a really simple example. So let's assume that we have a car moving in a single direction only and is already in motion. So if we plot a graph of its speed versus time, it communicates to us how the speed varies as the time keeps increasing and it halts after a certain point. Now if we want to know the rate at which the speed varies with respect to the time, it turns out to be that we are actually finding the acceleration. The acceleration of the car can be plotted as follows. So what this means is that acceleration is actually a derivative of speed, because the speed we have here is just the magnitude and does not hold any more factors, just for simplifying everything. So if there was no speed, there would be no acceleration. It's as simple as that. Now that we have the acceleration, we can justify whether the car had a varying or a constant change in its speed, whether it was moving or not, and much more. But in this case, that is all we need. Now think that you want to find the change in acceleration between a certain range in a time span. Okay, we mark 2 points, x and some variable which is a small portion more than x. We can denote this using x plus delta x. So let's denote this on the graph so you can see it as it's shown over here. Now we know that this range has many values in between, but what if we want to know the rate of change only between one point and the next? We know that this is really kind of impossible, because between a range there are countless numbers as the function is continuous. Thus we approximate that the limit or the step between two input variables is 0. Remember that this 0 that we are assuming is only the smallest possible value that we can make up, and it is not the absolute 0. If we ever work with absolute 0, we would never have had any functions at all. So if you are still confused, this number is basically some value of 0.00000. It just keeps going and then some numbers ahead, but it is never really 0. That is the only way that we can put this as. Okay, so now that we have understood what we are really trying to find, let's make it a general equation. So let's derive the derivation formula. So the derivation formula is f dash of x is equal to limit delta x tends to 0, which is not exactly 0, but we are assuming it to be 0 point something. So we are just going to write 0. And then we have f of x plus delta x minus f of x divided by delta x. That is how the formula comes into existence. This helps us find the rate of change between one point to the other. It is such an important concept as it plays a huge role in the optimization of machine learning models. You need to understand that this is the first order of derivation only. If we differentiate the output of the first differentiation, it becomes the second order differentiation and so on. But that is all the introduction we need from differentiation. So now that we have the basic idea and formula of derivation, let's move over and understand some of the important rules that we need in differentiation. So the first rule that we will be talking about is the power rule. So whenever you have a function which has a variable with some power, you can basically use this formula and solve the equation much more faster. So for example, let's say that I had an equation called as f is equal to 3x square. So let me put this into the formula. So I have f dash of x is equal to limit x tends to 0, 3 of x plus delta x the whole square minus 3x whole square divided by delta x. So x plus delta x the whole square becomes a formula. Let me expand it. And then this is what I actually get. Plus x square and minus x square get cancelled. And then I have delta x which is being removed out of there. So delta x and delta x also get cancelled. Then I have 3 into delta x plus 2x. So I'm going to put the value of delta x is equal to 0 into the equation, which is not exactly 0, but it is so small that I can ignore it. So I have 3 into 2x, which becomes 6x. So that's how I had to solve the whole entire equation, right? So what about the power rule? Power rule is just 3 and whatever number I had, right? So if it is 3x square, let me take out 3 because 3 I am going to treat it as a constant. So x square. So x to the power of 2. So then what I do? I bring 2 down, which is n, and then I have x of n minus 1. So it is 2 minus 1. So it becomes 3 into 2x, which is equal to 6x. So I get the entire same answer, but I just had to do it in 3 steps. I can actually do it either in 1 step, but just for simplification, I've done it like this. The next rule that we are going to be studying is the rule of sum. So if you have a particular function which is the sum of two variables, their differentiation's sum also is the differentiation of the whole function. So if you have f of x1 plus x2, it will be x1 dash plus x2 dash. A simple example will be 3x square plus 5x. Okay, so I'm going to solve the equation right now. 3x square, I hope you remember, I just showed it to you before. And the same thing goes for 5x also. So 5x plus 5 delta x minus 5. And then I'm going to just, cancel out 5x's. And then I have delta x being cancelled out. And then I have x square minus x square being cancelled out. So the whole same process goes on. Then delta x gets cancelled. Then I have 6x plus 5. So I'm going to use the same rule that we learned earlier. That was the power rule. And then I have 3 into 2x plus 5. So I get 6x plus 5. This is basically how the sum rule works. Next, I have something called as the product rule. So if I have a function which is in the form of x into 2x or something like that, the differentiation is very simple. This is how the differentiation looks. If it is f dash of x1 into x2, that is equal to x1 dash into x2 plus x2 dash into x1. That is how you're going to find out the differentiation. And the next rule that we are going to look at is the chain rule. So basically, if I have f dash of g dash of x, it will be f dash of g into x dot g dash of x. This is a very simple example and it's really easy to understand. So if you want to learn more about the common functions, I have my blog which is also put up in the description. And you can go ahead, click over there and learn more about the common functions. Okay. So now that we have understood all the basics that we really needed from differentiation, we'll now be moving over to partial differentiation. Partial differentiation is an important concept that most of us have ignored throughout our academy. What has partial differentiation helped us achieve might be the question that most of you may be having right now. So let me give you an example so that you can understand its importance. Okay. Suppose you are a car designer who deals with the exterior of the car only. You have been given the task to maximize the performance of the car. So how do you do that? You do not go into the car, you do not take out the engine, you do not tune the engine. You are not supposed to do any of that. You just are going to change the particular exterior of the car. So what's happening over here? You know that even the engine and all the other tires and all that, all those are variables also that come to making the car better in its performance. But you are not going to do that. You're not supposed to do that, because you are only going to deal with the exterior of the car. Those variables of the engine and all of that, those are kept constant. If those are kept constant, that means that those variables will be performed by somebody else. You are just going to look at your particular variable that you have to change. That is the exterior of the car. So this is how partial differentiation comes into play. You are just going to change one particular variable. All the other variables become a constant. Okay, it's that simple. So what do? You would change the windshields, change the body if necessary, air vents, and many, many more. I've just given whatever I could find. You are just changing what is necessary. That is basically what is partial differentiation. So what are the equations that partial differentiation goes according with? Now, if you can see, it is the f dash of x, y, and z. If you remember the previous slides, we were just working on one variable, that is x, which is x1, x2, which may be x squared, 3x, 5x. It was all on x. Partial differentiation is not like that. It is x, y, z, whatever variables it can find. So that is what makes partial differentiation much more realistic, much more easier to understand. Because you are just going to change your factors, your variables. You're going to keep everything else constant. So let's say, for example, you have to find it with respect to y. So y and z become a constant, f dash of x. If you want to find it with respect to y, x and z become a constant, f dash of y. With respect to z, x and y become a constant, f dash of z. So what is the complete differentiation? It is the addition of all the three differentiations that we've just found out. So this is how partial differentiation works. Let's show you an example. So if I have a function which is x square plus 3y plus 4xz square, how am I going to find the differentiation of this? So with respect to x, y becomes a constant, so it is 0. And then you have 2x plus 4z square. So with respect to y, x square plus 4xz square become a constant, so I'll just have 3. So with respect to z, it will become x square becomes a constant, 3y becomes a constant, and then 4xz square is what I am going to differentiate. So I will have 8xz. So what is the total differentiation? It is a 2x plus 4z square plus 8xz plus 3. So I hope you've understood this really simple example of it. So this is how partial differentiation works. So what are the applications that multivariate calculus comes into play? We have something called as the Jacobian vector. Now what is the Jacobian vector? It is basically differentiating the vector once. Jacobian is basically differentiating the vector once and then putting it into the form of a matrix. That becomes the Jacobian vector. It helps in finding the global maximum of the data set. It is pointing to the maximum data that is there in the data set. And it also helps in linearizing a non-linear function to a linear at a particular point. So that's how the Jacobian helps. So differentiating the Jacobian or differentiating the actual vector twice gives us the Hessian. And it is used in minimizing the errors. It is used in deep learning models, gradient descent for optimizing all the weights and all of that. So that is how multivariate calculus helps us in real life. Let me show you how the gradient descent works. I already have code ready for you guys. Let me go back to the presentation mode. I have a particular import, which is the numpy. And then I have the sigmoid function, which is basically 1 divided by 1 minus e to the power of minus SOP. So this is what I'm going to return back to it. And then I have the error, that is a predicted minus target whole square, or x to the power of 2. This is what the error is basically. And then I have the errors derivation, which I'm going to use over here. So that is basically 2x or 2 into predicted minus the target part. And then I have the actual function over here, which is sigmoid into 1 minus sigmoid, which is the activation function, which is basically trying to find if my particular model is working or not. And then I have the derivation of it, which is just basically x. And then I have the updating function of the weight. So I'm just going to get the weight, I'm going to get the gradient, and I'm going to get learning rate. And I'm going to basically keep trying to, find out the best way that I can find my weight. So here's my function. I have x is equal to 0.1, which is my input. And then I have the target, which is 0.3. and I'm going to have a learning rate of 0.01, and then I'm going to get a random number, which is the weight of it, and then this is the initial weight. What I'm going to do then is I'm going to find the value of y and x, and I'm going to find the errors also. And then I'm going to find all the gradients, and then I'm going to pass the gradient into it and then update the weight. Let me show you an example now how increasing the number of steps is going to make me reach my target much more better. So as you can see, my initial weight was 0.50 thing and all that, and I have just run this for 10 times, right? Let me change this to 1000. My input is 0.1 and this is 0.3. I have to make 0.1 as 0.3, right? So let me run this again. It is still at 0.50. Let me add another 0, which is 10,000 times. Let me run this. So as you can see, it has now become 0.47, which is much more better than what we were actually doing. Let me add another 0 over here. So this is going to take a lot of time because the amount of, steps to be performed are more. But as you can see over there, which was 0.5 previously has now come up to 0.36, which is much, much better than what we were actually getting. Let me add another 0. Let me run it again. 4.6, 4.4, 4.0. As you can see, it is reducing. It's just reducing. The input and our output is almost close enough. What we really needed, the target was 0.3. And as you can see here, we've already reached 0.30 and all the numbers that are succeeding it, right? If you remember, we had 10 steps, which would just give us 0.50 or 51 something. Now for the amount of times it has learned, it has become much better than what we were previously getting. So now it is 0.300002 something. It's still reducing. It is still reducing. So this is how the gradient descent works. It keeps repeating, learning. This is the final output that we've achieved. 0.30000577, and it is much better than what we were already getting from the output. So this is how the gradient descent works. It uses differentiation. Where is the derivation over here? This is my derivation function. This is my derivation function. So these derivation functions are what are helping me to get my new error. And then put that into the gradient descent function, and then basically find and make my weight much more better so that I can get the output, which is from my input 0.1, I have to get the target of 0.3. So I hope you've understood how the gradient descent works. It keeps going in, and it uses differentiation a lot. So I hope that was very easy for you guys to understand. So with that, we have come to the end of all that was required from multivariate calculus. Let's move over to the next topic, which is probability. So what is probability? Probability is measuring how likely an event will occur. What this means is that how much are you sure, or how much quantity that you can give to your sureness that this particular event is going to happen. So that is what is probability. It is the ratio of the desired outcomes by the total outcomes, right? So with that particular formula, you will be able to understand what is the probability. It is the desired outcomes by the total outcomes. So always remember that probabilities always come up to 1. So if you have 0.6, that means you have a 60% probability that this particular thing will happen. If you have 0.6 of something happening and 0.4 of something not happening, they always sum up to 1. Remember, probabilities always sum up to 1. So some examples that I've given over here are rolling a dice. There are 6 possibilities, right? So every possibility has 1 outcome out of the 6 outcomes. So for example, the probability of getting a number 2 is 1 by 6. So that is the probability of getting a number 2. This is basically what is probability. So what are the terminologies that you need to understand when it comes to probability? There are 3 things, okay? You need to understand what is a random experiment, what is a sample space, and what are the events. Let's understand all of these terminologies one by one now. So what is a random experiment? It is an experiment or a process for which the outcome cannot be predicted with certainty. So for example, if I give you a dice, okay, and I tell you to roll it and tell me the number that you're going to get it, you are not sure because that's a random experiment. You have this uncertainty whether this particular event will happen or not. Okay. So that process where you roll a dice and all of that, that is a random experiment. So what is the sample space? The entire possible set of outcomes of a random experiment is the sample space of that experiment. It's really simple, right? I tell you to roll a dice, there are 6 outcomes. So it can be either 1, 2, 3, 4, 5, 6. That particular range of 1, 2, 3, 4, 5, 6 is the sample space. It is all the possible outcomes for the random experiment that you've been doing. Simple enough. So what is an event? An event is one or more outcomes of the experiment. So if I told you roll the dice, you get a number 1, that is an event. You roll the dice again, you get a number 6, that is an event. So what outcome you get from your random experiment is called the event. There are 2 types of events. There are joint events and disjoint events. Let's understand both of these. So joint events have common outcomes, right? Joint events can be together. That is what is a joint event. For example, you have a student who can get 100 marks in statistics and 100 marks in probability. The outcome of a ball that can be delivered can be a no ball also, and it can be a 6 also. And it can be possible are called joint events. Disjoint events do not have common outcomes. So the outcome of a ball that is to be delivered cannot be a 6 and a hit wicket or something like that. Okay. So a single card cannot be a king and a queen together, and a man cannot be alive and dead at the same time. So those are disjoint events. Those are not at all possible to happen. Now that we've understood all the types of events, we need to understand the distributions. So now we have 3 distributions that come under probability. We have the probability density function, we have the normal distribution, and central limit theorem. So let's understand all of these distributions one by one. So the first one is PDF, probability distribution function. So the probability now can be described using an equation. The equation that describes a continuous probability distribution is called the probability density function. I hope it's very clear to you. If it is not, let me just simplify it even more. You have a function which is going to describe the probability of something happening in the form of a graph. It's that simple enough to understand. You have a function which will give you the probability which you can plot a graph on. So that is the reason it is a continuous probability distribution. Okay. As you can see here, you have A and B. Between the range of A and B is the most likely that something is going to happen. So now that you've understood what a PDF is, let's understand the properties of the PDF. The graph of the PDF will always be continuous. It's simple enough to understand that. Then the area bounded by the curve of the density function and the x-axis is always going to be 1. And the probability that a random variable assumes a value between A and B is equal to the area under the PDF bounded by A and B. What this means is basically if you have any particular value or any particular probability that is between A and B, it is going to be equal to the area that is bounded by A and B, the probability value. So that is basically what a probability density function is. So next we have the normal distribution. So what is a normal distribution? It is a probability distribution that associates the normal random variable x with a cumulative probability. So how do you find this particular cumulative probability? It is using this formula, which is y is equal to 1 by sigma into the square root of 2 pi into e to the power of minus x minus mu into 2 divided by 2 sigma 2, where x is the normal random variable that we have just taken up, then mu is the mean and sigma is the standard deviation. And this is how the normal distribution looks like. The graph of the normal distribution depends on basically 2 factors, which is the mean and the standard deviation. So the mean determines the location of the center of the graph and the standard deviation determines the height of the graph. So if you have a very big deviation between, your variables, it becomes a very short graph and very wide graph. Whereas if you have a good deviation, which is, very less, you will have a tall graph. That is basically what's going to happen over here. That is all we have from normal distribution. Then the central limit theorem. So this is basically a theorem which is stating that the probability is always going to be in the center of the graph. Let me tell you the statement of this. The central limit theorem states that the sampling distribution of the mean of any independent random variable will be normal or nearly normal if the sample size is large enough. So what this basically means is that the distribution of your mean or your samples are always going to be near the center or always going to be near the mean of your graph if your sample size is much large enough. So what this means is that if your sample size is very big, it is going to be a normal distribution. It is as simple as that. So as you can see, if I have n is equal to 1 component, you can see the graph as it increases to 3, as it increases to 10, as it increases to 50. So as you can see, it almost becomes nearly identical to a normal distribution. So that is what the central limit theorem is. So once we are done with that, we will look at the types of probability. We have marginal probability, joint probability, and conditional probability. Let's understand each of this. So what is marginal probability? Marginal probability is the probability of occurrence of a single event. If I flip a coin, it is going to be either a head or a tail. That occurrence of that single event is called as a marginal probability. So for example, I have a deck of cards here and I randomly take out a card from there and I want it to be a hard card, right? So that will be the probability, which is 13/2, and it can be expressed by this particular formula. So once we are done with marginal probability, let's go to joint probability. What is joint probability? It is the measure of two events happening at the same time. So the same example over here, I have a deck of cards out of which I want to take out the ace, which is a hearts. So it has to be a ace card and it has to be a heart card, which will be the probability giving me 1/52. So now that we've understood what is joint probability, let's understand what is conditional probability. So the probability that depends on something already happened is called as the conditional probability. It is basically the outcome of the event is based on the occurrence of a previous event or an outcome. Conditional probability of an event B is the probability that an event will occur given that A event has already occurred. What are the two types of formula that we have in conditional probability? If A and B are dependent events, then the expression for the conditional probability is given by P of B by A is equal to P of A and B divided by P of A. If A and B are independent events, that means the expression will be P of B only. So it is just the probability of B occurring. Whereas if they are dependent events, means that if you want to find the probability of B, A already has to be occurred. So it is a probability of A and B divided by the probability of A. So that is basically all the introduction that was required from probability. We now have Bayes' theorem. So what is Bayes' theorem? It shows the relationship of one conditional probability and its inverse. What is Bayes' theorem? It shows the relation between one conditional probability and its inverse. So this is the formula, that is P of A by B is equal to P of B by A into P of A divided by the P of B. So what does this particular thing mean? So what we are trying to find out is the probability of the occurrence of A given that B has already occurred is equal to the probability of B occurring when A is already there and the P of A, which is the prior probability, which is something that we already think of, and then the probability of B occurring. So this is basically what the Bayes' theorem is. Let me give you an example for it, okay? Suppose you're a doctor and you're running a clinic where you test if a patient has a liver problem or not. All the previous patients that had come to you, out of them, 10% of your patients had liver problems, okay? So all the patients that had come before, they had around 15% probability that they were drinking. So now we have found out the probability of A and probability of B, the prior probability and the probability of B. So what was the probability that out of all of those patients, even though they had a liver problem, they were drinking? It is 5%, which is P of A by B. Hence, the Bayes' theorem says that the probability that a new patient, whoever is entering, will have a particular liver disease is calculated by 0.05 into 0.10 divided by 0.15 is equal to 3.33%. What this means is that if a new patient is going into the clinic, there is a chance of 3.33% that that particular person is also having a liver problem. This is basically how the Bayes' theorem works. So what are the applications of probability? Probability helps you to optimize your model. Classification of our algorithms also requires probability. The loss can also be calculated using a probability. Then models are built on probability. So let me show you how the naive Bayes classifier works over here. So let me go to naive Bayes. This is the knife based classifier. So let me tell you what I have done over here. I have imported the data sets, the metrics, and all the required knife based classifier, and I've imported the Gaussian knife based classifier. The Gaussian is also another name for the normal distribution. Okay, so normal distributions are also called as the Gaussian knife based classifiers. And why I have done this is because I had visualized it and I came to know that it was a normal distribution. Okay, so I load the iris, that is the load iris dataset, and I load a model, and then I'm just going to fit the model. Okay, then I'm going to get the predicted model of it, and then I'm just going to, basically find all the metrics of it. So basically, let me show it to you. What is the precision, recall of all of that? So this is all the accuracy. Then my model has an accuracy of 96%, and this is the confusion matrix, which means that out of 50 it was able to classify all the 50 correctly. Then out of 50 it classified 47 correctly and 3 were wrong. And then out of 50 again over here, 3 were classified wrong and 47 were classified correct. So this is the knife based classifier. So as you can see, probability is actually being used in all of this. The Gaussian knife based classifier already does all of that. So we do not need to, worry about it much more. So now that we have finished up everything that we needed to do from probability, let's move over to the last topic for today, statistics. What is statistics? Statistics is an area of applied mathematics concerned with data collection, analysis, interpretation, and presentation. What this means is that you are going to analyze, understand all the data that you've collected and how you're going to present it. So for example, your company has created a new drug that may cure cancer. How would you conduct a test to confirm the drug's effectiveness? What are you going to do? You are basically going to collect a large amount of people around. You're going to take all of those people. You're going to, give them basically the new drug that you have created, and then you're going to interpret all the results that you get from it, and then you're going to present that out of, let's say, 1,000 people, around 900 of them were cured or 950 were cured. So all of those parts come under statistics. Okay, so I hope you've understood that. What are the terminologies that you need to understand when you work with statistics? There is population and there is sample. So what is population? It is the collection or a set of individuals or objects whose properties are to be analyzed. All the data that you have collected is called as the population. So out of all the data that you've collected, you take out a set of data for your analysis. That set of data is called a sample. So what is a sample? A subset of the population is called as a sample. So a well-chosen sample will contain most of the information about the population parameter. So how do you choose the sample? The sample needs to be chosen such that all the data that the population is trying to convey can be conveyed through the sample itself. So that is what is population and sample. Now that we've understood the basic terminologies, let's look at some of the sampling techniques that we have in statistics. So sampling can be classified as probabilistic and non-probabilistic type of approaches. So in probabilistic sampling, we have random sampling, systematic sampling, and stratified sampling. In non-probabilistic one, we have snowball, quota, judgment, convenience, and all of that. Okay. So, but for machine learning, we do not need to take a look at the non-probabilistic approach. We just need the probabilistic approach. So we will be now covering about random sampling, systematic sampling, and stratified sampling. So let's go ahead with that. So what is random sampling? You take out a sample randomly out of the population. That is basically what is random sampling. Each member of the population has an equal chance of being selected in the sample. So that is what is random sampling. So what is systematic sampling? Systematic sampling is basically you follow a particular order out of which how the sample has to be taken. As you can see here, I have 6 particular groups. Now from this 6 particular groups, I'm going to take all the even ones, right? So that will be 2, 4, and 6. That is basically how the systematic sampling works. I follow a system. I follow an order of how I'm going to take the sample. So once we are done with that, what is stratified sampling? What is a stratum, first of all? A stratum is basically a subset of the population that shares at least one common characteristic, which is the gender, which I have taken over here. So as you can see here, I have the whole population, out of which I have found out one property that is common between all of them. that is gender. They are either male or female. So I'm going to break the whole population based on that. I'm going to break my population into the male subset and the female subset. So after that, I'm going to apply the random sampling, and I am going to take out all the samples that I am going to be needing. Okay. So once I have now broken down my particular subsets, now I'm just going to be using random sampling and take out all the samples that are required by me. So this is what is stratified sampling. So what are the types of statistics that we need to infer from? We have descriptive statistics and inferential statistics. So let's understand each of these right now. Okay. So what is descriptive statistics? Descriptive statistics is mainly used to focus upon the main characteristics of the data. It provides the graphical summary of the data. So as you can see over there, descriptive statistics uses the data to provide descriptions of the population, either through numbers or calculations or graphs or tables. Okay. So as you can see here, I have my shirt, and there can be either three particular sizes. There can be the most minimum one, the most average one, and the most maximum one. And all of that is based on the weight of the person. Suppose, for example, if a person weighs 60, he's going to get the maximum one. If the person weighs 40, he's going to get the average one. The person weighs 20, he's going to get the minimum one. So that is how I am describing my data, and I'm going to infer data from it. So that is descriptive statistics. So what is inferential statistics? Inferential statistics makes inferences and predictions about a population based on the sample that is being taken from it. So what this means is basically I'm going to generalize a large data set and apply probability and draw a conclusion to it. So it allows me to, infer data parameters based on the statistical models which is using the sample data. I have a whole bunch of population, out of which they can tell me they have either the large size or the medium size or the small size. So according to their sizes, I'm going to supply them the t-shirts. So this is basically what are the two types of statistics. There are descriptive statistics and inferential statistics. Descriptive statistics, what does it do? It describes the data. Whereas inferential statistics takes information from the data and then analyzes accordingly to however we want it to. So these are the two types of statistics. Let's go in depth with descriptive statistics. What is descriptive statistics? It is used to describe and understand the features of a specific set of data. So what is descriptive statistics? It is a method used to describe and understand the features of a specific data set by giving short summaries about the samples and measures of the data. In descriptive statistics, it is broken down into the measures of center and the measures of variability. So what does measures of center have? Measures of center has the mean, median, and the mode, whereas the measures of center have the range, interquartile range, variance, and standard deviation. So let's understand all of this right now. So for example, here you can see that I have a data set of a car which contains the variables, the car, the mileage, the cylinder type, the displacement, the horsepower, and the real axle ratio. So I'm going to find out the mean. So what is a mean? Mean is the average of all the samples. So for example, if I want to find the mean of the horsepower, I'm going to just add the values and divide it by the number of values. So I get 103.625. This is the mean of the horsepower. So what is the median? It is the measure of the central value of the sample set. That is what is a median. So let me show you how to find it for the miles per gallon. To find the order of the center value, you have to basically arrange it in the ascending order. Okay. So you have 21, 21, 21.3, 22.8, 23, and accordingly. Now I have to take the two middle values. Okay. So that will be 22.8 plus 23 divided by 2. That becomes 22.9. So that is the median of my sample. Next, let's move over to mode. The value which is most recurrent in the sample set is called as the mode. So let me find the mode for the cylinder type. What is most recurring? The 6-stroke or the 4-stroke? I can see here that there are 1, 2, 3, 4, 5. So there are 5 times that the cylinder's type of 6-stroke has been repeated, and 3 times cylinder type 4-stroke has been repeated. So 6 becomes the mode of the data. Okay. So now that we have understood all that is required from measures of center, let's move over to the measures of spread. So a measure of spread is also called as a measure of dispersion, is used to describe the variability in the sample or the population. Okay, so the first one is a range. Range is the given measure of how spread apart the values are in a data set. So it is the maximum value minus the minimum value, which gives us the range. So what is an interquartile range? Quartiles tell us about the spread of the data by breaking the data into many quarters, just like the median breaks itself. So for example, if I have 8 datas over here, I can break it down into 3 quarters, where I have a 1, 2, then I have 3, 4, 5, 6, and 7, 8, which become different samples accordingly. Okay. How do I find what is the interquartile range? So how will I find the interquartile range of this? Okay. So the first quartile Q1 comes between the 25th and the 26th. So it'll be 45 plus 45 divided by 2. That becomes 45. The second one comes under 50 and 51st. And that'll be 58 plus 59 by 2. That'll be 58.5. And the next one comes at 75 and 76. That is 71 plus 71 divided by 2, which is always 71. So that is basically what is an interquartile range. It is the measure of variability based on the dividing set into the quartiles. So that is basically how you break down the interquartile range, and it is the measure of variability based on dividing the set into quartiles. So quartiles divide a rank ordered data set into 4 equal parts, which would be Q1, Q2, and Q3 respectively. And the interquartile range is measured by Q3 minus Q1. So if you can see this, you have the whole data, which is 100%, and you have broken down the data into 25% each. So the quartiles come in between the first Q1, Q2, and Q3. So those are the interquartile ranges. So now that we've understood that, let's move over to variance. So variance describes how much a random variable differs from its expected value. It entails the computing squares of the deviations. So that is how you find the variance, which is s square is equal to the summation of 1 to n is equal to 1, xi minus x bar, the whole square divided by n. So xi is the value and x bar is the mean. I hope that's simple for you to understand. What does a variance mean? It means the difference between the data which it should have actually been. So what does the variance actually try to tell you? Okay, it basically means that the data which should have been something and what it really is, what is the difference between them, how much it differs from each other. So that is what is the variance. So what is a standard deviation? Deviation is the difference between each element from the mean. So I have xi and I have the mean. What is the difference between each of them is the deviation. So what is the population variance? The population variance is given by this particular formula, that is sigma square is equal to 1 by n. The whole summation of I is equal to 1 to n is equal to xi minus mu the whole square. Once we have found out the population variance, what is the sample variance? So it is s square is equal to 1 divided by n minus 1, the summation of I equal to 1 to n, and xi minus x bar the whole square. That is the sample variance. So what is the standard deviation? Standard deviation is the measure of the dispersion of a set of data from its mean. What the standard deviation is trying to tell you is basically that how much this data is trying to disperse from its actual data. So how is that given by? It is given by 1 divided by n, summation of I equal to 1 to n xi minus mu the whole square, which is basically the variance's square root. So that is standard deviation. So how do you find the standard deviation? I'm just going to give you an example over here. So say for example, Daenerys has 20 dragons and they have the numbers accordingly. So how do you work out the standard deviation? So the mean is given by adding all the numbers, dividing it by 20. So mu is equal to 7. And then what is the standard deviation? So it'll be xi minus mu the whole square. So it'll be 9 minus 7 the whole square is equal to 2 square is equal to 4. Then you have 2 minus 7, all accordingly. You keep on going and you get the following results, which is 4, 25, 4, 9, 25, 0 accordingly. Once you have done that, put that into the formula. So you have this formula accordingly. So we get the variance square is equal to 8.99 and the standard deviation will just be the square root of 8.9, which will be 2.983. What this means is that with a value of 2.983, the values are differing from the mean. So if you are trying to add 2.983 to all the other values, you will be getting something which is much more similar and much more realistic and much more, closer to the mean of the. So that is how standard deviation works. Now that we've understood all of that, we have a very classic example of information gain. So what does information gain help us with? This is an ideology that comes into picture for decision trees. So let's understand the basic concepts of what we require in information gain. So the first topic that we need to understand is entropy. So what is entropy? Entropy measures the impurity or uncertainty that is present in a data, and it is given by the formula h of s is equal to minus summation of minus 1 to the power of n p of I log base 2 p of I, where s is all the instances in the data set, n is the number of the distinct class values, and p of I is the event probability. Because entropy is the impurity that a data has. So what is information gain? Information gain is how much information a particular feature will give to the final outcome. So that is given by gain of A of s is equal to h of s, which is the entropy, minus summation of j is equal to 1 to v, s of j divided by j into h of s of j is equal to h of s minus h of a by s. H of s is the entropy of the whole data set. S of j is the number of instances with j and a value of attribute a. S is the total number of data sets. V is the distinct value of attribute a. H is the entropy of the data set with value a, and entropy of attribute a. So these are all the requirements. So let me give you an example of information gain. You can see the data set over here, which is for 14 days, and the particular, attributes that are given to it. So the forecast is to find out whether the match will be played or not according to the weather conditions. So this is what we are trying to find. Here we have 5 no's and 9 yeses. So we have the outlook, and then we have sunny, overcast, and rainy. So in sunny, we have 3 no's and 2 yeses. In overcast, we have 4 yeses and 0 no's. And in rainy, we have 3 yes and 2 no's. So how are we going to find out which particular node is going to, attribute the most to it? So let's find out the entropy first for the whole data, which is 9 instances say yes and 5 instances say no. So we have a minus 9 by 14 log base 2 of 9 by 14 minus 5 by 14 log 2 of 5 by 14 is equal to 0.940. So what this means is that the data that we have has 0.940 times bad data. Means it cannot give us much information. There is much more impurity in the data. So let's move over. The first step in information gain is to find the root variable. So how are we going to find the root variable? We are going to take all of the attributes and find the information gain from them. We have outlook, we have windy, humidity, and temperature. So let's find out the information gain. So for information gain of windy, we have 6 instances true and 8 instances false, right? So h of s is equal to 0.940 minus 8 into 14, and as you can see, all the other variables. So the gain that we have achieved from windy is 0.048, which is really, really less. So for outlook, the same thing happens over here. We have the information gain that is being passed by it is 0.247. Then we have the information gain from humidity, that is 0.15, which is also really good. And then we have temperature, which is 0.029. You can pause and look at the steps if you want to. Out of all the gains that we have, the variable with the highest information gain is used to split the data. So outlook has 0.247, windy has 0.048, gain has 0.151, and gain of temperature is equal to 0.029. So what are we going to choose? We are going to choose outlook. Why is that? It's because it has the highest information gain. So that becomes our root node. That is a simple example of how statistics is used in the information gain. Next, let's move over to the confusion matrix. So what is a confusion matrix? Confusion matrix is a table that is often used to describe the performance of a classification model. So it is a table that is used to describe the performance of a classification model on the set of test data. So how are you going to calculate the accuracy of this? It will be true positives plus true negatives divided by true positive, true negative, false positive, false negatives. So if you are confused with what is true positive, true negative, false positives, false negatives, let me explain that to you right now. Let's say, for example, there are 2 possible predictor classes which are yes or no. The classifier made a total of 165 predictions. That means 165 predictions were total. So out of the 165 cases, the classifier predicted yes 110 times and no 55 times. So in reality, 105 patients only had the disease and 60 patients did not. So how are we going to put this into the table? So as you can see here in the table, we have n is equal to 165. Then we have predicted no and predicted yes, actual no and actual yes. So if our classifier predicted it no and it was actually no, that is the correct output. If it predicted yes and it was actually yes, that is also the correct output. But it predicted it as yes and it was actually no, that means it has made a mistake. And it predicted no but it was actually yes, it has still made a mistake. What are the correct values over here? Which is 50 and 100. So 50 and 100 are the correct values and 10 and 5 are the wrong values. What is a true positive? True positive are which it was predicted as yes and they actually have the disease. True negatives are predicted no and they did not have the disease. False positives are classifier predicted it as yes but they did not have the disease, and false negatives we predicted no but they also had the disease. So this is basically what a confusion matrix is, and it is helpful in finding out the performance of the classifier that you are working with. So that is what is a confusion matrix. Next comes inferential statistics. It is a method where we infer and understand what the data is trying to communicate with us. So it is broken down into 2 points. It is point estimation and interval estimation. So let's understand about point estimation. Point estimation is concerned with the use of a sample data to measure a single value which serves as an approximate value or the best estimate of an unknown population parameter. So we have such a huge population of India, right? Out of that, you're just going to randomly take out some sample of it. You're going to find out the sample mean, and this sample should be so good enough that it is going to estimate the whole mean of the population. So this is how you use point estimation and try to approximate it for the whole, population. So what are the different methods? We have methods of movement, methods of likelihood, Bayes estimator, and best unbiased estimators. So estimates are found out by equating the first k sample movements to the corresponding k population movements, which is the method of movements. And then we have the maximum of likelihood, which uses a model to maximize a likelihood function. Bayes estimator minimizes the average risk, and it is an expectation of all the random variables. And then we have the best unbiased estimators, which is used to find out the best depending parameter. So that is all that we require from point estimation. Let's move over to interval estimates. So an interval or a range of values is used to estimate the population parameters. So we have a point estimate and we have an interval which gives us the low confidence and the high confidence limit. How is this going to happen? There are 3 things that you need to remember. There is something called as the confidence interval, and it is the measure of your confidence that the interval estimate contains the population mean mu. So statisticians use a confidence interval to describe the amount of uncertainty associated with a sample. Technically, a range of values are so constructed that it is specified probability of including the true value of a parameter within it. So for example, let's take a sample where we have 10,000. So let's say that we have something called as a supermarket. So out in that supermarket, we have collected a lot of data. And in that data, I'm saying that this particular items, okay? So item 1 and item 2, if they both are kept together, they are going to be sold together. And I say that with 90% confidence. So that 90% confidence, okay, is what is my confidence interval. It can be in between this range. It can be between 90 to 95%. And between 90 to 95%, it is highly likely that that particular thing is going to happen. So that is my confidence interval. So what is the sampling error? It is the difference between the point estimate and the actual population parameter, which is the sampling error. Okay. So when mu is estimated, the sampling error is mu minus x bar. It is mean minus the point. What is the margin of error? So for a given level of confidence, it is the greatest possible distance between the point estimate and the value of the parameter it is estimating. What this basically means is that it is the greatest possible distance between what you have predicted and what it actually is, and what level of confidence you are giving to it. Okay, so that is the margin of error. How much error you can allow for the predicted model is what is the margin of error. So I hope you have understood that. So the level of confidence is the probability that the interval estimate contains the population parameter. So as you can see here, all the parameters that come under C, right, are what we are allowing. Okay, that is the margin of error that is allowed. But whatever comes in minus ZC and plus ZC, we are not going to take that. Those are the interval estimates. So finding these intervals is what is our probability. So finding these interval estimates is what is our work over here. Okay. So for example, if the level of confidence is 90%, this means that you are 90% confident that the interval contains the population mean. 0.05 and 0.05 of minus ZC and plus ZC is equal to plus 1.645 and minus 1.645. Those are the Z scores. Anything minus or plus of 1.645 is not allowed. So those are the values that we are concerned with when we are working with interval estimates. So now that we have understood everything we needed to from inferential statistics and descriptive statistics, let's move over to hypothesis testing. So what is a hypothesis first of all? It is some event that you have made up which may have the probability of happening or not happening. Testing that hypothesis is what is hypothesis testing. Is, formally checking whether this hypothesis is accepted or rejected. So how is the hypothesis testing conducted? You first state the hypothesis and then you formulate an analysis plan of how you are going to, test this particular hypothesis. Then you get all the output. You analyze the data that you've got from all of it. So then you understand whether this particular hypothesis has failed or it is a good hypothesis. Okay. Suppose I have 4 boys over here, which are Nick, John, Bob, and Harry. So they were caught doing mischief in the class and they have to now serve detention for almost 2 months. Okay. The detention is basically they have to clean the classrooms. So John over here comes up with an idea saying that I'm going to write all the names of ours into chits and then put them into a bowl. Whoever name comes out has to clean the classroom. So what happens here that we are going to assume that the event is free of bias. So our hypothesis is what is the probability of John not cheating? Let's find out what happens actually. The probability of John not being picked up for a day is 3 by 4. Now the probability just keeps increasing on and on if he is not picked up for 3 days. Okay, so it is 3 by 4 into 3 by 4 into 3 by 4 is equal to 0.42 approximately. And what is the probability of John not being picked up for 12 days? It is 3 by 4 into 12 is equal to 0.032, which is equal to 3.2%, which is less than 0.05, which is 5%. So what this means is that our hypothesis was that John is not cheating, but actually John is cheating over here because it has come down and it has come below the threshold value of 5%, which is 3.2%. So now all of us have come to know that John is cheating because he has not even written his name in the chits. So this is how the hypothesis works. So what is the null hypothesis? The hypothesis that we have created in the beginning, okay, that John was not cheating, that was a null hypothesis. It has no result which is different from the assumption. And we have an alternate hypothesis, which means that our results disapprove the assumption. We had a hypothesis that John is not cheating, but actually through our results, we found out that John is cheating. So this is what is the hypothesis testing. And we have a threshold value. If the probability that we are testing goes below this threshold value, it means that the particular hypothesis has failed. So this is what is the hypothesis testing. So now we need to know something about the P and T values. Okay. What is the P and T values? The P value and the T value help us in our hypothesis testing. Okay. We want to find the height of students who are greater than 5 feet and 7 inches. Okay. So we take a sample of 100 students and find that the mean height was 5 feet and 9 inches. Okay. We make a hypothesis that out of all the 100 students, there is going to be at least 6 students who are greater than 5 feet and 9 inches. So this is our P value. It is the probability value that we are saying that this particular hypothesis is going to be correct. We say that at least out of 100 times, 6 students will at least have a height which is greater than 5 feet and 9 inches. Okay. So this is the p-value. This is the probability value that we have given to a hypothesis. The t-value is testing this particular hypothesis and finding the difference that we have found out from our assumption and what we have actually calculated from our results. So this is how the p-value and the t-value help in making the null and alternate hypothesis. You find the result of the null hypothesis and the alternate hypothesis. So this is how the p and the t values help in making and observing the results from the null and alternate hypothesis. Okay. Let me show you a code where we are going to find the mean median mode accordingly and how that becomes helpful to us. Okay. So let me go back to the presentation mode. I have my data over here, which is this particular data. So I'm going to import statistics as S, and I'm going to just find the mean median mode of it. So let me just run this program for now. So as you can see here, the mean is 33.43 and the median is 3 and the mode is 2. 2 has been repeated the most number of times, so that is the reason it is the mode. And the variance is 5124 and the standard deviation is 73. That is how the mean median mode is calculated. Let me run the program now so that you can understand what we are trying to do. So let me close this out. What's happening over here is I have the iris data, which is the load iris, and then I am creating it into a data frame. Okay, simple enough. After that, I am saying that the species is the target and the data of species is equal to, I am going to just apply all the lambda parts of it. Okay, and then I am going to get the description of the data. And after that, what I'm going to do is I'm going to take this data and I'm going to pair plot it. And then I'm going to show the plot to you. So let me run the program. Let me show you the figure first. So I had 4 features over here, right? So that was the petal length, petal width, sepal length, and sepal width. So if you can take a look at this data, you can see that there is a normal distribution here. There's a normal distribution here. Also, there's a normal distribution over here with some exclusions over here. And there is the normal distribution here too, but with some exclusions here. So looking at this, I will be able to understand if I want to, apply the Gaussian naive-Bayes classifier or accordingly to however I wanted to. So this is how statistics has helped me to understand what is my data looking like. Now let me go back over here. So as you can see, this is the count of 150, right? Simple enough. Then what is the mean? What is the standard deviation? What is the maximum length and maximum width that you can find over here? All of this is done using the describe part of it. Okay. And describe is a function that is already available in pandas. So that was a very simple example of how I was able to understand how I have to use the Gaussian naive-Bayes classifier for my iris data, which I showed in the probability part, right? Now we are done with this. Let's go back to the presentation. So with that program, that brings us to the end of statistics and also to the end of our tutorial.
Now, machine learning and deep learning are just ways to achieve artificial intelligence. Now that you are familiar with artificial intelligence, let's talk briefly about machine learning and understand what it means when we say that we are programming machines to learn. Here I have a famous quote by Tom Michel of Carnegie Mellon University. He says, a computer program is said to learn from the experience E with respect to some task T and some performance measure P if its performance on T as measured by P improves with experience E. Now this might seem a little confusing, E, P, and T. So if you want your program to predict the traffic pattern at a busy intersection, let it be the task T, which I'm talking about. You can run it through a machine learning algorithm with data about past traffic patterns, that is the experience E. Now, the accuracy of the prediction, which is the performance measure P, or the prediction, will depend on the fact that whether the program has successfully learned from the dataset or not, and the dataset being the experience E. So basically, machine learning is referred to as a type of artificial intelligence that provides computers with the ability to learn without being explicitly programmed by exposing them to vast amount of data. Now, the core principle behind machine learning is to learn from the data sets and try to minimize the error or maximize the likelihood on their predictions being true. Even though machine learning had great advancement, there were some drawbacks of machine learning. So traditional machine learning algorithms are not useful while working with high dimensional data. That is where we have large number of inputs and output. For example, in case of handwriting recognition, we have a large amount of input where we have different types of input associated with different types of handwriting. Now, handling and processing such types of data becomes very complex and resource exhaustive. This is termed as the curse of dimensionality. Now, to understand this in simpler terms, let's consider the following image. Now, consider a line of 100 yards, and you have dropped a coin somewhere on the line. Now, it's quite convenient for you to find the coin by simply walking on the line. This very line is a single dimensional entity. Next, consider you have a square of 100 yards, and yet again you drop the coin somewhere in between. Now it's quite evident that you are going to take more time to find the coin within the squares as compared to the previous scenario. Now this square is a two-dimensional entity. Let's take it a step ahead by considering a cube of side 100 yards. Now you have dropped a coin somewhere in between. Now it's even more difficult to find the coin this time. The cube is a three-dimensional entity. Hence, you can observe that the complexity is increasing as the dimensions are increasing. And in real life, the high-dimensional data that we are talking about has thousands of dimensions that makes it very complex to handle the process. Now, the high-dimensional data can easily be found in use cases like image processing, natural language processing, and image translations. Now, machine learning was not capable of solving these use cases. Now, the second major challenge is to tell the computer what are the features it should look for. That will play an important role in predicting the outcome as well as to achieve better accuracy while doing so. Now, this very process is referred to as feature extraction. Feeding raw data to the algorithm rarely ever works, and this is the reason why feature extraction is a critical part of the traditional machine learning workflow. Therefore, without feature extraction, the challenge for the programmers increases as the effectiveness of the algorithm very much depends on how insightful the programmer is. Hence, it is very difficult to apply these machine learning models or algorithms to complex problems like object detection, handwriting recognition, and image processing. Now here comes deep learning to the rescue. Now, deep learning is capable of handling the high-dimensional data and is also efficient in focusing on the right features on its own, which is the process of feature extraction. So before we understand how exactly deep learning works, let's have a look at the applications of deep learning. So the first application of deep learning is speech recognition. Now, all of you might have heard about Siri, Cortana, or the Google Assistant. Now, Apple has also started investing on deep learning like the other big giants to make its services better than ever. In the area of speech recognition and voice-controlled intelligent assistant like Siri, one can develop more accurate acoustic model using a deep neural network and is currently one of the most active fields for deep learning implementation. In simple words, you can build such systems that can learn new features or adapt to you, therefore provide better assistance by predicting all the possible beforehand. Next on our list we have automatic machine translation. So we all know that Google can instantly translate between 100 different human languages, and that too very quickly as if by magic. The technology behind Google Translate is called machine translation and has been a savior for people who cannot communicate with each other because of the difference in speaking of language or because of some language barrier. Now, you would be thinking that this feature has been there for a long time, so what's new in this? Now, let me tell you that over the past 2 years, with the help of deep learning, Google has totally removed the approach to machine translation in its Google Translate. In fact, deep learning researchers who know almost nothing about the language translation are putting forward relatively simple machine learning solutions that are beating the best experts built language translation systems in the world. Text translation can be performed without any pre-processing of the sequence, allowing the algorithm to learn the dependencies between words and their mapping to a new language. Stacked networks of large recurrent neural networks are used to perform these kind of translations. Next, we have instant visual translation. So as you know, deep learning is used to identify images that have letters and where the letters are on the scene. Once identified, they can be turned into text, translated, and the image recreated with the translated text. This is often called instant visual translation. Now imagine a situation where you have visited any other country or any other place whose native language is not known to you. Well, no need to worry. Using various apps like Google Translate, you can go ahead and perform instant visual translation to read the signs or the shop boards written in another language. Now, this has been possible only because of deep learning. Now, if we talk about automated self-driving cars, it's not something which isn't there. It's very well there and people are using it. Now, Google is trying to take their self-driving car initiative known as Waymo to a whole new level of perfection using deep learning. Therefore, rather than using old-handed coded algorithms, they can now program systems that can learn by themselves using data provided by different sensors. Deep learning is now the best approach to most perceptron tasks as well as to many low-level control tasks. Hence, now when people who do not know how to drive or are disabled can go ahead and take the ride without depending on anyone else. Now, if we talk about predicting the future, what deep learning does is that it can help us in predicting the earthquakes, tsunami beforehand so that the preventive measures can be taken to save many lives from falling into the clutches of natural calamities. Another implementation of deep learning is the chatbots. Now, all of you have heard about Siri, which is Apple's voice-controlled virtual assistant. Believe me, with the help of deep learning, these virtual assistants are getting smarter day by day. Now, chatbots also work with the help of deep learning. Now, if you might have used any of the online ordering apps like Amazon or Flipkart, you might have gotten. If you have ever visited or used the customer care services of any online or e-commerce website like Amazon, Alibaba, or in fact Flipkart, the customer care service to which you are interacting with might not be an actual human. So that is where chatbots are heavily implemented, and also in the transportation apps like Uber and Ola. Now, these chatbots can adapt itself according to the user and provide better personalized assistance. Now, there is a very cool application of deep learning which is the Google AI Eye Doctor. It is a recent initiative taken by Google where they are working with an Indian eye care chain to develop the AI software which can examine retina scans and identify a condition called diabetic retinopathy, which can cause blindness. Now, if we talk about artificial intelligence and deep learning in general, there is a dream reading machine. Now, this is one of my favorites, a machine that can capture your dreams in the form of video. With so many unrealistic applications of deep learning we have seen so far, I was not surprised to find out that this was tried in Japan a few years back on 3 test subjects and they were able to achieve close to 60% of accuracy. That is something quite unbelievable, yet true. Now, let's move ahead in this deep learning tutorial and understand how deep learning works. Now, basically, deep learning mimics the way our brain functions. That is, it learns from experience. As you know, our brain is made up of billions of neurons that allow us to do amazing things. When the brain of a 1-year-old kid can solve complex problems which are very difficult to solve even using supercomputers. For example, recognizing the face of their parent and different objects as well. Discriminating different voices and even recognizing a particular person based on his or her voice. Draw inference from facial gestures of other person and many more. Actually, our brain has subconsciously trained itself to do such things over the past years. Now the question arises, how deep learning mimics the functionality of a brain? Well, deep learning uses the concept of artificial neurons that functions in a similar manner as the biological neurons present in our brain. Therefore, we can say that deep learning is a subfield of machine learning concerned with algorithms inspired by the structure and function of the brain called artificial neural network. Now let us understand the functionality of the biological neuron and how we mimic this functionality in the perceptron or an artificial neuron. Now if we focus on the structure of a biological neuron, it has dendrites, which is used to receive the inputs. Now these inputs are summed in a cell body and using the axon it is passed on to the next biological neuron as shown in the above image. Similarly, a perceptron receives multiple inputs, applies various transformations and functions and provides an output. Now as we know that our brain cell consists of multiple connected neurons called the neural network, we also have a network of artificial neurons called perceptrons to form a deep neural network. Now, one can categorize all kind of classification problems that can be solved using the neural networks into two broad categories. One is the linearly separable problems, and the second one is non-linearly separable problems. So basically, a problem is said to be linearly separable if you can classify the dataset into two categories or classes using a single line. For example, separating cats from other groups of cats and dogs. On the contrary, in case of nonlinear separable problems, the dataset contains multiple classes and requires nonlinear line of separating them into respective classes. You guys might be familiar with AND gates. I will be using this as an example to explain how perceptron works as a linear classifier. So as you know, AND gate produces an output as 1 if both the inputs are 1 and 0 in all the other cases. Therefore, a perceptron can be used as a separator or as a decision line that divides the input sets of an AND gate into two classes. Class 1, inputs having output as 0, that lies below the decision line, and second class is inputs having the output as 1, that lies above the decision line or the separator. Now the diagram here shows the above idea of classifying the inputs of AND gate using a perceptron. So till now you understood that a linear perceptron can be used to classify the input dataset into two classes. But how does it actually classify the data? So mathematically one can represent a perceptron as a function of weights, inputs, and bias. Now each of the input received by the perceptron has been weighed based on the amount of its contribution for obtaining the final output. Now bias allows us to shift the decision line so that it can best separate the inputs into two classes. Now enough of this theory, let us look into the example of the perceptron learning algorithm where I will implement the AND gate using a perceptron from scratch. So for this purpose I am going to use Python. A few important things to note here that there are certain deep learning frameworks that can be used to achieve the solution. So there are TensorFlow, we have Theano, we have PyTorch. So what I'm going to do is use the most famous framework, which is TensorFlow, and I'm going to use Python for programming here. What you need to do is install TensorFlow. We have another tutorial on TensorFlow in which we have shown the exact steps to how to install TensorFlow and what exactly is TensorFlow. So I'm not going to go into the details of that. So first of all, what we need to do is I'm going to use the Jupyter notebook here to do all my coding. So created a Jupyter notebook called Deep Learning with Python. So first of all, what we're going to do is we're going to import all the required library. So I will begin with importing all the required libraries. And in this case, I just need to import one library, that is TensorFlow. So what I'm going to do is now import TensorFlow as TVF. So once we have imported TensorFlow, now what we're going to do is define the vector variables for the input and output. I will create the variables for storing the input and outputs and the bias for my perceptron. So here I have the training input and here I have the training output. So as you can see here, we have the training input and the training output. So now what I need to do is define the weights variable and assign some random values to it initially. Since I have three inputs over here, input 1, 2, and the bias, I will require 3 weight values for each input. So what I'll do is I'll define a tensor variable of the shape 3 cross 1 for our weights that will be initialized with random values. Now, one thing important to note here is that in TensorFlow, variables are the only way to handle the ever-changing neural network weights that are updated with the learning process. Now next what we're going to do is we're going to define the placeholders for input and output. Now in TensorFlow, you can specify placeholders that can accept external inputs on the run. So I will define 2 placeholders, X for input and Y for output. Later on, you will understand how to feed inputs to a placeholder. Now, as discussed earlier, the input received by a perceptron is first multiplied by the respective weights, and then all these weights inputs are summed together. Now this summed value is then fed to the activation for obtaining the final result as shown in the image below. Now I'll show you the code of how to do this. So guys, as you can see here, in this case I have used the ReLU as my activation function. So there are a lot of other activation functions like the sigmoid function, the ReLU, we have the CReLU. Other important activation functions will be introduced as you proceed further. Now that I have used ReLU function as my activation function, I need to calculate the error value with respect to the perceptron output and the desired output. So generally this error is calculated as the mean squared error, which is nothing but the square of the difference of perceptron output and the desired output. So this will be our loss. Now another thing important here to note is that what we need to do is minimize the error. So TensorFlow, the deep learning library, provides optimizers that slowly change each variable, that is the weights and the biases, in order to minimize the loss in successive iterations. Now, one of the most simplest optimizer available here is the gradient descent or optimizer, which I'll be using in this case. So guys, if you want to know more about the gradient descent optimizer and how exactly a neural network works, go check out the gradient descent video which is posted by Edureka, the link to which I'll share in the description box below. So in case if you want to know more about the mathematics, the exact mathematics of how the gradient descent works, and what exactly is the purpose of a perceptron when we are talking about minimizing the error, you can check out that video. So as you can see here, I have used the gradient descent optimizer. Now next step, what I'm going to do is initialize the variables. So another important thing to note down here is that the variables are not initialized when I use the tf.variable method. So for that, I need to explicitly initialize all the variables in a TensorFlow program using the following code. So as you can see here, I have init, and I'm going to use the tf.globalvariables._initializer. That will initialize all the variables that I have placed under the tf.variable. So let me run it. So now I need to train our perceptron, that is, update the values of the weights and bias in successive iterations to minimize the error or the loss, which is our main goal. Now, one important thing to note down here is that when we talk about deep learning models, there are certain hyperparameters to work on. So, for example, we have epochs, we have the learning rate. As you learn more about deep learning, how the neural network works, what are the other possible parameters or the hyperparameters used. Moving forward, if you learn about the convolutional neural network or the recurrent neural network, you'll learn there are a lot of other hyperparameters involved there also. So here I've just used the epoch, which is the number of iterations which I'm going to do to train this particular model. So for me, the epoch is 1000. So I'm going to use for I in range of 1000. I'm going to run this session and calculate the cost. And let's see exactly what's the output of this model. As you can see, we already have the output and it's increasing 100, 200, 300, 400, 500, 600, 700. And finally, as you can see here, we already have the output here till 999 epochs. So as you can see here, if we start from the first epoch, you can see the loss is 1.03. It became 1.02, 1.00. It came down to 0.98. And the more we train the particular model, the more it will understand the particular data set, and the loss will decrease as long as we train the model. If we have a look at the loss at the 999th or the 1000th step, as you can see, 1000th epoch, so the loss is 0.0003. That's an amazing loss. And since our data was so small, it was very easy for the perceptron to learn the data during the 1000th iterations because there's nothing new about AND gate. But the complications arises when we are dealing with large amounts of data in which the data is of high dimensionality and each data differs from the previous one in some other respect. So this is how you create a perceptron using Python. In TensorFlow, you can use other deep learning frameworks as well, which work with Python via PyTorch. So this was a single perceptron on which we did the coding and understood how exactly it works and mimics the human neuron which takes on decisions. So as I mentioned earlier, our brain has a network of these neurons which is known as the neural network. So let's move ahead with this deep learning video to understand how a deep neural network looks like. So as you can see in the image above, deep learning works as follows. At the lowest level, the network fixates on patterns of the local contrast as important. Now the following layer is then able to use those patterns of local contrast to fixate on those things that resemble eyes, nose, and mouth. Finally, the top layer is able to apply those facial features to face templates, and a deep neural network is capable of composing more and more complex features in each of the successive layers. Now, one important thing here to note down is that we have not explicitly mentioned what to look for. So this is one of the amazing features of deep learning, is that it automatically attracts the features which are important for the dataset to categorize the photos, the videos, or whatever be your input data. So have you ever wondered how Facebook automatically labels or tags all the persons present in an image? So well, Facebook uses deep learning in a similar fashion as stated in the above example I showed. Now you would have realized the capability of deep learning and how it can outperform machine learning in those cases where we have very little data, very little idea about all the features that can affect the outcome. Therefore, deep neural network can overcome the drawbacks of machine learning by drawing inferences from the dataset consisting of the input data without proper labeling. Now, let's understand another deep learning use case. So now if we talk about this example of this image recognition, here we are passing the high dimensional data to the input layer first to match the dimensionality of the input data. The input layer will contain multiple sublayers of perceptrons so that it can consume the entire input. The output received from the input layer will contain patterns and will only be able to identify the edges of the images based on the contrast level. This output will be fed to the hidden layer 1, where it will be able to identify various face features like eyes, nose, ears. Now, this will be fed to the hidden layer 2, where it will be able to form the entire face. Then the output of layer 2 is sent to the output layer. Finally, the output layer performs classification based on the result obtained from the previous and predicts the same. Now, let me ask you a question. What will happen if any of these layers is missing or the neural network is not deep enough? Now, the answer to it is very simple. We will not be able to accurately identify the images. Now, this is the very reason why these use cases did not have a solution all these years prior to deep learning. Just to take this further, we will try to apply deep learning networks on the MNIST dataset. Now, the MNIST dataset is a very popular dataset which consists of around 100,000 training samples and 10,000 testing samples of handwritten digits. Now, the task here is to train a model which can accurately identify the digits present in the image. Now, to solve this use case, a deep network will be created with multiple hidden layers to process all the 60,000 images pixel by pixel. And finally, we will receive an output. The output layer will be an array index 0 to 9, where each index corresponds to respective digit. Index 0 contains the probability of 0 being the digit present on the output image. So guys, if you want to dig deep into a neural network and want to know how exactly this MNIST dataset works, Edureka has another video on this artificial neural network and how exactly it works on this particular data set. So I'll leave the link to that video in the description box below. Let's get ahead and understand how exactly we can code this in Python. So first of all, what we're going to do is from future import the print function. So what it will do is it will help us in reducing the errors which are caused by version mismatch, and it helps a lot when you are coding in deep learning, because every now and then we have another deep learning framework or we have new frameworks and libraries coming up which creates a problem while we are working with old data or old data sets, and MNIST being one of the earliest big data, or what we can call it as a huge data set. So working on it might create a little bit of problems while working in Python. What we need to do is use the future import print function. So next what we're going to do is import the MNIST data. Now we can import the MNIST data if you have it saved in your PC, but what TensorFlow does is that it provides certain examples and tutorials, and inside that we have the data of MNIST. So what I'm going to do is import it from tensorflow.examples.tutorials. So next what I'm going to do is import TensorFlow STF and import matplotlib, which is the Python library for plotting the plots. We're going to use the matplotlib.pyplot. So as you can see here, we have a certain warning, but there's not an error just because we use the from future import print function. Once we have imported TensorFlow and matplotlib, so next what I'm going to do is initialize the parameters, which are the learning rate, the training epochs. We have the batch size of 100. So here I'm going to take a batch size of 100 because initially you need to train it with a small example and then move forward. Like you can change the batch size to 1000 and 10,000, but it will delay the process of learning. These things you have to keep in mind is that the hyperparameters which I'm talking about are the learning rate, the training epochs, and the batch size. These all need to be calculated and be taken care of by you. And that is where most of the data scientist roles comes in. So the major role of a data scientist is to decide the value of these parameters, how exactly to initialize these variables so as the model would be perfect to run. Next, what I'm going to do is initialize the network parameters. So in the image earlier, we saw that we had two hidden layers, one input layer, and we have one output layer. What I'm going to do is create two hidden layers which have 256 number of perceptrons. This number is arbitrary. You can use any number of perceptrons in a particular single layer. It depends on you. For input layer, I'm going to use 784 input because the image shape is 28 into 28 and that equals 784. So it will be 784 pixels. And the output classes or the output layer, which will be 10, because as you know, the MNIST tool classes are 0 to 9, which are 10 digits. So let me initialize this for you as well. I'm going to use the network parameters here. So as you can see here, I've even mentioned it in the code here as the first layer of number of features, 256. So as you can see, the MNIST data input of the image shape, the size of the image is 28 into 28 pixels, which makes it 784. So that will be our input layer, the number of perceptrons in the input layer. So after that, what we're going to do is create a TensorFlow graph, and we're going to use the placeholders X and Y we're going to create. So one is for the input, one is for the output, the placeholders. Now next step, what we're going to do is create our model. So for that, what we're going to do is create the hidden layers. So if you have a close look at the definition of this multi-layer perceptron, so that we have the input X, we have the weights and the biases. So the layer 1 in which we have the matrix multiplication of X into the weights and the biases. And then again, we are applying the NN, which is the tf.nn, which is the TensorFlow.NeuralNetworks.ReLU. You can use sigmoid, you can use any other activation function which you want to get a different result. For this practical, I'm going to use the ReLU activation function. So similarly for layer 2 also I'm doing that, and for output layer also, but then again in the output layer we are not using any activation functions. There we're going to do only the matrix multiplication. So one thing here to notice is that for the layer 2 the input is layer 1, and for the output layer the input is layer 2. We need to store the layer weights and biases. So for that we're going to create the weights and biases for each of these particular layers. So here we have H1, H2 and out, which are the weights for these H1, H2. We have the biases. So next what we're going to do is construct a model, and we're going to use the multi-layer perceptrons in which we have the X as the input and the weights and biases. And we're going to name this as PRED, predict. So next our step is to define the loss and the optimizer. So as I mentioned earlier when we were talking about perceptrons, so the main goal is to reduce the cost. So we're going to use the tf.reduce mean function here. And inside this, what I'm going to use is tf.nn.soft max cross entropy with logist. So if I have a close look here, I'm going to use the tf.reduce means so that we can reduce the cost. We're using the neural network softmax cross entropy function here. And for optimizer, we are using the Atom optimizer. It's up to you. You can use the gradient descent optimizer as well as any other optimizer for training the data and training the models. So what you can see here, we are providing the learning rate, and in the optimizer, we're going to use the function called minimize so as to minimize the cost using the particular optimizer. So as you can see, we have a small warning, major versions mismatch. That's cool because it's not creating any error as of now. So once again, what we're going to do is initialize all the variables. So we're going to use the tf.global_variable initializer. Then again, we're going to create an empty list to store the cost history and the accuracy history so as to get a track of whether our deep neural network is working in the right direction or not. So don't get afraid when I show you this code. What we're going to do is launch the graph which we created. So for that, we're going to use tf.session as SCSS. And then we have the training cycle for epochs in the range training epochs. So epochs, which we mentioned earlier, are 15. So we're going to train this for 15 epochs. First of all, what we're going to do is create the average cost as 0, but we're going to do next is that loop it over all the batches. So the batch size is 100. We're going to use a batch size of 100, iterate it for 15 epochs. For I in range total batches, we're going to MNI state.train the next batch size. Next, what we're going to do is run an optimization backdrop and the cost operation to get the loss value. We're going to calculate the average cost, and then finally we'll calculate the accuracy. So what we're going to do is accuracy will be tf.reduce mean of the tf.cast of the correct prediction. What we're going to do is now append the accuracy to the list. And next what we're going to do is append the cost to the list also, so as the final output we get the accuracy and the cost, and we'll see how the accuracy increases while the cost decreases. And then again we have the plot the cost history to just have a look at the plot of what the cost looks like and the accuracy looks like. So let me run this code. So as you can see, in first epoch we have cost 171, accuracy 0.8. Second epoch the cost has reduced to 41 from 171. So you can see we have already reached the accuracy of 0.92. On the fifth epoch, it's 0.925. So as you can see here, as the cost is decreasing, the accuracy is increasing, because that's the main goal of any deep neural network, is to decrease the cost and increase the accuracy. So till epoch 8, you can see it's 0.93 and the cost has reduced to 5 now. The hyperparameters, what we talked about, the epochs, batch size, and if we talk about the number of perceptrons in the layers, these parameters should be chosen wisely, and that is where the experience of a data scientist comes in, as in the data scientist has an experience, and this thing can only be achieved with lots of practice. So as you can see here, the optimization has finished, and you can see the first graph here is of the cost. So it initially started with 171 and it came down all the way to 0.9. And as you can see, at the same time, the accuracy started from 0.86 and it has reached all the way to 0.947, almost 0.95, that is 95%. So guys, this is it for today's session. I hope you guys came to know what exactly is deep learning, how artificial intelligence, machine learning, and deep learning are connected in terms of data science as we speak, how artificial intelligence is a subset. Now machine learning is a subset of artificial intelligence and deep learning is a subset of machine learning, and how exactly a perceptron works, the idea behind a neural network mimicking the human brain, how you can create your own perceptron from scratch, how you can create a neural network from scratch using Python and the other deep learning frameworks.
So this is the problem statement, guys. We need to figure out if the banknotes are real or fake. And for that, we'll be using artificial neural networks. And obviously, we need some sort of data in order to train our network. So let us see how the data set looks like. So over here, I've taken a screenshot of the data set with few of the rows. In it, data were extracted from images that were taken from genuine and forged banknote-like specimens. After that, wavelet transform tools were used to extract features from those images. And these are few features that I'm highlighting with my cursor. And the final column, or the last column, actually represents the label. So basically, label tells us to which class that pattern represents, whether that pattern represents a fake note or it represents a real note. Let us discuss these features and labels one by one. So the first feature, or the first column, is nothing but variance of a wavelet transformed image. The second column is about skewness. The third is curtices of wavelet transformed image. And finally, fourth one is entropy of the image. After that, when I talk about label, which is nothing but my last column, over here, if the value is 1, that means the pattern represents a real note. Whereas when value is 0, that means it represents a fake note. So guys, let's move forward and we'll see what are the various steps involved in order to implement this use case. So over here, we'll first begin by reading the data set that we have. We'll define features and labels. After that, we are going to encode the dependent variable. And what is a dependent variable? It is nothing but your label. Then we are going to divide the data set into two parts, one for training, another for testing. After that, we'll use TensorFlow data structures for holding features, labels, etc. And TensorFlow is nothing but a Python library that is used in order to implement deep learning models, or you can say neural networks. Then we'll write the code in order to implement the model. And once this is done, we will train our model on the training data. We'll calculate the error. Error is nothing but your difference between the model output and the actual output. And we'll try to reduce this error. And once this error becomes minimum, we'll make prediction on the test data and we'll calculate the final accuracy. So guys, let me quickly open my PyCharm and I'll show you how the output looks like. So this is my PyCharm guys. Over here I've already written the code in order to execute the use case. I'll go ahead and run this and I'll show you the output. So over here, as you can see, with every iteration the accuracy is increasing. So let me just stop it right here. Alright, till now any questions, any doubts with respect to what is our use case, what is the data set about? Any questions guys, you can go ahead and ask me. Okay, there's a question from Arpan. He's asking, can you explain the code? Definitely Arpan, I'll be doing that at the end of this class. When you are done with all the fundamentals of neural networks, I'll explain you the entire code, how I've written that and how I've used TensorFlow in order to implement a neural network. I hope you are satisfied with the answer. Okay, he's fine with it. Any other questions, any other doubts guys, just go ahead and ask me. Over here, you don't need to worry about code right now guys, because I'll explain this later in the session. So what I'll do, I'll open my slides once more and we'll discuss the fundamentals of neural networks that are required in order to implement this use case. So in order to understand why we need neural networks, we are going to compare the approach before and after neural networks. And we'll see what were the various problems that were there before neural networks. So earlier, conventional computers use an algorithmic approach. That is, the computer follows a set of instructions in order to solve a problem. And unless the specific steps that the computer needs to follow are known, the computer cannot solve the problem. So obviously, we need a person who actually knows how to solve that problem, and he or she can provide the instructions to the computer as to how to solve that particular problem, right? So we first should know the answer to that problem, or we should know how to overcome that challenge or problem which is there in front of us. Then only we can provide instructions to the computer. So this restricts the problem solving capability of conventional computers to problems that we already understand and know how to solve. But what about those problems whose answer we have no clue of? So that's where our traditional approach was a failure. So that's why neural networks were introduced. Now let us see what was the scenario after neural networks. So neural networks basically process information in a similar way the human brain does. And these networks, they actually learn from examples. You cannot program them to perform a specific task. They will learn from their examples, from their experience. So you don't need to provide all the instructions to perform a specific task. And your network will learn on its own with its own experience. Alright, so this is what basically neural network does. So even if you don't know how to solve a problem, you can train your network in such a way that with experience, it can actually learn how to solve the problem. So that was a major reason why neural networks came into existence. We'll move forward and we'll understand what is the motivation behind neural networks. So these neural networks are basically inspired by neurons, which are nothing but your brain cells. And the exact working of the human brain is still a mystery though. So as I've told you earlier as well, that neural networks work like human brain, and so the name. And similar to a newborn human baby, as he or she learns from his or her experience, we want a network to do that as well. But we want it to do very quickly. So here's a diagram of a neuron. Basically, a biological neuron receives input from other sources, combines them in some way, perform a generally non-linear operation on the result, and then outputs the final result. So here, if you notice these dendrites will receive signals from the other neurons. Then what will happen, it will transfer it to the cell body. The cell body will perform some function. It can be summation, it can be multiplication. So after performing that summation on the set of inputs, via axon, it is transferred to the next neuron. Now let's understand what exactly are artificial neural networks. It is basically a computing system that is designed to simulate the way the human brain analyzes and processes the information. Artificial neural networks has self-learning capabilities that enable it to produce better results as more data becomes available. So if you train your network on more data, it will be more accurate. So these neural networks, they actually learn by example. And you can configure your neural network for specific applications. It can be pattern recognition, or it can be data classification, anything like that, all right? So because of neural networks, we see a lot of new technology has evolved. From translating web pages to other languages, to having a virtual assistant to order groceries online, to conversing with chatbots. All of these things are possible because of neural networks. So in a nutshell, if I need to tell you, artificial neural network is nothing but a network of various artificial neurons. Alright, so let me show you the importance of neural network with two scenarios, before and after neural network. So over here we have a machine, and we have trained this machine on 4 types of dogs, as you can see where I'm highlighting with my cursor. And once the training is done, We provide a random image to this particular machine which has a dog. But this dog is not like the other dogs on which we have trained our system on. So without neural networks, our machine cannot identify that dog in the picture, as you can see it over here. Basically, our machine will be confused. It cannot figure out where the dog is. Now, when I talk about neural networks, even if we have not trained our machine on this specific dog, but still it can identify certain features of the dogs that we have trained on, and it can match those features with the dog that is there in this particular image, and it can identify that dog. So this happens all because of neural networks. So this is just an example to show you how important are neural networks. Now I know you all must be thinking how neural networks work. So for that, we'll move forward and understand how it actually works. So over here, I'll begin by first explaining a single artificial neuron that is called as perceptron. So this is an example of a perceptron. Over here, we have multiple inputs, x1, x2, dash, 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 till xn. And we have corresponding weights as well, w1 for x1, w2 for x2, similarly wn for xn. Then what happens, we calculated the weighted sum of these inputs. And after doing that, we pass it through an activation function. This activation function is nothing but it provides a threshold value. So above that value, my neuron will fire, else it won't fire. So this is basically an artificial neuron. So when I talk about a neural network, it involves a lot of these artificial neurons with their own activation function and their processing element. Now we'll move forward and we'll actually understand various modes of this perceptron or single artificial neuron. So there are two modes in a perceptron. One is training, another is using mode. In training mode, the neuron can be trained to fire for particular input patterns, which means that we'll actually train our neuron to fire on certain set of inputs and to not fire on the other set of inputs. That's what basically training mode is. When I talk about using mode, it means that when a taught input pattern is detected at the input, its associated output becomes the current output, which means that once the training is done and we provide an input on which the neuron has been trained on, so it will detect the input and will provide the associated output. So that's what basically using mode is. So first you need to train it, then only you can use your perceptron or your network. So these were the two modes, guys. Next up, we'll understand what are the various activation functions available. So these are the three activation functions, although there are many more, but I've listed down three. Step function. So over here, the moment your input is greater than this particular value, your neuron will fire, else it won't. Similarly for sigmoid and sine function as well. So these are three activation functions. There are many more that I've told you earlier as well. So yeah, these are the three majorly used activation functions. Next up, what we are going to do, we are going to understand how a neuron learns from its experience. So I'll give you a very good analogy in order to understand that. And later on, when we talk about neural networks, or you can say multiple neurons in a network, I'll explain you the math behind it. I'll explain you the math behind learning, how it actually happens. So right now, I'll explain you with an analogy. And guys, trust me, that analogy is pretty interesting. So I know all of you must have guessed it. So these are two beer mugs, and all of you who love beer can actually relate to this analogy a lot. And I know most of you actually love beer, so that's why I've chosen this particular analogy, so that all of you can relate to it. All right, jokes apart. So fine, guys. So there's a beer festival happening near your house and you want to badly go there. But your decision actually depends on three factors. First is how is the weather, whether it is good or bad. Second is your wife or husband is going with you or not. And the third one is any public transport is available. So on these three factors, your decision will depend whether you will go or not. So we'll consider these three factors as inputs to our perceptron, and we'll consider our decision of going or not going to the beer festival as our output. So let us move forward with that. So the first input is how is the weather. We'll consider it as x1. So when weather is good, it will be 1, and when it is bad, it will be 0. Similarly, your wife is going with you or not, so that will be your x2. If she is going, then it's 1. If she's not going, then it's 0. Similarly, for public transport, if it is available, then it is 1, else it is 0. So these are the three inputs that I'm talking about. Let's see the output. So output will be 1 when you're going to the beer festival, and output will be 0 when you want to relax at home. You want to have beer at home only. You don't want to go outside. So these are the two outputs, whether you're going or you're not going. Now what a human brain does. Over here, okay, fine. I need to go to the beer festival. But there are three things that I need to consider. But will I give importance to all these factors equally? Definitely not. There'll be certain factors which will be of higher priority for me. I'll focus on those factors more, whereas few factors won't affect that much to me. All right, so let's prioritize our inputs or factors. So here our most important factor is weather. So if weather is good, I love beer so much that I don't care even if my wife is going with me or not, or if there is a public transport available. So I love beer that much that if weather is good, then definitely I'm going there. That means when X1 is high, output will be definitely high. So how we do that, how we actually prioritize our factors, or how we actually give importance more to a particular input and less to another input in a perceptron or in a neuron. So we do that by using weights. So we assign high weights to the more important factors or more important inputs, and we assign low weights to those particular inputs which are not that important for us. So let's assign weights, guys. So weight W1 is associated with input X1, W2 with X2, and similarly W3 with X3. Now, as I've told you earlier as well, that weather is a very important factor, so I'll assign a pretty high weight to weather and I'll keep it as 6. Similarly, W2 and W3 are not that important, so I'll keep it as 2, 2. After that, I've defined a threshold value as 5, which means that when the weighted sum of my input is greater than 5, then only my neuron will fire, or you can say then only I'll be going to the beer festival. Alright, so I'll use my pen and we'll see what happens when weather is good. So when weather is good, our X1 is 1, our weight is 6, we'll multiply it with 6. Then, if my wife decides that she is going to stay at home and she will probably be busy with cooking and she doesn't want to drink beer with me, so she's not coming. So that input becomes 0. 0 into 2 will actually make no difference because it will be 0 only. Then again, there is no public transport available also. Then also this will be 0 into 2. So what output I get here? I get here as 6. And notice the threshold value, it is 5. So definitely 6 is greater than 5. That means my output will be 1. Or you can say my neuron will fire, or I'll actually go to the beer festival. So even if these two inputs are 0 for me, that means my wife is not willing to go with me and there is no public transport available, but weather is good, which has very high weight value and it actually matters a lot to me. So if that is high, it doesn't really matter whether the two inputs are high or not. I will definitely go to the beer festival. Alright, now I'll explain you a different scenario. So over here our threshold was 5. But what if I change this threshold to 3? So in that scenario, even if my weather is not good, I'll give it a 0. So 0 into 6. But my wife and public transport both are available. Alright, so 1 into 2 plus 1 into 2, which is equal to 4. And it is definitely greater than 3. Then also my output will be 1. That means I will definitely go to the beer festival even if weather is bad. And my neuron will fire. So these are the two scenarios that I have discussed with you. Alright, so there can be many other ways in which you can actually assign weight to your problem or to your learning algorithm. So these are the two ways in which you can assign weights and prioritize your inputs or factors on which your output will depend. So obviously in real life, all the inputs or all the factors are not as important for you. So you actually prioritize them. And how you do that in perceptron, you provide high weight to it. This is just an analogy so that you can relate to a perceptron to a real life. We'll actually discuss the math behind it later in the session as to how a network or a neuron learns. Alright, so how the weights are actually updated and how the output is changing, that all those things we'll be discussing later in the session. But my aim is to make you understand that you can actually relate to a real life problem with that of a perceptron. Alright, and in real life problems are not that easy. They are very, very complex problems that we actually face. So in order to solve those problems, a single neuron is definitely not enough. So we need networks of neurons. And that's where artificial neural network, or you can say multi-layer perceptron, comes into the picture. Now let us discuss that. Multi-layer perceptron or artificial neural network. So this is how an artificial neural network actually looks like. So over here we have multiple neurons present in different layers. The first layer is always your input layer. This is where you actually feed in all of your inputs. Then we have the first hidden layer. Then we have second hidden layer, and then we have the output layer. Although the number of hidden layers depend on your application, on what are you working, what is your problem. So that actually determines how many hidden layers you'll have. So let me explain you what is actually happening here. So you provide in some input to the first layer, which is nothing but your input layer. You provide inputs to these neurons. All right, and after some function, the output of these neurons will become the input to the next layer, which is nothing but your hidden layer 1. Then these hidden layers also have various neurons. These neurons will have different activation functions. So they'll perform their own function on the inputs that it receives from the previous layer, and then the output of this layer will be the input to the next hidden layer, which is hidden layer 2. Similarly, the output of this hidden layer will be the input to the output layer. And finally, we get the output. So this is how basically an artificial neural network looks like. Now let me explain you this with an example. So over here, I'll take an example of image recognition using neural networks. So over here, what happens, we feed in a lot of images to our input layer. Now this input layer will actually detect the patterns of local contrast and then will feed that to the next layer, which is hidden layer 1. So in this hidden layer 1, the face features will be recognized. We'll recognize eyes, nose, ears, things like that. And then that will be again fed as input to the next hidden layer. And in this hidden layer, we'll assemble those features and we'll try to make a face. And then we'll get the output, that is the face will be recognized properly. So if you notice here, with every layer, we are trying to get a more abstract version or the generalized version of the input. So this is how basically an artificial neural network, how it works. All right. And there's a lot of training and learning which is involved that I'll show you now. Training a neural network. So how we actually train our neural network. So basically the most common algorithm for training a network is called backpropagation. So what happens in backpropagation, after the weighted sum of inputs and passing through an activation function and getting the output, we compare that output to the actual output that we already know. We figure out how much is the difference. We calculate the error. And based on that error, what we do, we propagate backwards. And we'll see what happens when we change the weight. Will the error decrease or will it increase? And if it increases, when it increases by increasing the value of the variables or by decreasing the value of variables. So we kind of calculate all those things and we update our variables in such a way that our error becomes minimum. And it takes a lot of iterations. Trust me guys, it takes a lot of iterations. We get output a lot of times and then we compare it with the model, with the actual output. Then again, we propagate backwards, we change the variables. Then again, we calculate the output. We compare it again with the desired output of the actual output. Then again, we propagate backwards. So this process keeps on repeating until we get the minimum value. All right. So there's an example that is there in front of your screen. Don't be scared of the terms that I used. I'll actually explain you with an example. So this is the example over here. We have 0, 1 and 2 as inputs and our desired output or the output that we already know is 0, 1 and 4. All right. So over here, we can actually figure out that desired output is nothing but twice of your input. But I'm training a computer to do that, right? The computer is not a human. So what happens, I actually initialize my weight. I keep the value as 3. So the model output will be 3 into 0 is 0, 3 into 1 is 3, 3 into 2 is 6. Now obviously it is not equal to your desired output. So we check the error. Now the error that we have got here is 0, 1 and 2, which is nothing but your difference. So 0 minus 0 is 0, 3 minus 2 is 1, 6 minus 4 is 2. Now this is called an absolute error. After squaring this error, we get square error, which is nothing but 0, 1 and 4. All right. So now what we need to do, we need to update the variables. We have seen that the output that we got is actually different from the desired output. So we need to update the value of the weight. So instead of 3, our computer makes it as 4. After making the value as 4, we get the model output as 0, 4 and 8. And then we saw that the error has actually increased. Instead of decreasing, the error has increased. So after updating the variable, the error has increased. So you can see that square error is now 0, 4 and 16 and earlier it was 0, 1 and 4. That means we cannot increase the weight value right now. But if we decrease that, make it as 2, we get the output which is actually equal to desired output. But is it always the case that we need to only decrease the weight? Definitely not. So in this particular scenario, whenever I'm increasing the weight, error is increasing, and when I'm decreasing the weight, error is decreasing. But as I've told you earlier as well, this is not the case every time. Sometimes you need to increase the weight as well. So how we determine that? All right, fine guys, this is how basically a computer decides whether it has to increase the weight or decrease the weight. So what happens here, this is a graph of square error versus weight. So over here, what happens, suppose your square error is somewhere here and your computer, it starts increasing the weight in order to reduce the square error. And it notices that whenever it increases the weight, square error is actually decreasing. So it'll keep on increasing until the square error reaches a minimum value. And after that, when it tries to still increase the weight, the square error will increase. So at that time, our network will recognize that whenever it is increasing the weight after this point, error is increasing. So therefore, it will stop right there and that will be our weight value. Similarly, there can be one more scenario. Suppose if we increase the weight, but then also the square error is increasing. So at that time, we cannot increase the weight. At that time, computer will realize, okay, fine, whenever I'm increasing the weight, the square error is increasing. So it'll go in the opposite direction. So it'll start decreasing the weight and it'll keep on doing that until the square error becomes minimum. And the moment it decreases more, the square error again increases. So our network will know that whenever it decreases the weight value, the square error is increasing. So that point will be our final weight value. So guys, this is what basically backpropagation in a nutshell is. Fine, so we'll move forward, and now is the correct time to understand how to implement the use case that I was talking about at the beginning. That is how to determine whether a node is fake or real. So for that, I'll open my PyCharm. This is my PyCharm again, guys. Let me just close this. All right. So this is the code that I've written in order to implement the use case. So over here, what we do, we import the first important libraries which are required. Matplotlib is used for visualization. TensorFlow we know in order to implement the neural networks. NumPy for arrays, pandas for reading the data set. Similarly, sklearn for label encoding as well as for shuffling, and also to split the data set into training and testing parts. All right, fine guys. So we'll begin by first reading the data set, as I've told you earlier as well when I was explaining the steps. So what I'll do, I'll use pandas in order to read the CSV file which has the data set. After that, I'll define features and labels. So X will be my feature and Y will contain my label. So basically X includes all the columns apart from the last column, which is the fifth one. And because the indexing starts from 0, that's why we have written 0 till 4th. So it won't include the 4th column. All right. And so our last column will actually be our label. Then what we need to do, we need to encode the dependent variable. So the dependent variable, as I've told you earlier as well, is nothing but your label. So I've discussed encoding in TensorFlow tutorial. You can go through it and you can actually get to know why and how we do that. Then what we have done, we have read the data set. Then what we need to do is to split our data set into training and testing. And these are all optional steps. You can print the shape of your training and test data. If you don't want to do it, it's still fine. Then we have defined learning rate. So learning rate is actually the steps in which the weights will be updated. All right. So that is what basically learning rate is. Then when we talk about epochs, means iterations. Then we have defined course history. That will be an empty NumPy array, and its shape will be 1, and it will include the float type objects. Then we have defined ndim, which is nothing but your X shape of axis 1, which means your column. Then we'll print that. After that, we have defined the number of classes. So there can be only 2 classes, whether the node can be fake or it can be real. And this model path I've given in order to save my model. So I've just given a path where I need to save it. So I'll just save it here only in the current working directory. Now is the time to actually define our neural network. So we'll first make sure that we have defined the important parameters like hidden layers, number of neurons in hidden layers. So I'll take 10 neurons in every hidden layer, and I'm taking 4 layers like that. Then X will be my placeholder, and the shape of this particular placeholder is none, comma n underscore dim. N underscore dim value, I'll get it from here, and none can be any value. I'll define one variable W and I'll initialize it with zeros, and this will be the shape of my weight. Similarly for bias as well, this will be the particular shape, and there will be one more placeholder Y dash, which will actually be used in order to provide us with the actual output of the model. There'll be one model output and there'll be one actual output, which we use in order to calculate the difference, right? So we'll feed in the actual values of the labels in this particular placeholder Y dash. And now we'll define the model. So over here we have named the function as multi-layer perceptron, and in it we'll first define the first layer. So the first hidden layer, and we are going to name it as layer underscore 1, which will be nothing but the matrix multiplication of X and weights of H1, that is the hidden layer 1, and that will be added to your biases B1. After that, we'll pass it through a sigmoid activation function. Similarly, in layer 2 as well, matrix multiplication of layer 1 and weights of H2. So if you can notice, layer 1 was the network layer just before the layer 2, right? So the output of this layer 1 will become input to the layer 2. And that's why we have written layer underscore 1. It will be multiplied by weights H2, and then we'll add it with the bias. Similarly for this particular hidden layer as well, and this particular layer as well. But over here we are going to use the ReLU activation function instead of sigmoid. Then we are going to define the weights and biases. So this is how we basically define weights. So weights H1 will be a variable which will be a truncated normal with the shape of n underscore dim and n underscore hidden underscore 1. So these are nothing but your shapes. All right. And after that, what we have done, we have defined biases as well. Then we need to initialize all the variables. So all these things actually I've discussed in brief when I was talking about TensorFlow. Since in TensorFlow, we need to initialize the variables before we use it. So that's how we do it. We first initialize it and then we need to run it. That's when your variables will be initialized. After that, we are going to create a saver object. And then finally, I'm going to call my model. And then comes the part where the training happens. Cost function. Cost function is nothing but you can say an error that will be calculated between the actual output and the model output. Alright, so y is nothing but our model output and y dash is nothing but the actual output or the output that we already know. Alright, and then we are going to use a gradient descent optimizer to reduce the error. Then we are going to create a session object as well. And finally what we are going to do, we are going to run the session. So this is how we basically do that. For every epoch, we will be calculating the change in the error as well as the accuracy that comes after every epoch on the training data. After we have calculated the accuracy on the training data, we are going to plot it for every epoch how the accuracy is. And after plotting that, we are going to print the final accuracy, which will be on our test data. So using the same model, we'll make prediction on the test data. And after that, we are going to print the final accuracy and the mean squared error. So let's go ahead and execute this, guys. All right, so training is done. And this is the graph we have got for accuracy versus epoch. This is accuracy, y-axis represents accuracy, whereas this is epochs. We have taken 100 epochs and our accuracy has reached somewhere around 99%. So with every epoch, it is actually increasing. Apart from a couple of instances, it is actually keep on increasing. So the more data you train your model on, it will be more accurate. Let me just close it. So now the model has also been saved where I wanted it to be. This is my final test accuracy and this is the mean squared error. Alright, so these are the files that will appear once you save your model. These are the 4 files that I've highlighted. Now what we need to do is restore this particular model. And I've explained this in detail how to restore a model that you have already saved. So over here what I'll do, I'll take some random range. I've taken it actually from 754 to 768. So all the values in the row of 754 and 768 will be fed to our model and our model will make prediction on that. So let us go ahead and run this. So when I'm restoring my model, it seems that my model is 100% accurate for the values that I've fed in. So whatever values that I have actually given as input to my model, it has correctly identified its class, whether it's a fake node or a real node. Because 0 stands for fake node and 1 stands for real node, okay? So original class is nothing but which is there in my data set, so it is 0 already. And what prediction my model has made is 0, that means it is fake. So accuracy becomes 100%. Similarly for other values as well. Fine guys, so this is how we basically implement the use case that we saw in the beginning. So in the slide you can notice that I've listed down only 2 applications, although there are many more. So neural networks in medicine. Artificial neural networks are currently a very hot research area in medicine, and it is believed that they will receive extensive application to biomedical systems in the next few years. And currently the research is mostly on modeling parts of human body and recognizing diseases from various scans. For example, it can be cardiograms, CAT scans, ultrasonic scans, etc. And currently the research is going mostly on 2 major areas. First is modeling and diagnosing the cardiovascular system. So neural networks are used experimentally to model the human cardiovascular system. Diagnosis can be achieved by building a model of the cardiovascular system of an individual and comparing it with the real-time physiological measurements taken from the patient. And trust me guys, if this routine is carried out regularly, potential harmful medical conditions can be detected at an early stage and thus make the process of combating disease much easier. Apart from that, it is currently being used in electronic noses as well. Electronic noses have several potential applications in telemedicine. Now let me just give you an introduction to telemedicine. Telemedicine is a practice of medicine over long distance via a communication link. So what the electronic noses will do, they would identify odors in the remote surgical environment. These identified odors would then be electronically transmitted to another site where an door generation system would recreate them. Because the sense of the smell can be an important sense to the surgeon, telesmell would enhance telepresent surgery. So these are the 2 ways in which you can use it in medicine. You can use it in business as well, guys. So business is basically a diverted field with several general areas of specialization such as accounting or financial analysis. Almost any neural network application would fit into one business area or financial analysis. Now there is some potential for using neural networks for business purposes, including resource allocation and scheduling. I've listed down 2 major areas where it can be used. One is marketing. So there is a marketing application which has been integrated with a neural network system. The airline marketing tactician is a computer system made of various intelligent technologies, including expert systems. A feed-forward neural network is integrated with the AMT, which is nothing but airline marketing tactician, and was trained using backpropagation to assist the marketing control of airline seat allocation. So it has wide applications in marketing as well. Now the second area is credit evaluation. Now I'll give you an example here. The HNC company has developed several neural network applications, and one of them is a credit scoring system which increases the profitability of existing model up to 27%. So these are few applications that I'm telling you guys. Neural network is actually the future. People are talking about neural networks everywhere, and especially after the introduction of GPUs and the amount of data that we have now, neural network is actually spreading like plague right now.
Well, Keras is a Python-based deep learning framework which is actually the high-level API of TensorFlow. And now I have 4 major highlights for you guys, so let's check it out from the start. Well, Keras basically runs on top of Theano, TensorFlow or CNTK. Since it runs on top of any of these frameworks, Keras is amazingly simple to work with. You might be wondering why. Well, building models are as simple as stacking layers and later connecting these graphs. Guys, Keras attracts a lot of attention, but why? Since it is open source, it is actively developed by all the contributors across the world and the documentation is nearly endless. Well, we're good with the documentation, but how does Keras perform? Guys, since it is an API which is actually used to specify and train differentiable programs, high performance naturally follows through here. So now that we know what Keras actually is, who makes Keras what it is? Well, we need to check out some of the contributors and the backers to the deep learning framework. Well guys, Keras had over 4,800 contributors during its launch and the initial stages. And now that number has gone up to 250,000 active developers. Well, what amuses me is that there is a 2x growth every year since its launch. Also, it holds a really good amount of traction among multiple startups. Big players like Microsoft, Google, Nvidia and Amazon actively contribute to the development of Keras. Good enough. So at this point, I'm sure all of you are curious about who uses Keras. Well, Keras has an amazing industry traction and it is used in the development of popular firms like Netflix, Uber, Expedia, Yelp and more. Well, now that you know, the next time you watch a movie on Netflix or book an Uber, you know Keras is being used. So guys, if Keras is getting all this attention, what makes it so special? What makes Keras stand out among all the top framework? Here I have for you top 10 snippets that makes Keras so special. Well guys, the focus on user experience has always been the major part of Keras. And next, large adoption in the industry, definitely. We just checked out all of the industry traction it gets and this holds well. And next, it is multi-backend and supports multi-platform as well. This helps all the coders come together and code easily. Next up, the research community present for Keras is amazing along with the production community. So this is a win-win for me guys. So what do you think? And moving on, all the concepts are really easy to grasp with Keras guys. And next up, it supports fast processing, which is really good. And guys, it runs seamlessly on both the CPU and the GPU, and it has support for both Nvidia and AMD as well. And the best part for me is the freedom to design on any architecture and then later implement it as an API for your projects, guys. This definitely is a major advantage for me. So next up, for all the beginners, Keras is really simple to get started with, and I'm here to help you guys with this tutorial for that. So stay tuned. And lastly, the easy production of models makes Keras that much special, guys. Now that we know Keras is special, guys, let's dig in a little bit about one of the major concepts which make Keras what it is, the user experience. Well, in my opinion, this is very important for anyone who wants to know more about Keras, or better, they want to start creating their own neural nets using Keras. So clearly, Keras is an API designed for humans. Well, why so? Because it follows the best practices for reducing cognitive load, which ensures that the models are consistent and the corresponding APIs are simple. And moving on, Keras provides clear feedback upon occurrence of any error, and this minimizes the number of user actions required for the majority of the common use cases, guys. And lastly, Keras provides high flexibility to all of its developers. Well, we all love high flexibility, right? So how is Keras doing this? Guys, it's very simple. It integrates with lower level deep learning framework languages like TensorFlow or Theano. So guys, this ensures that you can implement anything in Keras which you actually built in your base language, which is amazing. So next up, we need to talk about how Keras supports the claim of being able to support multi-platform and lets us work with multiple backends. You can develop Keras in Python as well as R. The code can be run with TensorFlow, CNTK, Theano, or MXNet totally based on your requirement. This almost feels like a tailor-made API for the framework, guys. The code can be run on the CPU or the GPU as well. Support for both the big players being Nvidia and AMD here. So this ensures that producing models with Keras is really simple. Total support to run with TensorFlow Serving, GPU acceleration such as CUDA when using modules such as WebKeras and Keras.js, native support to develop Android and iOS apps using TensorFlow and Core ML, and yes, full-blown support to work with Raspberry Pi as well. So guys, moving on, we need to check one quick concept which forms the backbone as a working principle of Keras. So let's check out a computation graph. Here is an example for you guys. Just before decoding and working our way through the graph, let's look at the features. So guys, do note that computational graphs are used for expressing complex expression as a combination of simple operations for Keras to work with. It is mainly useful for calculating the derivatives during the phase of backpropagation, and hence it makes it easier to implement distributed computing on the whole. So all it takes is to specify the inputs, outputs, and to make sure that the graph is connected throughout. I hope you guys know what a connected graph is. So let's check out our graph. We'll be working our way from the leaf nodes to the top. So guys, here as you can see, E equal to C multiplied with D, where C is equal to A plus B and D is equal to B plus 1. So all we're doing is we're making sure we land at E equal to C cross T, which is the head of our tree, and we get to this by performing two operations on the leaf nodes. So as you can see, working down further, E equal to A plus B into B plus 1 actually makes sense now. And in our case, A and B are inputs. So guys, it is as simple as that. So next, let's dive a little bit deeper and check out the two major models, guys. So the first model is a sequential model. The working is basically like a linear stack of layers. So the first thing that comes into my mind when I think about the layered approach is the sequential model. It is majorly useful for building simple classification network and encoder-decoder model, guys. And definitely yes, this is the model which we all know and love. So here we basically treat every layer as an object that feeds into the next layer and so on. And now in the simple code, we'll import Keras into Python. We define the model as sequential, and with the hidden layers, we have 20 neurons and we'll be using ReLU here. ReLU is rectified linear unit, guys. It is one of the activation functions we'll be using. Well, model.fit is used to train the network. Here, by epoch, I'm sure all of you guys are familiar with it already. So it is basically the forward and the backward pass of all of our training examples. And batch size is really straightforward as well. It is the number of training examples in one forward and backward pass, guys. So higher the batch size, the more the memory you'll need. So next, we need to check out the functional model. It is widely used and it holds good for about 95% of the use cases. Well, imagine the concept of playing with Legos, guys. I'm pretty sure most of us have played with Legos in our childhood. It's pretty much the same here as well. Well, the highlights of the functional model is that it supports multi-input, multi-output, and an arbitrary static graph topology. We have branches, so whenever we have a complex model, the model is forked into two or more branches based on the requirement, guys. The code which we have here is pretty much similar to the previous one, but with subtle changes. We first import the models, we work on its architecture, and lastly, we train the network. Well, with functional models, we have this concept called as domain adaptation. So guys, what we did until this stage is that we train a model on one domain but test it on the other. This definitely results in poor performance on the overall test dataset because the data is different for each of the domains, right? So what's the solution for this? Well, we adapt the model to work on both the domains at the same time. And guys, we'll be looking at a very interesting use case using the functional models in the upcoming slides. So stay tuned for that. So moving on, we need to understand about the two basic types of execution in Keras, deferred and eager execution. It is also called as symbolic and imperative execution as well. Well, with deferred, we use Python to build a computation graph first like we previously discussed, and then this compiled graph gets executed. Well, with eager execution, there is a slight change, guys. It is here that the Python runtime itself becomes the execution runtime for all of the models. It is very similar to execution with NumPy. So if you're familiar with NumPy, then it's a cakewalk, guys. So on the whole, here is a quick note. Symbolic tensors don't have a value in the Python code as of yet, but eager tensors will have a value in the Python code. And with eager execution, we make use of a type of recurring neural networks called as trees. So guys, it is basically a value dependent dynamic topology structure. So what are you guys thinking about Keras at this point? Well, it is actually really easy to grasp, guys. Well, next, let's look at the steps needed to implement our own neural network using Keras. There are 5 major steps here, guys. So starting out, we need to prepare the inputs for the model. We do this by analyzing our requirements and specifying the input dimensions. Well, as you know it, the common inputs are images, videos, text, or audio based on your model requirement. The next step is to actually define the artificial neural network model. Here we do everything from defining the model architecture to building the computation graph And also defining the style we'll be using for the model. It is as straightforward as that. Well, step 3 is to specify the optimizer. Think of it this way, a neural network is just a complex function. We need to simplify the process of making the machine learn. Well, the optimizer is just for that. There are many types of optimizers such as SGD, which is stochastic gradient descent. We have RMSProp, which is based on root mean square, and ADAM, and so on. And the next step is to define the loss function. So for every step in our training, we'll be checking the accuracy of prediction by comparing the obtained value with the actual one. We check for the difference between them and we print out the loss, guys. Well, the goal is to actually define a function which we will use to reduce the losses in each pass of the training phase. There are many types of loss functions such as MSE, which is mean squared error, and we have cross entropy loss, which is also called as the log loss in most cases, and so on. And the last step is to actually train the network based on the input data, which is also called as a training data. And after training, we will need to test the model based on the trained data to check if the model actually learned anything. So it is as simple as this, guys. What do you think? I would love to know your views on this, so head to the comment section, let's have an interaction there. And now, guys, let's spice things up a bit. I'm sure you guys were curious about the use case, so let me walk you through the entire thing. Well, we'll be checking out a wine classifier in this use case, so let's begin by checking out our problem statement. So we're trying to predict the price of a bottle of wine just by knowing the description and the variety of wine. Well, we can work this out with the Keras functional API and TensorFlow. We'll be building a wide and a deep network using Keras to make predictions for us. Well, can we achieve this goal? Yes, we can. This is a problem statement suited for wide and deep learning networks, as I mentioned. Well, it involves textual input and there isn't any correlation between the wine's description and its price. Well, this is what makes it fun in my opinion, guys. So next we need to check out the model. A lot of Keras models are built using the sequential model API as I told you earlier. But let's make use of the functional API for our use case. Well, true, the sequential API is still the best way to get started with Keras. Why? Because it lets you define models easily as a stack of layers like I explained earlier. However, the functional model allows for more flexibility and is best suited for models with multiple inputs. So we need to know a little bit about wide and deep model, guys. Well, wide models are models with sparse feature vectors. Well, what I mean by sparse feature vectors is that it consists of mostly zeros and a little bit of ones. And deep networks are networks which do really well on tasks like speech and image recognition. So now that that's sorted, we need to take a look at the dataset. Well, for this case, we'll be using a wine dataset from Kaggle. So what's the data? Well, it's basically 12 columns of data and it's as follows. Here we'll be talking about the country that the wine is from. Next up is description, a few sentences from the sommelier describing the wine's taste, smell, look and feel. A sommelier is a person who is a professional wine taster, guys. Next up is designation, the vineyard within the winery where the grapes that the wine has been made from. Next up is points, the number of points that the wine enthusiasts rated the wine on a scale of 1 to 10. However, they only say that they post reviews for the wines which scores greater than equal to 80. Next up is price, the cost of the bottle of the wine obviously, followed by province, the province or the state where the wine is from. Next up I have something called as region 1. Well, with region 1, it's the wine growing area in a province or a state. Let's say for example India. Next I have region 2. Well, sometimes there are more specific regions within a specified wine growing area. For example, we can say Bangalore, India. But this value can sometimes be blank as well. Next up is taster's name. Well, as it suggests, it's the name of the person who tasted and reviewed the wine. Taster Twitter handle for the person who tasted and reviewed the wine. Well, the title of the wine review, which often contains the vintage if you're interested in extracting that feature. Variety, the type of the grapes that is used to make the wine. Let's say for example Pinot Noir, that's a type of the grape. And finally, the winery that made the wine. Guys, the overall goal here is to actually create a model that can identify the variety, winery and the location of a wine based on the description alone. And this dataset offers some really great opportunities for sentiment analysis and other text-related predictive models as well. So now that that's clear, we need to take a look at the sample data case. So here we have a description for the wine such as scent, if it's tart, firm or needs more decanting, etc. So this forms our input for the model, guys. And the output our model provides just from all of this textual information is the pricing that it predicts. How cool is that, guys? So basically we need to check out some of the prerequisites before jumping into the code. Since you're working with Python, we'll require pandas, we'll require NumPy, scikit-learn and Jupyter Notebook. So yes, Keras works on top of TensorFlow, so we'll require both Keras and TensorFlow to be installed on the machine. So now that that's done, moving on, let's look at a small piece of code. Here are all the inputs that we'll require to build the model. And lastly, we test the presence of TensorFlow by printing the installed version. Well, without TensorFlow, it wouldn't make any sense. So we go to Kaggle and download the data and end up converting the data to a pandas data frame, guys. Well, that's good enough to start. Let's look at the code for this model. I'll quickly open up Google Colaboratory, which is basically a Jupyter notebook hosted on their Google Cloud. You can actually do this on your local machine as well by installing all of the frameworks that I've previously mentioned. So let me go ahead and open Colaboratory and let's begin, guys. So guys, we'll be executing each of these blocks and we'll be going on from there. So let us check out the first block. So here we import all of the modules that we require. So guys, let me run it. And that's done. So next we'll need to install the latest version of TensorFlow. Well, with Google Colab, it doesn't require any extra setup, so it's pretty much straightforward. So guys, that took about 2 minutes and TensorFlow is installed. And as I explained before, we need to import the models that we'll use to build the model. And after that, we'll actually run the code to check the version output of the TensorFlow that we just installed. And the output we're supposed to be expecting is version 1.7 because 1.7 is the TensorFlow version that we installed. As you can check out the output, you have TensorFlow version 1.7. So beautiful. So moving on, we need to download the data, which is from a CSV file hosted on the cloud. So let's go ahead and do that. Now that it is downloaded and ready, let us convert all the data from the CSV file into a pandas data frame as I mentioned. So now that that is done, let's go ahead and mix up the data by shuffling it. And yes, so let's start printing samples from our data set. So we'll be printing the first 5 rows, and as you can see, all the columns that we discussed earlier from country, price, province, all the way till a detailed description of the wine is present here. So now that that's done, next we need to do some pre-processing to limit the number of varieties of wine in the data set. So let us go ahead and set a threshold of 500 in our case. So anything less than 500 will be removed from analysis in our model. We'll be replacing it with NaN, which is not a number, instead of letting it to be blank. So let me go ahead and run this. So now that that's done, the next step we need to do is actually split the data into a training data set and a testing data set. So let's go ahead and do that and print the size of both the training data set and the testing data set. So let me go ahead and run this code for you guys, and there it is. We have the training data set size and the testing data set size. Now that we have the size, we need to actually extract the testing and the training features and all of the labels. So let me go ahead and run this code and we can actually get the labels. And so that does it. The training and the testing features and the labels are known to our machine by now. So now it's very obvious that we're using a test description. Well, instead of looking at every word that we have found in our description in our data set, let us limit our bag of words to, let's say, top 12,000 words in our data set. So guys, don't worry, there is actually a built-in Keras utility for creating just this vocabulary. This is considered as wide because the input to our model for each description will be a 12K element wide vector with zeros and ones, indicating the presence of word from our vocabulary in a particular description. Well, Keras has some handy utilities for text pre-processing that we'll use to convert the text descriptions into a bag of words. With the bag of words model, we'll typically want to use only a subset of all the total words that we found in our dataset. And in this example, I used 12,000 words, but this is a hyperparameter that you can tune. Well, you can try out a few values to see what works best on your dataset. Well, we can use the Keras tokenizer class to create our bag of words vocabulary for us. So let me go ahead and run this to create the tokenizer. Guys, so now that that's done, we'll be actually using text to matrix function to convert each description to a bag of words vector. So let me go ahead and run it. Well, now that that's done, guys, in the original Kaggle dataset, there are about 632 total varieties of wine. To make it easier for our model to extract the patterns, we did a bit of pre-processing to keep only the top 40 varieties. Well, around 65% of the original dataset or 96K total examples. Well, we use a Keras utility to convert each of these varieties to integer representation. And then we'll create 40 element wide one-hot vectors for each input to indicate the variety. So let me go ahead and run it, guys. So now that that's run, guys, at this stage, we are ready to build our wide model. Well, guys, Keras has two APIs for building the models, the sequential API and the functional API. The functional API gives us a bit more flexibility in how we define our layers and lets us combine multiple feature inputs into one layer. It also makes it easy for our wide and deep models into one when we are ready. Guys, with the functional API, we can define our wide model in just a few lines of code as you see. Well, first we need to define our input layer as a 12K element vector, well, for each word in our vocabulary, and then we'll connect this to our dense output layer to generate the price prediction. So let me go ahead and run this. Well, now that that's done, we'll compile the model so that it is ready to use. If we were using the wide model all on its own, this is when we'd actually start training it with the fit function and evaluate later with the evaluate function. Since we're going to combine it with our deep model later on, we can hold off on training until the two models are combined, which is done later, guys. So let me go ahead and execute this so we define our wide model. And yep, our wide model is done. Let's go ahead and print out a summary from the wide model. Well, now that we have a summary, we can realize the total number of trainable parameters and non-trainable parameters. Well, in our case, the non-trainable parameters are 0, guys. So guys, that's the end to the construction of the wide model, and it's time to build our deep model. So let's go ahead and check that. Well, to create a deep representation of the wine's description, we'll represent it as an embedding. Well, there are a lot of resources on word embeddings, but the short version is that they can provide a map word to vectors so that the similar words are closer together in the vector space. Well, to convert our text descriptions to an embedding layer, we'll need to first convert each description to a vector of integers corresponding to each word in our vocabulary. We can do that with the handy Keras text to sequence method. And now we've got the integerized description vectors, we need to make sure that they're all the same to feed into our models. Well, Keras is fancy and it has a handy method for that too. We'll use pad_sequences to add zeros to each description vector so that they're all the same length. Well, in this case, I used 170 as the max length, so no descriptions were cut short. So let me go ahead and run this. Well, with our descriptions converted to vectors that are all the same length, we're ready to create our embedding layer and then feed it into our deep model, guys. So let's start building our deep model. Well, there are two ways to create an embedding layer. We can use weights from the pre-trained embeddings as I previously explained, or we can actually learn the embeddings from our vocabulary. Well, it's best to experiment with both and to see which performs better on your particular dataset. Here, we'll consider using learned embeddings. Well, firstly, we'll define the shape of our input to the deep model. Then, we'll feed it into the embedding layer, and here I'm using an embedding layer with 8 dimensions. Well, you can experiment this with tweaking the dimensionality of your embedding layer as per your choice. And the output of the embedding layer will be a 3-dimensional vectors with the following shape. Well, it'll have a batch size, a sequence length. Well, in our case, the sequence length is 170. It'll have an embedding dimension. It is 8 in our example. And in order to connect our embedding layer to the dense, fully connected output layer, we actually need to flatten it first. So let's go ahead and define our model and then we can flatten our layer. Well, once the embedding layer is flattened, it's ready to be fed into the model and to compile it. So let's go ahead and compile it. And now that the compilation is done, as you can see, the loss function we've used in this case is MSE, which is mean squared error. The optimizer we'll be using is Adams and the metrics is accuracy. And at this point of time, we have established the wide model and the deep model. So once we have defined both our models, combining them is really easy, guys. We simply need to create a layer that concatenates the output from each of the model and then merge them into a fully connected dense layer, and finally define a combined model that combines the input and the output from each one. Well, obviously, since each model is predicting the same thing, which is the price, the outputs or the labels from each one will be the same. Also, guys, do note that since the output of our model is a numeric value, we will not need to do any pre-processing and it's already in the right format as well. How cool is that? Well, that's done, guys. It's time for the training and the evaluation. Well, you can experiment with the number of training epochs and the batch size that works best for your data set. Well, this is going to take some time, so I'll save you the pain by fast forwarding this a bit. So guys, as you can see, the training is actually done. So each of the epoch took about 100 seconds and we had 10 epochs for the same. So guys, here's the important thing that you have to notice. With every epoch, we were actually reducing the loss all the way from 1100 to 130, guys. And the accuracy of prediction went from 0.02 all the way till 0.0994, which is almost 0.1. Well, wow, that's definitely a breakthrough for just 10 passes, guys. And now that the training is done, it's time to evaluate it. So let me go ahead and run this piece of code for you guys. So that was quick. That took only about 5 seconds and we have evaluated the model. And now it's time for the most important part, guys, seeing how our model actually performs on the data that it has never seen before. To do this, we'll actually call the predict function on our trained model and we'll be passing it our data set. So let's go ahead and do just that. Well, now that that's done, we'll have to compare the predictions to the actual values for the first 15 wines from our test data set. So guys, as you can see, we have a set of predictions from the description, and the predicted value is about $24 while the actual value is $22. Next up, we have $34 as a predicted one while the average is 70. Well, this is not a really good case, but okay, that's tolerable. And next up, we have predicted 11.9 when the actual value is 12. Wow, that is actually really close. So next up, we have 15.7 versus 9. Well, this goes on and on for the first 15, and it's actually really good. Well guys, pretty well it turns out that there is some relationship between a wine's description and its price. Well, we might not be able to see it instinctively, but our machine learning models certainly can. So lastly, let's compare the average difference between the actual price and the model's predicted price. Well, the average prediction difference is about $10 for every wine bottle. Wow, that is really nice, guys.
What is TensorFlow? TensorFlow is a popular open source framework developed by Google for building and training machine learning models. It's like a toolkit for creating artificial intelligence systems. TensorFlow can be used for various tasks, including neural networks, computer vision, where computers learn to see and understand images, and natural language processing, where computers can understand and use human language. So now we got an understanding of TensorFlow, so let's get deeper into it. TensorFlow is a versatile machine learning framework that utilizes tensors, multi-dimensional arrays, and computational graphs to perform operations. This architecture makes it adaptable and scalable for various machine learning tasks. TensorFlow caters to users with different levels of expertise by offering both high-level APIs like Keras for simplified model building and low-level APIs for greater customization. Furthermore, its capabilities with CPUs, GPUs, and TPUs ensures its suitability for both small-scale research and large-scale production environments. Now that you are familiar with TensorFlow, so let us see its significance in AI and machine learning. TensorFlow is a powerful platform that empowers developers to transform AI and ML ideas into scalable solutions, seamlessly transitioning from research prototypes to real-world applications. It is adaptable to diverse needs, with features like visualizations and debugging tools that enhance model understanding and troubleshooting. TensorFlow streamlines the entire machine learning pipelines, enabling efficient handling of large datasets and complex tasks while ensuring scalability and performance. Its versatility allows it to be customized for various applications, from simple experiments to advanced AI systems. Ultimately, TensorFlow has a real-world impact by enabling developers to create innovative solutions that address global challenges and drive technological progress. Now that you know the significance of TensorFlow, so let's discover why to use TensorFlow. TensorFlow is one of the leading deep learning frameworks widely used for machine learning and AI research and production. Its scalability allows TensorFlow to handle massive datasets and complex models efficiently, making it ideal for large-scale AI systems in applications like image recognition and natural language processing. Next, flexibility. Flexibility is another key strength, as TensorFlow offers APIs ranging from high-level Keras for simplicity to low-level APIs for advanced customization, catering to diverse developers' needs. Next, its rich ecosystem includes an active community, extensive documentation, pre-trained models, and numerous resources that simplify its adoption and usage. TensorFlow's cross-platform support enables seamless deployment across different operating systems and hardware platforms. Finally, its optimized performance, as TensorFlow runs efficiently on CPUs, GPUs, and TPUs, ensuring faster training and inferences times. These strengths such as scalability, flexibility, ecosystem, cross-platform compatibility, and optimized performance make TensorFlow a preferred choice for AI and ML projects. Now that we know what is TensorFlow, so let's compare TensorFlow with other frameworks. So here is the comparison between TensorFlow and another deep learning framework, likely PyTorch, highlighting their respective strengths. TensorFlow is known for its flexibility and versatility, enabling developers to build a wide range of models with customizable implementations, while PyTorch is recognized as initiative and Pythonic, offering a user-friendly approach that appeals to many developers. Next, when it comes to production readiness, TensorFlow excels with robust tools for deploying models in real-world environments, whereas PyTorch is more research-focused, favored for its dynamic computational graphs and ease of experimentations. Next, TensorFlow boasts a large and established ecosystems with an active community, extensive documentation, and a proven track record while PyTorch is growing rapidly in academic circles, gaining traction as a popular choice for research projects. In terms of performance, TensorFlow is optimized and scalable, capable of handling large-scale models and datasets efficiently, while PyTorch is seen as a competitive alternative, offering its own strengths and appealing to a different subset of developers. Ultimately, the choice between TensorFlow and PyTorch depends on the specific use case and developer preferences, as both frameworks offer compelling features suited to different needs. Next, let's explore the real-world applications of TensorFlow. Real-world applications of TensorFlow in computer vision, showcasing its versatility and impact across various fields. TensorFlow is widely used for identifying objects in images, with algorithms like YOLO, you only look once, and SSD, single shot detector, enabling tasks such as detecting pedestrians and obstacles in self-driving cars or identifying suspicious objects in security systems. It plays a crucial role in medical imaging and satellite imagery, where it aids in analyzing X-rays or MRIs to detect anomalies and assist in monitoring deforestation, identifying land use patterns, and predicting natural disasters. Additionally, TensorFlow powers security systems and user authentications, enabling facial recognitions for tasks like facial detection and identifications. This application highlights TensorFlow's ability to transform industries like healthcare and security, making it an indispensable tool in computer vision. Next, TensorFlow in natural language processing. TensorFlow is instrumental in tasks like spam detections and sentiment analysis, where it helps identify spam emails and determine the emotional tone or polarity, which is positive, negative, or neutral of text, such as customer reviews or social media posts. It provides services like Google Translate, enabling accurate translations between numerous languages and facilitating global communications. TensorFlow also enhances security systems and user authentication by analyzing text data to detect suspicious patterns, fraudulent activities, or by improving authentication process through text-based inputs like passwords and security questions. These applications demonstrate TensorFlow's versatility in advancing communication, enhancing security, and driving innovations in NLP. TensorFlow in the field of generative AI, showcasing its role in driving innovation. TensorFlow powers GANs as similar models, enabling the creation of realistic images, art, and even the manipulation of existing visuals. It is instrumental in training large language models like GPT, which stands for Generative Pre-trained Transformers, translate languages, write creative content, and perform summarization tasks. Additionally, TensorFlow facilitates the creation of deep-fake audio and speech generation, producing synthetic media where a person's likeness or voice can be convincingly replicated. These applications demonstrate TensorFlow's pivotal role in advancing image creation, text generation, and audio synthesis within the field of generative AI. Now, let us explore the industrial use of TensorFlow. There are diverse applications of TensorFlow across various industries, showcasing its transformative impact. In healthcare, TensorFlow is used for predicting analytics to forecast disease outbreaks, identify high-risk patients, and optimize treatment plans, as well as for medical image analysis to detect anomalies in X-rays, MRIs, and CT scans. In autonomous vehicles, TensorFlow powers object detection systems, enabling safe navigation and supports decision-making models in industries like supply chain management and risk assessment. In finance, TensorFlow is utilized for algorithmic trading, analyzing market trends, and detecting fraudulent transactions. Retail applications include inventory management to predict demand and reduce stock outs, along with personalized recommendations to enhance customer experience and boost sales. In entertainment, TensorFlow facilitates content creation, such as generating music or art, and it is used in video and audio processing tasks like noise reduction and voice stabilization. Overall, TensorFlow's versatility and advanced capabilities are driving innovation across these industries. Now, let us move ahead and install TensorFlow. To get started with TensorFlow, you first need to install the necessary prerequisites, including Python 3.5 or a higher version. You can use a package manager like pip or conda for installation. Here's how you can proceed based on your operating system. First, open your terminal or command prompt and run the following command to create a virtual environment. And the command is python-m virtual environment my environment. Next, activate the environment. For Linux or Mac OS, activate the environment with the following command. And the command is source my environment /bin/activate. For Windows, activate the environment by running my environment /scripts/activate. Once the environment is activated, you can install TensorFlow by running pip install TensorFlow. Now, to ensure that TensorFlow has been installed successfully, you can verify the installation by running the following command, and that is python-c. Inside the double quotes, type import TensorFlow as tf print. Inside the bracket, type tf dot _version . And this will display the installed version of TensorFlow, confirming that the installation was successful. Once the environment is activated, you can install TensorFlow by running this command, pip install TensorFlow. Now, let us open our VS Code terminal and install the TensorFlow. So let us type the command pip install TensorFlow. As you can see, TensorFlow is installed. Now, to ensure that TensorFlow has been installed successfully, you can verify the installation by running the following command. So now, let us run this command in our terminal. Now, as you can see on the screen, the version is displayed. So, this will display the installed version of TensorFlow, confirming that the installation was successful. Now, let us discuss TensorFlow ecosystem. The TensorFlow ecosystem provides a comprehensive set of tools for building, training, and deploying machine learning models. At its core is TensorFlow, the foundation of the ecosystem. TensorFlow Lite enables running models on mobile and embedded devices, while TensorFlow Extended supports building production-grade ML pipelines, including data validation and model serving. Next, the TensorFlow Model Garden offers pre-trained models and examples for tasks like image classification and NLP. TensorFlow.js allows running ML models in web browsers, and TensorFlow Hub provides a library of pre-trained models for easy integration into projects. Now, let us take a look at the key capabilities of TensorFlow, where we will be showcasing its strengths as an open-source, community-driven framework that evolves through contributions. At its core, TensorFlow utilizes tensors, multi-dimensional arrays for efficient data representation and manipulations. Its flexible architecture allows developers to choose between static graphs for optimized performance and eager execution for an interactive development experience. TensorFlow supports a wide range of applications, including natural language processing, generative AI, computer vision, and more, making it highly versatile for various machine learning tasks. Furthermore, it offers cross-platform compatibility, running efficiently on CPUs, GPUs, and TPUs, enabling developers to leverage the best hardware for their needs. So overall, TensorFlow stands out as a robust, adaptable, and versatile framework for machine learning. Now, let us head towards hands-on. There are three main steps in building a churn prediction model using TensorFlow. In step 1, a model is created by defining its architecture, including layers and parameters tailored to the specific problem of prediction customer churn. In step 2, the model is trained using historical data, where it learns patterns and relationships that help predict customer behavior. Finally, in step 3, the trained model is used to make predictions, identifying customers likely to churn based on input data. This process demonstrates how TensorFlow can be effectively utilized for churn prediction in machine learning projects. Now, without any further delay, let's code it. So first, let us import the libraries. So let us import TensorFlow as tf. Next, import matplotlib.pyplot as plt. Next, from TensorFlow.Keras, import sequential. Next, from TensorFlow.Keras.layers, import flatten, dense. So over here, we are importing the TensorFlow library, a popular framework for machine learning and deep learning. Next, import matplot's plotting model for data visualization. Then we are importing the sequential class from TensorFlow's Keras API, which is used to build models layer by layer. Next, we are importing the following Keras layers, which is flatten and dense. Flattens multi-dimensional data into a 1D array for input into dense layers, and then dense creates fully connected dense layers for the neural network. And this imports set up the tools needed to build and train a neural network, and then visualize data and results. Now, to get the data and split it for training and testing, let us write the command. So inside the bracket, let us type train underscore images, comma, train underscore labels, and give comma, and again inside the bracket let us type test underscore images, comma, test underscore labels, and equal to tf dot keras dot datasets dot mnist dot load underscore data. So this code loads the MNIST dataset of handwriting digits using TensorFlow. Here, the train images and train labels were images and labels for training 60,000 samples. And the test images and test labels are where the images and labels for testing 10,000 samples. Here, each image is a 28 by 28 grayscale image and the labels represent the digits 0 to 9. Now, let us scale down the values of the pixels from 0 to 255 to 0 to 1. So for that, let us type train underscore images equal to train underscore images by 255.0. Next, test images equal to test images by 255.0. Now next, let us visualize the data. For that, print, and inside the bracket, let us type train underscore images dot shape. Next, print test images dot shape, and finally print train underscore labels. So in this code, the print train images dot shape displays the shape of the training images dataset. So let us run the code to check the output. So as you can see the output, here it says 60,000, 28, 28. This means there are 60,000 images, each of size 28 by 28 pixels. Next, we have the code print test images dot shape, which displays the shape of the testing images dataset. So the output here is 10,000, 28, 28, which means there are 10,000 images, each of size 28 by 28 pixels. The next piece of code is train labels, which prints the labels digit 0 to 9 for the training set. Now, let us display the first image. So for that, let us type plt dot image show, and inside the bracket, let us type train underscore images at index 0, comma, cmap equal to gray inside the single quote. To see the graph, let us type plt dot show. So over here, the plt dot mshow train images. This displays the first image in the data set, which says train images of index 0. Then cmap equal to gray ensures that the image is shown in grayscale. So let us run this code. So as you can see the screen, here is the output. Now let us move ahead. The next step is to define the neural network model. So let us type my model equal to tf.keras.models.sequential function. Next, type my model. Okay, next is my model.add flatten, and inside the bracket let us keep input underscore shape equal to 28, 28. Okay, next let us type my model.add, and inside the bracket let us type dense and open bracket and write 128, activation equal to, inside the single quote let us type ReLU. Next type my model.add, and inside the bracket let us type dense. Again open the bracket and let us give 10, activation equal to softmax. So over here, the tf.keras.model sequential, which creates a sequential model where layers are added one after another. And next we have this code, myModel.add flatten input shape equal to 28,28, which flattens the 28 by 28 input images into 1D array of 784 values and making them suitable for the dense layers. And the next code, myModel.add dense 128, activation equal to ReLU, which adds a dense fully connected layers with 128 neurons. And then the activation equal to ReLU, which applies the ReLU activation function to introduce non-linearity. And the next code, which is myModel.add dense 10, activation equal to softmax, which adds the output layer with 10 neurons corresponding to the 10-digit classes, which is 0 to 9. And activation equal to softmax outputs probabilities for each class. Now, let us compile the model. The network will be actually created. So, let us type myModel.compile. And inside the bracket, let us give optimizer equal to, inside the single quotes, let us give Adam, loss equal to, inside the single quote, let us keep it as parse underscore categorical underscore cross entropy, metrics equal to accuracy. Over here, the optimizer equal to Adam uses the Adam optimizer, an efficient and widely used algorithm for optimizing neural networks. This specifies the loss function for multi-class classification where labels are integers. Next, the matrix equal to accuracy tracks the model's accuracy during training and evaluation. Next, let us train the model. So for that, let us type myModel.fit inside the bracket, type train underscore images, train underscore labels, epochs equal to 3. So here the myModel.fit, this is a function where it trains the model with the provided data. And then we have the train images, train labels, where the input data train images and corresponding labels, which is train underscore labels for training. Next is the epochs equal to 3. The model will go through the entire training dataset 3 times to learn patterns. Next, let us check the model accuracy on the test data. For that, let us type value underscore loss, value underscore ACC equal to myModel.evaluate, and inside the bracket, let us type test underscore images, test underscore labels. Next, let us give a print statement. So type print test accuracy of my model, value underscore ACC. So here in this code, myModel.evaluate evaluates the model using the test images and their corresponding labels, which returns two values, which is value loss, the loss on the test set, and the value ACC, the accuracy on the test set. And next statement we have print. So this will display the test accuracy, showing how well the model performs on unseen data. Now let us check the output. So let's run the code. So as you can see the screen, the model is finding patterns in 3 iterations because we had set the epochs to be 3. And here you can see the accuracy is 0.97%. So let us change the epochs value to be 50. So initially we had set 3. So now let us give 50 and run the code. Now as you can see, it's making 50 iterations. However, achieving perfect accuracy on the training set could also indicate potential overfitting, where the model might not generalize well to new unseen data. So to confirm the model's effectiveness, it is essential to evaluate its performance on a separate validation or test dataset. And if the accuracy remains high and the loss is minimal on the test set, the model can be considered robust and effective.
So this is an image of New York skyline. I personally love this picture. So when a human will see this image, he'll first notice there are a lot of buildings in different colors and stuff like that. But how a computer will read this image? So basically there will be 3 channels. One will be red, another will be green, and finally we have blue channel. which is popularly known as RGB. So each of these channels they have their own respective pixel values, as you can see it over here. So when I say that image size is B cross A cross 3, it means that there are B rows, A columns and 3 channels. Alright, so if somebody tells you that the size of an image is 28 cross 3 pixels, it means that it has 28 rows, 28 columns and 3 channels. So this is how a computer sees an image. And this is for colored images. For black and white images, we have only 2 channels. So let's move forward and we'll see why can't we use fully connected networks for image classification. So consider an image which has 28 cross 3 pixels. So when I feed in this image to a fully connected network like this, then the total number of weights required in the first hidden layer will be 2352. You can just go ahead and multiply it yourself. All right. But in real life, the images are not that small. All right. So whatever images that we have, they are definitely above 200 cross 3 pixels. So if I take an image which has 200 cross 3 pixels and I feed it to a fully connected network, so at that time, the number of weights required at the first hidden layer itself will be 120,000 guys. So we need to deal with such huge amount of parameters, and obviously we require more number of neurons. So that can eventually lead to overfitting. So that's why we cannot use fully connected network for image classification. Now let's see why we need convolutional neural networks. So basically, in convolutional neural network, a neuron in the layer will only be connected to a small region of the layer before it. So if you consider this particular neuron which I'm highlighting right now is only connected to 3 other neurons. Unlike the fully connected network where this particular neuron will be connected to all these 5 neurons. Because of this, we need to handle less amount of weights, and in turn, we need less number of neurons as well. So let us understand what exactly is convolutional neural network. So convolutional neural networks are special type of feed-forward artificial neural networks, which is inspired from visual cortex. So visual cortex is nothing but a small region in our brain which is present somewhere here where you can see the bulb. And basically what happened, there was an experiment conducted and people got to know that visual cortex is small regions of cells that are sensitive to specific regions of visual field. So what I mean by that is, for example, some neurons in the visual cortex fires when exposed to vertical edges. Some will fire when exposed to horizontal edges. Some will fire when exposed to diagonal edges. And that is nothing but the motivation behind convolutional neural network. So now let us understand how exactly a convolutional neural network works. So generally a convolutional neural network has 3 layers: convolution layer, ReLU layer, pooling layer and fully connected layer. We'll understand each of these layers one by one. We'll take an example of a classifier that can classify an image of an X as well as an O. So with this example, we'll be understanding all these 4 layers. So let's begin guys. Now there are certain trickier cases. So what I mean by that is X can be represented in these 4 forms as well, right? So these are nothing but the deformed images of X. Similarly for O as well. So these are deformed images. So even I want to classify these images either X or O. All right, because even this is X, this is X, this is X, this is X. But all these are deformed images, but they are in turn X, right? So I want my classifier to classify them as X. So basically that's what I want. So if you can notice here, this is a proper image of an X and which is actually equal to this particular X, which is a deformed image. Same goes for this O as well. So now what we are going to do is we know that a computer understands an image using numbers at each pixels. So what we'll do, whatever the white pixels that we have, we are going to assign a value -1 to it, and whatever black pixels we have, we are going to assign a value 1 to it. When we use normal techniques to compare these 2 images, one is a proper image of X and another is a deformed image of X, we got to know that a computer is not able to classify the deformed image of X correctly. Why? Because it is comparing it with the proper image of X, right? So when you go ahead and add the pixel values of both of these images, you get something like this. So basically our computer is not able to recognize whether it is an X or not. Now what we do with the help of CNN, we take small patches of our image. So these patches or these pieces are known as nothing but features or filters. So what we do, by finding rough feature matches in roughly the same positions in 2 images, CNN gets a lot better at seeing the similarity between the whole image matching schemes. What I mean by that is we have these filters, right? We have these filters that you can see. So consider this first filter. This is exactly equal to the feature or the part of the image in the deformed image as well. So this is our proper image and this is our deformed image, all right? So this particular feature or this particular part of the image is actually equal to this particular part of the image. Same goes for this particular feature or filter as well. And similarly, we have this filter as well, which is actually equal to this particular part of the deformed image, all right? So let's move forward and we'll see what all features that we'll be taking in our example. So we'll be considering these 3 features or filters. This is a diagonal filter, this is again a diagonal filter, and this is nothing but a small X. So we'll take these 3 filters and we'll move forward. So what we are going to do is we are going to compare these features, the small pieces of the bigger image. We are going to put it on the input image, and if it matches, then the image will be classified correctly. Now we'll begin, guys. The first layer is convolution layer. So these are the beginning two steps of this particular layer. First, we need to line up the feature in the image and then multiply image by the corresponding feature pixel. Now let me explain you with an example. So this is our first diagonal feature that we'll take. We are going to put this particular feature on our image of X, all right? And we are going to multiply the corresponding pixel value. So 1 will be multiplied with 1, we'll get 1 and we'll put it in another matrix. Similarly, we are going to move forward and we're going to multiply -1 with -1. We're going to multiply -1 with -1, as you can see. Similarly, we multiply this as well, -1 into -1, then again -1 into -1. So we are going to complete this whole process when we are going to finish up this matrix. All right. And once we are done finishing up the multiplication of all the corresponding pixels in the feature as well as in the image, we need to follow two more steps. We need to add them up and divide by the total number of the pixels in the feature. So what I mean by that is, after the multiplication of the corresponding pixel values, what we do, we add all these values, we divide it by the total number of pixels, and we get some value, right? And then now our next step is to create a map and put the value of the filter at that particular place. We saw that after multiplying the pixel value of a feature with the corresponding pixel value of with that of our image, we get the output, which is 1. So we place 1 here. Similarly, we are going to move this filter throughout the image. Next up, we are going to move this filter here. After that, we are going to move it here, 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 everywhere on the image. We are going to move it and we are going to follow the same process. All right, so yeah, this is one more example where I've moved my filter in between, and after doing that, I've got the output something like this, 1, 1, -1 and all. So over here, if you notice, I've got a couple of times -1 as well, due to which my output that comes is 0.55, right? So I'm going to place 0.55 here. Similarly, after moving the pixel, after moving the filter throughout the image, I got this particular matrix. All right, and this is for one particular feature. After performing the same process for the other two filters as well, I've got these two values. So we have these three values after passing through the convolution layer. Let me give you a quick recap of what happens in convolution layer. So basically we have taken three features, all right, and one by one we'll take one feature, move it through the entire image, and when we are moving it, at that time we are multiplying the pixel value of the image with that of the corresponding pixel value of the filter, adding them up, dividing by the total number of pixels to get the output. So when we do that for all the filters, we got these three outputs, all right? So let's move forward and we'll see what happens in ReLU layer. So this is ReLU layer, guys, and people who have gone through the previous tutorial actually know what it is. So let me just give you a quick introduction of ReLU layer. So ReLU is nothing but an activation function, all right? So what I mean by that is, it will only activate a node if the input is above a certain quantity. While the input is below 0, the output is also 0, all right? And when the input rises above the certain threshold, it has a linear relationship with the dependent variable. Now I'll explain you with an example. We have a graph of ReLU function here. So my function says that when f of x is equal to 0 if x is less than 0, and it is equal to x when x is greater than 0, all right? So whatever values that I have which are below 0 will actually in turn become 0, and whatever values that are above 0, our function value will also be equal to that particular value. So f of x will be equal to x if it is greater than or equal to 0, and it will be 0 if it is less than 0. So if I have x value as -3, so definitely it is less than 0, so f of x becomes 0. Similarly, if I have -5x value, then again it is less than 0, so my f of x value becomes 0. But when I consider 3 as my x value, then my f of x becomes equal to x, which is nothing but 3. So over here I'll have 3. Again, if I take my x value as 5, then obviously it is greater than or equal to 0. Then my f of x becomes equal to x, so my f of x value becomes 5. So this is how a ReLU function works. So why are we using ReLU function here is we want to remove all the negative values from our output that we got through the convolution layer. So we'll only take the first output that we got by moving one feature throughout the image. So this is the output that we have got for only one filter. All right, so over here I'm going to remove all negative values. So over here you can see that it was -0.11 before, and I've converted that to 0. Similarly, I'm going to repeat the whole process for the entire matrix, and once I'm done with that, I get this particular value. Now remember, this is only for the output that we got through one feature. All right, so when we were doing convolution at that time, we were using three features, right? So this is the output only for one filter. After doing it for the output of the other two filters as well, we have got these two values more. So totally we have these three values after passing through ReLU activation function. Next up, we'll see what exactly is pooling layer. So in pooling layer, what we do, we take a window size of 2 and we move it across the entire matrix that we have got after passing through ReLU layer. And we take only the maximum value from there so that we can shrink the image. So what we are actually doing is we are reducing the size of our image. So let me explain you with an example. So this is basically one output that we have got after passing through ReLU layer. And over here we have taken a window size of 2 cross 2. So when we keep this window at this particular position, we see that 1 is the highest value. So we are going to keep 1 here. And we are going to repeat the same process for this particular window as well. So over here, the maximum value is 0.33, so 0.33 will come. So if you notice here, earlier we had 7 cross 7 matrix, and now we have reduced that to 4 cross 4 matrix. So after doing that for the entire image, we have got this as our output. This output we have got after moving our window throughout the image that we have got after passing through ReLU layer, right? And when we repeat this process for all the 3 outputs that we have got after the ReLU layer, then we get this particular output after pooling layer, right? So basically we have shrinked our image to a 4 cross 4 matrix. Now comes the tricky part. So what we are going to do now is stack up all these layers. So we have discussed convolution layer, ReLU layer, and pooling layer. So I'll just give you a brief recap of what all things we have discussed. In convolution layer, what we did, we took 3 features, and then after that, one by one, we moved each filter throughout the image. And when we were moving it, we were continuously multiplying the image pixel value with that of the corresponding filter pixel value. And then we were dividing it by the total number of pixels. All right. With that, we got 3 output after passing through the convolution layer. Then those 3 output, we passed through a ReLU layer where we have removed the negative value. All right. And after removing negative value, again, we have got the 3 outputs. Then those 3 outputs we passed through pooling layer. So basically we're trying to shrink our image. And what we did, we took a window size of 2 cross 2, moved it through all the 3 outputs that we have got through ReLU layer. And after doing that, we were only taking the maximum value, pixel value in that particular window. And then we were putting it in a different matrix so that we get a shrinked image. And after passing it through pooling layer, we have got a 4 cross 4 matrix. And since we took 3 features in the beginning, so therefore we have got 3 outputs after passing through pooling layer. All right. Next up, we are going to stack up all the layers. All right. So let's do that. So after passing through convolution, ReLU, and pooling, we have got this 4 cross 4 matrix. This was our input image. Now when we add one more layer of convolution, ReLU, and pooling, we have shrinked our image from 4 cross 4 to 2 cross 2, as you can notice here. Now we are going to use fully connected layer. Now what happens in fully connected layer? The actual classification happens here, guys. Okay. So what we are doing here is we are going to take the shrinked images and put it into a single list. So basically this is what we have got after passing through 2 layers of convolution, ReLU, and pooling. And this is what we have got. So basically we are converting into a single list or a vector. How we do that? We take the first value 1, then we take 0.55, then we take 0.55, then we take 1 again. Then we take 1, then we take 0.55, 0.55, 0.55. Then we again take 0.55, 1, 1, and 0.55. So this is nothing but a vector, or you can say a list. If you notice here that there are certain values in my list which is high for X, and similarly if I repeat the entire process that we have discussed for O, there will be certain different values which will be high. So for X we have first, fourth, 5th, 10th, and 11th element vector values are high. For O we have 2nd, 3rd, 9th, and 12th element vector which are high. So basically we know now if we have an input image which has 1st, 4th, 5th, 10th, and 11th element vector values high, we know that we can classify it as X. Similarly, if our input image has a list which has the 2nd, 3rd, 9th, and 12th element vector values high, then we can classify it as 0. Now let me explain you with an example. So after the training is done, after doing the entire process for both X and O, you know that our model is trained now. Okay, so we have given a new input image, and that input image passes through all the layers. And once it has passed through all the layers, we have got this 12 element vector. Now it has 0.9, 0.65, all these values, right? Now, how do we classify it, whether it is an X or O? So what we do, we'll compare this with a list of X and O. Right, so we have got the list in the previous slide. If you notice, we have got 2 different lists for X and O. We are going to compare this new input image list that we have got with that of X and O. Right, so first let us compare that with X. Now, as I've told you earlier as well, for X, there are certain values which will be high, which is nothing but 1st, 4th, 5th, 10th, and 11th value, right? So I'm going to sum 1st, 4th, 5th, 10th, and 11th value, and I've got 5. 1 plus 1 plus 1 plus 1 and plus 1. So 5 times 1, I've got 5. And now I'm going to sum the corresponding values of my input image vector as well. So the first value is 0.9, then the 4th value is 0.87, 5th value is 0.96, 10th value is 0.89, and the 11th value is 0.94. So after doing the sum of these values, I've got 4.56. When I divide this by 5, I got 0.91, right? Now this is for X. Now when I do the same process for O, so in O, if you notice, I have 2nd, 3rd, 9th, and 12th element vector values as high. So when I sum these values, I get 4. And when I do the sum of the corresponding values in my input image, I've got 2.07. When I divide that by 4, I got 4.51. So now we notice that 0.91 is a higher value compared to 0.51. So when we have compared our input image with the values of X, we got a higher value than the value that we have got after comparing the input image with the values of O. So the input image is classified as X. Alright, so now let us move towards our use case. So this is our use case, guys. So over here what we are going to do is we are going to train our model on different types of dogs and cat images, and once the training is done, we are going to provide it an input and it will classify whether the input is of a dog or a cat. Now let me tell you the steps involved in it. So what we are going to do in the beginning is obviously first we need to download the data set. After that we are going to write a function to encode the labels. Labels are nothing but the dependent variable that we are trying to predict. So in our training data and testing data, obviously we know the labels, right? So on that basis only we can train our model. So we are going to encode those labels. After that, we'll resize the image to 50 cross 50 pixel and we are going to read it as a grayscale image. Then we are going to split the data, 24,000 images for training and 50 for testing. Once this is done, we are going to reshape the data appropriately for TensorFlow. Now TensorFlow, I think everyone knows about TensorFlow. TensorFlow is nothing but a Python library for implementing deep learning models. Then we are going to build the model, calculate the loss. It is nothing but categorical cross entropy. Then we are going to reduce the loss by using Adam optimizer with a learning rate set to 0.001. Then we are going to train the deep neural network for 10 epochs, and finally we are going to make predictions. Alright, so I'll just quickly open my PyCharm and I'll show you the code, how it looks like. So this is the code that I've written in order to implement the use case. In the beginning, I need to import the libraries that I require. And once it is done, what I'm doing, I'm defining my training data and the testing data. So train and test one contains both my training data as well as testing data respectively. Then I've taken my image size as 50 and learning rate I've defined here. And I've given a name to my model. You can give whatever name you want. Alright, so first thing that we saw, we need to encode the dependent variable. That's what we are doing here. We are encoding our dependent variable. So whenever the label is cat, then it will be converted to an array of 1, 0, and when it is dog, it will be converted to an array of 0, 1. So why we are actually encoding the label? Because our code cannot understand the categorical variable. So we need to encode it, right? Next, what I'm doing is I'm resizing my image to 50 cross 50 and I am converting it to a grayscale image, right? And once this is done, I'm going to split my data set into training and testing parts. So yeah, we are basically splitting the data set into two parts for training and testing. And here we are defining a model. So I can just go ahead and throw in a comment here. Building the model. Yeah. So this is where we are building the model. So basically what we have done here is we have resized our image to 50 cross 1 matrix, and that is the size of the input that we are using, right? This input that I'm talking about. Then what we have done, a convolution layer we have defined with 32 filters and a stride of 5 with an activation function, a ReLU. And after that we have added a pooling layer, max pool layer. Okay. Again, what we have done, we have repeated the same process, but over here we are taking 64 filters and 5 stride, passing it through a ReLU activation function, and after that we have a pooling layer, max pool layer. Then we have repeated the same process for 128 filters. After that we have repeated for 64 filters, then for 32 filters, and after that we are using a fully connected layer with 1024 neurons. And finally we are using the dropout layer with key probability of 0.8 to finish our models. This is where our model is actually finished. And then what we are doing is we are using the Adam optimizer to optimize our model. So basically whatever the loss that we have, we are trying to reduce it. And this is basically for your TensorBoard. So we are creating some log files, and then with that log file, TensorBoard will create a pretty fancy graphs for us that helps us to visualize the entire model. And then what we are doing is we are trying to fit the model. And we have defined epochs as 10. That is the number of iterations that will happen will be 10. And yeah, so this is pretty much it. Model name we have given. Then input is x_test to check the accuracy. Similarly, the target will be y_test. The labels associated with that test data will be a y_test, and which we have encoded basically. So this is how we are going to actually calculate the accuracy, and we'll try to reduce the loss as much as possible in 10 epochs. So till now our model is complete. We are done with it. Next, what I'm doing is I'm feeding in some random input from the test data, and I'm validating whether my model is predicting it correct or not. All right. So I've already trained the model because it takes a lot of time, and yeah, I cannot do it here. So I've already trained the model, and you can see that the loss that came after the 10th epoch is 0.2973, and the accuracy is somewhere around 88%, which is pretty good, guys. And yeah, and I've done the prediction on the test data as well. So let me just show it to you that. So this is the prediction that it has done on few of the images in the test data. So yeah, it is a cat predicted as cat, cat predicted as cat, 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 and dogs as well. There are certain dogs as well. Why can't we use feed-forward networks? Now let us take an example of a feed-forward network that is used for image classification. So we have trained this particular network for classifying various images of animals. Now if you feed in an image of a dog, it will identify that image and will provide a relevant label to that particular image. Similarly, if we feed in an image of an elephant, it will provide a relevant label to that particular image as well. Now if you notice, the new output that we have got, that is classifying an elephant, has no relation with the previous output, that is of a dog. Or you can say that the output at time t is independent of output at time t minus 1. As we can see that there is no relation between the new output and the previous output. So we can say that in feed-forward networks, outputs are independent to each other. Now there are few scenarios where we actually need the previous output to get the new output. Let us discuss one such scenario. Now what happens when you read a book? You'll understand that book only on the understanding of your previous words. Alright, so if I use a feed-forward network and try to predict the next word in a sentence, I can't do that. Why can't I do that? Because my output will actually depend on the previous outputs. But in the feed-forward network, my new output is independent of the previous outputs. That is, output at t plus 1 has no relation with output at t minus 2, t minus 1, and at t. So basically, we cannot use feed-forward networks for predicting the next word in a sentence. Similarly, you can think of many other examples where we need the previous output, some information from the previous output, so as to infer the new output. This is just one small example. There are many other examples that you can think of. So we'll move forward and understand how we can solve this particular problem. So over here, what we have done, we have input at t minus 1. We'll feed it to our network. Then we'll get the output at t minus 1. Then at the next timestamp, that is at time t, we have input at time t that will be given to our network along with the information from the previous timestamp, that is t minus 1, and that will help us to get the output at t. Similarly, at output for t plus 1, we have two inputs. One is a new input that we give. Another is the information coming from the previous timestamp, that is t, in order to get the output at time t plus 1. Similarly, it can go on. So over here, I have just written a generalized way to represent it. There's a loop where the information from the previous timestamp is flowing. And this is how we can solve this particular challenge. Now let us understand what exactly are recurrent neural networks. So for understanding recurrent neural network, I'll take an analogy. Suppose your gym trainer has made a schedule for you. The exercises are repeated after every third day. Now this is the order of your exercises. First day you'll be doing shoulders, second day you'll be doing biceps, third day you'll be doing cardio. And all these exercises are repeated in a proper order. Now what happens when we use a feed-forward network for predicting the exercise today? So we'll provide in the inputs such as day of the week, month of the year, and health status. All right, and we need to train our model or our network on the exercises that we have done in the past. After that, there'll be a complex voting procedure involved that will predict the exercise for us. And that procedure won't be that accurate. So whatever output we'll get won't be as accurate as we want it to be. Now what if I change my inputs and I make my inputs as what exercise I've done yesterday? So if I've done shoulder, then definitely today I'll be doing biceps. Similarly, if I've done biceps yesterday, today I'll be doing cardio. Similarly, if I've done cardio yesterday, today I'll be doing shoulder. Now there can be one scenario where you are unable to go to gym for one day. Due to some personal reasons, you could not go to the gym. Now what will happen at that time? We'll go one timestamp back and we'll feed in what exercise that happened day before yesterday. So if the exercise that happened day before yesterday was shoulder, then yesterday there were biceps exercises. Alright, similarly biceps happened day before yesterday, then yesterday would have been cardio exercises. Similarly, if cardio would have happened day before yesterday, yesterday would have been shoulder exercises. Alright, and this prediction, the prediction for the exercise that happened yesterday will be fed back to our network, and these predictions will be used as inputs in order to predict what exercise will happen today. Similarly, if you have missed your gym say for 2 days, 3 days or 1 week, so you need to roll back. You need to go to the last day when you went to the gym. You need to figure out what exercise you did on that day, feed that as an input, and then only you'll be getting the relevant output as to what exercise will happen today. Now what I'll do, I'll convert these things into a vector. Now what is a vector? Vector is nothing but a list of numbers. Alright, so this is the new information guys along with the information from the prediction at the previous timestamp. So we need both of these in order to get the prediction at time t. Imagine if I have done shoulder exercises yesterday. So this will be 1, this will be 0, and this will be 0. Now the prediction that will happen will be biceps exercise, because if I've done shoulder yesterday, today it will be biceps. So my output will be 0, 1 and 0. And this is how vectors work, guys. So I hope you have understood this, guys. Now this is how a neural network looks like, guys. We have new information along with the information from the previous timestamp. The output that we have got in the previous timestamp will use certain information from that, will feed into our network as inputs, and then that will help us to get the new output. Similarly, this new output that we have got will take some information from that, feed in as an input to our network along with the new information to get the new prediction, and this process keeps on repeating. Now, let me show you the math behind the recurrent neural networks. So this is the structure of a recurrent neural network, guys. Let me explain you what happens here. Now consider at time t equals to 0, we have input x naught, and we need to figure out what is h naught. So according to this equation, h of 0 is equal to wi weight matrix multiplied by our input x of 0 plus wr into h of 0 minus 1, which is h of minus 1, and time can never be negative, so this particular equation cannot be applied here, plus a bias. So wi into x of 0 plus bh passes through a function g of h to get h of 0 over here. After that, I want to calculate y naught. So for y naught, I'll multiply h of 0 with the weight matrix wi, and I'll add a bias to it and pass it through a function g of y to get y naught. Now in the next timestamp, that is at time t equals to 1, things become a bit tricky. Now let me explain you what happens here. So at time t equals to 1, I have input x1. I need to figure out what is h1. So for that, I'll use this equation. So I'll multiply wi, that is the weight matrix, by the input x1 plus wr into h of 1 minus 1, which is 0. H of 0, we know what we got from here. So wr into h of 0 plus the bias, pass it through a function g of h to get the output as h1. Now this h1 will use to get y1. We'll multiply h1 with wi plus a bias and we'll pass it through a function g of y to get y1. Similarly, in the next timestamp, that is at time t equals to 2, we have input x2. We need to figure out what will be h2. So we'll multiply the weight matrix wi with x of 2 plus wr into h of 1 that we have got here plus b of h and pass it through a function g of h to get h of 2. From h of 2, we'll calculate y of 2, wi into h of 2 plus by, that is the bias, pass it through a function g of y to get y2. And this is how recurrent neural network works, guys. Now you must be thinking how to train a recurrent neural network. So a recurrent neural network uses backpropagation algorithm for training. But backpropagation happens for every timestamp. That is why it is commonly called as backpropagation through time. Over here, I won't be discussing backpropagation in detail. I'll just give you a brief introduction of what it is. Now with backpropagation, there are certain issues, namely vanishing and exploding gradients. Let us see those one by one. So in vanishing gradient, what happens? When you use backpropagation, you tend to calculate the error, which is nothing but the actual output that you already know minus the model output, the output that you got through your model, and the square of that. So you figure out the error. With that error, what do? You tend to find out the change in error with respect to change in weight or any variable. So we'll call it weight here. So change of error with respect to weight multiplied by learning rate will give you the change in weight. Then you need to add that change in weight to the old weight to get the new weight. All right. So obviously what we are trying to do, we are trying to reduce the error. So for that, we need to figure out what will be the change in error if my variables are changed, right? So that way we can get the change in the variable and add it to our old variable to get the new variable. Now over here, what can happen if the value dE by dW, that is a gradient, or you can say the rate of change of error with respect to our variable weight, becomes very small than 1, like it is 0.00 something. So if you multiply that with the learning rate, which is definitely smaller than 1, then you get the change of weight, which is negligible. All right. So there might be certain examples where you are trying to predict, say, a next word in a sentence, and that sentence is pretty long. For example, if I say I went to France dash dash dash, I went to France, then there are certain words, then I say few of them speak dash. Now I need to predict speak, what will come after speak. So for that, I need to go back in time and check what was the context, which will be very complex. And due to that, there will be a lot of iterations. And because of that, this error, this change in weight will become very small, very small. So the new weight that we'll get will be actually almost equal to your old weight. So there won't be any updation of weight that will be happening. And that is nothing but your vanishing gradient. All right, I'll repeat it once more. So what happens in backpropagation, you first calculate the error. This error is nothing but the difference between the actual output and the model output and the square of that. With that error, we figure out what will be the change in error when we change a particular variable, say weight. So dE by dW, multiply it with learning rate to get the change in the variable or change in the weight. Now we'll add that change in the weight to our old weight to get the new weight. This is what backpropagation is, guys. All right, I'm just giving you a small introduction to backpropagation. Now consider a scenario where you need to predict the next word in a sentence. And your sentence is something like this. I have been to France. Then there are a lot of words. After that, few people speak. And then you need to predict what comes after speak. Now, if I need to do that, I need to go back and understand the context. What is it talking about? And that is nothing but your long-term dependencies. So what happens during long-term dependencies, if this dE by dW becomes very small, then when you multiply it with n, which is again smaller than 1, you get delta W, which will be very, very small. That will be negligible. So the new weight that you'll get here will be almost equal to your old weight. So I hope you're getting my point. So this new weight, so there will be no updation of weights, guys. This new weight will always be almost equal to our old weight. So there won't be any learning here. So that is nothing but your vanishing gradient problem. Similarly, when I talk about exploding gradient, it is just the opposite of vanishing gradient. So what happens when your gradient or dE by dW becomes very large, becomes greater than 1, all right? And you have some long-term dependencies. So at that time, your dE by dW will keep on increasing, delta W will become large, and because of that, your weights, the new weight that will come, will be very different from your old weight. So these two are the problems with backpropagation. Now let us see how to solve these problems. Now exploding gradients can be solved with the help of truncated BTD, backpropagation through time. So instead of starting backpropagation at the last timestamp, we can choose a smaller timestamp like 10. Or we can clip the gradients at a threshold. So there can be a threshold value where we can, clip the gradients. And we can adjust the learning rate as well. Now for vanishing gradient, we can use a ReLU activation function. We have discussed ReLU activation function in artificial neural network tutorial, guys. Similarly, we can also use LSTM and GRUs. In this tutorial, we'll be discussing LSTMs, that are long short-term memory units. Now let us understand what exactly are LSTMs. So guys, we saw what are the two limitations with the recurrent neural networks. Now we'll understand how we can solve that with the help of LSTMs. Now what are LSTMs? Long short-term memory networks, usually called as LSTMs, are nothing but a special kind of recurrent neural network. And these recurrent neural networks are capable of learning long-term dependencies. Now what are long-term dependencies? I've discussed that in the previous slide, but I'll just explain it to you here as well. Now what happens, sometimes we only need to look at the recent information to perform the present task. Now let me give you an example. Consider a language model trying to predict the next word based on the previous ones. If we are trying to predict the last word in the sentence, say the clouds are in the sky. So we don't need any further context. It's pretty obvious that the next word is going to be sky. Now in such cases where the gap between the relevant information and the place that it's needed is small, RNNs can learn to use the past information. And at that time, there won't be such problems like vanishing and exploding gradient. But there are few cases where we need more context. Consider trying to predict the last word in the text, I grew up in France. Then there are some words. After that comes, I speak fluent French. Now recent information suggests that the next word is probably the name of a language. But if we want to narrow down which language, we need the context of France from further back. And it's entirely possible for the gap between the relevant information and the point where it is needed to become very large. And this is nothing but long-term dependencies. And the LSTMs are capable of handling such long-term dependencies. Now LSTMs also have a chain-like structure like recurrent neural networks. Now all the recurrent neural networks have the form of a chain of repeating modules of neural networks. Now in standard RNNs, the repeating module will have a very simple structure such as a single TANH layer that you can see. Now this TANH layer is nothing but a squashing function. Now what I mean by squashing function is to convert my values between -1 and 1. Alright, that's why we use TANH. And this is an example of an RNN. Now we'll understand what exactly are LSTMs. Now this is a structure of an LSTM. Or if you notice, LSTM also have a chain-like structure, but the repeating module has different structures. Instead of having a single neural network layer, there are 4 interacting in a very special way. Now the key to LSTM is the cell state. Now this particular line that I'm highlighting, this is what is called the cell state. The horizontal line running through the top of the diagram. So this is nothing but your cell state. Now you can consider the cell state as a kind of a conveyor belt. It runs straight down the entire chain with only some minor linear interactions. Now what I'll do, I'll give you a walkthrough of LSTM step by step, alright? So we'll start with the first step. Alright guys, so the first step in our LSTM is to decide what information we are going to throw away from the cell state. And you know what is the cell state, right? I've discussed in the previous slide. Now this decision is made by the sigmoid layer. So the layer that I'm highlighting with my cursor, it is a sigmoid layer called the forget gate layer. It looks at ht-1, that is the information from the previous timestamp, and xt, which is the new input, and outputs a number between 0 and 1 for each number in the cell state ct-1, which is coming from the previous timestamp. A 1 represents completely keep this, while a 0 represents completely get rid of this. Now if we go back to our example of a language model trying to predict the next word based on all the previous ones, in such a problem, the cell state might include the gender of the present subject so that the correct pronouns can be used. When we see a new subject, we want to forget the gender of the old subject, right? We want to use the gender of the new subject. So we'll forget the gender of the previous subject here. This is just an example to explain you what is happening here. Now let me explain you the equations which I've written here. So ft will be combining with the cell state later on, that I'll tell you. So currently ft will be nothing but the weight matrix multiplied by ht-1 and xt and plus the bias, and this equation is passed through a sigmoid layer. Alright, and we get an output that is 0 and 1. 0 means completely get rid of this, and 1 means completely keep this. Alright, so this is what basically is happening in the first step. Now let us see what happens in the next step. So the next step is to decide what information we are going to store. In the previous step, we decided what information we are going to keep, but here we are going to decide what information we are going to store here. Alright, what new information we are going to store in the cell state. Now this has two parts. First, a sigmoid layer, this is called a sigmoid layer, and which is also known as an input gate layer, decide which values we'll update. Alright, so what values we need to update. Then there's also a tan layer that creates a vector of the candidate values c bar of t-1 that will be added to the state later on. Alright, so let me explain it to you in a simpler terms. So whatever input that we are getting from the previous timestamp and the new input, it will be passed through a sigmoid function which will give us I of t. Alright, and this I of t will be multiplied by ct, which is nothing but the input coming from the previous timestamp and the new input with that is passed through a tan that will result in ct. And this will be later added on to our cell state. And the next step will combine these two to update the states. Now let me explain the equations. So I of t will be what? Weight matrix, and then we have ht-1 comma xt multiplied by the weight matrix plus the bias, pass it through a sigmoid function, we get I of t. C bar of t will get by passing a weight matrix ht-1 xt plus bias through a tan squashing function, and we'll get C bar of t. Alright, so as I've told you earlier as well, in the next step we'll combine these two to update the state. Let us see how we do that. So now is the time to update the old cell state ct-1 with the new cell state ct. Alright, and the previous steps we have already decided what to do. We just need to actually do it. So what we'll do, we'll multiply the old cell state ct-1 with ft that we got in the first step, forgetting the things that we decided to forget earlier in the first step, if you can recall. Then what we do, we add it to it and ct, then we add it by the term that will come after multiplication of it and c bar t, and this new candidate value scaled by how much we decided to update each state value. Alright, so in the case of the language model that we were discussing, this is where we would actually drop the information about the old subject gender and add the new information as we decided in the previous steps. So I hope you are able to follow me, guys. Alright, so let us move forward and we'll see what is the next step. Now our last step is to decide what we are going to output, and this output will depend on our cell state, but it will be a filtered version. Now finally what we need to do is we need to decide what we are going to output, and this output will be based on our cell state. First we need to pass ht-1 and xt through a sigmoid activation function so that we get an output that is OT. Alright, and this OT will be in turn multiplied by the cell state after passing it through a tan squashing function or an activation function. And why we do that? Just to push the values between -1 and 1. So after multiplying OT, that is this value, and a tan CT, we'll get the output H2, which will be our new output, and that will only output the part that we decided to. Whatever we have decided in the previous steps, it will only output that value. Alright, now I'll take the example of that language model again. Since it just saw a subject, it might want to output information relevant to a verb, and in case that's what is coming next. For example, it might output whether the subject is singular or plural, so that we know what form of a verb should be conjugated into. All right, and you can see from the equations as well. Again, we have a sigmoid function. Then that whatever output we get from there, we multiply it with tan h ct to get the new output. All right, guys. So this is basically LSTMs in a nutshell. So in the first step, we decided what we need to forget. In the next step, we decided what are we going to add to our cell state, what new information we are going to add to our cell state, and we were taking an example of the gender throughout this whole process. All right, and in the third step, what we do, we actually combined it to get the new cell state. Now in the fourth step, what we did, we finally got the output that we want. And how we did that? Just by passing ht minus 1 and xt through a sigmoid function, multiplying it with the tan h ct, the tan h new cell state, and we get the new output. Fine, guys. So this is what basically LSTM is, guys. Now we'll look at a use case where we'll be using LSTM to predict the next word in a sentence. All right, let me show you how we are going to do that. So this is what we are trying to do in our use case, guys. We'll feed our LSTM with correct sequences from the text of 3 symbols. For example, had a general and a label, that is council in this particular example. Eventually, our network will learn to predict the next symbol correctly. So obviously, we need to train it on something. Let us see what we are going to train it on. So we'll be training our LSTM to predict the next word using a sample short story that you can see over here. All right, so it has basically 112 unique symbols. So even comma and full stop are considered as symbols. All right, so this is what we are going to train it on. So technically, we know that LSTMs can only understand real numbers. All right, so what we need to do is we need to convert these unique symbols into a unique integer value based on the frequency of occurrence, and like that we'll create a dictionary. For example, we have had here that will have value 20, A will have value 6, general will have value 33. All right, and then what happens, our LSTM will create a 112 element vector that will contain the probability of each of these words or each of these unique integer values. All right, so since 0.6 has the highest probability in this particular vector, it will pick the index value of 0.6, then it will see what symbol is attached to that particular integer value. So 37 is attached to council. So this will be our prediction, which is absolutely correct, as a label is also council according to our training data. All right, so this is what we are going to do in our use case. So guys, this is what we'll be doing in our today's use case. Now I'll quickly open my PyCharm and I'll show you how you can implement it using Python. We'll be using TensorFlow, which is a popular Python library for implementing deep neural networks or neural networks in general. All right, so I'll quickly open my PyCharm now. So guys, this is my PyCharm, and over here I've already written the code in order to execute the use case that we have. So first we need to do is import the libraries. NumPy for arrays, TensorFlow, we know TensorFlow.contrib. From that we need to import RNN, then random collections and time. All right, so this particular block of code is used to evaluate the time taken for the training. After that we have log underscore path, and this log underscore path is basically telling us the path where the graph will be stored. All right, so there will be a graph that will be created, and then that graph will be launched. Then only our RNN model will be executed. Then that's how TensorFlow works, guys. So that graph will be created in this particular path. All right, and we are using summary writer. So that will actually create the log file that will be used in order to display the graph using TensorBoard. All right, so then we have defined a training underscore file, which will have our story on which we'll train our model on. Then what we need to do is read this file. So how are we going to do that? First is read line by line whatever content that we have in our file. Then we are going to strip it. That means we are going to remove the first and the last white space. Then again we are splitting it just to remove all the white spaces that are there. After that we're creating an array, and then we are reshaping it. Now during the reshape, if you notice, this -1 value tells us the compatibility. All right, so when you're reshaping it, you need to make sure that we are providing in the correct parameters to reshape it. So you can convert a 3x2 matrix to a 2x3 matrix, right? So just to make sure that it is compatible enough, we add this -1 and it will be done automatically. All right, then return content. After that, what we are doing, we are feeding in the training data that we have, training underscore file. We are feeding in our story and calling the function read underscore data. Then what we are doing, we are creating a dictionary. What is a dictionary? We all know key value pairs based on the frequency of occurrences of each symbol. All right, so from here collections.counter words.most common. So most common words with their frequency of occurrence, there will be a dictionary created. And after that, we'll call this dict function, and this dict function will feed in word, and which is equal to length of dictionary. That means whatever the length of that particular dictionary is, how many times it is repeated. So we'll have the frequency as well as a symbol. That will be our key value pair, and we are reversing it as well. Then what we are doing, we are calling it build underscore data set, and we're feeding in our training data there. This is our vocabulary size, which is nothing but the length of your dictionary. And then we have defined various parameters such as learning rate, iterations or epochs. Then we have display step and underscore input. Now learning rate, we all know what it is. The steps in which our variables are updated. Training underscore iterations is nothing but your epochs, the total number of iterations. So we have given 50,000 iterations here. Then we have display underscore step, that is 1000, which is basically your batch size. So batch size is what? After every 1000 epochs, you'll see the output. All right. So it'll be processing it in batches of 1000 iterations. Then we have n underscore input as 3. Now the number of units in the RNN cell will keep it as 512. Then we need to define X and Y. So X will be our placeholder that will have the input values, and Y will have all the labels. All right. Vocab size. So X is a placeholder where we'll be feeding in our input dictionary. Similarly, Y is also one more placeholder, and it'll have a shape of none, comma, vocab size. Vocab size we have defined earlier, as you can see, which is nothing but the length of your dictionary. Then we are defining weights as well as biases. After that, we have defined our model. All right, so this is how we are going to define it. We'll create a function RNN when we'll have X weights and biases. And after that, we are calling in RNN.multi-RNN cell function. And this is basically to create a 2-layer LSTM, and each layer has n underscore hidden units. After that, what we are doing, we are generating the predictions. But once we have generated the prediction, there are n underscore input outputs, but we only want the last output. All right, so for that, we have written this particular line. And then finally, we are making a prediction. We are calling this RNN function, feeding in X weights and biases. After that, we are calculating the loss and then we are optimizing it. For calculating the loss, we are using reduce underscore mean, softmax cross entropy. And this will give us basically the probability of each symbol, and then we are optimizing it using RMS prop optimizer. All right, and this gives actually a better accuracy than Adam optimizer, and that's the reason why we are using it. Then we are going to calculate the accuracy, and after that we are going to initialize the variables that we have used. As we have seen in TensorFlow that we need to initialize all the variables, unlike constants and placeholders in TensorFlow. All right, and once we are done with that, we are feeding in our values, then calculating the accuracy, how accurate it is, and then when optimization is done, we are calculating the elapsed time as well. So that will give us how much time it took in order to train our model. Then this is just to run the TensorBoard on local host 6006. And this particular block of code is used in order to handle the exceptions. So exceptions can be like whatever word that we are putting in might not be there in our dictionary or might not be there in our training data. So those exceptions will be handled here, and if it is not there in our dictionary, then it will print word not in our dictionary. All right, so fine guys, let's input some values and we'll have some fun with this model. All right, so the first thing that I'm gonna feed in is had a general. So whenever I feed in these three values, had a general, there'll be a story that will be generated by feeding back the predicted output as the next symbol in the inputs. All right, so when I feed in had a general, so it will predict the correct output as council, and this council will be fed back as a part of the new input, and our new input will be a general council. So it will be a general council. All right, so these three words will become our new input to predict the new output, which is 2. All right, and so on. So surprisingly, LSTM actually creates a story that somehow makes sense. So let's just read it. Had a general council to consider what measures they could take to outwit their common enemy, the cat. By this means, we should always know when she was about and could easily. All right, so somehow it actually makes sense when you feed in that. So what will happen when you feed in these three inputs? It will predict the next word, that is council. After that, it will take council and it will feed back as an input along with a general. So a general council will be your next input to predict 2. Similarly, in the next iteration, it will take general council 2 and predict consider for us. And this will keep on repeating.
Alright, now to start off, let us now understand what is natural language processing and why do we even need it. You see, natural language refers to the speech analysis in both audible data as well as a text document. NLP system can capture meaning from an input such as sentences, paragraph, pages, and give out a desired output based on our application. So why do we need NLP? You see, natural language processing helps computer communicate with humans in their own language and scale other language related tasks. For example, NLP makes it possible for computers to read text, hear speeches, interpret it, measure the sentiment, and then determine which part of it are important. Today's machines can analyze more language-based data than humans, that too with consistency, accuracy, and in an unbiased manner. More or less, we all know that there is a staggering amount of unstructured data that is generated every day, be it from a medical record or to a social media. Automating NLP tasks will critically be helpful in future for analyzing text and speech data efficiently. So moving ahead, let us now see the ways we can process our textual data. We can process our textual data in one of two ways. One is a machine learning way and other one is a deep learning method. In machine learning, we can make use of algorithms such as bag of words, TF-IDF to classify and predict the desired output. But the drawback of this is that these machine learning algorithms do not consider the context of the word or a sequence. Here, the way it works is based on number of times the word is repeating, a probability is derived out of it, and then performs a classification task. This is the reason why we have deep learning model for NLP tasks. Speaking about deep learning model, we have something like recurrent neural network, LSTM, transformer network, Google's BERT algorithm, and many more. This deep learning model learns the pattern of a word or a sequence and then tries to predict the desired outcome of the task. We can perform NLP using deep learning in one of two ways. One by pre-trained models such as Google's Word2Vec or global vector models. And the other way is to train our own model. If we are trying to train our own model, it would require a very huge amount of data and also compute power to support it. In most of the cases, we will be using pre-trained models. Moving ahead, let us now discuss recurrent neural networks. As I mentioned earlier, the bag of word or TF-IDF model for processing our text is very inefficient. As I mentioned earlier, the bag of word or TF-IDF model that was used in machine learning to process our textual data is very inefficient, as it takes one word at a time and also the context of the word in which it is being spoken about is totally ignored. Although this would give us some prediction, but we can expect a lot of loss. This is why we use RNN model or recurrent neural network. Here, it requires a sequential data. Now you might be wondering, what does this sequential data mean, right? In simple words, sequential data is dependent on the past values. What I'm trying to say here is that we can read our document, right? We can read our document or English documents only from left to right side. Or take example of stock price prediction. We cannot randomly place the dates, right? If you have to make a prediction for next 2-3 months, we'll obviously refer to the data that was previously recorded. So this is what a sequential data means. So what makes RNN capable of handling sequential data? Well, you see, RNN model makes use of something called a state. This is nothing but a temporary memory that stores the previous data. As you can see here in an image, this is the general architecture of a recurrent neural network. So let me now move to my canvas and show you how a recurrent neural network works and what are its internal workings. Alright, so as we have seen in an image right back in our slide, you saw that recurrent neural network have something called as states, and then we also had some boxes, right? So what does those boxes represents? So let me quickly draw over here and show you what does this box represents. So if you remember, right, it goes something like we have a box here, okay, and then we also had another box, and then let's consider like 2 more boxes, that would be sufficient, okay. And then the way we provide input for our recurrent neural network is over here, okay. Now based on our application, we can demand our recurrent neural network to provide output in either one of the 3 ways. It can either be like we can have multiple inputs, as you can see here, or we can have single input and multiple outputs, or the other way around is we can have single input and single output. So here what we'll consider is we are using multiple inputs and also we have multiple outputs. Okay, so now let us see, as this is a supervised learning model, right? Obviously it will have some kind of input and then it will also have labels to clarify the data. So let's take something like if this is our X data, right? So if this is the X data, so let's take this as a list, and then over here we'll have data which would represent something like X1, then we'll have X2, then we'll have X3, and then so on, and we'll have something like Xn. Okay, so what does this X over here represents? See, here let's take an example that Uri, which was a movie, is a good movie. We can have a couple more X's and we'll just put here as good movie. Okay, so this is nothing but the inputs, each of these words. Now, what our model over here does, let's take an example that we are trying to find name entity prediction, which stands for NER, right? So what this name entity prediction does is, it trains the model in such a manner that it finds a pattern. So as you can see here, this is Uri, right? Uri, it's something like a name, right? So this goes as 1, and is not a name, so this would be 0. Good, this is also not a name, and movie is also not a name. So the output over here would be something like 1000. All right. So now let's see what are the inputs and how it would look like. So first off, we have inputs. So if this is our X data, so we'll have input something like Xi. This would be in lowercase. Okay. So this would be X1. Then we'll have X2. We'll have X3. And then we'll have X4. Similarly, the Y, the output over here would be something like, we'll give it Y hat of 1, Y hat of 2, Y hat of 3. At the same time, we'll also have Y hat of 4. Now, if you're wondering what does this Y hat represents, Y hat over here is nothing but predicted values. And Y is nothing but, the labeled value or trained values. And now, as we all know that the main thing or the main feature behind recurrent neural network is nothing but the states. And the way the states are represented is by using the state vector, or it can also be called as context vector. So the state vector over here starts with A. Let me give it as a different color here. Let me give it as blue. So here we'll have A, and this would be 0. Okay. And now this A would be passed down to this. Okay. So this would be A of 1, and over here we'll have A of 2, A of 3, and then finally A of 4. I'm pretty sure you might be wondering what does this A contains, right? So over here, as I have mentioned, let me take this very example. So here Uri is good movie. Okay. And so what this A1 will contain? A1 will contain Uri. See, if we take the normal algorithm, what's going to happen is it will just consider only this one particular block. Okay. If this was just a normal algorithm or something which is used in the olden days, it will just consider this particular block and it won't be considering the previous values. So this previous value is being stored over here in the form of a memory. So now A1 will contain Uri, and what A2 will contain over here. So A2 will be having something like Uri is. And similarly, as it goes through here, it will collect each and every word. And finally, A4 will be complete context vector. So it will have the entire sentence, Uri is a good movie. Okay, I hope you understood what does this A signifies over here. Let me quickly erase all of these. Okay, so another important part which goes over here in any machine learning or deep learning model is nothing but the weights. So let's consider that we have weights, which is nothing but W, or let's take it as U. Let me give another color here, U, V, and W. In this RNN model, right, what we're going to do is we're going to have a single, or we'll have just only one weights, right? So the U weight is same for all of these inputs here. V weight over here is same for all the outputs. The weight W is same for all our state metrics. Okay, so this is how the weights are determined. So now to get a better understanding of what's happening over here and to derive a mathematical equation for feed-forward network, let's take a single block over here. And let's see how this internal working of this is working, okay? So over here we'll have a box, okay? And this will be our input. So let's give our input as x of t, because this is a generalized model, right? And now what we're going to do over here is this would be a of t minus 1. That's because a of t will be present over here. And now if we have an output which is present over here, and this would be nothing but y hat of t. All right. So as I mentioned earlier that we will be having weights. So the weights over here is nothing but u, v, and w. So what's happening over here? Okay. So first off, there will be a matrix multiplication between these two values. Okay. Another, there will be a matrix multiplication between these two values. And once they are done, we'll add these two values and then give an activation function to it. Okay. And the activation function that would be used over here is tan h. So if I have to put it in an equation form over here, so the product of these two, x of t times, or it would be a dot product of u, okay? And the sum of these two, so it will be t minus 1 times w. And now what we're going to do is we're going to pass an activation function, which is nothing but tan h over here. So let's just give a small dotted notation over here. So whatever the output which comes, we'll be performing an addition of these two and also give an activation function which will represent here by f. All right. So this is how we get an activation function over here. So what does this value signifies this? This is nothing but this output over here, a of t. So I hope you understand what is a of t. A of t is this value. Okay, let me quickly highlight that for you. So a of t is this value. Okay, so a of t is represented over here, and the way we get this is by this particular equation. Now what about the value for y hat of t, or the prediction of y of t? So for y of t, it's going to be something like this. So y hat of t, this would be nothing but, we have to multiply this particular a of t with this matrix over here, okay, or the weights I can say. So it's going to be nothing but a of t times the weight matrix, that is v, and then we have to pass activation function. Usually the activation function that is going to be used over here is softmax or sigmoid. It totally depends upon what kind of output you are expecting. All right, and this is how it works. And now an important thing that I would like to mention over here is that we also have to add something called as bias. So it will be b over here. I'll just represent this by a different color. So this is an equation for our recurrent neural network in a mathematical form. So now what's going to happen is, in order to find a loss, right, we have to subtract whatever value we have predicted with the given value. So the predicted value over here, let's say this is as capital Y, okay, and we also have been given the trained value. So this would be looking something like this. So we'll obviously have the trained values. Let's just give a random output, but there will be 4. So it'll be 0, 1, 0, 1. Okay, so this is nothing but the trained values. And now we'll have the other, this is nothing but the given label data. So this would be correct values. So 1, 0, 0, 1. As this is a supervised learning, so we obviously will be given this label data over here. So now what this will do is, this will subtract each of these values and calculate a loss. So how do you calculate a loss, right? Okay, so as you can see here, if I give this L, like, let me change the color here. So if I say L is loss, so this would be nothing but y hat of first value minus the actual value. Okay, so this is nothing but the predicted value, and this is nothing but the given value. So if I try to find out the loss of this, then what this would look like is, this is just for the one value, right? So if I have to do it for all the values, then it would be the summation. So it would be nothing but loss is equal to summation I, which ranges from 1 to n, right? And then we'll have loss and then theta I. Okay, so this Li over here represents these values. Okay, so this is just for one. So if you want me to explain you this in detail, so over here we have y1, y2, y3, and y4. How this would look like is something, so this would be for 1 plus y hat of 2 minus actual value of y of 2, then summation predicted value of y3 minus the actual value of y3, and then it'll be predicted value of y4 minus the actual value of y4. And when I perform addition over here, or when I perform summation, I can generalize this equation into this form. But we are not yet done over here. As you can see, we have something called as theta values. So what does this theta values represents? You see, the main agenda behind finding a loss is to increase our accuracy, right? So if I say this is my gradient descent and this is the lowest global minima, right? So my agenda over here is to reach this global minima. So now, in order for me to do this, in order to increase my accuracy, I have to obviously change my values. So how do I do that? How do I increase an accuracy? It's obviously by these weights. Okay, it's by this W, U, and V. So W, U, and V are nothing but the weights. So what this theta over here represents, let me quickly erase this. Okay, so what this theta over here represents is nothing but the values of W, U, and V. So now what we're going to do is, we are going to have a partial derivative of the loss with respect to U, and then we'll have a partial derivative of loss with respect to V, and then we'll also have partial derivative of loss with respect to W. These are nothing but weights, and we are trying to train the weights. This is done in order to increase our accuracy. Okay, and the way these models get trained is with the help of backpropagation, and the way the backpropagation works over here is by partial derivative. So what I'm trying to say here is, as if I get my weights over here, so let me just take another color. So this V, we know that it is totally dependent upon this value over here. This won't be V, this would be W. Okay, so this W value will be totally dependent on the previous one, and this value will be dependent on this one, and this value will be dependent on this one, and this one would be finally dependent on this. So this is in order to move from here to here to here and then to here, we'll use something called as partial derivatives, right? So that's how we update our old weights. All right. And another important concept that make neural network or recurrent neural network very important is nothing but embedding layer. So let me quickly draw a boundary over here. Okay, so embedding layer. All right, so what does this embedding layer signifies? Okay, so if I take a convention way, right? So like, let's say that, our X, or, our input over here, this is nothing but X over here, right? So what is the dimension or the shape of this X? The shape of this X is nothing but 1, 4, right? 1, 4. Similarly, it's 1, 4 here, 1, 4, and 1, 4. But this is not usually the case when you're working with real world examples. When you're working with real world examples, we won't be having 4 different words, right? We'll obviously have lakhs of values. So for example, let's say we have X, and the shape of this X is something like we have 10,000 values. Okay, so now if I try to feed this 10,000 values into my network over here, obviously I would be using batch propagation. So it would take a lot of time, right? Because it's 10,000 values after all. So in order to overcome this, what we're going to do is we're going to reduce the size of this. Okay, so basically what word embedding layer does is think that we have a matrix. This is our input layer, right? Or input word. So we call this as sparse matrix. This is nothing but, an individual value, that's xi or x1, x2, x3. Let's, for generalization, we'll give here as xi. And the shape of this is nothing but 1, v. V here represents the n number of dimensions. And 1 is because it's just going to be one word, right? So it's going to be 1. So if I consider with respect to this is 1 and this is v. Okay. So now what will happen is, if v is 10,000 or pretty great, it obviously we won't have much, we are going to lose a lot of time on computation and also take huge compute power. So what we'll do is I'll multiply this with an embedding layer. And what this embedding matrix does is it is basically a set of features. So this is something, this is a black box model. And all this would do is this would attract a couple of features. If you want me to give you a better analogy of what this is, and if you want me to compare this with respect to a CNN, which is nothing but another great algorithm for image processing using deep learning, right? Over there, we are going to use something called as filters or kernels. So each of those filters or kernels is responsible for extracting one specific feature, right? So this is what embedding layer does. And what this would do, for example, now let's say that the size of embedding layer is v, k. K is something that we provide an input over here. So now what this would happen is this would give us a new matrix or embedded matrix whose size would be 1, k. I'm pretty sure you didn't understand this because over here I'm using, these letters. So in order to make you better understand this, what I'm going to do is let me take a matrix over here. Okay, let me take something like, because this would be in an embedded form, right? This would be a sparse matrix. So it will be like 0, 0, 0, 0, 0, 1, then we'll have 0, 0, and so on. Okay, so now what this would do is we'll also create a matrix over here. The size of this would be something similar to that of v. This is nothing but 1, v, and over here it would be k. So the matrix shape over here would be v, k, right? To give you a better analogy, let me also draw a couple of boxes here. So this is the matrix, and this is the matrix over here again. So now what will happen over here is when I try to perform this matrix multiplication, right? What this would do, as everything is 0 and only one value is true. So let's say this is the one value, right? And this would be going across, from left to right, and this would be from top to bottom. Only one part over here would be marked, and rest everything would be 0. Therefore, reducing the dimension, let me give some random values like 0.5, 1.8, 0.5, just some random values. So now this would obviously reduce the size of 1, k. So what I'm trying to say here is, now for example, say that I have a size over here as 1, 10,000, okay, which is a very huge matrix. And the shape of this, let's say that it's 10,000, 200. When I perform this embedding, right, word embedding, the shape of the new matrix would be nothing but 1, 200. If I compare this part over here to the embedding, whatever we have received over here. So let me just give a quick brief. So this is our embedded layer. So this is really 1, 200. So you will see that we have decreased the dimensions by a drastic amount. Okay, so this is 10,000 and this is only 200. And this would be very efficient when we are trying to feed this to our recurrent neural network. And let me quickly show you how this would go. So first let me draw our architecture. Let's take this blocks like this. And then we'll have an output over here. Okay, so this would be our inputs, right? So let me give something like this. So initially we used to provide X values over here, right? Now we won't be doing that. We won't be providing any X values directly. Instead of that, what I'm going to do is I'll have an embedding layer over here. And this will have the X values. So let me give here as X of 1, so X of 2, X of 3, and then we'll have X of 4. And then similarly, let's take this model to be multiple input and single output. So here we'll have y hat of t, and then we'll have weights obviously. So this would be u, v, and w. And this is nothing but our matrix over here. So this would be a of 0, a of 1, a of 2, a of 3, and finally a of 4. Okay, so this is our context matrix. And obviously we'll be performing an activation function here. So I'll just give it as f. You can put f, you can put g, it's totally up to you. So this is how a recurrent neural network would actually work. All right. So now that we know how RNN works, let us now understand what is LSTM, or we can also say it as long short-term memory. You see, traditional RNNs are not good at capturing long-range dependencies. What I mean to say here is that when we tend to work with a very huge data set and multiple RNN layer, we are at the risk of vanishing gradient problem. Now you might be wondering, what is this vanishing gradient, right? Well, you see, when training a very deep neural network, gradient or the derivatives decrease exponentially as it propagates down the layer. This is known as vanishing gradient problem. These gradients are actually used to update the weights of a neural network. But when the gradients vanish, these weights will not get updated. In the worst case scenario, it will completely stop the neural network from training. This vanishing gradient problem is a common issue in very deep neural networks. So to overcome this vanishing gradient problem in RNNs, long short-term memory was introduced. You see, LSTM or long short memory is a modification to RNN's hidden layer. LSTM is capable of remembering RNN's weights and their inputs over a very long period of time. In LSTM, in addition to the hidden state, cell state is passed down to the next block. The way LSTM works is that it can capture long-range dependencies, that is all weights. It can have memory of previous inputs for a very extended time duration. The way LSTM cell does this is by using three main gates. First one is a forget gate. Forget gate removes the information that is no longer useful in the cell state. Then we have input gate. Additional information to the cell state is added by input gate. And finally, we have something called as output gate. Additional useful information to the cell state is also added by an output gate. This gating mechanism of LSTM has allowed network to learn the conditions for when to forget, ignore, or keep information in the memory cell. So let me now quickly move to my Jupyter notebook and show you how I can implement LSTM on name entity prediction. Alright, so let me quickly move there. Alright, so over here, first off, I'll be opening my Google Colab. Okay, so let us give a name for our Google Colab over here. Let's give a short term, right? Name entity prediction. And let's connect our Google Colab to our server. Okay, meanwhile that's connecting. So now you might be wondering, from where am I going to use my data set? So for me to use my data set, I'll just go for Kaggle, Kaggle, baby names. So let me just quickly show you how this data set would look like. So this is a CSV file over here. All right, so as you can see here, we have our 93,889 unique values. Okay, so this is a very huge data set. And let's try downloading this. To download this is pretty simple. All you need to do is click this and it will get downloaded. As I've already downloaded this file, let me quickly upload this on my Jupyter notebook. So let me go here and upload it from here. Okay, so let me go to this upload file. And yeah, so I have my CSV file here and let me open this. As this is a pretty huge data set, it will take some time. Meanwhile, that's loading. Let's see what we can do. So first off, let's import a couple of libraries. So we'll have import pandas as PD. And then we are going to import numpy as np. And then we also need to have matplotlib. So from sklearn. All right. And we also need something like label encoder, but I'll show you a shortcut way to bypass label encoding. Okay. So let's try to load our cell here. And in order for us to read this data, so it's pretty simple. All we are going to do is let's give this as a data. This would be nothing but pandas.readcsv. And then we are going to pass our file name. Let me change this to our root directory. We're putting a dot over here. Okay, so I won't be executing this as of now because it's trying to load our file. All right, so now that we have successfully loaded our data, so let's try running this cell over here. Okay, so let me close this and let me zoom in over here. So now what we're going to do is let's see the shape of our data. So let's see what's the data shape, data.shape, and now let's see what it would be like. Okay, so as you can see here, we have 5 columns, but the number of rows that we have is 1.8 million. That is approximately 18 lakhs, right? So this is a pretty huge value. So now what we're going to do is we'll just see how our data is looking like. So we'll see data.head, and let's see what we need. So as you can see here, we have ID, which is of no use for us. Then we have name. Okay, then this year, I don't think it's of any use for us. Then we have gender and count. Count here represents, how many people have the name Mary, how many people have the name Anna, how many people have the name Emma, Elizabeth, and Minnie. This is over here. Out of this, if you see, right, there are a couple of things that we don't need. We can drop them out. All we need is a name. Okay, and then we also need the gender, because this is going to be our prediction. We are going to predict, we'll give our own custom name, and then we'll see whether the name that is we are giving is a male or a female. Okay, so now what we're going to do is let's see how many unique values we have. So let me quickly erase this first. Okay, so what I'm going to do is data.names. So this should give us here a name, and then we'll type here as unique. Okay, so this would give me unique values. Okay, so over here I have 93,889 unique names. Okay, so now what we're going to do is we want to label encode this, right? So we want our female, or which is nothing but F, we want female to be 0 and then male to be 1, or vice versa. So in order to do that, either we can use label encoder, or there's a shortcut method to this. Let me quickly show you how that works. So first off, we'll take our data frame. So it's data, and which column we want to do this for? We want to do this for our gender column, right? So let me pass this and give gender. And now what we're going to do is, okay, we'll take this as type. Okay, this would be obviously in the form of category. And now what we'll do is this is cat dot codes. Okay, so this is nothing but panda shortcut, do label encoding. Let's try to execute this and see what it would look like. So as you can see here, we have a couple of zeros and ones. This is nothing but it's representing females with 1 and males with zeros. Okay, so now what we'll do is we have to update this column. So we'll paste this, and this should be something like this over here. And let me execute this. Okay, so if you want to see how our data would look like now, let me just quickly run this once again. So you'll see here now the values has been label encoded. Okay, so now what we're going to do is we obviously need to take the unique names, right? And then we'll obviously group it by, right? So what we'll do for this is we'll take something like data. We'll group this by the names. So group by names. All right. And now what we'll do is we'll calculate the mean of the genders. We'll reset the index. The reason why we want to reset the index is because, if we don't give the index, then our name over here will become the index, right? So we'll give reset underscore index. All right. So let's give this to a new data frame, and we'll call this as df. Okay, let me execute this now. And let's see how this df would look like. Okay, let me execute this right after this. So as you can see here, it has grouped by names, everything in an ascending order. So this is all in an alphabetical manner. And yeah. And now only thing that I want to work on is this gender. Okay. The reason is because over here I'm getting a floating point value. I don't want this floating point value. I want to change this to integer value, right? So what I'll do is df gender. This would be nothing but df gender. Then all I'm going to do is type. I'll just put here as int. So let's now see what this value would look like. Fantastic. We over here have now, ones and zeros, which is nothing but an integer value. Okay. So if you want to see this, so either I can write df or I can also put as head. Okay. So these are the first 5 values. Okay. So now the way our neural network is going to work, or the recurrent neural network is going to work, is that, I hope you remember these boxes, right? So when I was talking, or when I was explaining this RNN, I was saying that I would be passing around the words. But here in this project or in this program, we won't be passing words over here. We won't be passing like Abha or Abida or Adam. We won't be passing these words. Instead of that, we'll be passing letters. So over here, it's going to be like alphabets. So A, B, it can be any alphabet, it can be Z here. So basically it depends upon whatever the value is coming here. So in order to do that, we have to find number of unique alphabets. So we know how many unique alphabets we have, right? So it's 26. So in order to get these alphabets, what we'll do is, let me first quickly erase this. Erase all drawing. So now we have 26 alphabets. We have to create our own vocabulary. So what I'm going to do is I'm going to import string. So now I need letters, right? So letters, this would be nothing but list of string.ascii. Okay. And if you want to see what this would give me, this would be nothing but the list of alphabets, which are in lower cases. Okay. And now what we'll do is we'll try to create a label encoding, or we have to create a vocabulary, right? So we'll have something like vocab. This would be nothing but I'll be using dictionary. And now what I want is zip. The way I want over here is, for every individual values of this A, B, C, D, I want to label encode this to 0, 1, and whatever the value it is, right? So it would be from 1 to 27, unique numbers, right? So this would be nothing but letters. And then we need something like range 1, 27. So this would give me the matrix from 1 to 26, right? And let's now see what this would look like. So we have vocab, and let me execute this. This should give me a dictionary. Okay. So here we'll convert A to 1. Okay. And then B would be 2, C would be 3, and so on. Z would be 26. And now what we are going to do is we'll just try to create the reverse vocabulary. And the reason is we obviously won't be needing this, but just in case if you want to use, it should be something very similar to this. Let me just copy the exact same thing and paste it over here. So we'll just give it as reverse, right? So it will be R underscore, and here instead of numbers being second, we'll just cut this letters and we'll pass letters over here. And now you'll see if you're trying to decode whatever we have predicted, we can just pass it down like this. Okay, so now what will happen is we need to do something like, all our data, whatever is there, we have to convert them into a lowercase. So, and then once we convert them into a lowercase, we have to encode them into numbers. So whatever I'm saying is this AABAN, right? ABAN. So this AA, obviously first off, we have to convert all of this into a lowercase, this value. And then whatever the equivalent value of A, the numerical value of A, so it's obviously going to be 1. We'll substitute that with this, and it's going to be a list, right? So how do I do that? So for that, I'll write a function. So we'll have def word to number, right? Word to. So now what I'm going to do is I'm going to have for loop for I in range. So this would be nothing but we have to go through the entire shape, right? So df dot shape. This would give me a list, and I just need the first index. Okay, so now what I'm going to do is I'll create one new list sequence. This would be nothing but for letters in df. Obviously we want the names part, and in this we are going to pass the index value. It's going to be I. Let me just give some space here just so that you better understand this. And now what I'm going to do is, I'll have this vocabulary, vocab. See, every time I pass a letter, it will convert it into, this individual letter, it will convert it into a list or the equivalent, numerical representation. It will be letters, and obviously it has to be in lower, so it will be lower. And then we'll just close this bracket here. So now what we are going to do is, before we execute this function, we'll have to append this. So it will be df, and this is going to be names dot I. We'll replace the name in that index with this particular sequence. Okay, so now all we need to do is run this function over here, and yeah, this will take some time. The reason is because we have almost around 18 lakh values. So yeah, this will take some time. Meanwhile, let me just comment this. Okay, so in the next stage, what we are going to do is, let's see how this value over here would look like. So let us now first execute this. All right, so let us now see how our data frame will look like. So let me execute this block now. So as you can see here, our names have been completely changed or converted into a list of numbers. But now only issue that we are trying to have is the imbalance in the size of the list. Because when we are trying to have the number of boxes, right, we won't be having variable number of boxes. Okay, so what we're going to do is either we set a value like something like take an average number like 10, 20, or you can take something like, something like you either depend on maximum number or the minimum number of list. But the thing is, if you take the maximum number, then we have to pad a lot of zeros, and this would lead to a loss. So if I reduce the size, this would also decrease the accuracy, right? So what we're going to do is we'll plot this name and gender in the form of a histogram. So let's take here X. This would be df names, and we'll give here as dot values. And then same thing, we'll do it for Y, df gender, and this would be dot values. So what we'll do is we also need a list. Okay, so now as we are going to plot this on a histogram, and what we're going to see in the histogram is just to analyze, this is a graph. We want to analyze, where does the highest number of sequence, or if suppose this is a size, if this is size 8 and this is like 8,000 words or 8,000 names have the size 8, then we can keep our average somewhere near, and then we can also decide, if the number after 10, if not many names have a longer number or the longer length of that name, so we can keep our average somewhere around 9 or 10. Okay, so let's now quickly see how we can do that to get the length of our names. So length X or name length, this would be like list comprehension for I in range 0, df dot shape of 0. And now what we're going to do is we need to find the length. So this would be length X of I. Over here you can either give df or you can also give this X, right? So it would be length of X. Okay, so let me quickly execute this. Okay, so here we're getting an error. Oh yeah, it's not O, it's going to be 0, right? So let me execute this now. Okay, so let me show you how this would look like. Name length, and let me print this off. So as you can see, this is giving me a list of names. So there are a huge amount of names. So as you can see, first we had 5, 5, and then 9. So let's now plot this and see how it would look like. Import matplotlib as PLT. All right, this is perfect. So now what I'm going to do is I have to plot this, right? So all I'm going to do is plt.hist. All right, and now I'm just going to give name length and number of bins. This would be like, let's give 20, okay? And then plt.show. Okay, so what do we find from this graph over here? You see, this is nothing but the length of the names. So 2, 4, 6, 8, 12, all these are the length of the names. And this is nothing but 0, 5,000, 10,000. This is nothing but number of names that have a length 4 or number of names that have the length 6. So as you can see, right, there are around almost 25,000 names whose length is 6. And then as I cross like 10 or as I cross 12, not many names are there whose length is greater than, 12. So what I'm going to do here now is, now we have to pad, right? Now we have to pad the number of zeros. So in order to pad zeros, we have something called as built-in function from Keras. So from Keras, or you can also set as keras.preprocessing.sequence import pad sequence. So let me quickly execute this now. And now what I'm going to do is I'm going to create a new list. So let this be X. This is in lowercase. So pad sequence. And the things that this is going to take is obviously the sequence. We have to give a list of sequence. Okay. And then we'll give something like df.names. And then this is going to be values. And now we want to define the max length. So this is going to be 10. We also have an option of providing where do you want to do the padding. So we can also do it as pre or post. We'll obviously be doing pre. So let's see, how do we do that? This would be nothing but, if you can see this sequence over here. So we have padding is equal to pre. It's by default, right? So pre. So let me execute this now. And let's see how this X would look like. Okay, so as you can see here, X is a matrix whose length is 10. Okay, so each of these, like this is nothing but 19 million cross 10. So there are 10 columns throughout all. So now what we're going to do is we're going to create our own model. So for that we'll do from keras.layers import input layer, and then we have to have embedding layer, because if you don't have embedding layer, then it would be like each input would be something like 1,1.9 million, that is 18 lakhs. So it's a pretty huge value to compute. So we don't want that. So that's why we'll use embedding layer. Then we have dense layer, and then we have LSTM. We also, rather than taking this as a sequential model, we'll take it as, feed forward. So what we'll do is from keras.models import model. So now what we are going to do is we'll have to create our input layer. So this will be input is equal to input. And now the shape that we are going to pass over here. So for this shape, so how many columns do we have? We obviously have 10 columns, right? So it's going to be 10. So now what we're going to do is next we are going to have embedding layer. So let's say this is EMB and this would be embedding. So input over here, or the input dimension over here, is nothing but vocab size. We haven't defined this vocab size, so let's quickly do that. So vocab size, this would be nothing but length of vocabularies plus 1. The reason why I'm doing plus 1 is because we also have zeros over here, right? And this would be like vocab size if you want to see. And let me execute this. So we have 27, right? So 26 are the number of alphabets, and 1 is because we have number of zeros. So we'll pass this as vocab size. Okay, and now we are also going to pass output dimension. So output dimension, this is nothing but how many dimensions we want. So now this is going to be 5. All right, and the input for this embedded layer is going to be from INP. Okay, and now we are going to have our first LSTM layer. So it's going to be LSTM1. So this will be LSTM layer. Number of units we have to define here. So units, this is going to be like 32. The units over here does not represent the number of boxes. The units over here represent the A values, right? So now we have to do return sequence, and this is going to be true. And the input for this is going to be from embedded layer. Then we have LSTM second layer, and this is be LSTM units we're going to pass. So number of units that we're going to pass now is 64. And now the input for this is going to be LSTM1. Finally, we have an output layer. So at the end, right, we're going to have a dense layer, right? So dense. So number of units or number of neurons at the end, we are going to have 1. And kind of activation function that I'm going to have here is going to be sigmoid, because we have to predict either it's a male or a female. Okay, so sigmoid, and the input for this is going to be LSTM2. So finally, we have to add this to our model. So I'll give it as my model. This would be model. So now I have to define the inputs. So INPUTs, this is going to be inputs, INP, and outputs, this is going to be out. Okay, so let me quickly execute this now. Okay, so we have this error. Please provide either a shape. Okay, so let's see what's, oh yeah, here I've given it as sparse, right? So it's not going to be sparse, it's going to be shape. So let me quickly execute this once again. Okay, as you can see, we have successfully executed this. And now let's see the model.summary. So as you can see here, first off, we have input layer. Okay, so we can have a number of values, but there will be only 10 features. Okay, that's 10 columns. And then we are going to have, once you go through this embedding layer, then instead of having 10, instead of having that 1 million or whatever it is, 1.8 million, we'll have just 135 parameters. Okay, similarly over here, and finally at the dense we have 65 parameters, and then we have 1. The reason why we have 65 here, just for if you don't know, is because 64 plus 1 bias, and this would give us 65. Okay, so now finally we are going to train our model, but before that we have to compile it. It's going to be my model dot compile. Okay, so we have to find an optimizer. So optimizer, best one that I feel is Adam. Then we have to find the loss. So as we are going to use just 2 predictions, right? Either it's male or female, we'll use binary cross entropy. And then finally the matrix that we want to use here is, this will be accuracy. So let me execute this now. And finally we are going to compile this. So we'll have history. So this will be model.fit. Okay, and now we are going to pass our values. We're going to give x, we're going to give y. As you know, x is nothing but the matrix which has a padding, and y is nothing but the other classes. They're telling us either it's ones or zeros. And number of epochs, this is going to be 10. Batch size, as this is a pretty huge data set, we are going to keep a pretty high batch size. So I'll give a batch size here as 256. And then finally we need validation split. Okay, it's not going to be my model, it's going to be my model, right? So my underscore model. So finally we're going to have validation split here. So let's give it as 20%. So it's going to be 0.2. All right, so finally it's the moment of truth. Let us now execute our code. This would take some time to execute. So let's see how this would look like. Okay, so if you can analyze this data over here. So as you can see, right, this validation accuracy has to increase. And we cannot see every time, if our model is overfitting, the accuracy over here will keep on increasing. All right. So the more reliable source over here to see is nothing but validation accuracy. So if validation accuracy is increasing, that means our model is neither overfitting nor underfitting. And you can also see that we have our validation loss, which is kind of decreasing. And over here as well, we can see the validation loss. Over here, we can see the loss of a model is decreasing from 60, then 40, then 39, 39, and 80, 38. So let's now wait for a few more epochs. So we have 4 more to go. Okay, so as you can see here, our validation accuracy has been increasing. So this is a very healthy growth. And even over here, our accuracy of a model is also increasing. Fine. And the loss is decreasing. It's decreased from 60% to 37%. And over here, our validation loss decreased from 42% to 36%. So let us now map this, like whatever values we have received. So in order to map this, we have h. This model over here retrieves us the history function, right? So we'll give hist.history, and let me execute this. Okay, so now what we're going to do is, this is nothing but key value paste. So if I put h, if I give something like accuracy, okay, well, let's plot this. So model.plot, right? So plt.plot. Okay, we'll have accuracy. We'll compare this with respect to accuracy, and then plt.plot. Then we'll have validation accuracy, and we want to show this, right? So plt.show. So as you can see here, okay, so just to give a better analogy, let's execute one of these first. Okay, so the blue line over here represents the accuracy of a model, and then this is nothing but the accuracy of our training data, right, or testing data. So as you can see, our model accuracy isn't decreasing, so it's a very good model and it has trained very well. So now coming down to the moment of truth. So let's now take a random name and see whether it can predict whether the name is true or false. Okay, so we'll give here as test_name. So let's give something like, this would be like name, right? So we'll give name.lower, and now we are going to pass the name over here. So this would be, let's say, Tom. Okay, so we have to convert this into letters, right? So it will be vocab of I for I in test name. And now we'll give the name here as xtest. So this would be nothing but we have to pad the sequence, pad sequence. We'll pass this in a form of a tuple. Then this would be seq. And then we know that we have to pad 10, right? And anyways, we don't have to say whether it's pre or post, because by default it's going to be pre. Fine. So let us now see how our text data would look like. So x test string attribute has, okay. Oh yeah, so I have done a typo over here. It's going to be LOWER. So let me execute this once again. So as you can see here, we have a matrix which has a size of 10. And let's now see what this would predict. So it's the moment of truth. So y.predict, this would be model.predict, and I'm going to pass here as xtest. And let's see what does this predict. So we'll give here as ypred, and yeah, let us execute this. Okay, so we are getting this in a form of an array. So what this tells us, this tells us that, this is like 70% chances that this name is Tom. In order to make this, layman stuff, so what we are going to do is we'll have if ypred. Let me execute this first. So let me go down to another block. So this would be something like if ypred is less than 0.5, then we'll say the name is female, okay? Else print name is masculine or name is, or let it be male, okay? So same thing over here, we'll just keep it as male. So let's now see what this thing predicts. Okay, so this thing predicts male. So let's take another common name. Let's take something like, let's go to Google and see what name can we take. Yeah, we can take up something like Brad Pitt. Okay, so let's execute this, and let's execute this again, and then this. So as you can see here, this is giving me a male name. And let's give a female name over here. Let's give as Mary, and let's see whether this would predict it as male or female. So as you can see here, it's female. Now, as if you have seen the data set, right, it says this is the name from the US kids, right? What will happen if I give an Indian based name? So let me give an Indian based name like Priyanka, and let me execute this. It's giving me a female name, right? So this is something pretty astonishing, right? So why do you think it gave me a female name? Well, the reason is because when we are training this model like RNN, using RNN, right, it's not looking at the name. It doesn't know whether the name is female or not. But as a matter of fact, it is looking at the pattern. Okay, so it might be looking at, if the name ends with so and so, it is a female. If the name starts with this, or if a name have something like this, it means, it's a female or a male. So to give you a better analogy, let's give something like Julia. So let me execute this. This will give me a female, right? So what if I give something like Junaid? This would give it as male. So all it's trying to do is it's trying to see, recognize a pattern. That's why it's taking individual words at the same time. So this is what makes NLP using LSTM very effective. All right, so moving ahead, let's see some of the LSTM's use cases. You see, LSTM is a very popular deep learning algorithm for sequential models. Apple Siri and Google's voice search are some of the real-world examples that have used LSTM. And you won't believe it, LSTM is a success story for those algorithms. So let us now have a look and see how LSTM changed that technology. Okay, so starting off with Apple. In 2003, Apple was the first major tech company to integrate a smart assistant, that is Siri, into an operating system. And the Siri was actually a byproduct of some other company. So Siri was a company's adoption of a standalone app that has been purchased along with the creators who made it. It was somewhere in 2010. The initial reviews about Siri was that it was intense. But over the next few months and years, the users became more impatient with the shortcomings. And all too often, it wrongly interpreted commands. And then, no matter what you do, there was no fix for it. So this is when Apple moved Siri's voice recognition to a neural-based system. Some of the previous techniques remain operational, something like, applying hidden Markov models. But most of the time, DNN or deep neural network using LSTM was used. Although people did not find any changes on the outside, but from within, it was a supercharged deep learning model. Speaking about Google's implementation, Google implemented Google Voice Search somewhere in 2009. Google Voice Transcription had initially used something called as Gaussian matrix model. This was nothing but an acoustic model, and this was something considered to be a state-of-the-art speech recognition for almost 30 plus years. But it was in 2012, there was a boom in deep neural network. And when Google implemented deep neural network, that too using multiple layer networks, there was a huge performance gap. But things really improved when the recurrent neural network, especially with LSTM RNN, first launched on an Android speech recognition in May 2012. Compared to deep neural network, LSTM RNNs have additional recurrent connections and memory cell that allows them to remember the previous data. Alright, so moving ahead to our last topic of our session, let us now see some of the real-world applications of LSTM RNN networks. First off, we can perform name entity recognition. This is something which we did in our previous demo, right? So what is this name entity recognition? You see, name entity recognition is a subtask of information extraction that seeks to locate and classifies name entity mentioned in an unstructured data. Okay. Next, we have something called as sentiment analysis. Sentiment analysis is a predictive modeling task where model is trained to predict the polarity of a textual data or sentiments like positive, neutral, or negative. Sentiment analysis is performed by various businesses to understand their consumers' behavior towards the product. Then we have machine translation. The task of machine translation consists of reading text in one language and generating text in another language. When neural networks are used for this task, we talk about neural machine translation. Within neural machine translation, an encoder-decoder structure is quite a popular LSTM RNN architecture. Why should we choose deep learning for various tasks? So the big advantage of using deep learning is that we can extract more number of features. And when we have more number of features and when we can work at the same time with huge amount of data, we can perceive an object like a human being does. What I'm trying to say over here is, like, if you want to perform a classification task between pen and a pencil, you'll obviously know, as a human being, you'll know the difference because you have looked at a pen and a pencil continuous number of times. And now when you're trying to actually classify it, you can do it with ease. Okay, and the reason for this is because you know the features of a pen and you know the features of a pencil. Okay, similarly, this is how deep learning works. More the data you feed, more the dimensions it can analyze, more the dimensions it can learn. All right, so as I've already mentioned, one of the most popular application of deep learning is image classification. And when it comes to image classification, it can be something as simple as classifying between two different animals to something as complicated as hiding data or trying to run automated cars using classification tasks. Okay, All right, so next type of application using deep learning is using on sequential data. Sequential data basically refers to something like time series data or having to understand natural language. So the reason why we call it sequential data is because here the previous word or the previous feature is dependent upon the next feature. Okay, so as you can see over here, we have what time is it, right? So if I just say it is, like over here, what time is and it are basically features, right? And in order for you to make an analogy or to understand, obviously you have to know what has happened in the past. So in order to do this, we use something called as RNNs. Okay, and there are various versions of RNN that go around in order to overcome the disadvantages, which we'll look in some time. All right, so moving on to the next application, that is GANs. GANs, which stands for Generative Adversarial Network, is an unsupervised part of a deep learning application. Some of the common applications which you can see in recent days is nothing but deep fakes and many more. Finally, coming down to performing classification and regression tasks using multi-layer perceptron. If you remember, or if you're well versed with machine learning, in order to perform classification in machine learning, we had algorithms like decision tree, random forest, or something very simple as linear regression or logistic regression. But let me tell you what, when we try to perform classification using MLP or multi-layer perceptron, we get a very high accuracy even compared to SVM and decision trees. Alright, so now that we know what exactly is deep learning and why we use it, let's now stream down to understand how can we process natural language data using RNNs. So what are RNNs, right? Well, RNN basically stands for Recurrent Neural Network. And we usually use this in order to deal with a sequential data. Sequential data can be something like a time series data or a textual data of any format. So why should one use RNN, right? Well, this is because there's a concept of internal memory here. RNN can remember important things about the input it has received, which allows them to be very precise in predicting what can be the next outcome. So this is the reason why they are performed or preferred on a sequential data algorithm. Okay, and some of the examples of sequential data can be something like time series, speech, text, financial data, audio, video, weather, and many more. Although RNN were the state-of-the-art algorithm for dealing with sequential data, they come up with their own drawbacks. And some of the popular drawbacks over here can be like, due to the complication or the complexity of the algorithm, the neural network is pretty slow to train. And as there are a huge amount of dimensions here, the training is very long and difficult to do. Okay. Apart from that, the most decisive feature for RNN or for the improvement in RNN is that of a vanishing gradient. What this vanishing gradient is that, when we go deeper and deeper into our neural network, the previous data is lost. This is because of a concept called as vanishing gradient. And due to this, we cannot work on a large or a longer sequence of data. Okay. To overcome this, we came up with some new or upgrades to the current recurrent neural networks or RNNs. Starting off with bidirectional recurrent neural network. You see, bidirectional recurrent neural network connect two hidden layers of opposite direction into the same output. With this form of generative deep learning, the output layer can get information from past, future states simultaneously. So as you can see here, we have two layers over here. And as they are bidirectional, what happens is when the algorithm feels that it is kind of losing its gradients or the previous data, it can go back and get the data from the past. So why do we need bidirectional recurrent neural network? Well, bidirectional recurrent neural network duplicates RNN processing chain so that the input process both forward and reverse time order, thus allowing bidirectional recurrent neural network to look into future context as well. The next one is long short-term memory. Long short-term memory, or also sometimes referred to as LSTM, is an artificial recurrent neural network architecture used in the field of deep learning. Unlike standard feed-forward neural network, LSTM has a feedback connections. It can not only process single data point, but also the entire sequence of data. So as you can see here, from what I'm trying to say is, with LSTM or long short-term memory, it has something like, we can feed a longer sequence compared to what it was with bidirectional RNN or RNNs. So why is LSTM better than RNN? We can say that when we move from RNN to LSTM, we are introducing more and more control over the sequence of the data that we can provide. Thus, LSTM gives us more control ability and thus better results. Alright, so the next type of recurrent neural network is the gated recurrent neural network, or also referred to as GRUs. You see, GRU is a type of recurrent neural network that is, in certain cases, is advantageous over long short-term memory. GRU makes use of less memory and also is faster than LSTM. But thing is, LSTMs are more accurate while using longer data sets. I'm sure by now you might have got a hint about the trend that has led to the improvement, right? So the trend over here is, the model should be capable of remembering and taking in on a longer input sequence. The game changer part for the sequential data was developed when we came up with something called as transformers. And this paper was something which is based on a concept called as attention is everything. All right, so let's take a look at this. The paper Attention is All You Need introduces a novel architecture called as transformers. Like LSTM, transformers is an architecture for transforming one sequence into another while helping other two parts, that is encoders and decoders. But it differs from previously described sequence to sequence model because it does not work like GRUs. Okay, so it does not implement recurrent neural networks. Recurrent neural network until now were one of the best ways to capture the timely dependence on a sequence. However, the team presenting this paper, that is Attention is All You Need, proved that an architecture with only attention mechanism does not use RNN can improve its result in translation tasks and other NLP tasks. One of the best examples for transformers is Google's BERT. So what exactly is this transformer, right? You see here we have encoder on the top and decoder on the bottom. Both encoder and decoder are comprised of modules that can stick onto the top of each other multiple times. So what happens here is the inputs and outputs are first embedded into n-dimension space since we cannot use this directly. So we obviously have to encode our inputs, whatever we are providing here. One slight but important part of this model is the positional encoding of different words. Since we have no recurrent neural network that can remember how sequences are fed into the model, we need to somehow give every word or part of our sequence a relative position since a sequence depends on the order of the elements. Okay, these positions are added to the embedded representation of each words. Alright, so this was the brief about transformers. So let us now move ahead and see some of the popular language models that are available in the market. Alright, so let us now start off by understanding OpenAI's GPT-3. The successor to GPT and GPT-2 is the GPT-3 and is one of the most controversial pre-trained models by OpenAI. The large-scale transformer-based language model has been trained on 175 billion parameters, which is 10 times more than any previous non-sparse language model. The model has been trained to achieve strong performance on many NLP datasets, including tasks like translation, answering questions, as well as several other tasks. Then we have Google's BERT. BERT stands for Bidirectional Encoder Representations from Transformers. It is a pre-trained NLP model which is developed by Google in 2018. With this, anyone in the world can train either their own question answering module with up to 30 minutes on a single cloud TPU, or few hours using single GPU. The company then released this showcasing the performance of 11 NLP tasks, including very competitive Stanford dataset questions. Unlike other language models, BERT has only been pre-trained on 250 million words of Wikipedia and 800 million words of book corpus, and has been successfully used as a pre-trained model in deep neural network. According to researchers, BERT has achieved 93% accuracy, which has surpassed any previous language models. Next, we have ELMO. ELMO, also known as Embedding for Language Model, is a deep contextualized word representation that models syntax and semantic words as well as their logistic context. The model developed by Allen NLP has been pre-trained on a huge text corpus and learned functions from bidirectional models, that is BiLM. ELMO can easily be added to their existing models, which drastically improves the features of functions across vast NLP problems, including answering questions, textual intent, and sentiment analysis.
Data compression is a big topic that's used in computer vision, computer networks, and many more. Now, the point of data compression is to convert our input into a smaller representation that we recreate to a degree of quality. The smaller representation is what would be passed around, and when anyone needed the original, they would reconstruct it from the smaller representation. Now, autoencoders are unsupervised neural networks that use machine learning to do this compression for us. The aim of an autoencoder is to learn a compressed, distributed representation for the given data, typically for the purpose of dimensionality reduction. Now, for that, we already have principal component analysis. Then, why do we need autoencoders? So, an autoencoder can learn nonlinear transformations, unlike PCA with a nonlinear activation function and multiple layers. Now, it doesn't have to learn dense layers. So it can use convolutional layers to learn too, which could be better for video, image, and series data. Now, it may be more efficient in terms of model parameters to learn several layers with an autoencoder rather than learn one huge transformation with PCA. An autoencoder also gives a representation as the output of each layer, and having multiple representations of different dimensions is always useful. So an autoencoder could let you make use of pre-trained layers from another model to apply transfer learning to prime the encoder or the decoder. Despite the fact that the practical applications of autoencoders were pretty rare some time back, today data denoising and dimensionality reduction for data visualization are considered as two main interesting practical applications of autoencoders. Now, with appropriate dimensionality and sparsity constraints, autoencoders can learn data projections that are more interesting than PCA or other basic techniques. It also provides a more accurate output when compared to PCA. Now, autoencoders are simple learning networks that aim to transform inputs into outputs with the minimum possible error. This means that we want the output to be as close to input as possible. An autoencoder neural network is basically an unsupervised machine learning algorithm that applies backpropagation, setting the target values to be equal to the inputs. So let's have a look at some of the key features about autoencoders. So it is an unsupervised machine learning algorithm that is similar to PCA but minimizes the same objective function. An autoencoder is a neural network whose target output is its input. Autoencoders, although, is quite similar to PCA, but they are more flexible when compared to the other. Autoencoders can represent both linear and nonlinear transformation in encoding, but PCA can only perform linear transformation. So now let's have a look at the components of autoencoders. So there are basically three main layers. The first one is the encoder, then code and decoder. The first component, that is the encoder, is the part of the network that compresses the input into a latent space representation. The encoder layer encodes the input image as a compressed representation in a reduced dimension. Now the compressed image typically looks garbled, nothing like the original image. The next component represents the latent space. Now, code is the part of the network that represents the compressed input fed to the decoder. The third component is the decoder. Now, this layer basically decodes the encoded image back to the original dimension. The decoded image is a lossy reconstruction of the original image. Now, it reconstructs the input from the latent space representation. So now let's talk about some of the properties of autoencoders. They are only able to compress data similar to what they have been trained on. An autoencoder which has been trained on human faces would not be performing well with images of modern buildings. This improvises the difference between the autoencoders and MP3 kind of compression algorithms, which only hold assumptions about sound in general, but not about specific types of sounds. Autoencoders are lossy, which means that the decompressed outputs will be degraded compared to the original inputs, just like what you see in JPEG or MP3. Now, if you have appropriate training data, it is easy to train specialized instances of the algorithm that will perform well on a specific type of input. Now, it doesn't require any new engineering. Additionally, in almost all contexts where the term autoencoder is used, the compression and decompression functions are implemented with neural networks. So now let's have a look at the training of an autoencoder. Now there are four hyperparameters that we need to set before training them. The first one is the code size. The code size represents the number of nodes in the middle layer. Smaller size results in more compression. The second parameter is the number of layers. Now the autoencoder can be as deep as we want it to be. We can have two or more layers in both the encoder and decoder without considering the input and the output. Next is the loss function. So we either use mean squared error or binary cross entropy. Now if the input values are in the range 0 to 1, then we typically use cross entropy, otherwise we use the mean squared error. Next is the number of nodes per layer. So the number of nodes per layer decreases with each subsequent layer of the encoder and increases back in the decoder. Also, the decoder is symmetric to the encoder in terms of layer structure, But this is not necessary and we have total control over these parameters. Now let's have a look at the architecture of an autoencoder and have a deeper insight about the hidden layers. So in an autoencoder, we add a couple of layers in between the input and the output, and the sizes of these layers are smaller than the input layer. Let's say the input vector has a dimensionality of n, which means that the output will also have a dimensionality of n. Now we make the input go through a layer of size p where the value of p is less than n, and we ask it to reconstruct the input. Now the autoencoder receives unlabeled input, which is then encoded to reconstruct the input. One important part of the autoencoders is the bottleneck. Now the bottleneck approach is a beautifully elegant approach to a representation learning, specifically for deciding which aspects of observed data are relevant information and what aspects can be thrown away. It does this by balancing two criteria, that is the compactness of representation measured as the compressibility, number of bits needed to store the representation, and the second one, information the representation retains about some behaviorally relevant variables. Now it assumes we know what the behaviorally relevant variables are and how they are related to observed data, or at least we have to have data to learn or approximate the joint distribution between observed and relevant variables. Now let's have a detailed description about the encoder. The encoder is a neural network. Its input is a data point x, its output is a hidden representation z, and it has weights and biases theta. Now to be concrete, let's say x is a 28 by 28 pixel photo of a handwritten number. The encoder encodes the data, which is 784 dimensional, into a latent representation space z, which is much less than 784 dimensions. Now this is typically referred to as a bottleneck because the encoder must learn an efficient compression of the data into this lower dimensional space. Next is the decoder. The decoder is another neural net. Its input is the representation z. It outputs the parameters to the probability distribution of the data and has weights and biases as phi. Running with a handwritten digit example, let's say the photos are black and white and represent each pixel as 0 or 1. Now the probability distribution of a single pixel can be then represented using a Bernoulli distribution. The decoder gets as input the latent representation of a digit z and outputs 784 Bernoulli parameters, one for each of the 784 pixels in the image. The decoder decodes the real valued numbers in Z into 784 real valued numbers between 0 and 1. Information is lost because it goes from a smaller to a larger dimensionality. Now, how do we find out how much information is lost? The loss function equation helps us find the value. Now, this measure tells us how effectively the decoder has learned to reconstruct an input image X given its latent representation Z. The loss function of the variational autoencoder is the negative log likelihood with a regularizer. Because there are no global representations that are shared by all data points, we can decompose the loss function into only terms that depend on a single data point. So in the loss function, the first term is the reconstruction loss, or expected negative log likelihood of the ith data point. The expectation is taken with respect to the encoder's distribution over the representations. This term encourages the decoder to learn to reconstruct the data. Now, if the decoder's output does not reconstruct the data well, it will incur a large cost in the loss function. The second term is a regularizer that we throw in. This is the callback labeler divergence between the encoder's distribution. Now, this divergence measures how much information is lost when using Q to represent P. It is one measure of how close Q is to P. If the encoder outputs representations Z that are different than those from a standard normal distribution, it will receive a penalty in the loss. This regularizer term means keep the representation Z of each digit sufficiently diverse. If we didn't include the regularizer, the encoder could learn to cheat and give each data point a representation in a different region of Euclidean space. So now let's move on and have a look at the different types of autoencoders. The convolution operator allows filtering an input signal in order to extract some parts of its content. Autoencoders in their traditional formulation do not take into account the fact that a signal can be seen as a sum of other signals. Convolution autoencoders use the convolution operator to exploit this observation. Basically, they learn to encode the input in a set of simple signals and then try to reconstruct the input from them, modify the geometry or the reflectance of the image. Now, the encoder consists of three convolutional layers. The number of features changes from 1, the input data, to 16 for the first convolutional layer, then from 16 to 32 for the second layer, and finally from 32 to 64 for the final convolutional layer. Now, while transacting from one convolutional layer to another, the shape undergoes an image compression. So the decoder consists of three deconvolution layers arranged in sequence. For each deconvolution operation, we reduce the number of features to obtain an image that must be the same size as the original image. So in addition to reducing the number of features, deconvolution involves a shape transformation of the images. A convolution is the general continuous case defined as the integral of the product of two functions after one is reversed and shifted. As a result, a convolution produces a new function and it is a commutative operation. Now, in the 2D discrete space, the convolution operation is defined as the following equation. And in the image domain where the signals are finite, this formula becomes as such, where O of ij is the output pixel in position ij, and 2k plus 1 is the side of a square, that is the odd convolutional filter. F is the convolutional filter and I is the input image. Now, this operation is done for every location of the input image that completely overlaps with the convolutional filter. Now, let's see the use cases of convolution autoencoders. The first one is image reconstruction. Now, the convolution autoencoders learn to remove noise from a picture or reconstruct the missing parts. So, the input noisy version becomes the clean output version. The network also fills the gap in the image. Next is image colorization. Now, convolution autoencoders maps circles and squares from an image to the same image but with red and blue respectively. Purple is formed sometimes because of blend of colors where network hesitates between circle or square. Next up are some of the advanced applications such as fully image colorization, latent space clustering, and generating higher resolution images. Moving on to the next type of autoencoders. Sparse autoencoders offer us an alternative method for introducing an information bottleneck without requiring a reduction in the number of nodes at our hidden layers. Rather, we will construct our loss functions such that we penalize activations within a layer. So for any given observation, we will encourage our network to learn an encoding and decoding, which only relies on activating a small number of neurons. Now, this is a different approach towards regularization as we normally regularize the weights of a network, not the activations. Now, there are two main ways by which we can impose this sparsity constraint. Both involve measuring the hidden layer activations for each training batch and adding some term to the loss function in order to penalize excessive activations. The first one is the L1 regularization. Now we can add a term to our loss function that penalizes the absolute value of the vector of activations A in layer H for observation I, now scaled by a tuning parameter lambda. The next one is the KL divergence. In essence, KL divergence is a measure of the difference between two probability distributions. We can define a sparsity parameter rho, which denotes the average activation of a neuron over a collection of samples. This expectation can be calculated in the following equation. Now, the KL divergence between two Bernoulli distributions can be written as such. Now, this loss term is visualized below for an ideal distribution of rho equals to 0.2, corresponding with the minimum penalty at this point. The next one is the deep autoencoders. Now, the extension of the simple autoencoder is basically the deep autoencoders. Now, the only difference to its simpler counterpart is number of hidden layers. The additional hidden layers enable the autoencoder to learn mathematically more complex underlying patterns in the data. The first layer of the deep autoencoder may learn first-order features in the raw input. The second layer may learn second-order features corresponding to patterns in the appearance of first-order features. Deeper layers of the deep autoencoder tend to learn even higher-order features. To put everything together, we need additional layers to be able to handle more complex data, such as the data we use in collaborative filtering. So let's have a look at some of the use cases of deep autoencoders. The first one is image search. Deep autoencoders are capable of compressing images into 30 number vectors. Image search therefore becomes a matter of uploading an image, which the search engine will then compress to 30 numbers and compare that vector to all the others in its index. Vectors containing similar numbers will be returned for the search query and translated into their matching image. A more general case of image compression is data compression, and deep autoencoders are useful for semantic hashing. Next up is the topic modeling and information retrieval. So deep autoencoders are useful in topic modeling or statistically modeling abstract topics that are distributed across a collection of documents. In brief, each document in a collection is converted to a bag of words, and those word counts are scaled to decimals between 0 and 1, which may be thought of as the probability of a word occurring in the document. For example, one document could be the question and others could be the answers. Now, a match the software would make using vector space measurements. The next type of autoencoders is the contractive autoencoders. One would expect that for very similar inputs, the learned encoding would also be very similar. We can explicitly train our model in order for this to be the case by requiring that the derivative of the hidden layer activations are small with respect to the input. In other words, for small changes to the input, we should still maintain a very similar encoded state. Now, this is quite similar to a denoising autoencoder in the sense that these small perturbations to the input are essentially considered noise, and that we would like our model to be robust against noise. Now, we can accomplish this by constructing a loss term which penalizes large derivatives of our hidden layer activations with respect to the input training examples, essentially penalizing instances where a small change in the input leads to a large change in the encoding space. Now, in fancier mathematical terms, we can craft our regularization loss term as the squared Frobenius norm of the Jacobian matrix J for the hidden layer activations with respect to the input observations. A Frobenius norm is essentially an L2 norm for a matrix, and the Jacobian matrix simply represents all first-order partial derivatives of a vector-valued function. Now, for m observations and n hidden layer nodes, we can calculate the values using the following equations. So now that we know the various types of autoencoders, let's have a look at how it actually works. So let's see the code that provides us with a reconstructed image. So this is the code for autoencoder that generates a similar output as the input with reduced dimensions. The packages that are needed to be pre-installed are NumPy, Keras, and Matplotlib. So first we define the size of our encoded representations. The encoded representation of the input is declared as encoded, while the lossy reconstruction of the input is declared as decoded. The input is then mapped to its encoded representation in order to create the decoder model. Next, we have to prepare our input data and normalize all the values between 0 and 1. The 28 by 28 images will be then flattened into vectors of size 784. Now, once the data is trained and tested, the autoencoder is trained. It will take certain values from the test set, encode, and decode them. Now, for the visualization of the reconstructed inputs and the encoded representations, it is done with the help of Matplotlib library. So let's see what happens when we execute this code. So now we can see that the data is being trained and tested, and this will take a few minutes to complete. Now, once we are done with the training of the data, we will have an original image and a reconstructed image as our output. Our output will look like this. So the first row shows the original input image and the second row shows the reconstructed image with reduced dimensions. So now we have seen how an autoencoder actually works and how it provides us a reconstructed image. So now let's move on to some of the applications of autoencoders. Now, autoencoders are used for converting any black and white picture into a colored image. Depending on what is in the picture, it is possible to tell what the color should be. For example, the leaves of trees are generally green, the sky is blue, and the clouds are white. So all that is needed to be done is to make a computer be able to do this, and that is where autoencoders step in. The next application is the feature variation. It basically extracts only the required features of an image and generates the output by removing any noise or unnecessary interruption. Now, using autoencoders, we receive the same image as the input but with reduced dimensions. It helps in providing the similar image along with a reduced pixel value. Now, during the training, the autoencoder learns to extract important features from input images and ignores the image noises because the labels have no noises. The input seen by the autoencoder is not the raw input but a stochastically corrupted version. Now, autoencoders are also used for removing watermarks from images or to remove any object while filming a video or a movie. So now we have reached the end of today's session, and I hope you have a clear idea about what are autoencoders and how do they actually work.
What are GANs? So we are going to start with generative models. So generative models are nothing but those models that use an unsupervised learning approach. In a generative model, there are samples in the data, that is input variables x, but it lacks the output variable y. And we use the only input variables to train the generative model, and it recognizes patterns from the input variables to generate an output that is unknown and based on the training data only. In supervised learning, we are more aligned towards creating predictive models from the input variables. And this type of modeling is also known as discriminative modeling. And in a classification problem, the model has to discriminate as to which class the example belongs to. And on the other hand, unsupervised models are used to create or generate new examples in the input distribution. To define a generative model in layman terms, we can say generative models are able to generate new examples from the sample that are not only similar to the examples but are indistinguishable as well. And the most common example of a generative model is a naive Bayes classifier, which is more often used as a discriminative model. Other examples of generative models include Gaussian mixture model and a rather modern example, that is generative adversarial networks. So let us try to understand what exactly are GANs, or generative adversarial networks. Generative adversarial networks, or GANs, are a deep learning based generative model that is used for unsupervised learning. It is basically a system where two competing neural networks compete with each other to create or generate variations in the data. It was first described in a paper in 2014 by Ian Goodfellow, and a standardized and much stable model theory was proposed by Alec Radford in 2016, which is also known as DGCAN, also known as DCGAN, or we can call it as Deep Convolutional General Adversarial Networks. And most of the GANs today use Deep Convolutional General Adversarial Networks. The GANs architecture consists of two submodels known as the generator model and the discriminator model. So a generator network takes a sample and generates a sample of data. A discriminator network decides whether the data is generated or taken from the real sample using a binary classification problem with the help of a sigmoid function that gives the output in the form or the range 0 and 1. So let us go ahead and take a look at how GANs actually work. To understand how GANs work, let's break it down. So generative means that the model follows the unsupervised learning approach and is a generative model. When we talk about adversarial, the model is trained in an adversarial setting. And network simply means for the training of the model, we use the neural networks as artificial intelligence algorithms. In GANs, there is a generator network that takes a sample and generates a sample of data. And after this, the discriminator network decides whether the data is generated or taken from the real sample using a binary classification problem with the help of a sigmoid function that gives the output in the range 0 to 1. The generative model analyzes the distribution of the data in such a way that after the training phase, the probability of the discriminator making a mistake maximizes. And the discriminator, on the other hand, is based on a model that will estimate the probability that the sample is coming from the real data or not the generator. The whole process can be formalized in a mathematical formula. So G over here is generator, D is equal to discriminator, P data X is the distribution of real data, P data Z is the distributor of generator, X is the sample from the real data, and Z is the sample from generator, where DX is the discriminator network and GZ is a generator network. So let's take a look at the flowchart once again, guys. So we have the training data, which is going to give the real sample, and the generator network is going to generate the sample from the random noise or the examples. And then it will go to the discriminator network, where it's going to check if the sample that is coming is real or fake. So that is how a GAN actually works. Now let's take a look at the training phase, like how a generative adversarial network is actually trained. So it happens in two phases, guys. So the first phase is where we train the discriminator and we actually freeze the generator, which means that the training set for the generator is turned false and the network will only do the forward pass and there will not be any back propagation. Basically, the discriminator is trained with real data and checks if it can predict them correctly. And the same with the fake data to identify them as fake. After this, there's the second part where we train the generator and freeze the discriminator. So we get the result from the first phase and we use them to make better from the previous state to try and fool the discriminator better. So to understand this in the layman's term, I'm gonna tell you a few steps for training, like how you should start. So the first step is you have to define the problem. You have got to define the problem and collect the data. After this, the second step is you have to choose the architecture of GAN. So in this step, depending on your problem, you have to choose how your GAN should look like. The third step is training the discriminator on real data. So we train the discriminator with real data to predict them as real for n number of times, so we call it epochs as well. And then we generate the fake inputs from the generator. So in this step, we are going to generate the fake samples from the generator. And the next step is we train the discriminator on fake data. So whatever samples are generated from the generator network, you're going to train the discriminator to predict the generator data as fake. So that's how we know that discriminator is actually predicting the values as correctly. And the last step is we train the generator with the output of discriminator. So after getting the discriminator predictions, we train the generator to fool the discriminator. So that's how we train the GAN to actually get our solution from the problem, which is like defining the problem. So you'll understand this when I'm talking about the applications, guys. So no worry. Now let's go ahead and take a look at a few challenges of generative adversarial networks. So the concept of GANs is rather fascinating, but there are a lot of setbacks that can cause a lot of hindrance in its path. Some of the major challenges faced by GANs are, the first one is the stability. So there has to be a stability that is required between discriminator and the generator network. Otherwise, the whole network would just fall. For example, in case, let's say, if the discriminator is too powerful, the generator will fail to train altogether. Won't be able to push fake samples to the discriminator and it will always identify them as fake. And let's say if the network is too lenient, the discriminator network is too lenient, so any image that would be generated by the generator network would make the network useless. The next challenge that is faced by GANs is GANs fail miserably in determining the positioning of the objects in terms of how many times the object should occur at that location. Suppose we have an image in which we have, let's say, 3 dogs with 2 eyes, and sometimes a GAN will fail to determine the positioning of the objects in terms of it will generate an image with like 1 dog and 6 eyes. So that's kind of a problem that we face while working on GANs. And the next challenge is 3D perspective troubles GANs, as it is not able to understand the perspective also. So it will often give a flat image for a 3D object. So that's one challenge that we face with GANs as well. And GANs have a problem of understanding the global objects, and it cannot differentiate or understand a holistic structure. Like if you're talking about trees or if you're talking about flowers, that's a problem that GANs will follow. And last but not least, newer types of GANs are more advanced that I've talked about, that is deep convolutional generative adversarial networks, and are expected to overcome these shortcomings altogether. So we don't have to worry about these. These are the shortcomings that we face with normal GANs. the initial generative adversarial networks. Now that they have become more advanced, they actually overcome these shortcomings, so you don't have to worry, guys. So last but not the least, I want to talk about a few applications of generative adversarial networks. So the first one is prediction of next frame in a video. So let's say the prediction of future events in a video frame is made possible with the help of GANs, and DVD GAN, or we can call it as dual video discriminator GAN, can generate a 256 by 256 videos of notable fidelity up to 48 frames in length. And this can be used for various purposes, including surveillance, in which we can determine the activities in a frame that gets distorted due to other factors like rain, dust, smoke, etc. So the possibilities are immense with this. If you are able to predict the next frame in a video, that actually helps in a lot of things like surveillance, security, and we can predict outcomes based on these frames that we generate from a video. After this comes the text to image generation. So basically, object-driven attentive GAN, which is also known as object GAN, performs the text-to-image synthesis in 2 steps. So the first step is generating the semantic layout, and then generating the image by synthesizing the image by using a deconvolutional image generator is the final step. So this could be used intensively to generate images by understanding the captions, the layouts, and refine details by synthesizing the words. And there is another study about the story GANs that can synthesize the whole storyboards from mere paragraphs. So that's actually a very good idea if you're talking about GANs. So you can just give a few layouts and captions. Based on that, it will generate an image for us. Talking about the next application, we have image to image translation. So Pix2Pix is a model which is designed for general purpose image to image translation. So let's say we have 3 images. We have a real image, then we'll be having a generated image, which is basically a fake, and then it will be reconstructed to the previous image, which was real. So this is how image to image translation work, guys. And after this, we have enhancing the resolution of an image. So super resolution generative adversarial network, or also known as SR-GAN, is a GAN which can generate the super resolution images from low resolution images with finer details and better quality. So this is actually a very good application of GANs, guys. The applications can be immense. So you imagine a higher quality image with finer details generated from a low resolution image. The amount of help it would produce to identify details in low resolution images can be used for wider purposes, including surveillance. We can use it for documentation, security. We can use it for detecting patterns, etc. And last but not least, we have interactive image generation. So GANs can be used to generate interactive images as well. And Computer Science and Artificial Intelligence Library, also known as CSAIL, has developed a GAN that can generate 3D models with realistic lighting and reflections enabled by the shape and texture editing. And more recently, researchers have come up with a model that can synthesize a reenacted face animated by a person's movement while preserving the appearance of the face at the same time. There are a lot more applications we can work on.
So what is computer vision? Well, you see, computer vision basically deals with anything that humans can see and perceive. There are so many tasks that we humans do subconsciously that we hardly think are even worth mentioning. However, for a computer to learn, to perform, or even try mimicking such things is very difficult. To give you a better understanding of what I'm talking about, imagine looking outside a window. What do you see? You might be sitting in an office building and seeing a traffic outside, right? So do you ever wonder how you recognize something or someone? Do you know how you can look at someone and know who they are? Well, you see, subconsciously we are identifying objects in any image you see. Then we try to find what relation exists between the object to identify the scene or a place. Only then we get an idea of what is happening in an image. Sometimes we can also look at an incomplete image and use our knowledge and previous experience to determine what is missing from it. All of these are the task of computer vision. Speaking about different tasks of computer vision, we can perform various tasks like object detection, object classification, image captioning, and image reconstruction. I'm sure you might be wondering, what does this task do, right? So let's now discuss each of them in brief. Object detection is the ability to detect object or identify object in any given image correctly. Then we have image classification, which basically means to identify what class the object belongs to. Image captioning is nothing but looking at an image and describing what is happening in an image. Last but not least, we have image reconstruction. In image reconstruction, we basically have the ability to identify what is missing in an image in order to reconstruct it. Now that we have gone through object detection and gained knowledge of what we can do with it, let's now see how it works. There are two main approaches for object detection, that is machine learning approach and a deep learning approach. Both of these approaches are capable of learning and identifying the objects, but the execution of them is very different. Starting off with machine learning approach. Machine learning is the application of artificial intelligence for making computers learn from what the data is given to them. Here, they can make decisions on their own similar to that of human beings. It gives computers the ability to learn and make predictions based on the data and information that is fed to it through the real-world interaction and observation. Machine learning basically is the process of using algorithms to analyze data and then learn to make predictions and determine things based on the given data. Machine learning methods for object detection are SIFT, then we have support vector machine, and then we have YOLO-Jones object detection framework. Moving on to the next method, that is deep learning. Deep learning, which is also referred to as deep structured learning, is a class of machine learning algorithm. Deep learning uses multiple layer approach to extract high-level feature from the data that is provided to it. Deep learning model does not require any feature to be provided manually for classification. Instead, it tries to transform its data into an abstract representation. Deep learning is also influenced by artificial neural network present in our brain. Most of the deep learning method implement neural network to achieve the results. All the deep learning models require a huge amount of computational power and large volume of labeled data to learn from the features. Some of the deep learning methods for object detection are RCNN, faster RCNN, YOLO algorithm, and the faster RCNN. Moving on, let's speak about open source tool called as OpenCV. OpenCV is a huge open source library for computer vision, machine learning, and image processing. And now it plays a major role in real-time operation, which is very important in today's system. By using OpenCV, we can pre-process images, videos to identify objects, faces, or even handwriting of a human being. When it is integrated with various libraries such as NumPy, Python is capable of processing the OpenCV array structure for an analysis. As I mentioned earlier, we use OpenCV tool to pre-process our data. Let me now quickly jump to my code editor and show you how I can use this to manipulate our images. Alright, as you can see here, I'm using my Google Colab as a code editor. So let me quickly give a name over here as demo. And let me start off by writing our code. So first off, you might be wondering, how can I install my OpenCV, right? So it's pretty simple. In order to install your OpenCV, all you need to do is pip install OpenCV Python. Alright, and after this, all you need to do is shift enter. As I'm using Google Colab here, it comes pre-built in our system. But if you're trying to download this on your system, you can just type this on your command prompt. Now, let's import our OpenCV, import CV2. And also a matplotlib, import matplotlib as plot. And then let us also import our NumPy, right? Okay, let me quickly execute this. Fine. And let us now have an image over here. Let's give a variable image. And let's see how we can read our image using OpenCV, right? So cv2.readImage. And then we're supposed to pass a URL. All right. So let me now quickly upload our image over here. Okay, you can see I have a couple of images over here. Let me quickly select this image and upload it. Okay, let me copy the path for this and paste it over here. All right, so the reason I'm using dot over here is because we are in the same directory, right? So let me execute this part over here. Okay, and let's see the type of this image. You will see that this gives us a NumPy array, right? If you're trying to read an image using OpenCV2, the image is going to be in the form of BGR, wherein it stands for blue, green, and red. But we don't want that, okay? Before I move ahead, let me just show you what is the size and shape of this, okay? So image.shape, and let me hit enter. You will see over here we have the width and we have the height, and this is the number of channels. And the reason why we have number of channels is because it's a colored image, right? So it's going to be R, G, and B. As we are using OpenCV2 to reconstruct our image, we have to convert this back. Okay, so let me quickly show you how our image looks like. So in order to read our image, I'll use plt.imShow image. Okay, so this is our image. Now you might be wondering, like, doesn't OpenCV have its own built-in method to plot an image? But yes, OpenCV has a built-in method to plot an image or to display an image. But unfortunately, it is not supported by either Google Colab or Jupyter Notebook. Okay, and as I mentioned earlier that OpenCV reads the image in BGR format, you can see the color has been inverted over here. So let me quickly run this again. So in order to change our color, right? So let me give it as image, or let me give it as new image, right? So it's going to be new image is equal to cv2 dot cvt color. Okay, and this method takes an image over here, and then we're supposed to pass which format we want to convert this to. So it's going to be cv2 dot color. Okay, and now we have to convert this from BGR to RGB. So you can see over here. So let me quickly execute this, and before that, let me plot this image, right? So plt dot imShow new image. Okay, then if we are getting an error here, let's see why we are getting this error, right? So before that, let me execute this here. Okay, we are getting this error because it's saying demo scaling, right? So let's see where we are going wrong. Okay, you can see that we are getting an error over here, right? And the reason why we are getting an error is because we have not placed our comma over here. And it's going to be BGR. Okay, so it's going to be blue, green, red to RGB. And let me quickly execute this over here. Okay, let me rerun the image from start. Okay, and let us now see how this image would look like. So plt dot imShow. Okay, and then we're going to put our new image over here. Fine, and let's see how it looks like now. So as you can see here, right, there's a huge amount of difference. Okay, so here we have a blue color bus and a red bus in the behind, and you can see there's a lot of difference over here. It's a yellow bus and a blue bus in the back. So the reason why we were getting this is because, you know, this is actually the original image. Okay, and this is what it looks like every time we pick it up from the CV2. All right, so let us now see some more pre-processing or the basic operations that we can do. So to start off, let's see how we can split our images. And when I say split our image, we're going to split all the different channels. So if you can see over here, we have the shape over here as we have X, Y, and then we also have 3, right? So after splitting, it's going to be 1. Okay, so let us now see how we can do that. So all right, we obviously have 3 channels, right? So R, G, and B, which stand for red, green, and blue. And then all we need to do is cv2.split and new image. All right, so let us now quickly execute this. But before that, let's print the shape. Okay, so print. So we are going to have shape of R, which is nothing but R over here. And similarly, we'll do it for G and B, right? So let me copy this and change the values. So this is going to be green and blue, green and blue. So let me quickly execute this now. Okay, we are getting the entire array here. So what we'll do is r.shape, and same thing we'll do over here as b.shape, and even for G, it is going to be g.shape. And let me execute this. So you'll see here, right, we don't have any more channels. But if I want to print this new image, it's going to be 720, 2 or 1280, 3. All right, so this is all about splitting our image. Now what to do if you want to merge our image, right? So it's pretty simple. We have cv2.merge for that. So let's give the same name, new image. This is going to be cv2.merge, and we're going to pass our channels. And this will be in the form of a tuple. So it's going to be R, G, and B. All right, so this is how we can merge our image. Let's see how we can resize the image, right? So let's see another operation wherein we are going to resize the image. Okay, first off, we need a scale, right? Scale is nothing but by what amount we want to resize, right? So let's give scale is equal to 10. All right. And then we also need the width. So W, which would stand for width, and this would be an integer value. Okay. And then we'll have image, or it would be new image, right? So new image dot shape. And then as we all know, this shape gives us a tuple. So we are going to pass the value, right? So this is going to be the shape present at 1. Okay. And then we'll scale this down by our scaling factor, that is S, and then divide it by 100. And same way we are going to do it for the height. So only thing that's going to change over here is H, and then we'll change this by 0, and rest everything remains the same. So now what we'll do is we'll create a tuple here. So we'll give this as dimension, dim, and this will be having width and height. And now in order to reshape, what we'll do is first we'll have a variable here, resize, and this would be nothing but cv2 dot resize, and then we are going to pass the original image and then the dimension of the new image. All right, and then we are going to pass our interpolation, which is nothing but an argument over here, and then we'll have cv2 dot init area, cv2 dot fine. So let us now execute this, and but before that, let's print the size, right? So resize dot shape. Okay, and let's execute this. So as you can see here, we have reduced our image size, but the number of channels has not changed. But the value, which was something like 720 and 1080, has been reduced to 72 and 182, right? All right, so let us now see another operation that we can perform here. Okay, so let's see one more operation, that is nothing but rotate operation. Okay, so similarly, we obviously need to have the height and width. So it's going to be height and then width. Okay, and now we'll have new image, and then we'll take shape, and we all know it gives us a tuple, right? So we'll have all the values from 0 to 1. Okay, and now we'll have to calculate the center. So we'll just give a variable rather than center, let's give it as C, and then we'll have tuple value W by 2, and then we'll also have height by 2, because that's how we calculate the center, right? And now let's say we want to rotate this by angle 90 degrees. Okay, so now what we'll do is we'll declare a variable, let's say M, and then we'll have cv2 dot get rotation matrix. Okay, and now we are going to pass center value, oh that's C over here, and then we'll have an angle, and at the same time we'll also have the scaling factor, that is we don't want to reshape our image, right? We don't want to reduce the image size, so we'll give 1 over here. And now we have to rotate, right? So rotate 90 degrees, and this would be equal to cv2 dot wrap. All right, and now we are going to pass our image, that is the new image, and then we'll have M over here, that is nothing but the object over here which is returning, and then obviously height and the width. Okay, so this is going to be the tuple value. Okay, and let's now see how this would look like. Okay, so over here we are having an error, C is not defined. So let us quickly do that. Okay, rather than C, it's going to be 2 over here, because we are going to find our height, and let me execute this now. Okay, so it has been successfully executed, and now in order to see our image, right, we have rotated this by 90 degrees counterclockwise. So let's now just print this and see how it looks like. So plt.imshow, fine. So as you can see here, we have rotated our image counterclockwise by 90 degrees. So moving ahead, let us now see how convolution neural network work. Okay, so what is convolution neural network? CNN, or a convolution neural network, is a class of deep learning neural network. What I'm trying to say here is, think of CNN as a machine learning algorithm that can take in an input image, assign importance to an object, and then to be able to differentiate between one object and the other. CNN works by extracting features from the images. Any CNN consists of following 3 things: an input layer, which is a grayscale image. Then we have the output layer, which is the binary or multi-class labels. And then we have hidden layers, which contains convolution layer, ReLU, and then we also have pooling layers. Finally, we'll be having artificial neural network in order to perform the classification. It is very important to understand artificial neural network or ANN in order to perform multi-class classification. Let me quickly move to the canvas and show you how CNN architecture is. Alright, so as I've mentioned earlier, when we are dealing with CNN, right, we'll have three things. That is nothing but the input image. So consider that we have an input image over here. And this is a grayscale image, so the number of channel over here is going to be 1. Let's take image size to be 10, and then we also have image size over here as 10. Okay, in reality we won't have image size to be 10. All right, so this is just for just so that we can understand. And now what we'll do is we'll perform convolution by passing a convolution filter, which would be of a size 3 and 3. This convolution filter will go through each and every part of this image and extract all the important features. So for example, this convolution layer, right? So let's give it this name over here as convolution layer. Okay, now this convolution layer, we can have multiple of them. Okay, we can have like suppose 35 convolution layer, and each of these 35 convolution layer are responsible for extracting a very specific features. Okay, so now for example, let's think that we have 35 layers over here. And now this will undergo convolution, right? So this is convolution. We'll get a new image over here. And the new image would look something like, and we'll get a new image over here. And the new image would look something like, this is the actual image, right? Initially it was having single channel. After undergoing convolution, it will have 35 layers or dimensions, I should say. So this would be 35. And the size over here will be reduced from 10 to 8. So if you didn't understand this, right, let me quickly make you understand what's happening over here. So what's going to happen over here is this filters over here, right, this 3x3 filters, they will go on each and every part of this image. Okay, so now let's take image as a matrix, right? So let's take obviously this 10x10. Just for the illustration, I'm going to draw 5x5. So this 3x3 matrix will fit over here. Okay. Then there will be a stride. Stride is nothing but how this matrix moves, and then there will be a second stride. So it will go through every 3x3 matrix, and then it will go throughout the image. All right, and then we'll have an image over here which will reduce to 8x8, but then we'll have more number of features. That is nothing but 32 features or 35 features over here. Now, as you can see here, right, we have huge amount of dimensions. So this would lead to cursive dimensionality. In order to overcome this, what we'll do is we'll pass this through a max pool layer. And here we are not trying to reduce or perform any kind of action over here. All this max pool layer will do, this is usually 2x2, right? Okay, this is 2x2 matrix. So what this max pool layer will do, it will go through each and every layer of this image over here. So like let's think that this is the max pool layer, right? And this will sit over here at this 4 pixels. And like for example, let's say this has 6, 7, 9, and let's say 11, right? So these are nothing but the probability values. Okay, and it will choose the maximum value from this part. So it's going to be something like, it's going to create a pixel, and this would be 11. Now you might be wondering, right, like why is it giving 11 value? Well, you see, as I mentioned, these are the probability values, right? As 11 is the highest value, it indicates that 11 is a place where we have highest probability of that particular feature. Similarly, this will go through each and every box. All right, and now the size of an image will reduce. Okay, so let me quickly show you by what. So now we are going to pass the max pool layer. After this, the size of the image will be reduced by half. That's going to be 4x4, but number of filters will not change. All right, now we can pass this through another convolution layer. I mean to say all of these steps can be repeated again, but once we are done with that, right, we'll flatten this entire layer, and this is going to be a simple artificial neural network. And every time what happens over here is we are going to pass this through a multiple layers, or I can say as deep layers. Okay, and then we can perform our classification here. And another important thing that I forgot to mention over here is in order to increase the linearity, right, we're going to also have an activation function over here. Usually I would be using ReLU. I hope you know what is ReLU, right? So what activation function does is after reaching a certain threshold, it'll activate that part. So what ReLU does is, this is how the graph for ReLU does, and here it ranges from 0 and 1. And now in order to perform the classification, in our last output layer, right, I would be passing an activation function called as softmax. Because softmax gives me the probability which would range from -1 to +1. All right, so this is all about convolution neural network. Using deep learning, we can detect objects either by using RCNN model, which stands for region-based convolution network, or by using YOLO method. So moving ahead, I'll be talking about YOLO algorithm. Now you might be wondering, why do we have two different families for object detection, right? Well, you see, there's a lot of difference between YOLO family and RCNN based approach. In the RCNN based approach, it focuses mostly on division of an image into parts and then assign probability values to those parts. And whichever part has the highest probability, it's where we consider an object to be present. Whereas the YOLO framework focuses on the entire image as a whole and predicts the bounding boxes, and then calculate the class probability to label the boxes. The family of YOLO framework is very fast as compared to RCNN. YOLO algorithm has evolved over the years. It first started with YOLO V1. This model is also called as YOLO Unified. And the reason behind this is that it unifies object detection and classification model together as a single detection network. This was first attempt to create network that can detect real-time objects very fast. YOLO only predicts limited amount of bounding boxes to achieve the goal. The YOLO algorithm has improved over the years. Now we have YOLO V2 and the latest version of YOLO is YOLO V3. You see, the YOLO V1 framework makes several localization error, and YOLO V2 improves this by focusing on recall and localization. The YOLO V2 uses batch normalization, anchor boxes, high resolution classifiers, fine gradient features, and multi-level classification. And also it uses something called as darknet. All these features made YOLO V2 better than V1. Speaking about darknet, darknet is actually a pre-trained model. And here YOLO V2 was using darknet 19, which means it contained 19 convolution layer, 5 max pool layer, and a softmax layer for object classification. The latest model of YOLO is YOLO V3. This model is the fastest and most accurate object detection model. It accurately classifies the object by using logistic classification compared to softmax, which was used in YOLO V2. This makes us capable of making multi-label classification. YOLO V3, which also uses darknet 55 as a feature extractor. You see over here, YOLO V3 makes use of darknet 53, which means that there are 53 convolution layer. As a result of this, it can make more accurate predictions of an object. Now that we know what is object detection and what is YOLO algorithm and how to work with OpenCV, let me quickly move to my code editor and show you an application to detect objects in an image as well as in a video. Alright, let me quickly jump to my code editor. So as you can see here, I'm in my code editor, and as I've mentioned earlier that I would be using Google Colab. Okay, so first off, let me import all the important libraries here. So I have imported my CV2, NumPy, Matplotlib, and so on. Okay, so let me execute this. So let me quickly move to the another tab and show you the official website of our YOLO algorithm. YOLO algorithm webpage. Okay, and this is the official website for our YOLO algorithm. And as you can see here, we have multiple versions. We have different versions over here, and then we have YOLO V3, and then we have various versions, right? So in order to use this YOLO algorithm, we need to download this weights folder and also the configuration file. The configuration file is basically a GitHub repository. So let me quickly show you that. As I've already installed this, I won't be reinstalling this on my system, but it's pretty similar. All you need to do is click on weights and it'll automatically download this on your folder. And as you can see, I've already installed this weights folder as well as a configuration file. All right, so let me upload these files from my folder. Okay, so as you can see here, we have the Coco names. Coco names is nothing but the classes that have been pre-trained, right? So we'll have a Coco names, then we'll have the configuration file as well as the weights. And let me quickly open this. One thing that I would like to mention over here is that we have a couple of flavors of YOLO V3. One over here we have 360, 416, 608, Tiny, and SPP. Tiny is the one whose file size is pretty small. As I'm using Google Colab over here, I'll be using Tiny because I'm supposed to upload this file to this environment over here. So the first thing that we're going to do is get these files loaded over here. So let's give the name of variable over here as net. Okay, let's give it as network, or we can give it here as YOLO. Okay, and this would be CV2 dot DNN, which stands for deep neural network dot read network. All right, and now here we're going to pass an argument over here. We are going to pass our weights as well as a configuration. All right, so let me quickly copy the path for this and paste it over here like this. Similarly, we're going to copy the configuration file path, and let me minimize this over here and let me paste it over here. All right, so let's wait for 2-3 minutes because this is still uploading over here. So let's wait for like 2-3 minutes, and once that's done, we can execute our code over here. All right, so now that we have uploaded our weights folder, let me quickly execute this. And now what we'll do is, let us now import the classes. As I mentioned earlier, our Coco contains the list of names, right? It has the list of names that our YOLO algorithm is capable of detecting. And as is a pre-trained model, there are a couple of things. We can detect cats, we can detect dogs, horse, sheep, cow, elephant, bear, and many more. Let me now quickly import that and put them in the form of a list. So I've already imported matplotlib over here. So let's create a class, CLA, and this would be an empty list. All right, and now what we'll do is, as it's a file, we'll use this file handling with open, and we'll give the name of this place, that is a path. So let's copy the path over here. And then we'll also define the type of operation that we are doing. We're going to do read operation as F, right? And now what we'll do is classes. So this would be nothing but f.read. And now we'll have, as this will give the entire page, right? We want to split it in lines, right? So we'll have split lines. All right, so let me quickly execute this over here. Okay, so now let us see what is there for us in our classes. So let me have len, and then let me give a classes. So it should approximately show around 80. And if you want to see what these classes contain, they'll contain the name of the different objects that we can identify. All right, so let me change this back to the length and execute this. So now that we have our classes and we have loaded our model over here, so what we'll do is let's load our image. So let's take the same old image. Let's take this bus image over here. And in order to load our image, all I'm going to do is cv2.imread and pass the path over here. So I'll copy the path and just paste it over here. And let me change this back to the directory. All right. And we all know that this would read in BGR format, and we have to convert this to RGB format, right? So let's quickly get that done. Okay, so we'll give here as new image, or let it be like blob, okay, blob, and this would be nothing but cv2 dot deep neural network dot blob from image. All right, so blob from image. And now what we're going to do is we'll pass our image over here, and then we'll pass. So obviously these values over here would be in the form of integer, right? And we have to convert that back to float. So we'll do the regularization by dividing all the pixels by 255. This will ensure that values are ranging from 0 and 1. All right. And now we obviously have to define the shape. If the image is pretty huge, right? So consider that we have this image over here. So if this image over here is like, say, 1000 cross 1000, right? So, and over here again, it's going to be 1000 cross 1000. Now we have to rescale this image, okay? Because an algorithm cannot read this huge image and it will take huge amount of computation power. Okay, so what we're going to do is we'll resize this image both on the x-axis and y-axis size to 320. Okay, so basically we're trying to reshape this. So let me quickly mention this over here. Okay, so this is where we can add our reshape image. So it's going to be 320 cross 320. All right, and then we'll have to pass the images 0, 0, 0. And then an argument over here which would say swap is equal to true. And the reason why we are using the swap RB, the reason is because we all know this is going to read in BGR, right? And we obviously have to interchange RG and B. So we'll have true over here. And then finally, we'll be passing crop. We don't want our image to be cropped, so it's going to be false. All right. So let me quickly print this over here. Let me execute this line. Okay, we are having an invalid syntax, and the reason for this is because I have passed a full stop rather than a comma. And let me execute this once again. And you can see here that we have successfully run our image. So let me quickly run this and let's see the shape and size of this. So blob.shape. This is still a numpy array, so it's going to be shape. Okay, so we are not getting the shape over here, right? So blob, so it's going to be blob. So I've put here blob. So blob dot shape. So as you can see here, the weights have been changed. If you want to print this on your matplotlib, all you need to do is you need to reshape this, and it's going to be 3 channels over here. Okay, so let me quickly show you that as well. So this is an optional part to do. So to print image. So what we're going to do is we'll give an image over here, or let's give I. Okay, and what this I will contain is image blob, sorry, and this would be 0 dot reshape 320 comma 320 comma 1. All right, and now we'll just plot it I. And if we try to plot the blob directly, it's not going to plot. The reason is because it's not in the correct format. So let me quickly execute this now. So if you can see here, we have our images, right? This has been divided into 3 channels, that is R, G, and B channels. And that's the reason why we are getting 3 images over here. So now we have this blob, right? Now we are supposed to set this blob as an input image. And in order to do that, what we'll do is YOLO. Okay, this is the model or module that we have imported from outside. So we'll set the image, that is set input, and then we'll pass blob. And let me execute this. All right. And now we also have to define our output layer. So output layer names, and this would be dot get. All right. And we'll have unconnected output layer names. Okay. And now what we'll do is we're going to pass this for our output, right? So layer output, and this is going to be YOLO dot forward, and we are going to pass just the output layer names. All right, so let me copy this over here and paste it here. So all that is left over here is we need to read the image, we need to find where the bounding boxes are, and then we need to put the bounding boxes on our image. Okay, so in order to capture our bounding boxes, there can be multiple number of boxes in our image, right? So we'll create a list. So box, and we'll give here as array. So this will be boxes, and then we'll have confidence, in the sense by what confidence is the value being predicted, and this would be an array yet. And then we'll have class IDs, and the class ID over here refers to what we have imported, right? So in order to get this, we'll be using class IDs. So we'll run through an image for output in layers. That's going to be this one, layer output. And then we'll have for detection in output. Okay, and now we'll first capture the score, and this would be nothing but detection. So this would be like score, right? Score is nothing but an array. So what this output will give is for every object that has detected, right? It will give an output over here from 0 to 18. And then the first 4 box, right? This is responsible for the position of our boxes. So here it gives X, Y, center, and other parameters. And rest of it, it gives me whatever the parameters we have, right? Like we have 80 parameters. It gives a confidence or probability of that particular character being in that box. Okay, so we'll calculate the score over here. So excluding the first 4 boxes, we'll have 5 over here. And then we'll also capture the class IDs. So class ID, that is np.rmax score. Okay, and let us also get our confidence over here. Confidence, this is nothing but score, and then we'll pass the class IDs over here. Okay, so if you want me to explain this, what is happening over here, see, we are getting this list, right? So by detection, we are going to get a list. Okay, and what the score ID is doing is we are going to get the place or the placeholder in that array where there is a maximum probability of that image. And what this class ID will do is it will just get the whatever the values there or the percentage of that probability. Okay, so now moving ahead, we'll have, in order to prevent multiple bounding boxes, we'll have confidence. All we're trying to do over here is we're going to set a threshold if the confidence is greater than 0.7. Okay, And then what we'll do is then we'll extract all our features. So we'll have center X. This would be nothing but we obviously need an integer value over here. Detection, as I mentioned, is detection, right? The first 4 boxes is responsible for giving us the X, Y, height and width. So it's going to be 0 times width. All right. And now similarly, we are going to do it for X, height and width. Okay. So let me copy this again and paste it here. This is for the height and then for the width. So let me just change the name to width and then we'll have height. All right. And then we also need to mark height over here. And similarly, we're going to do it over here. And now finally, to find the center value of X, we'll have X, which is nothing but int center X minus W by 2. All right. And similarly, we'll do it for Y is equal to int center Y. We're using this, right? The X and Y values in order to find the corners, right? So we'll similarly find it for Y, which is nothing but height by 2. All right. And now finally, all we need to do is we need to append these values to these boxes over here. So what we'll do is boxes, that is nothing but these layer. So it will be BOX, should be ES. That shouldn't be an issue. Dot append. We'll pass a tuple value here of X, Y, width and height. Similarly, we are going to pass the confidence values. That is nothing but this tuple confidence. So we'll append the values to the list, dot append. And then all we're going to do is float confidence value. So which is present over here. Okay, and finally we need to have class IDs, right? So let me get this as well. And then all we are going to do is append and then class ID. All right, so now that we are done with this, let me quickly execute this block of code over here. And let's see if we get any error or not. All right, so as you can see here, we have successfully executed our code. Now what we'll do is we'll see how many number of bounding boxes up there. And to do that, what we'll do is we'll find the list, or we'll just print the amount of elements that are present in the list. Okay, so what we'll do is length of boxes. Okay, and this should give us, okay, 2. That means whatever image we are passing, it is able to detect only 2 objects over there. All right. And now what we'll do is we have to obviously add these bounding boxes to our image, right? So we'll do indices, and this will be CV2 dot deep neural network dot NMS boxes. All right. And now what we'll do is we'll pass the boxes, that is nothing but the values over here. And then we'll pass the confidence. All right. And then we'll also pass 0.5 and then 0.4. All right. So let me quickly execute this. All right. So we are getting an error. That's because I have to put a comma over here, and let me execute this now. All right. So now what we'll do is we'll obviously have to add this. So we have to add the font and confidence to our image, right? So we'll give font. So let me give here. So this is nothing but CV2 dot font underscore. You can choose any one over here. I'm going to use Hashly plain, right? So we have over here, and then we'll pass colors to our font. That is nothing but COLORS. This is nothing but np dot random. Okay, we don't want the same color, right? We want to pass random colors for each of our bounding boxes. So we'll give the range 255, and then size. This would be equal to the length of the bounding boxes. So size, this would be length. And then we'll also pass 3 over here. All right, perfect. So now all that is left is to add the images. So, okay, so let's see what is the issue over here. All right, so the reason why we are getting this is because I have forgot to mention uniform over here. So let me quickly mention that, dot uniform. And let me execute this now. Perfect. Now what we'll do is we'll take each and every object over there and we'll add bounding boxes to this. And in order to do that, we'll use a for loop for I in indexes dot flatten. All right. And now we have to take our XY coordinates. So X comma Y comma width and height. This would be nothing but boxes. And then this is for that particular image, right? And now let's have a label. So here we are basically trying to add label. So this is going to be str classes. I hope you know from where we are getting these classes. We are getting these classes from here. We imported this Coco names, right? So we are importing the classes from there. All right. And then all we are going to do is pass class ID. And then we'll have a list. Fine. And similarly, we are going to do it for confidence. So we'll convert this to string. And then we obviously don't want it to be floating point number. So we'll round it off and confidence. And then let's have it by 2 decimal places over here. And now for the color. Yep. So what is happening over here is we are just trying to extract each and every information from the list that we have created above. And now all we'll do is we'll add rectangular bounding boxes. To do that, we have cv2.rectangle. And then we'll have to define the image, the coordinates, that is x comma y. And then we obviously have to define the edges, right? So it's going to be x plus width. Then we need y plus width. And the color. And then we'll have 1. The 1 over here refers to what is the size of the rectangular box you want. And now similar way, let's add the text. So cv2.put text. Obviously we want them in the image. All right. And now we have to pass all of these parameters. So it's going to be label, and then we'll give some space and then give some confidence value, right? And then we'll also pass a couple of parameters like where we want it. We want it in the top left corner. So it's going to be x and then y plus 20. And then we'll have font. This selects which kind of font you want, font size, and the background. So we'll keep a white background over here. Okay, so this is not the background, this is what color of text you want. So it's going to be 255, 255, 255. So it's white color, and then the size of a bounding box. So let me quickly execute this and see what happens, whether we get any error or not. All right, so as you can see, we have no errors which are present over here. So what we'll do is we'll try saving this model, or we can also see it over here. So in order to see this, all we need to do is plt.imshow and pass the image name. And then we can see the image. All right, so what's happening over here is it's trying to read the original image, right? So let me now quickly show you if we have any bounding boxes in our image. So as you can see here, right, there's a thin box which says person with a 99% probability, but we are unable to see it. So what we'll do is I'll just increase the size of this over here. And let me rerun this from the beginning. All right, so let's see what happens. Okay, so as you can see here, it's detecting this person with 89% probability, right? So let's do one thing. Let's take one more image and see what happens. So let's take this image over here and let me quickly upload this. Okay, so let's copy the file path. All right, so let me quickly just change this value over here and give it this as a root directory. So all I have to do is dot, and let me execute this from the start, right? So let me execute this. So as we can see here, we have a couple of images which bounding boxes. So in order to look at these bounding boxes clearly, let me save this image so that we can zoom in, right? So in order to save the image, all we need to do is cv2.imwrite. All right, give the path where you want to save this. So let's give image.jpg, and then which image you want to save, right? So it's going to be img over here, and let me quickly execute this. All right, so if you're getting true over here, this means that we have our image over here, and let me quickly run this up for us. So as you can see here, this is detecting a person, and as there are too many number of people over here, so it's going to detect a lot of people, right? So that's why it has given a single bounding box, and it has detected a person over here. All right, as I mentioned earlier, using OpenCV, we can take 3 types of inputs, right? One is a webcam feed, another one is the images, another one is a video. Although the procedure remains the same, only thing that you're going to do is you're going to change how you take the input and put all of this in the form of a for loop.
What is object detection? The object detection is actually a task that we do, and it's a computer technology related to computer vision and image processing, which deals with detecting the instances of semantic objects of a certain class, such as humans, buildings, cars, in a digital images or videos. I know this sounds purely technical, but let me make it simpler for you. Object detection means, suppose if I have an object, okay, suppose if I have a digital image, I'll open up an example image for you to make it easier for your intuition. Let me get an image. Let's say I'm having this image or this image with me, okay? When I'm talking about object detection, I want to identify what is in this image, and I also have to identify where exactly is that object in my image. So when I'm talking about object detection, I'll be talking in terms of two things. So I'll be saying two things. I'll be saying what is present in this image. I'll also be saying where exactly is the position in this image. Now, in this example photograph, I can say that, okay, what is in this image? I can say there is a person's face is present in this image. And along with saying as what is present in this given image, when I'm doing the object detection, I'll also be saying where exactly is that person's face. So two things will happen over here. One is detection of what, and the another is detection of where. And both of these things constitutes the object detection. And that's what would happen, or that's what we expect from any object detection model. We not only have to identify what is present, but also we want to detect where exactly is that object is present. I'll give you a simple example, guys, which is relevant for today's scenario. Let's say if I have some like digital image with me, okay, I'm having some big digital image, or if I have the similar image with me, I'm getting the video feed and I want to detect whether that person is wearing a mask or not. The reason, because as you know, with the current pandemic, everyone is expected to wear the mask and follow the social distancing so that everyone will be safe, not only the person but also the person around them. So I want to build an application where I want to detect whether a person is wearing a mask or not. So the task that I want to check is whether that person is wearing a mask or not. Okay, now if I want to check whether this given person or whether the given video feed or given image, whether this person is wearing a mask or not, as a first step, I have to identify whether this given image has a face in it. So I have to first detect whether this given image has a face in it. And if there is a face, I have to detect where exactly is the face in this given image. And once I find these two, whether I'm having a face or where exactly is that face, then I can check whether this person is wearing a mask or not. I hope you can understand the importance of object detection that I'm talking about. So if I want to do any task by looking into the digital images, be it images or be it video feed, I want to identify what is present in that given object, or what is exactly present over there in a given digital image or the video. And along with that, I want to identify where exactly is present. And that's the expectation, or that's the output that we would get when we perform the object detection. Okay, I hope this gave you some clarity about object detection and what exactly we are trying to achieve when we talk about object detection. Now with this intuition, if you look at the technical terms that is present over in the slides, so you can understand that object detection is a computer technology which is related to computer vision. Now don't get intimidated by the new terms called computer vision, guys. So this computer vision is actually an ability that we give to the computer to be able to see the outside world. Now, just like we humans see the outside world with our eyes, we'll enable the computers to see the outside world. How can I enable the computers to see the outside world? Exactly, I can I can enable the computer to see the outside world with the help of camera. So object detection is a computer technology related to computer vision, where I'm enabling my system to see the outside world. And once it captures the outside data, it could be either video or it could be images. So I'll process this individual video or image data, and then I'm going to detect that specific instance or that specific image, whether it has objects of certain class. Okay. So this object can be something as whether my given image has humans in it, or whether my given image has buildings in it, or whether my given image has cars in it. So all these things we will be detecting. Now in this example, this is the image that I have given as an input, and I'm detecting what exact like what are the objects that I'm present in this image. So in this example, I'm having a retriever dog, American Staffordshire dog, and there is one more dog. I think I'm unable to see its complete name. So there is another word called another variant of the dog, and this is one more so this is one more breed of dog. So along with saying what exactly is present in the image, I'm drawing the bounding box around it, which says where exactly is that specific object is present. And if you look at the image which I'm having on my left hand side, I'm doing the same thing. I'll just uh, start the slide share again so that you can visualize it. See, I'm identifying what exactly is present on top of my table. So I'm checking like I can see there is a soda can, I can say there is a hat, I can see there is a cup, so coffee mug and everything. I can see everything. Now along with saying as what is present in these images, I'm also drawing a bounding box around it to say where exactly is that object is present. And that's the technology, or that's what we are trying to achieve when we perform the object detection. We are determining what and also where. These are the two things that we'll be doing over here in case of object detection. Now where do we see this application, this application of object detection? One common application, or one application can be is face recognition. So I hope like everyone has experienced this. So if you upload any photograph into your Facebook, so it not only identifies who is present in that image, it also identifies like where is that person's face is present. So it will draw a bounding box around that person, and it is going to ask us whether you want to tag that specific person in your image or not. So that's an application of that's an application of object detection. I'm deciding what is present in the image. I'm also saying where exactly is that object. And with the current pandemic, as we know that we want to follow the social distancing, so we can have the applications where we can identify in a large crowd, so how many number of people are present in this entire crowd, and we can also take a step ahead and measure whether they are following the social distancing or not. So those are some of the examples for object detection. And yeah, another thing can be is like for a given image data or for a given video feed, so what are the various objects that are present over there. Now just for a quick fun activity, you can, like, there's a video that I've come across in YouTube, guys, so which actually talks about how entire world is actually embracing towards this object detection. So there is a video I want to share, how China tracks everyone. So this is one of the video. Just make sure that you watch it and you watch in your free time, and to understand how much close we are going ahead, and where exactly we are going ahead in terms of using various object detection tools. So just to give you an intuition, so in that video they have actually explained uh, how China is actually using their various webcam feed and the various surveillance feed, and they are trying to like they have taken the computer vision to such an extent that they are monitoring each and every individual in each and every place. So to do all those things, they are actually making use of deep learning models, and they are actually perform the object detection over there. You once you watch that entire video, you'll understand the powerful things that we can do with object detection, guys. And another example can be is we can use this computer vision technique to check the industrial quality checking. So whenever something is getting manufactured, so instead of manually validating everything, we can just capture the images and we can have the deep learning model to run through it to identify how exactly like how exactly is it working, or whether is it good, whether the quality of the product that I'm producing, is it a good one or not. And in the recent years, we are seeing another application of computer vision, that is building the self-driving cars. Now, in case of self-driving cars, it's a artificial intelligence system which actually observes the outside images. So to observe the outside image, it will actually have cameras around it. So it will have the cameras on top, fixed on top of it, which will be a powerful camera, and which captures the 360-degree video data which are present on the outside. And we will have a deep learning system inside it. it the deep learning system, or this deep learning model, gets the video feed from this outside camera. It does the pre-processing, and once it does the pre-processing, it identifies, okay, if I have a red signal over there in front of me, so it is able to identify, okay, I'm having a red signal, I have to stop. So that is the prediction that my deep learning model is going to give. And with that prediction, this uh, self-driving car or this system is going to apply the brake so that it stops. So that's one of the application of using the computer vision, guys. Now, even in this scenario, we'll be performing the task of object detection, because I'll be capturing the outside world, and I'll be seeing what is present in that given image and what is the information that it is trying to tell me. Now, with that analysis, I'll be taking the action. And another example is security. So like we can use this computer vision application to identify whether the person is following the security protocol or not, or whether this person is a valid person or not. So all these things can be the, or are the applications of computer vision and the object detection, guys. Now, when I'm talking about computer vision, it's the whole topic, guys. Like inside the computer vision, we have various tasks. So object detection, image classification, and many things. So under that computer vision, we have the subtask of object detection. So don't get me confused when I'm using both the words uh, like interchangeably. So both would mean the same thing. So I'm using the computer system to capture the outside world data and give the analysis to me. Now, let's look at the workflow of object detection. So if I want to perform any object detection, so we actually are going to follow some key steps. So some key steps can be is, if I want to perform any object detection, I'll need to have a data. So I need to have a data. I'll use some data with me which is already present. Suppose if I'm trying to classify, or suppose if I'm trying to identify whether my given image has a cat in it, and if it is a cat, I want to draw a bounding box to represent where exactly is the cat. So what we do in such scenarios is, as a step one, we are going to get the data. So the step one is get the data. So when I say get the data, I'll collect the data from the outside world. I can collect the data. There are various sources, guys. I can use my existing business data, or I can collect the data from open source. So if the open source is not available, I can employ some Amazon mechanical Turks. I can use this service, and I can have real people to get the data for me, and or I can make use of Amazon image labeling service that they have, and I can just AWS. So when I say Amazon, it's actually AWS, guys. Okay, AWS image labeling technique services that they have, and I can use all these services, and I can get the data. Now, when I'm talking about getting the data, what exactly is the type of data are we looking for? Now, suppose the task for me is to, for a given image, let's say this is a given image, this is an image which contains tree. Now let's say for this given image, I want to identify what is present in the image, and I also have to identify where it is present in the image. So if I want to identify both, that is what and where, then my training data, so if I want to detect what is present in the image and where exactly is present in the image, then my training data should basically have these two things. So if I'm building an image classifier or a classifier which can actually detect whether my given image has an image of cat or not, and if the cat is present, where exactly is that cat, then my training data will have the image. Now along with this image, I want to have what is present in the given image. So an example can be as cat, and I also have to have the bounding box coordinates which says as where exactly is that cat is present. An example can be something as I can have x comma y comma h comma w, which is nothing but, suppose if I draw a bounding box, I'll choose a different color. So x comma y represents the, let's assume this is the x comma y it represents, and I should have width and I should have height. So my training data, that means the data that I'll be using, it should have the image of that cat or image of the object, and it should say what is present in that image, and it should also specify the bounding box coordinates. Okay, so these are the things that I need to have in my data. Now, once I have the data, let's say I'm building some classifier which detects whether cat is present. Similarly, I'll be building a classifier whether a dog is present. So likewise, let's say I'm building a simple object detection classifier which says whether my given input image has a cat or a dog. And if any of this is present, it's also going to give me bounding box. Then I'll be having a set of data which contains images of cat and images of dog, and each and every individual image will have the label which says what is present in that given image, and it also says where exactly is present in my given image. Now I'll be using all this data. Using all this data, I'll be making use of my deep learning neural network. Okay, I'll make use of my deep learning neural network. And using this deep learning neural network, I'm going to train this model such that it learns it learns to identify what is present in the image, and it also learns to identify where exactly the object is present if it identifies what. So that will be the common flow, guys. So we'll have the data and we'll pass this data to the deep learning neural network. We perform the training, and once we perform the training, we'll make sure that the deep learning model that we train, so it will have the ability to identify what is present in the image, and also it can identify where exactly is that given object, or where exactly this what is present in my given image. Okay, now while performing the training, so we make use of various network architecture. I can make use of CNN or any other models. So I'll make use of many network architecture, various network architecture, do the hyperparameter tuning and do all those things, and I'll complete the training. And once I have the trained data, I can send a new image. Okay, I can send a new image, and an example can be something like this. Let's say once I've done the training, I'll be sending this data, this new image data, to my deep learning model. And once I send this new image data for my deep learning model can say what is present in the image. It is going to say it as cat, and to say where exactly it is present in the image, it's going to give us the x, y, h, and w. That means the bounding box coordinates, x comma y, and this is the height, width, and this is the height. So that is what my deep learning model is going to give me. Now, as a part of today's session, we will be making use of pre-trained model. So when I say pre-trained model, I am having a deep learning neural network which is already trained. So I'll use this already trained model And I'm going to show you as how we can use this already trained model, send in the data which is already with us, and then we can get the predictions of what are the things that are present in my given input image. So that's what we are going to cover in today's session, guys. Now to perform this, that is to use this pre-trained model and to send the input data and to generate the predictions, we will be making use of TensorFlow. So TensorFlow is the deep learning framework that we will be using. Okay, and this TensorFlow is a deep learning or an open source machine learning platform created by Google, and this is one of the go-to tools now to perform any deep learning relevant task. Previously we were using the PyTorch, and now we are shifting most of our work towards TensorFlow because it is backed by the Google, and it has very good support for mobile and many such remote devices as well. And because of that reason, we are seeing most of our applications or deep learning applications getting deployed using this TensorFlow open source library. Okay, so that's how we proceed along, guys. So let's go to the slides and let's walk through the slides now. Now, whenever I want to perform the object detection, so I'll have my training data. In this example, I'm trying to understand whether a given image has a car or a bike. So I'll have images like this, and on top of my image, so I'll run the learning. So I'll learn, like I'll use my deep learning model, and I'm going to understand the various features that are present in each car and bike. So this process constitutes the training of deep learning model. And once we have done the training, we will have the trained model which can identify whether a given image belongs to either a car or either a bike. Now, once I have trained my deep learning model, I'll use the trained deep learning model for testing it with the new data. So let's say this is the new data that I'm having, which I have not used during my training. I'll send this new data. I'll send it to my trained model, that is this trained model, and I'll be able to generate the outcome which says as, okay, this this input image belongs to the class, or it belongs to the class of this bike. So that's how a typical object detection flow will be. So this is actually talking about classification, and once we have done that, we can also draw a bounding box around it and say where exactly is that given object. Okay, so this is just a overall view as how the training will be. Now, coming to TensorFlow, as I mentioned already, it's the deep learning framework that we have, which has been created by Google, which we'll be using to create the deep learning models. So this TensorFlow has one of the main object type that is called as tensors. Now, when we are working with TensorFlow, we are going to have all the objects into the data type of tensors. And this tensors is actually a standard way of representing the data whenever we are performing the task of deep learning. Now, this tensor is very similar to NumPy arrays, but the way it is going to give us an advantage compared to NumPy array is by making use of tensors in TensorFlow, it is going to help me in tracking the operations. And by tracking the operations, I can directly perform the auto differentiation on top of it so that I can make use of those gradients to update the values in my parameters. And not only that, by making use of tensors, we can also get the speed boost, because using these tensors, we can have the computation run on the GPU rather than the CPU. So by running on GPU, it has been shown that we are going to get the speed boost of close to 10 times the speed that we could get on CPU. And because of those two important reasons, we'll be representing all the data in terms of tensors while working with deep learning. Now this tensor, as I mentioned, it's similar to NumPy array. It's a multi-dimensional array, and it's an extension of two-dimensional tables matrices to data with higher dimension. It's a multi-dimensional array, guys. Suppose if I have a vector, I can say that tensor of dimension 6, which is a single dimension vector or a single dimension tensor. And if I have a two-dimension tensor, I can say this is a tensor of dimension 6, 4, so 6 rows and 4 columns. And if I'm having 3 dimensions, so this is a tensor which has 3 dimensions, which is having the shape as 6, 4, 2. Okay, so this is the basic representation, or like these tensors are the objects through which we represent the given data. Now in TensorFlow, as I mentioned already, so like in TensorFlow, the computation is approached as a data flow graph. So what it actually means is each operation that I'll be performing with the help of my tensor object, it's going to track it. Now by tracking it, I can directly go back and perform the back propagation, which will directly help me in finding the derivatives for the complex equations, because it is automatically tracking by its end. So because of that advantage, we'll be using this TensorFlow, guys. And so what we do in case of TensorFlow is we'll have the input data, and we'll send it to the TensorFlow, and we'll perform the training on the TensorFlow model. And once we perform the training, we will have the trained model with us. And once the training has been completed, we can just send in the test data, and we can validate how exactly are we getting the result. So like this is the typical flow that we would follow. Like we will have the trained model with us, so we will have the input data, we'll use the input data to perform the training, and once we perform the training, we will have the model trained for us. And once the model is trained, we can send in the new data. And if I'm doing the task of object detection, when I send a new data, I'm going to get an output that would look like this. So it is going to identify what are the objects that are present in the image, and along with that, it's going to draw a bounding box which says where exactly is that object is present. Okay, so this was about using the TensorFlow for performing the object detection. So with this understanding, let's go to our Google Colab notebook and let's implement it in a hands-on manner, guys. Now here, as I mentioned already, we'll be making use of TensorFlow. So this is going to take care of installing my TensorFlow. So I'll normally have the TensorFlow. This is to make sure that I'm having the required version. So in my case, I want to use the version of TensorFlow 2.2. Hence, I'm just installing that TensorFlow 2.2 version for this instance, okay, which is my Google Colab instance. So this is going to take care of all the necessary installations. And once I've done the installation, I'm just creating a folder for me. Okay, so the folder would look like this. So I'm importing the OS library, and I'm importing my pathlib library, and using both of this library, I'm just checking whether I'm having the let me do one thing. I'm going to restart the runtime so that you can understand what exactly is happening over here. So this will reset all the progress that I had till now. So this is going to assign me a fresh copy of system. Okay, so this is a fresh copy of the system that has been assigned to me. And here, while make sure that you have switched on the GPU. So to switch on the GPU, go to edit, notebook settings, and select the hardware acceleration as GPU and click on save button. Now by doing like this, you'll have the access to the GPU, that is graphical processing unit. So I have the fresh Google Colab instance that has been assigned to me, and this has the RAM of 12.69 GB and the hard disk space of 69 GB, and I've already utilized 38 GB of hard disk. Okay, so this is the Google Colab instance that has been assigned to me. Now I'm going to install the required version of TensorFlow. Now, as I mentioned already, to perform the task of object detection, we'll be making use of pre-trained model. Now to make use of pre-trained model, as a first step, we have to create the we have to get the clone from the GitHub. So from this clone of TensorFlow models, we have to clone it. So I'm going to copy that URL and I want to show you over here. So this is the TensorFlow model garden, guys. And if I want to perform the object detection with any of the pre-trained model, I have to first clone this repository. So this code is going to clone the repository from this GitHub link. Okay, so hence I've given as git clone and I've given the models folder. So from this models folder, it's going to create a clone, guys. When I say it is going to create a clone, it is going to copy everything that is present in this GitHub link. Okay, so you can observe the same in our left side as well. So on our left side, we have actually the file explorer. Currently, I'm having only single folder called sample data. Now, I'm going to, okay, let's wait for the completion of the installation over here. So this is taking a while for me to install the TensorFlow 2.2 version for me. So let's wait. Okay, so it has installed the required version of TensorFlow for me. Now, once it has been installed, here in this cell, I'm creating a clone from this GitHub link. So I'm going to execute this cell. So once I execute this cell, so it's going to connect to this GitHub URL and it's going to create the clone. See, if you just observe, it has created a folder called models, and if I expand this folder of models, I'll be having various subfolders: community, official, orbit, research, and so on. See, if I open the models, I'm having various subfolders: community, official, orbit, research. So all these things has been copied over for me. That means all these things have been cloned for my working. Now with this GitHub uh, models folder cloned, the next step would be is we want to make sure that we like all the system requirements will satisfy for us to make sure that we can work with the object detection API, which is our pre-trained model. Now to check whether everything is installed or whether we have all the dependencies with us, so we just have to run this cell. So this cell is going to make sure that it is going to create all the dependencies which are required for us to run, and along with that it is going to set up a system so that we can make use of all these pre-trained models. So I'm going to execute this cell. So please bear with the execution, guys. So since this is a object detection, which is a complex model, it would take a while for system to get ready. So this is going to uh, like verify everything, whether every library is present for me. And once it verifies everything is present, it is going to set up a system so that we can directly run that object detection API. Now, by the time it runs, let's explore this GitHub screen that we have over here. So here, if you observe, it says the TensorFlow Model Garden. It's a Tensor Model Garden for TensorFlow, and it says how you can use this TensorFlow Model Garden. And apart from this, there is one more link. Yes, there is one more URL which I want to share it with you, which is called as Object Detection TensorFlow. So I'll add it over here. So this URL contains the information of various object detection APIs that are available to us inside the TensorFlow. Okay, and if you come down, it actually talks about what are the individual models that we have inside our TensorFlow. So all the individual models inside the TensorFlow which are available to us is present inside this TensorFlow 2 model zoo. So this is the TensorFlow 2 model zoo. And if I click on that URL, you will be redirected to this URL, guys. This is that URL. And these are the various object detection models that we have and which has been given directly to us by the TensorFlow team. And all these models that you're seeing, so these are the object detection models. So these are the object detection models, and these models are already pre-trained on COCO 2017 dataset. If I open the information about this COCO 2017 dataset, so this is a dataset which is actually used for performing the object detection, and this has around more than 1 million of images, guys. So all these models that we have, it has been trained on this COCO 2017 dataset, and it is already pre-trained for us. We can just use this pre-trained trained models and we can do our own prediction. That's how easy it is for us to work with TensorFlow Model Zoo, guys. Okay, in our scenario, we'll be making use of what we call as image efficient DNet. So I think this is the one. Efficient det DeFi. So this is the pre-trained model that we'll be using to perform the object detection in our case. Okay. So here in this cell, I'm just importing all the necessary helper functions. So once I am importing all the necessary functions, I've just written a helper function which will help me to create a plot. So this is going to create a plot. That means it's going to pre-process the image and it will help me to create a plot. And along with that, I'm just creating a label map, because as I've already mentioned, this this model that we have, that is TensorFlow 2 object detection models, this has been trained on COCO 2017 dataset. Now to add a name for each and every image that I'll be using, I'll have to create a label map. Hence, I have created a label map in the form of a Python dictionary. This is going to take care of it. So in this way, I'll be creating my category index and it will have its ID as well as its name like this. So this will take care of defining the helper function as well as defining the various classes that we have. And here, this cell is actually going to download the saved model, and it is going to add under this folder of models research object detection test data. So I'll open the folder path for you to show you where it will be saved. So models research object detection, and in this folder I'm going to create a folder called, there is a folder called test data, and inside this folder we are going to download the file, which is a pre-trained model file from this URL. So this is going to download the pre-trained model, and once I download the pre-trained model, I'm going to extract that zip file, which is in actually tar.gz format. So I'm going to extract it, and then I'm going to move everything to this subfolder of this test data, guys. So I'm going to execute this. So this is going to take care of downloading the saved model from the URL. That means it's going to download from this TensorFlow object detection, download from this model zoo. And once I have everything, I'm going to have it inside my test data. See, under the subfolder of test data, I have created one more subfolder, which is called as efficient det DeFi, and which has been trained on COCO dataset. So we have the pre-trained model with us. So what I have already done over here is I have downloaded the pre-trained model for me. So this is where we are currently. So we have downloaded the pre-trained model. Now once we have the pre-trained model, which is a model which has been already trained, we can just send in some test data which is already with us, and we can generate the predictions. So to generate that, here in this here in this thing, like before I do that, I'm just loading that model into my TensorFlow instance. So to load the model, I'm just writing as tf.savedmodel.load. So this is going to make sure that it will load the pre-trained model for me. So once I load my pre-trained model, I'm going to select some test images. Okay, so there are some images which is already available to me inside the subfolder of test images. So this is the subfolder of test images, and there is an image 1, image 2, and image 3. So if I download any single image, so if I download this single image, so this is a one image that I'm having with me. Okay, I'm having an image of dog, and this is another image that I'm having with me over here. So I think this is an image of beach, and I'm having one more image. So this is an image of various tools that I'm having in this given image. Okay, so what we can do is we can, since we already have the pre-trained model, we can just go ahead and load load these three images which are present inside our test folder, and we can generate the predictions on top of each of these image. So I'm going to execute this cell, guys. So this is going to load each and every individual image, and it is going to run the detection on all this input image, and it's going to show us as how it's going to show us as where exactly each and every image is present for us. So this would take a while for generating the predictions. Okay, so we have the results for us. So there was a typo error, guys. Here I had given us for I in range 3, and normally when we call range function and when we give the value, so the input value starts from 0, but here I'm having only 3 images, but I was going through 4 times, so hence I was getting the error. So make sure that you correct this error if you are working over there. Just give it as for I in range 2. So this will load every image for us. So for the first image, it has said this image contains 3 objects. So one object belongs to the person with the confidence of 78%, and the another object that we have over here is dog with the confidence of 83%, and this is another object that is with me which is having the confidence of 83%. So this is second image it has loaded. So it has loaded that this is the image that it has, and this image has kite with 54%, kite with 56%, kite with 89%, so person with 87%. So what we have done over here is we have just ran through every image that we had over here from our test data test folder, and then we have just created like we have also detected the objects that are present. So to summarize, what we have done as a part of this today's session is we have seen what is object detection. So object detection is a task in the field of computer vision, and when we talk about this object detection, we want to identify what is present in the image, and along with that I want to detect, or I want to say where exactly is present that specific object that I'm trying to say what. Okay, what and where, both are the things that we will be getting when we are doing the task of object detection. Now to do this, in this specific session, we have actually made use of pre-trained model which is available to us from the object detection API of TensorFlow 2, and one such model is efficient D5. This is the research paper of efficient D5. So we use this pre-trained model, and using this pre-trained model we have chosen some of the data which is already present with us inside our folders, and we have ran the object detection. And once we ran the object detection, we were able to see what is present in a given image, and along with that we were also able to draw the bounding box to say where exactly is the given object. And that's the beauty of object detection. And we were able to do all this compound like complex things with very few lines of code. And that's the powerful, or that's the power of TensorFlow. It will help us in gaining, or it will help us in getting the boost from making use of pre-trained models instead of training everything from scratch. So this is about performing the object detection using TensorFlow using pre-trained models, guys.
Since the beginning of time, written texts have been a means to communicate, express, and document something of significance. Even in the modern age, it has been proven a lot of times that an individual's writing style can be a defining aspect of one's psyche. Ever since social media emerged, microblogging became the new form of writing, expressing, or documenting an event. This also gave rise to a lot of unstructured data, and with it, a need to understand that data. Now this is where text classification can be put to our advantage. Text classification is nothing but classifying unstructured text data into various categories. To further simplify how we use text classification, let's consider an example. You have a product that was launched a while ago, and you have also kept track of all the reviews that the product got on all the platforms across the internet. Now what you have is unstructured text data. And to do text classification on this unstructured data, you can follow two approaches. One, you can either make a few rules where a collection of words will decide the sentiment of the input text. This approach can be useful for a handful of data, but analyzing large sets of data is neither efficient nor cost-effective. But a better approach is making use of natural language processing and classification using machine learning. For this, we should train a classifier with a separate class labeled data And using this model, we can do classification on the input data. When we give input to the classifier, we will get an output with the class category based on our trained model, telling us if the review is bad, average, or good. This way, text classification on user reviews can help us improve user experience. Data is the new fuel. Thus, even bad reviews can help us identify the attributes which can help us improve our upcoming campaigns. Businesses and organizations are following this trend to understand user sentiment and user behavior. Text classification can also be used for applications like spam detection in emails, targeting customer needs, etc. In this day and age, where data is generated every second of the day, text classification becomes an asset for any organization. Have you ever imagined a world without machines? How about a basic one such as a calculator? Well, the grocery store guy would go nuts then, wouldn't he? Our world today is driven by machines of varying complexities. From a basic one like a calculator to a highly complex humanoid robot, everything is a machine. How many of us just look into our phones to unlock it? The moment you look at it, the phone knows it's you. Now, how does it do that? The smartphone isn't called smart just like that. There are reasons why it is, and one such reason is facial recognition. When you look at someone, the eyes send signals to the brain. These signals basically carry the facial pattern of that person. The brain then matches these patterns against the ones already saved in our memory. It is amazingly true that facial recognition in smartphones mimics human brain functionality. So when you are trying to unlock your phone, the phone detects the facial pattern and compares it against the one stored in the database. If the patterns are matched, your device is unlocked. Facial recognition is not just limited to unlocking a phone. Its applications are spread across areas such as healthcare, banking, security, and the list goes on and on. Automated facial recognition is just a simple example. The world of artificial intelligence and machine learning is booming with various other technologies. While the need for automation is ever increasing, the IT sector is always looking for skilled AI and ML engineers. And not just that, AI and ML engineers also fetch the best-in-class salaries.
Now, the success of human race is because of the ability to communicate and share information. Now, that is where the concept of language comes in. However, many such standards came up, resulting in many such language, with each language having its own set of basic shapes called alphabets. And the combination of alphabets resulted in words, and the combination of these words arranged meaningfully resulted in the formation of a sentence. Now, each language has a set of rules that is used while developing these sentences, and these set of rules are also known as grammar. Now, coming to today's world, that is the 21st century, according to the industry estimates, only 21% of the available data is present in the structured format. Data is being generated as we speak, as we tweet, as we send messages on WhatsApp, Facebook, Instagram, or through text messages. And the majority of this data exists in the textual form, which is highly unstructured in nature. Now, in order to produce significant and actionable insights from the text data, it is important to get acquainted with the techniques of text analysis. So let's understand what is text analysis or text mining. Now, it is the process of deriving meaningful information from natural language text, and text mining usually involves the process of structuring the input text, deriving patterns within the structured data, and finally evaluating the interpreted output. Compared with the kind of data stored in database, text is unstructured, amorphous, and difficult to deal with algorithmically. Nevertheless, in the modern culture, text is the most common vehicle for the former exchange of information. Now, as text mining refers to the process of deriving high-quality information from text, the overall goal here is to turn the text into data for analysis. And this is done by the application of NLP or natural language processing. So let's understand what is natural language processing. So NLP refers to the artificial intelligence method of communicating with an intelligent system using natural language. By utilizing NLP and its components, one can organize the massive chunks of textual data, perform numerous automated tasks, and solve a wide range of problems such as automatic summarization, machine translation, named entity recognition, speech recognition, and topic segmentation. So let's understand the basic structure of an NLP application. Considering the chatbot here as an example, we can see first we have the NLP layer, which is connected to the knowledge base and the data storage. Now, the knowledge base is where we have the source content. That is, we have all the chat logs which contain a large history of all the chats which are used to train the particular algorithm. And again, we have the data storage where we have the interaction history and the analytics of that interaction, which in turn helps the NLP layer to generate the meaningful output. So now if we have a look at the various applications of NLP, first of all, we have sentimental analysis. Now this is a field where NLP is used heavily. We have speech recognition. Now here we are also talking about the voice assistants like Google Assistant, Cortana, and the Siri. Now next we have the implementation of chatbot as I discussed earlier just now. Now you might have used the customer care chat services of any app. It also uses NLP to process the data entered and provide the response based on the input. Now, machine translation is also another use case of natural language processing. Now, considering the most common example here would be the Google Translate. It uses NLP and translates the data from one language to another, and that too in real time. Now, other applications of NLP include spell checking. Then we have the keyword search, which is also a big field where NLP is used. Extracting information from any particular website or any particular document is also a use case of NLP. And one of the coolest application of NLP is advertisement matching. Now here, what we mean is basically recommendation of the ads based on your history. Now NLP is divided into two major components, that is the natural language understanding, which is also known as NLU, and we have the natural language generation, which is also known as NLG. The understanding involves tasks like mapping the given input into natural language, into useful representations, analyzing different aspects of the language, whereas natural language generation, it is the process of producing the meaningful phrases and sentence in the form of natural language. It involves text planning, sentence planning, and text realization. Now, NLU is usually considered harder than NLG. Now, you might be thinking that even a small child can understand a language. So let's see what are the difficulties a machine faces while understanding any particular languages. Now, understanding a new language is very hard. Taking our English into consideration, there are a lot of ambiguity, and that too in different levels. We have lexical ambiguity, syntactical ambiguity, and referential ambiguity. So lexical ambiguity is the presence of two or more possible meanings within a single word. It is also sometimes referred to as semantic ambiguity. For example, let's consider these sentences and let's focus on the italicized word. She is looking for a match. So what do you infer by the word match? Is it that she's looking for a partner? Or is it that she's looking for a match, be it a cricket match or a rugby match? Now the second sentence here we have the fisherman went to the bank. Is it the bank where we go to collect our checks and money, or is it the river bank we are talking about here? Sometimes it is obvious that we are talking about the river bank, but it might be true that he's actually going to a bank to withdraw some money. You never know. Now coming to the second type of ambiguity, which is the syntactical ambiguity. In English grammar, this syntactical ambiguity is the presence of two or more possible meanings within a single sentence or a sequence of words. It is also called as structural ambiguity or grammatical ambiguity. Taking these sentences into consideration, we can clearly see what are the ambiguities faced. The chicken is ready to eat. So here, what do you infer? Is the chicken ready to eat his food, or is the chicken ready for us to eat? Similarly, we have the sentence like visiting relatives can be boring. Are the relatives boring? Or when we are visiting the relative, it is very boring. You never know. Coming to the final ambiguity, which is the referential ambiguity. Now this ambiguity arises when we are referring to something using pronouns. The boy told his father the theft. He was very upset. Now I'm leaving this up to you. You tell me, what does he stand for here? Who is he? Is it the boy? Is it the father? Or is it the thief? So coming back to NLP, firstly we need to install the NLTK library, that is the Natural Language Toolkit. It is the leading platform for building Python programs to work with human language data, and it also provides easy to use interfaces to over 15 corpora and lexical resources. We can use it to perform functions like classification, tokenization, stemming, tagging, and much more. Now, once you install the NLTK library, you will see an NLTK downloader. It is a pop-up window which will come up, and in that you have to select the all option and press the download button. It will download all the required files, the corpora, the models, and all the different packages which are available in the NLTK. Now, when we process text, there are a few terminologies that we need to understand. Now, the first one is tokenization. So tokenization is a process of breaking strings into tokens, which in turn are small structures or units that can be used for tokenization. Now, tokenization involves 3 steps, which is breaking a complex sentence into words, understanding the importance of each word with respect to the sentence, and finally produce a structural description on an input sentence. So if we have a look at the example here, considering this sentence, tokenization is the first step in NLP. Now, when we divide it into tokens, as you can see here, we have 1, 2, 3, 4, 5, 6, and 7 tokens here. Now, NLTK also allows you to tokenize phrases containing more than one word. So let's go ahead and see how we can implement tokenization using NLTK. So here I'm using Jupyter Notebook to execute all my practicals and demo. You are free to use any sort of IDE which is supported by Python. It's your choice. So let me create a new notebook here. Let me rename as text mining and NLP. So first of all, let us import all the necessary libraries here. We are importing the OS, NLTK, and the NLTK corpus. So as you can see here, we have various files which represent different types of words, different types of functions. We have samples of Twitter. We have different sentimental WordNet. We have product reviews. We have movie reviews. We have non-breaking prefixes and many more files here. Now, let's have a look at the Gutenberg file here and see what are all the fields which are present in the Gutenberg file. So as you can see here, inside this, we have all the different types of text files. We have Austen Emma, we have the Shakespeare, we have the Hamlet, we have Moby Dicks, we have the Carol Alice, and many more. Now, this is just one file we are talking about, and NLTK provides a lot of files. So let's consider a document of type string and understand the significance of its tokens. So if we have a look at the elements of the Hamlet, you can see it starts from the tragedy of Hamlet by William Shakespeare. So if we have a look at the first 500 elements of this particular text file, so as I was saying, the tragedy of Hamlet by William Shakespeare, 1599, Actus Primus. We can use a lot of these files for analysis and text for understanding and analysis purposes. And this is where NLTK comes into picture, and it helps a lot of programmers to learn about the different features and the different application of language processing. So here I have created a paragraph on artificial intelligence. So let me just execute it. Now this AI is of the string type, so it will be easier for us to tokenize it. Nonetheless, any of the files can be used to tokenize. For simplicity, here I'm taking a string file. The next what we are going to do is import the word underscore tokenize under the NLTK tokenize library. Now this will help us to tokenize all the words. Now we will run the word underscore tokenize function over the paragraph and assign it a name. So here I'm considering AI underscore tokens, and I'm using the word underscore tokenize function on it. Let's see what's the output of this AI underscore tokens. So as you can see here, it has divided all the input which was provided here into the tokens. Now let's have a look at the number of tokens here we have here. So in total, we have 273 tokens. Now these tokens are a list of words and the special characters which are separated items of the list. Now in order to find the frequency of the distinct elements here in the given AI paragraph, we are going to import the frequency distinct function, which falls under NLTK.probability. So let's create a fdist in which we have the function here, frequentDist. And basically what we are doing here is finding the word count of all the words in the paragraph. So as you can see here, we have comma 30 times, we have full stop 9 times, and we have accomplished 1, according 1, and so on. We have computer 5 times. Now here we are also converting the tokens into lowercase so as to avoid the probability of considering a word with uppercase and lowercase as different. Now suppose we were to select the top 10 tokens with the highest frequency. So here you can see that we have comma 30 times, the 13 times, off 12 times, and 12 times. Whereas the meaningful words which are intelligence, which is 6 times, and intelligence 6 times. Now there is another type of tokenizer which is the blank tokenizer. Now let's use the blank tokenizer over the same string to tokenize the paragraph with respect to the blank string. Now the output here is 9. Now this 9 indicates how many paragraphs we have and what all paragraphs are separated by a new line. Although it might seem like a one paragraph, it is not. The original structure of the data remains intact. Now another important key term in tokenizations are bigrams, digrams, and n-grams. Now what does this mean? Now bigrams refers to tokens of 2 consecutive words known as a bigram. Similarly, tokens of 3 consecutive written words are known as trigram, and similarly we have n-grams for the n consecutive written words. So let's go ahead and execute some demo based on bigrams, digrams, and n-grams. So first of all, what we need to do is import bigrams, trigrams, and n-grams from NLTK.util. Now let's take a string here on which we'll use these functions. So taking this string into consideration, the best and the most beautiful thing in the world cannot be seen or even touched. They must be felt with the heart. So first what we are going to do is split the above sentence or the string into tokens. So for that we are going to use the word underscore tokenize. So as you can see here, we have the tokens. Now let us now create the bigram of the list containing tokens. So for that, we are going to use the nltk.bigrams and pass all the tokens. And since it is a list, we are going to use the list function. So as you can see under output, we have the best, and most beautiful thing in the world. So as you can see, the tokens are in the form of 2 words. It's in a pair form. Similarly, if we want to do the trigrams and find out the trigrams, what we need to do is just remove the bigrams and use the trigrams. So as you can see, we have tokens in the form of 3 words. And if you want to use the n-grams, let me show you how it's done. So for n-grams, what we need to do is define a particular number here. So instead of n, I'm going to use, let's say 4. So as you can see, we have the output in the form of 4 tokens. Now once we have the tokens, we need to make some changes to the tokens. So for that, we have stemming. Now stemming usually refers to normalizing words into its base form or the root form. So if we have a look at the words here, we have affectation, affects, affections, affected, affection, and affecting. So as you might have guessed, the root word here is affect. So one thing to keep in mind here is that the result may not be the root word always. Stemming algorithm works by cutting off the end or the beginning of the word, taking into account a list of common prefixes and suffixes that can be found in an inflected word. Now this indiscriminate cutting can be successful in some occasions, but not always. And this is why we affirm that this approach presents some limitations. So let's go ahead and see how we can perform stemming on a particular given data set. Now there are quite a few types of stem, so starting with the Potter stem, we need to import it from nltk.stem. Let's get the output of the word having and see what is the stemming of this word. So as you can see, we have as the output. Now here we have defined words to stem, which are give, giving, given, and gave. So let's use the Potter stemmer and see what is the output of this particular stemming. So as you can see, it has given give, given, give, and gave. Now we can see that the stemmer removed only the ing and replaced it with an e. Now let's try to do it the same with another stemmer called the Lancaster stemmer. You can see the stemmer stemmed all the words. As a result of it, you can conclude that the Lancaster stemmer is more aggressive than the Potter stemmer. Now the use of each of these stemmers depend on the type of task that you want to perform. For example, if you want to check how many times the words GIV is used above, you can use the Lancaster stemmer. And for other purposes, you have the Potter stemmer as well. Now there are a lot of stemmers. There is one snowball stemmer also present, where you need to specify the language which you are using and then use the snowball stemmer. Now, as we discussed that stemming algorithm works by cutting off the end or the beginning of the word, on the other hand, lemmatization takes into consideration the morphological analysis of the word. Now, in order to do so, it is necessary to have a detailed dictionary which the algorithm can look into to link the form back to its lemma. Now, lemmatization, what it does is groups together different inflected forms of a word, which are called lemma. It is somehow similar to stemming as it maps several words into a common root. Now, one of the most important thing here to consider is that the output of lemmatization is a proper word. Unlike stemming, in that case where we got the output as GIV, now GIV is not any word, it's just a stem. Now, for example, if a lemmatization should work on gone, going, and went, it all stems into go, because that is the root of all the three words here. So let's go ahead and see how lemmatization work on the given input data. Now for that, we are going to import the lemmatizer from NLTK. Now we're also importing the wordnet here. As I mentioned earlier, that lemmatization requires a detailed dictionary because the output of it is a root word, which is a particular given word. It's not just any random word, it is a proper word. So to find that proper word, it needs a dictionary. So here we are providing the wordnet dictionary and we are using the wordnet lemmatizer. So passing the word corpora into the wordnet lemmatizer. So can you guys tell me what is the output of this one? I'll leave this up to you guys. I won't execute this sentence. Let me remove this sentence here. You guys tell me in the comments below what will be the output of the lemmatization of the word corpora. And what will be the output of the stemming? You guys execute that and let me know in the comment section below. Now let's take these words into consideration in give, giving, given, and gave, and see what is the output of the lemmatization. So as you can see here, the lemmatizer has kept the words as it is, and this is because we haven't assigned any POS tags here, and hence it has assumed all the words as nouns. Now you might be wondering what are POS tags. Well, I'll tell you what are POS tags later in this video. So for just now, let's keep it as simple as that, is that POS tags usually tell us what exactly the given word is. Is it a noun, is it a verb, or is it different parts of speech? Basically, POS stands for parts of speech. Now, do you know that there are several words in the English language such as I, ate, for, above, below, which are very useful in the formation of sentence, and without it, the sentence won't make any sense. But these words do not provide any help in the natural language processing. And this list of words are also known as stop words. NLTK has its own list of stop words, and you can use the same by importing it from the nltk.corpus. So the question arises, are they helpful or not? Yes, they are helpful in the creation of sentences, but they are not helpful in the processing of the language. So let's check the list of stop word in the NLTK. So from nltk.corpus, we are importing the stop words. And if we specify what all stop words are there in the English language, let's see. So as you can see here, we have the list of all the stop words which are defined in the English language. And we have 179 total number of stop words. Now, as you can see here, we have these words which are few, more, most, other, some. Now, these words are very necessary in the formation of sentences. You cannot ignore these words. But for processing, these are not important at all. So if you remember, we had the top 10 tokens from that particular word, that is the AI paragraph I mentioned earlier, which was given as ftest_top10. Let's take that into consideration and see. What you can see here is that except intelligent and intelligence, most of the words are either punctuation or stop words and hence can be removed. Now we'll use the compile from the RE module to create a string that matches any digit or special character, and then we'll see how we can remove the stop words. So if we have a look at the output of the post punctuation, you can see there are no stop words here in the particular given output. And if we have a look at the output of the length of the post punctuation, it's 233 compared to the 273, the length of the AI_tokens. Now this is very necessary in language processing as it removes all the unnecessary words which do not hold any much more meaning. Now coming to another important topic of natural language processing and text mining or text analysis is the parts of speech. Now generally speaking, the grammatical type of the word, which is the verb, noun, adjective, adverb, article indicates how a word functions in the meaning as well as the grammatical within the sentence. Now, a word can have more than one path of speech based on the context in which it is used. For example, if we take the sentence into consideration, Google something on the internet. Now, here Google acts as a verb, although it is a proper noun. So as you can see here, we have so many types of POS tags, and we have the descriptions of those various tags. So we have the coordinating conjunction CC, cardinal number CD. We have JJ as adjective, MD as modal. We have the proper noun singular, plural. We have verbs, different types of verbs. We have interjection, symbol. We have the Y pronoun and the Y adverb. Now we can use POS tags as a statistical NLP task. It distinguishes the sense of the word, which is very helpful in text realization, and it is easy to evaluate as in how many tags are correct. And you can also infer semantic information from the given text. So let's have a look at some of the examples of POS. So take the sentence, the dog killed the bat. So here, the is a determiner, dog is a noun, killed is a verb, and again, the bat are determiner and noun respectively. Now let's consider another sentence, the waiter cleared the plates from the table. So as you can see here, all the tokens here correspond to a particular type of tag, which is the parts of speech tag. It is very helpful in text realization. Now let's consider a string and check how NLTK performs POS tagging on it. So let's take the sentence, Timothy is a natural when it comes to drawing. First, we are going to tokenize it. And under NLTK only, we have the POS underscore tag option, and we'll pass all the tokens here. So as you can see, we have Timothy as noun, is a verb, as a determiner, natural as an adjective, when as a verb, it as a preposition, comes as a verb, to as a to, and drawing as a verb again. So this is how you define the POS tags. The POS underscore tag function does all the work here. Now let's take another example here. John is eating a delicious cake. Now let's see what's the output of this one. Now here you can see that the tagger has tagged both the word is and eating as a verb because it has considered is eating as a single term. This is one of the few shortcomings of the POS taggers. One thing important to keep in mind. Now after POS taggings, there is another important topic, which is the named entity recognition. So what does it mean? Now the process of detecting the named entities such as the person name, the location name, the company name, the organization, the quantities, and the monetary value is called the named entity recognition. Now under named entity recognition, we have three types of identification here. We have the noun phrase identification. Now this step deals with extracting all the noun phrases from a text using dependency parsing and parts of speech tagging. Then we have the phrase classification, this step classification. This is the classification step in which all the extracted noun phrases are classified into respective categories, which are the location, names, organization, and much more. And apart from this, one can curate the lookup tables and dictionaries by combining information from different sources. And finally, we have the entity disambiguation. Now, sometimes it is possible that the entities are misclassified. Hence, creating a validation layer on top of the result is very useful, and the use of knowledge graphs can be exploited for this purpose. Now, the popular knowledge graphs are Google Knowledge Graph, the IBM Watson, and Wikipedia. So let's take a sentence into consideration that the Google CEO Sundar Pichai introduced the new Pixel at Minnesota Roy Center event. So as you can see here, Google is an organization, Sundar Pichai is a person, Minnesota is a location, and the Roy Center event is also tagged as an organization. Now for using NER in Python, we'll have to import the NE underscore chunk from the NLTK module, which is present in Python. So let's consider our text data here and see how we can perform the NER using the NLTK library. So first we need to import the NE underscore chunk here. Let's consider the sentence here. We have the US president stays in the White House. So we need to do all these processes again. We need to tokenize the sentence first and then add the POS tags. And then if we use the any underscore chunk function and pass the list of tuples containing POS tags to it, let's see the output. So as you can see, the US here is recognized as an organization. And White House is clubbed together as a single entity and is recognized as a facility. Now this is only possible because of the POS tagging. Without the POS tagging, it would be very hard to detect the named entities of the given tokens. Now that we have understood what are named entity recognition, NERs, let's go ahead and understand one of the most important topic in NLP and text mining, which is the syntax. So what is a syntax? So in linguistics, syntax is the set of rules, principles, and the processes that govern the structure of a given sentence in a given language. The term syntax is also used to refer to the study of such principles and processes. So what we have here are certain rules as to what part of the sentence should come at what position. With these rules, one can create a syntax tree whenever there is a sentence input. Now, syntax tree in layman terms is basically a tree representation of the syntactic structure of the sentence of the strings. It is a way of representing the syntax of a programming language as a hierarchical tree structure. This structure is used for generating symbol tables for compilers and later code generation. The tree represents all the constructs in the language and their subsequent rules. So let's consider the statement, the cat sat on the mat. So as you can see here, the input is a sentence or a verb phrase, and it has been classified into noun phrase and the prepositional phrase. Again, the noun phrase is classified into article and noun. And again, we have the verb, which is sat. And finally, we have the preposition on, the article and the noun, which are the and mat. Now, in order to render syntax trees in our notebook, you need to install the Ghost script, which is a rendering engine. Now, this takes a lot of time, and let me show you from where you can download the Ghost script. Just type in download Ghost script and select the latest version here. So as you can see, we have two types of license here. We have the general public license and the commercial license. As creating syntax and following it is a very important part, it is also available for commercial license, and it is very useful. So I'm not going to go much deeper into what syntax tree is and how we can do that. So now that we have understood what are syntax trees, let's discuss the important concept with respect to analyzing the sentence structure, which is chunking. So chunking basically means picking up individual pieces of information and grouping them into bigger pieces. And these bigger pieces are also known as chunks. In the context of NLP and text mining, chunking means grouping of words or tokens into chunks. So let's have a look at the example here. So the sentence into consideration here is we caught the Black Panther. We is the preposition, caught is a verb, the determiner, black is an adjective, and panther is a noun. So what it has done is here, as you can see, is that pink, which is an adjective, panther, which is a noun, and the is a determiner are chunked together in the noun phrase. So let's go ahead and see how we can implement chunking using the NLTK. So let's take the sentence, the big cat ate little mouse who was after the fresh cheese. We'll use the POS tags here and also use the tokenizing function here. So as you can see here, we have the tokens and we have the POS tags. What we'll do now is create a grammar from a noun phrase and we'll mention the tags that we want in our chunk phrase within the curly braces. So that will be our grammar underscore NP. Now here we have created a regular expression matching string. Now we'll have to parse the chunk, and hence we'll create a chunk parser and pass our noun phrase string to it. So as you can see, we have a certain error, and let me tell you why this error occurred. So this error occurred because we did not use the Ghost script and we do not form the syntactical tree. But in the final output, we have a tree structure here, which is not exactly in the visualization part, but it's there. So as you can see here, we have the NP noun phrase for the little mouse. Again, we have the noun phrase for fresh cheese also. Although fresh is an adjective and cheese is a noun, it has considered a noun phrase of these two words. So this is how you execute chunking in NLTK library. So by now we have learned almost all the important steps in text processing, and let's apply them all in building a machine learning classifier on the movie reviews from the NLTK corpora. So for that, first let me import all the libraries, which are the pandas, the NumPy library. Now these are the basic libraries needed in any machine learning algorithm. We are also importing the count vectorizer. I'll tell you why it is used later now. Let's just import it for now. So again, if we have a look at the different elements of the corpora, as we saw earlier in the beginning of our session, we have so many files in the given NLTK corpora. Now let's now access the movie reviews corpus under the NLTK corpora. As you can see here, we have the movie reviews. So for that, we are going to import the movie underscore reviews from the NLTK corpus. So if we have a look at the different categories of the movie reviews, we have two categories, which are the negative and the positive. So if we have a look at the positive, we can see we have so many text files here. Similarly, if we have a look at the negative, we have 1,000 negative files also here, which have the negative feedbacks. So let's take a particular positive one into consideration, which is the CV00295990. You can take any one of the files here, doesn't matter. Now the above tokenization, as you can see here, the file is already tokenized, but it is generally useful for us to do the tokenization, but the above tokenization has increased our work here. And in order to use the count vectorizer and the TF-IDF, we must pass the strings instead of the tokens. Now, in order to convert the strings into token, we can use the detokenizer within the NLTK, but that has some licensing issues as of now with the Conda environment. So instead of that, we can also use the join method to join all the tokens of the list into a single string. And that's what we are going to use here. So first we are going to create an empty list and append all the tokens within it. We have the review underscore list, that is an empty list. Now what we are going to do here is remove all the extra spaces, the commas from the list while appending it to the empty list, and perform the same for the positive and the negative reviews. So this one we are doing it for the negative reviews, and then we'll do the same for the positive reviews as well. So if you have a look at the length of this negative review list, it's 1,000. And the moment we add the positive reviews also, I think the length should reach 2,000. So let me just define the positive reviews. Now execute the same for positive reviews. And then again, if we have a look at the length of the review list, it should be 2,000. That is good. Now let us now create the targets before creating the features for our classifiers. So while creating the targets, we are using the negative reviews. Here we are denoting it as 0. And for the positive reviews, we are converting it into 1. And also we will create an empty list and we'll add 1,000 zeros followed by 1,000 ones into the empty list. Now we'll create a pandas series for the target list. Now the type of Y must result into a pandas series. So if we have a look at the output of the type of Y, it is pandas.code.series. That is good. Now let's have a look at the first 5 entries of the series. So as you can see, it is 1,000 zeros, which were followed by 1,000 ones. So the first 5 inputs are all zeros. Now we can start creating features using the count vectorizer or the bag of words. For that, we need to import the count vectorizer. Now once we have initialized the vectorizer, now we need to fit it onto the rev list. Now let us now have a look at the dimensions of this particular vector. So as you can see, it's 2000 by 16,228. Now we are going to create a list with the names of all the features by typing the vectorizer name. So as you can see here, we have our list. Now what we'll do is we'll create a pandas data frame by passing the SciPy CSR matrix as values and feature names as the column names. Now let us now check the dimension of this particular pandas data frame. So as you can see, it's the same dimension, 2000 by 16,228. Now if we have a look at the top 5 rows of the data frame, so as you can see here, we have 16,228 columns with 5 rows, and all the inputs are here 0. Now the data frame we are going to do is now split it into training and testing sets, and let us now examine the training and the test sets as well. So as you can see, the size here we have defined as 0.25. That is the test set, that is 25%. The training set will have the 75% of the particular data frame. So if we have a look at the shape of the X train, we have 15,000. And if we have a look at the dimension of X test, this is 5,000. So now our data is split now. We'll use the naive Bayes classifier for text classification over the training and testing sets. So now most of you guys might already be aware of what a naive Bayes classifier is. So it is basically a classification technique based on the Bayes theorem with an assumption of independence among predictors. In simple terms, a naive Bayes classifier assumes that the presence of a particular feature in a class is unrelated to the presence of any other feature. To know more, you can watch our naive Bayes classifier video, the link to which is given in the description box below. If you want to pause at this moment of time and check quickly what a naive Bayes classifier does and how it works, you can check that video and come back here. Now to implement naive Bayes algorithm in Python, we'll use the following library and the functions. We are going to import the Gaussian NB from sklearn library, which is a scikit-learn. We are going to instantiate the classifier now and fit the classifier with the training features and the labels. We are also going to import the multinomial naive Bayes because we do not have only two features here. We have the multinomial features. So now we have passed the training and the test data set to this particular multinomial naive Bayes. And then we will use the predict function and pass the training features. Now let's have a look and check the accuracy of this particular matrix. So as you can see here, the accuracy here is 1. That is very highly unlikely, but since it has given 1, that means it is overfitting and it is overly accurate. And you can also check the confusion matrix for the same. For that, what you need to do is use the confusion underscore matrix on these variables, which is y underscore test and y underscore predicted. So as you can see here, although it has predicted 100% accuracy, the accuracy is 1. This is very highly unlikely, and you might have got a different output for this one. I've got the output here as 1.0. You might have got an output as 0.6, 0.7, or any number in between 0 and 1.
What exactly is MLOps? MLOps, short for Machine Learning Operations, is the practice of combining collaboration, automation, and best practices to streamline the lifecycle of machine learning models from development to deployment and maintenance in production environments. It bridges the gap between data science and operational teams, ensuring that ML models are reproducible, scalable, and reliable in real-world use cases. Now that we understand what MLOps is, let's dive deeper to explore its relationship with DevOps. Well, DevOps focuses on the development and deployment of software applications, emphasizing continuous integration, continuous delivery, and infrastructure management. Whereas MLOps extends these principles to machine learning systems, addressing unique challenges such as handling large and evolving datasets, managing model drift and data drift, and ensuring reproducibility in training and inference. However, similar to DevOps, MLOps emphasizes several key principles that streamline machine learning workflows. Automation plays a central role, enabling the automation of tasks such as data pre-processing, model training, testing, and deployment to improve efficiency and consistency. And the collaboration fosters teamwork among data scientists, machine learning engineers, and IT professionals, ensuring alignment across roles for successful project execution. Additionally, MLOps supports continuous processes such as continuous training, testing, and monitoring of ML models to maintain their performance and adaptability over time in dynamic production environments. This alignment enhances the scalability and reliability of ML solutions. Now, with an understanding of how MLOps relates to DevOps, let's see how it is driving the scaling of AI solutions. First, we have the producibility. It ensures that models can be retrained and evaluated consistently even with changing datasets. Next, efficiency. Speeds up the transitions from experimentations to deployment with automation. Then, scalability, which handles the complexity of deploying models to production across diverse environments such as cloud, edge, etc. Next, reliability, which monitors and updates models to maintain performance over time, reducing the risk of model degradations. And finally, the compliance, which ensures traceability and accountability for ethical AI and regulatory standards. And by adopting MLOps, organizations can confidently scale AI initiatives, making ML models operationally viable and impactful in solving real-world problems. Now, having learned how MLOps is scalable AI solutions, let's explore why MLOps have become essential. Well, MLOps is crucial for overcoming several challenges inherent in traditional machine learning workflows. It addresses issues like data drift, where data used in production differs from the training data, leading to degraded model performance. Additionally, MLOps resolves the lack of reproducibility and version control, which often hinders the ability to trace back model experiments and configurations. Furthermore, MLOps tackles the deployment bottlenecks such as long delays and manual errors during model deployment. By automating tasks like model training, testing, and deployment, MLOps ensures scalability, reliability, and efficiency, allowing models to continuously evolve and remain effective over time, thus improving the robustness of machine learning system across different environments and use cases. Now that we know why MLOps is needed, so let's examine the challenges in traditional ML workflows. Over time, production data might diverge significantly from the training data, leading to data drift, or the relationships between variables may evolve, causing concept drift. And these changes can degrade model performance, and without MLOps, detecting and addressing such drifts becomes challenging, resulting in inaccurate predictions. Additionally, machine learning experiments often involve frequent updates to datasets, code, and hyperparameters. And without version control, reproducing results or tracking specific configurations becomes difficult, creating inefficiency and risk, especially in collaborative environments. Lastly, transitioning a model from development to production requires multiple steps, such as scaling, system integration, and latency optimization. Well, the traditional workflow lack automation, leading to deployment delays, errors, and a high risk of production failures. MLOps addresses these issues by streamlining processes and improving reliability. Having identified the challenges, let's see how MLOps addresses them by looking at its benefits. MLOps brings several key benefits to machine learning systems, ensuring they are robust, efficient, and scalable. It facilitates scalability by enabling model deployment across diverse environments like cloud, edge, or on-premises systems, with automated pipelines that efficiently manage large datasets and user demands. Reliability is enhanced through continuous monitoring, which detects issues such as data drift and concept drift early, ensuring consistent model performance. Automated workflows minimize human error and the dependability of ML systems in production. Moreover, MLOps streamlines repetitive tasks like data preprocessing, model training, and deployment through CI/CD pipelines and orchestration tools. And this automation frees data scientists and engineers to focus on innovation, accelerating the ML lifecycle, and maximizing the value of AI investments. Now, with a clear understanding of the benefits of MLOps, let's explore its key components. MLOps consists of several key components that ensures the smooth lifecycle management of machine learning systems. Model development involves data preprocessing, feature engineering, model training, and evaluation using tools like Jupyter, TensorFlow, and PyTorch. Model deployment focuses on pushing models into production environments such as batch processing, all-in inference, or edge computing, leveraging tools like Docker, Kubernetes, Flask, and Fast API. Next, model monitoring ensures continuous performance assessment by tracking metrics like accuracy, latency, and data drift, supported by tools like Prometheus and Grafana. Continuous integration and continuous deployment automates testing, integration, and delivery pipelines for models. Next, data versioning and management track dataset changes to maintain reproducibility with tools like DVC and Delta Lake. Lastly, experiment tracking logs experiments to compare model performance utilizing tools such as MLflow and weights and biases. Together, these components streamline the development, deployment, and maintenance of ML systems. Since MLOps involves various aspects, let's learn about MLOps lifecycle. MLOps lifecycle consists of several critical steps that ensures the effective management of machine learning models in production. Here we have data preparation, which involves collecting, cleaning, and versioning data to ensure consistency and reproducibility. Next, model training and validation includes conducting experiments, fine-tuning hyperparameters, and selecting the best performing model. And once the model is finalized, model packaging takes place, where the model is wrapped into a deployable format using tools and frameworks suited for the target environment. Then, the deployment follows, where the packaged model is integrated into production systems, whether on-premises, cloud, or edge platform. And finally, monitoring and feedback ensures continuous observation of the model's performance in production by tracking metrics like accuracy and latency. while feedback loops allow for iterative improvements to maintain performance and relevance. And this lifecycle ensures a streamlined and efficient ML workflow. Now that we know the core aspects of MLOps, so let's discuss what you need to learn to build a career in MLOps. A wide array of tools and frameworks supports the implementation of MLOps workflows. For pipeline orchestrations, tools like Kubeflow and Apache Airflow help automate and streamline the end-to-end processes of ML workflows. For CI/CD, platforms such as Jenkins and GitHub Actions enable automated testing, integration, and deployment pipelines to ensure smooth transitions from development to production. And for model serving, frameworks like TensorFlow Serving and TouchServe provides robust solutions for deploying and serving machine learning models at scale. Finally, for monitoring, tools like Evidently AI and Prometheus are commonly used to track performance metrics, detect data drift, and ensures that deployed models maintain their accuracy and reliability in production environments. These tools collectively enhance efficiency, scalability, and reliability in the MLOps ecosystem. Now that we have covered the tools and frameworks of MLOps, let's explore its real-world applications. MLOps is widely applied across industries to enable efficient deployment and management of machine learning models. In finance, it supports fraud detection system by continuously monitoring and updating models to detect abnormal transactions. And in e-commerce, MLOps drives recommendation systems, ensuring they adapt to changing user behavior and preferences by managing data pipelines and model updates. In manufacturing, MLOps enable predictive maintenance by processing sensor data in real time and retraining models to predict equipment failures, thereby reducing downtime and improving efficiency. These applications demonstrate how MLOps ensures reliability, scalability, and adaptability in critical machine learning systems. Now, with a solid understanding of MLOps, let's dive into the challenges it faces. MLOps faces several challenges in effectively managing machine learning workflows, such as data drift and concept drift can degrade model performance over time as data patterns evolve, requiring constant monitoring and updates. Next, managing large-scale data and models poses technical challenges such as ensuring efficient storage, processing, and deployment. Integrating MLOps practices with existing DevOps workflows can be complex, as it requires aligning ML-specific needs with traditional software engineering practices. Additionally, staying compliant with regulatory and ethical standards is critical, especially when working with sensitive data, necessitating robust governance and documentation processes to maintain trust and accountability. Now, addressing the challenges in MLOps sets the stage for exploring how emerging trends and innovation are shaping its future, driving more efficient, transparent, and scalable machine learning solutions. Now, let us discuss the future of MLOps. The future of MLOps is poised for transformative advancements driven by emerging trends. AutoML and no-code MLOps are making it easier for organizations to adapt and scale machine learning by enabling non-technical users to build and manage models efficiently. The integration of explainable AI into MLOps workflow ensures the transparency and accountability, addressing critical concerns around bias and trust in AI systems. Furthermore, the incorporations of generative AI is automating various MLOps processes such as feature engineering, pipeline automation, and anomaly detection, accelerating workflows and enhancing model performance. These trends are reshaping MLOps, making it more accessible, reliable, and aligned with future AI demands.
So let's begin our deep learning interview question and answer session and understand what are the typical questions which are being asked in a deep learning interview. So the first and foremost question what any deep learning interviewer asks is the basic understanding of the relationship between machine learning, artificial intelligence, and deep learning. So basically, artificial intelligence is a technique which enables machine to mimic human behavior. And machine learning is a subset of artificial intelligence technique which uses statistical methods to enable machines to improve with experience. Now, deep learning, on the other hand, is a subset of machine learning which makes the computation of multi-layer neural network feasible. It uses neural networks to simulate human-like decision making. Now, coming to the second question, do you think deep learning is better than machine learning? And if so, why? Now, though machine learning algorithms, the traditional machine learning algorithms, solve a lot of our cases, but they are not very useful while working with high dimensional data. Now, that is where we have a large number of inputs and outputs. For example, in case of handwriting recognition, we have large amount of inputs where we have different types of input associated with different types of handwriting. Now, another major challenge is to tell the computer what all features it should look for that will play an important role in predicting the outcome as well as to achieve better accuracy while doing so. So these are some of the few shortcomings what machine learning have, and deep learning overcomes all of these shortcomings. Now coming to our third question, which is what is a perceptron and how does it work? Now actually our brain has subconsciously trained itself to do a lot of things over the years. Now the question comes, how does deep learning mimics the functionality of the brain? Well, deep learning uses the concept of artificial neuron that functions in a similar manner as the biological neuron present in our brain. Therefore, we can say that deep learning is a subfield of machine learning concerned with algorithms inspired by the structure and the function of the brain called artificial neural networks. Now, if you focus on the structure of a biological neuron, it has dendrites which is used to receive inputs. Now, these inputs are summed in the cell body, and using the axon, it is passed on to the next biological neuron. Now, similarly, a perceptron receives multiple inputs, applies various transformations and functions, and provides an output. Now, a perceptron is a linear model used for binary classification. It models a neuron which has a set of inputs, each of which gives a specific weight. Now, the neuron computes some function on these weighted inputs, and then finally it provides the output. As we know that our brain consists of multiple connected neurons called the neural network, we can also have a network of artificial neurons called the perceptron to form a deep neural network. Now coming to the next question, what is the role of weights and biases? Now for a perceptron, there can be one or more input called bias. While the weights determine the slope of the classifier line, the bias allows us to shift the line towards left or right. And normally bias is treated as another weighted input with the input value x in our case. If you have a look at a typical perceptron, what it receives is a set of input. Now these inputs are not just input which it gathers, so weights are an additional input which it takes, and according to that it computes and provides an output. Now which brings us to the next question, which is what exactly are activation functions? So activation function translates the inputs into outputs, and it uses a threshold to produce an output. So the activation function decides whether a neuron should be activated or not by calculating the weighted sum and further adding the bias with it. And the purpose of the activation function is to introduce a non-linearity into the output of a neuron. There can be many activation functions like linear or identity. We have the binary step, we have sigmoid, we have the tanh, we have relu and softmax. These are a lot of activation functions which are being heavily used in the deep learning industry. So one should actually know about all of these things. Now talking about perceptron, our next question, what an interviewer might ask is explain the learning of a perceptron. So basically a perceptron has 4 steps of learning. So the first steps is initializing the weights and threshold. So just now, as I mentioned, initializing the weights and the threshold so to the perceptron so that it can activate a neuron by calculating the weighted sum and further adding the bias in and all. This is the first step, and the second step is providing the input and calculating the output using the activation functions. And according to that, what we do is the third step involves updating the weights. Now, once a particular perceptron learns something, it has to update the weights so that it can learn much more things in a new manner. And the next step, what comes is to repeat the step number 2 and 3, which is provide the input and calculate the output and then update the weights accordingly. Now, if we have a look at the equation here, we have wj t plus 1 that equals wj of t plus n of t minus yx. The wj of t plus 1 is the updated weight, whereas wj of t is the old weight, d is the desired output, y is the actual output, and x is the input. So this is the equation of the learning of a perceptron. Now the next question is, what is the significance of a cost or a loss function? So a cost function is a measure of accuracy of the neural network with respect to a given training sample and expected output. It provides the performance of a neural network as a whole And in deep learning, the goal is to minimize the cost function. So for that, we use the concept of gradient descent. Now, which brings us to the next question, which is what exactly is gradient descent and what are its various types? So gradient descent is an optimization algorithm which is used to minimize some function by iteratively moving in the direction of the steepest descent as defined by the negative of the gradient. Now think of it as a bowl in which you start from any particular point and the goal is to reach the bottom of the bowl, which is the gradient descent. So there are three types of gradient descent, which are the stochastic, batch, and the mini batch. So stochastic gradient descent, it uses only single training example to calculate the gradient and update the parameters accordingly. Whereas the batch gradient descent calculates the gradients for the whole dataset and performs just one update at each iteration. Now, mini batch gradient descent is a variation of the stochastic gradient descent where instead of single training example, mini batch of samples are used, and it is one of the most popular optimization algorithm. Now, if we talk about mini batch gradient descent, one might ask is what are the benefits of the mini batch gradient descent, or how is it useful than the others? Now, the mini batch gradient descent is more efficient when compared to the stochastic gradient descent, and the generalization is done by finding the flat minima, which allows to help approximate the gradient of the entire training set, which help us to avoid the local minima. Now, this is why mini batch gradient descent is considered or is preferred over the regular gradient descent algorithm, which is the stochastic gradient descent. Now, one might ask, what are the steps for using a gradient descent algorithms? So, first of all, what you need to do is initialize some random weight and bias. And after that, you need to do is pass an input through the network and get values from the output layer. Next, what you're going to do is calculate the error between the actual value and the predicted value. Now, this can be done in a number of ways. Now, the next step involves is to go to each neurons which contributes to the error and change its respective values to reduce the error, which is basically our goal is to reduce the cost of any particular function or any particular model. So after that, what you do is reiterate until you find the best weights of the network and you find the lowest cost of the particular network. So one might ask you to write any gradient descent program or write the pseudocode of any gradient descent program. So what you need to do, first of all, what we do is define the parameters, which are the weights, the hidden weights, the weight output, the bias hidden, and the bias output. We define a function std with arguments as cost, the parameters what we have discussed, and the learning rate. Now, what we do is we then define the gradients of our parameters with respect to the cost function. So here we use the Theano library to find the gradients and we import Theano as T, and finally iterated through all the parameters to find out the updates for all the possible parameters. So you can see that we use vanilla gradient descent here, and as you can see it returns the updates, and what we do is update the parameters and the cost in this particular equation. The ultimate goal of any gradient descent algorithm is to minimize the cost. Now, talking about perceptron, what are the shortcomings of a single layer perceptron? So, well, there are two major problems. Now, first of all is that the single layer perceptron cannot classify non-linear separable data points. And the second point is that the complex problems that involve a lot of parameters cannot be solved by a single layer perceptron. Now consider an example here and the complexity which arises when the parameters are involved to take a decision by a marketing team. So first of all, we have the categories, which are the email, direct, paid, referral program, or the organic. And inside this category, we have subcategories, which are the Google, Facebook, LinkedIn, Twitter, we have Instagram now. And inside that, we have the type of subcategory, which are the search ads, remarketing ads, interested ads, lookalike ads. And again, if we do a subdivision, we have the parameters to consider, which are the customer acquisition cost, we have the money spent, the click rate, or the lead generated, the customer generated, and the time taken to become a customer. So one neuron cannot take in so many inputs, and that is why more than one neuron would be used to solve this problem. Now, which brings us to the question, what is a multi-layer perceptron? So a multi-layer perceptron or MLP is a class of feed-forward artificial neural network, and it is composed of more than one perceptron. They are composed of an input layer to receive the signal, an output layer that makes a decision or the prediction about the input, and in between these two, an arbitrary number of hidden layers that are the true computational engine of any multi-layer perceptron. Now one might ask, what are the different parts of any multi-layer perceptron or a neural network? So first of all, what we have are input nodes. So the input nodes provide information from the outside world to the network and are together referred as the input layer. No computation is performed in any of the input nodes. They just pass the information to the hidden layers. Now, hidden nodes have no direct connection with the outside world, hence the name hidden. And what they do is they perform computation and transfer the information from the input nodes to the output nodes. Now, a collection of hidden nodes forms the hidden layer, and while a network will only have a single input layer and a single output layer, it can have 0 to n number of hidden layers, and a multi-layer perceptron has more than one hidden layer. Now, if we talk about output nodes, the output nodes are collectively referred to as the output layer and are responsible for the computation and transferring information from the network to the outside world, and hence they are also responsible for the prediction. Now, coming to our next question, what exactly is data normalization and why do we need it? Now, data normalization is a very important pre-processing step, which is to normalize the data. The data should not be either left skewed or right skewed. It should be normal, and is used to rescale the values to fit in a specific range to assure the better convergence during backpropagation. And in general, it boils down to subtracting the mean of each data point and dividing by its standard deviation so that we get a normally distributed data. And it makes computation easy in terms of the backpropagation in case of neural networks. So this is a very important part of any deep neural network. Now talking about deep neural networks, or neural networks in general, coming to our next question, which is, now what is better, the deep networks or the shallow ones, and why? Now both the networks, be it shallow or deep, are capable of approximating any function. What matters is how precise that network is in terms of getting the result. Now, a shallow network works with only a few features as it cannot extract more, but a deep network goes deep by computing efficiently and working on more features or the parameters. Now, deeper networks are able to create deep representation. At every layer, the network learns a new, more abstract representation of the input, and hence deep neural networks are better than the shallow ones. So what exactly is weight initialization in a neural network? Now, as we saw, we had weight initialization in perceptrons. So weight initialization is one of the very important steps. A bad weight initialization can prevent a network from learning, but good weight initialization can help it in giving quicker convergence and a better overall error. Now, biases can be generally initialized to 0. The rule for setting the weights is to be close to 0 without being too small, because every time the weight is being multiplied to the inputs, the result gets smaller and smaller. Now, talking about neural networks, what is the difference between a feed-forward and a backpropagation neural network? Now, a feed-forward neural network is a type of neural network architecture where the connections are fed forward, that is, they do not form cycles. The term feed-forward is also used when you input something at the input layer and it travels from the input to the hidden and from the hidden to the output layer. The values are fed forward. Now, backpropagation is a training algorithm which consists of two steps majorly. The first one is feed forwarding the values, and the second one is to calculate the error and propagate it back to the earlier layers. So to be precise, forward propagation is a part of backpropagation algorithm, but it comes before the backpropagation. So one might ask the question, which is one of the most important questions, is that what are the hyperparameters in a neural networks, and name a few of these hyperparameters. So hyperparameters are the variables which determine the network structure. That is, for example, the number of hidden units and or the hidden layers, and the variables which determine how the network is trained, for example, the learning rate. Now, there are two types of hyperparameters usually. One are the network parameters, which are associated to the network. In that case, we have the number of layers, we have the network weight initialization, we have the activation function, and in the training parameters, we have the learning rate, we have momentum, number of epochs, we have the batch size, and much more. Now, a lot of hyperparameters also differ when we work along with different types of neural networks. So as in CNN, we get extra parameters to work on when considering CNN, which are the convolutional neural networks. And sometimes we have to deal with less number of hyperparameters. It all depends upon the type of neural network which you are using. So, which brings us to the next question, is that explain the different hyperparameters related to networking and training. So in training, we have, first of all, we have the number of hidden layers. So hidden layers are the layers between the input and the output layers, as we just discussed. And many hidden units within a layer with regularization technique can increase the accuracy, as smaller number of units may cause underfitting. Now, another important aspect is network weight initialization. So ideally, it may be better to use different weight initialization schemes according to the activation function used on each layer. Mostly uniform distribution is used, or the normal distribution. Now, if we talk about activation function, so they are also used to introduce non-linearity to the models. They are also used to introduce non-linearity to the models, which allows deep learning models to learn non-linear prediction boundaries. Now, generally, the rectifier activation function, or the ReLU, is the most popular. Now, if we talk about the training parameters, so these were the network parameters which have to be initialized to a deep neural network before the training begins. And just before the training, we have the training parameters, which are the learning rate. So the learning rate defines how quickly a network updates its parameter. Low learning rate slows down the learning process but converges smoothly. A larger learning rate speeds up the learning but may not converge as smooth as a low learning rate. Usually, a decaying learning rate is preferred so that we get the best of both worlds and we get the best expected output. Now, another hyperparameter is momentum. So momentum helps us to know the direction of the next step with the knowledge of the previous step. Now, it helps to prevent oscillation, and a typical choice of momentum is between 0.5 to 0.9. Now, if we talk about the number of epochs, so epochs is basically iterations. So number of epochs is the number of times the whole training data is shown to the network while training. So increase the number of epochs until the validation accuracy starts decreasing, even when tiering accuracy is increasing. So that results in sometimes overfitting. And if we talk about the batch size, so mini batch size is the number of subsamples given to the network after which parameters update happen. So a good default for batch size might be 32 or 16, 64. It depends upon the size of the data you have. It can be any arbitrary number, but it's always better to have it in the power of 2, right? So while we were talking about overfitting, which brings us to our next question, which is what exactly is a dropout? So dropout is a regularization technique to avoid overfitting, which is to increase the validation accuracy, thus increasing the generalization power. Now, generally use a small dropout value of 20% to 50% of the neurons, with 20% providing a good starting point, and a probability too low has minimal effect, and a value too high results in underlearning by the network. So first of all, what you need to do is use a large network, and you are likely to get better performance when the dropout is used on a larger network, giving the model more of an opportunity to learn independent representation. Now, our next question is, in a neural network, you notice that the loss does not decrease in the few starting epochs. So what could be the possible reason for this to happen? Now, the correct answer is the reason for this could be the learning rate is low, first of all, or it might be the regularization parameter is high, or it can be it is stuck at local minima, so it might take certain iteration to go out of that local minima and finally reach the lowest point. So it might happen in some cases that it is stuck at local minima. So another approach to that sort of problem must be initiated at that particular point of time. Now, talking about deep learning, one might ask to name you a few deep learning frameworks which are being used in the industry. So first of all, the foremost and the most amazing deep learning library is the TensorFlow. Followed by we have Caffe, we have the Microsoft Cognitive Toolkit, which is the CNTK. We have Torch or PyTorch, which is giving a good battle, or it's standing out from the crowd, and people are sometimes preferring PyTorch over TensorFlow. Now, MXNet is another deep learning framework. We have Chainer and we have Keras. Now, Keras, as you know, can be integrated with Theano as well as TensorFlow, and Keras has been considered one of the best or the simplest deep learning framework when it comes to deep learning. Now, one might ask, what exactly are tensors? So, tensors are nothing but a de facto for representing the data in deep learning. What I meant to say that tensors are just multi-dimensional arrays that allows you to represent the data having higher dimensions. In general, deep learning, you deal with high-dimensional data sets where dimensional refer to the different features present in the data set. So what you need is a multi-dimensional sort of array or a data structure, what you could say. So that's what exactly tensor is. And in fact, the name TensorFlow has been derived from the operations which the neural network perform on tensors. So it's literally a flow of tensor. Now, talking about TensorFlow, one might ask, since it's the most popular deep learning framework and companies prefer people having the knowledge of TensorFlow and been working on it. So what are the few advantages of TensorFlow? So first of all, it has the platform flexibility. It is easily trainable on CPU as well as GPU for distributed computing. Now, TensorFlow has auto differentiation capabilities and it has advanced support for threads, asynchronous computation, and it is a customizable and open source framework. And most importantly, if we talk about the latest TensorFlow 2.0, which has just been released, so those come up with a lot of interesting features, and it has adopted Keras as its high-level API fully so that the coding aspect of it is much simplified, and eager execution is now by default so that you do not have to write loads and loads of line of code. And if you want to know more about TensorFlow 2.0 and why it's the best deep learning framework in the industry right now, just go ahead and check our TensorFlow 2.0 video. I'll leave the link in the description box below. Go check it out, guys, and understand how exactly is it better from the previous version and why it is the best deep learning framework right now. Now, talking about computational graphs, one might ask what exactly they are. So, well, a computational graph is a series of TensorFlow operations arranged as nodes in the graph. Now, each node takes 0 or more tensors as input and produces a tensor as output. Now, basically, one can think of a computational graph as an alternative way of conceptualizing mathematical calculation that take place in a TensorFlow program. Now, the operations assigned to the different nodes of a computational graph can be performed in parallel, thus providing better performance in terms of computation. So, one might ask, what exactly is a convolutional neural network? Now, a convolutional neural network, or CNN or ConNet, is a class of deep learning neural networks which is most commonly applied to analyzing the visual imagery. So CNN use a variation of the multi-layer perceptron designed to require minimal processing. Now, one might ask the next question: if you are going for an interview which requires you to work with a lot of images or videos, so in that case, CNNs are very much used. So having a good knowledge of CNN is always better in that case. So the next question which we have here is, what are the various layers of CNN? Now, there are 4 layered concepts everyone should understand in convolutional neural networks are: first, the convolutional layer, the second is the ReLU layer, and finally we have the pooling layer, and finally we end up with the full connectedness or the full connected layer. Now, if we talk about CNN, we have to talk about RNN also. So one might ask, what exactly is RNN? So RNN, or the recurrent networks, are a type of artificial neural networks which are designed to recognize the patterns in the sequence of data, such as text, genomes, handwriting, the spoken word, numerical time series data, from sensors, the stock markets, and the government agencies. So recurrent neural networks use backpropagation algorithm for training, but it is applied for every timestamp. It is commonly known as backpropagation through time, which is BTT. Now, our next question is, what are some issues faced while training an RNN? So, recurrent neural networks use backpropagation algorithm, as I just mentioned, for training, but it is applied for every timestamp. And there are some issues with backpropagation, such as vanishing gradient or the exploding gradient, where the gradient vanishes or it is too much to handle. Which brings us to the next set of questions, the first of which is, what exactly is a vanishing gradient and how is it harmful? Now, when we do backpropagation, that is move backward in the network and calculating gradients of loss, which is the error, with respect to the weights, the gradients tend to get smaller and smaller as we keep on moving backward in the network. Now, this means that the neurons in the earlier layers learn very slowly as compared to the neurons in the later layers in the hierarchy. Now, the earlier layers in the networks are the slowest to train. Now, how is this harmful? So, earlier layers in the neural networks are important because they are responsible to learn and detect the simple patterns and are actually the building blocks of our neural network. Obviously, if they give improper and inaccurate result, then how can we expect the next layer and the complete network to perform nicely and produce the accurate result? So the training process takes too long and the prediction accuracy of the model will decrease. Now, another question here arises is, what exactly is then exploding gradient descent? Now, this is just the opposite of vanishing gradient descent. So exploding gradients are a problem when large error gradients accumulate and result in very large updates to the neural network model weights during training. So the gradients are used during the training to update the network weights, but typically when this process works best is when these weights are small and controlled, when the magnitudes of the gradients accumulate and the unstable network is likely to occur, now which causes a poor prediction and results, or even a model that reports nothing useful whatsoever. So vanishing gradient and the exploding gradient are two problems which occur while the backpropagation happens in a recurrent neural network. So our next question is, what are LSTM? So long short-term memory, which are the LSTM, is an artificial recurrent neural network architecture used in the field of deep learning. And unlike standard feed-forward neural networks, the LSTM has feedback connection that make it a general-purpose computer. Now it can not only process single data points, but also the entire sequence of data. They are a special kind of RNNs, or the recurrent neural network, which are capable of learning long-term dependencies. Now one might ask, what are capsules in a capsule neural network? So capsules are vector, or what we can say an element with a size and a direction, specifying the features of the object and its likelihood. Now these features can be any of the instantiation parameters like the pose, we have the position, size, orientation, deformation, velocity, the albedo, which is the light reflection, hue, texture, and much more. A capsule can also specify its attributes like angle and size, so it can represent with the same generic information. Now, just like a neural network has layers of neurons, a capsule network can have layers of capsules, so there could be higher capsules representing the group of objects or the capsules below them. Now, this helps in getting deeper knowledge of a particular object or a particular data set and having the knowledge from different aspects or different angles. So the next question arises is, explain autoencoders and its uses. So an autoencoder neural networks is an unsupervised machine learning algorithm that applies the backpropagation, setting the target values to be equal to the inputs. So autoencoders are used to reduce the size of our inputs into smaller representation, and if anyone needs the original data, they can reconstruct it from the compressed data. Now one might ask the question, how does autoencoder differ from PCA? So an autoencoder can learn from nonlinear transformation with a nonlinear activation function and multiple layer. It does not have to learn dense layers. It can use convolution layers to learn, which is better for video, image, and series data. It is more efficient to learn several layers with an autoencoder rather than learn one huge transformation with the PCA. An autoencoder provides a representation of each layer as the output and can take the use of pre-trained layers from other models to apply transfer the learning to enhance the encoder or the decoder. So these are few of the reasons why autoencoders are better from PCA, as we know both of them perform the same task, which is mostly dimensionality reduction. Now give some real life examples where autoencoders can be applied. So the first of all, we talk about dimensionality reduction, or the first thing that should pop up in your mind is dimensionality reduction. So the reconstructed image is the same as our input image but with reduced dimensions. Now it helps in providing similar image with reduced pixel value, and it can be used in various areas where we have limited storage or we have limited processing power. So when there is a high input or an image or a data with high dimension or which has higher values, pixel values, it can compress and provide the same image with a lower pixel value. Now, autoencoders are used for converting any black and white picture into a colored image, believe it or not. And depending on what is in the picture, it is possible to tell what the color should be. Now, feature variation, if we talk about feature variation, it attracts only the required features of an image and generates the output by removing any unnecessary noise or unnecessary interruption. And if we talk about denoising image, the input seen by an autoencoder is not the raw input, but a stochastically corrupted version. A denoising autoencoder is thus trained to reconstruct the original input from the noisy version. Now, talking about autoencoders, one might ask about the different layers of the autoencoders. So basically an autoencoder consists of three layers, which is the encoder, we have the code, and the decoder. Which brings us to the next question: explain the architecture of an autoencoder. If we talk about the three layers, which are encoder, code, and decoder. So if we talk about encoder, this part of the network compresses the input into a latent space representation. Now the encoder layer encodes the input images as a compressed representation in a reduced dimension, and the compressed image is the distorted version of the original image. Now coming to the middle part, which is the code. So this part of the network represents the compressed input which is fed to the decoder. It is basically the channel. And if we talk about decoder, this layer decodes the encoded image back into the original dimension, and the decoded image is a lossy reconstruction of the original image, and it's reconstructed from the latent space representation. Now one might ask, what exactly is bottleneck in an autoencoder and why is it used? Now the layer between the encoder and the decoder, that is the code, is also known as bottleneck. So this is a well-designed approach to decide which aspect of the observed data are relevant information and what aspects can be discarded. It does this by balancing two criteria. The first, the compactness of the representation measured as the compressibility, and second, it retains some behaviorally relevant variables from the input. Now, one might ask, are there any variation of autoencoders? Surely there are. So there are convolutional autoencoders, we have sparse autoencoders, we have deep autoencoders, we have contractive autoencoders. All of these autoencoders have a different structure or the different code layer. If we talk about the convolutional autoencoder, we have the convolutional CNN algorithm sort of structure in that particular autoencoder with encoder in one side. We have the convolution layers, the ReLU layer, the pooling layer inside it, and then finally we have the decoding layer. So another question what might pop into the interviewer's mind is, what are deep autoencoders? So the extension of simple autoencoders is a deep autoencoders. The first layer of the deep autoencoders is used for first order features in the raw input. Now the second layer is used for second order features corresponding to the patterns in the appearance of the first order features. So the deeper layers of the deep autoencoders tend to learn even higher order features. So a deep autoencoders is composed of two symmetrical deep belief networks. First 4 or 5 shallow layers representing the encoding half of the net, and the second set of 4 or 5 layers that make up the decoding half. Interesting, right? So another important topic in deep learning are the restricted Boltzmann machines. So one might ask, what exactly is an RBM or restricted Boltzmann machine? So RBM is an undirected graphical model that plays a major role in deep learning framework in recent times. and it is an algorithm which is used for dimensionality reduction. Not only that, it is used for classification, regression, collaborating filtering, feature learning, and topic model. So when we talk about RVM being useful for dimensionality reduction, another question might arise is, how does RVM differ from the autoencoders? So autoencoders is a simple 3-layer neural network where output units are directly connected back to the input units. Typically, the number of hidden units is much less than the number of visible ones. And the task of training is to minimize an error or the reconstruction, that is, find the most efficient compact representation for the input data. So RVM share a similar idea, but it uses stochastic units with particular distribution instead of deterministic distribution. The task of our training is to find out how these two set of variables are actually connected to each other. One aspect that distinguishes RVM from the autoencoders is that it has two biases. The hidden bias helps the RVM produce the activations on the forward pass, while the visible layer biases help the RVM learn the reconstruction on the backward pass. Now, this brings us to the final question of our deep learning interview, is that what are some limitations of deep learning? I bet you weren't thinking of this one, but there are some limitations. So, deep learning usually requires large amounts of training data, and deep neural networks are easily fooled. Now, the success of deep learning are purely imperial. Deep learning algorithms have been criticized as uninterpretable black boxes. Because one important thing about deep learning is that you do not specify what you are looking for, right? The algorithm learns on its own. So that is one of the shortcomings of deep learning, and deep learning thus far has not been well integrated with prior knowledge. So a lot of people still don't feel it as a way to solve their problem, as a way to approach to their problems, because a lot of people don't understand what exactly is deep learning, how it works, how to initialize all of the variables, which are the hyperparameters per se. These all things are some limitations of deep learning as of now, and we hope by the time technology advances, people get to know more about what deep learning is, how artificial intelligence can be achieved through deep learning. They'll be more open to this, and all of these limitations will be laid off. So guys, that's it from my side, and I hope you got to know a lot about deep learning interview questions, which might help you in cracking the interviews and landing a great job as data scientists, machine learning engineers, or artificial intelligence engineers, as a matter of fact. And one important thing what I would like to say is that data scientists' role are somewhat, industry specific, or I would say if you are working in healthcare, you should know about healthcare industry too, rather than just knowing about the data and the numbers. So if you are working in, suppose, imagery, so you should know about images, you should know what you're dealing with. So a good knowledge of the particular industry which you're working for will also provide you a great advantage over other competitors. And since you know a lot of these stuff with this video, I'm sure you might be able to land a great job in any of these industries.
And with this, we have come to an end to this full course on deep learning. If you enjoyed listening to this full course, please be kind enough to like it, and you can comment on any of your doubts and queries. We will reply to them at the earliest. And do look up for more videos and playlists, and subscribe to Edureka's YouTube channel to learn more. Thank you for watching and happy learning.